Hello everyone, welcome to this data science full course by Intellipaat. In today's age, if you're not thinking about learning the right skills, getting a job is not easy at all. Think about this. A decade ago, skills like PHP or Java developer were relevant, but they are not relevant anymore. The thing is, the business and IT industry have been changing constantly with every tech revolution, and the speed of that change has increased more since generative AI came into the picture. That's why, if you want to get a high paying job today, you need to choose the right domain and go through the right learning schema. And there is nothing more trending and demanding than the data science and AI domain in the industry right now. In fact, many people who have watched our previous free data science courses have received the jobs or cracked the data science interviews. And this particular course is even better considering that it's designed as per the industry requirements of 2024. So if you follow this course or do the real world projects that we have covered in this course and also practice the interview questions that we have put up at the end, you'll be able to get the high paying tech job as a data scientist. Let me talk about what you'll get to learn through this particular course. We'll start by understanding what data science is, how you can become a data scientist, what skills you'll have to master to become a data scientist, etc. Then we'll jump into the discussion about machine learning and we'll cover algorithms like linear, logistic regression, decision tree and random forest. Once you understand these fundamental algorithms, we'll cover the top data science interview questions and create hands-on project or book recommendation engine that you can add into your resume to impress the recruiters. So stay tuned till the end of this particular course and make sure to hit that subscribe button so that you receive multiple technical contents like this from Intellipaat's end.
Just a quick info guys, Intellipaat offers an executive postgraduate certification in data science and AI where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
Data science has been a trending field of study in recent times. This is because of the amount of data that we create constantly and the computing power that is available with advancements in technology. But what is data science? Think about what happens when you book a ride on Uber. You open the Uber app on your phone and tell the app where you want to go. Uber tries to find the nearest cab, sends them the directions to come pick you up, and take you to your destination. That was simple. But in the background, the seemingly simple task is carried out by collecting mountains of data from various sources, like the phones, the map, and historic trends of traffic and demand for rides. With this data, modern-day computers are programmed to calculate the nearest driver to you, the best route to your location and destination, the time it will take, and what you should pay. In other words, this is made possible with data science. Data science has countless other applications as well, and is at the intersection of statistics, data analysis, and machine learning. It is a combination of scientific methods, models, and algorithms working together to extract actionable business insights from data. The U.S. faces a shortage of 140,000 to 190,000 people with deep analytical skills, and 1.5 million managers who can analyze big data to make effective decisions. The average salary of a data scientist is around $118,000. So, still interested in data science as a profession? Continue on to learn more about who can become a data scientist, why data scientists matter, what is the data science life cycle, how big data is driving the data science revolution, the career prospects for data science. Data is the oil of our generation. Data science is becoming indispensable in today's digitally driven world, helping businesses understand consumer behavior, fine-tune its messaging, and capture new market share. To become a data scientist, you don't need to have a technical background to be a data scientist. What you do need is in-depth knowledge in mathematics, analytical reasoning, the ability to work with large amounts of data. It would also help to have a strong intellectual quest, knowledge of data engineering, visualization ability, and excellent business acumen. If you do come from a non-technical background, you will likely use R. If you are from a technical background, then you could use Python and R. It is all about understanding the possibilities and asking the right questions, all in the search for the best answers. Every company is flooded with data, and they have more data than they know what to do with. So, regardless of the industry vertical, data science is likely to play a key role in your organization's future success. Data scientists help find new ways of reducing costs, entering new markets and customer demographics, and launching new products or services. Data science also has found social and medical applications, such as child welfare and predictive diagnosis as well. So, what does the typical data science lifecycle look like? The data discovery step includes the search for different sources of relevant data, structured or unstructured data. Then, you make a decision to include specific data sets into your analysis. The data preparation includes converting data from different sources into a common format. You will standardize the data, look for anomalies, and make it more appropriate to work with. The data science models are built using statistics, logistic and linear regression, differential and integral calculus, among other mathematical techniques. You could use tools like R, Python, SAS, SQL, Tableau, and so on. Getting things in action phase includes checking the data models for its effectiveness and ability to deliver the results. You will have to verify the model works. If not, you have to rework on your model. A data scientist needs to liaison with the various teams and be able to seamlessly communicate his findings to key stakeholders and decision makers in the organization. Another critical element of data science are algorithms, which are a process of set of rules to solve a certain problem. Some of the important data science algorithms include regression, classification and clustering techniques, decision trees and random forests, machine learning techniques like supervised, unsupervised, and reinforcement learning. In addition to these, there are many algorithms that organizations develop to serve their unique needs. Big data is driven by the data science revolution. Big data is the engine propelling the rise of data science. Hadoop is a popular big data framework used by most organizations. Hadoop works in a distributed manner wherein both the processing and storing of data is distributed on commodity hardware. Hadoop is easily scalable, highly economical, fault-tolerant, and secure. Hadoop consists of Hadoop Distributed File System, or HDFS, for storing data and uses MapReduce for processing data. Another emerging framework is Apache Spark, which is touted to be up to 100 times faster than MapReduce. Spark stores the data in the RAM, so iterative processing is fast and efficient. It also deploys Direct Acyclic Graph, or DAG, for processing of data. There is a huge demand and supply mismatch when it comes to data scientists. Due to this, salaries of data scientists are among the best in the industry. Top companies like Amazon, Google, Facebook, Microsoft in the tech space, to others like ExxonMobil, Visa, Boeing, General Electric, and Bank of America are actively hiring data scientists. Now that you have learned about data science, why data science is indispensable, the data science lifecycle, how it relates to big data, it is time you start your journey in this promising domain and see your career soar.
It doesn't matter whether you have a computer science degree in hand or not. Neither does it matter whether you have programming experience behind your back or not. When it comes to getting a job in data science domain, all that matters is whether you have got the skills. It's true that for many aspirants back in the day, acquiring data science skills was only possible with master's and PhD degrees. Considering the fact that data science need mastery over 4 different things such as statistics, programming, machine learning, and business acumen. But what if I tell you that now you can attain this feat and become a data scientist within a year? What if I tell you that you don't necessarily need a master's background to become a data scientist today? Well guys, bear with me till the end of this video and I'll answer how you can make the above 2 things happen. first of all, let's discuss why you should consider a career in data science. When it comes to choosing a career domain, you need answers to 3 questions. Does the domain have high demand right now? And will it be relevant in the coming years? Number 2, are there better job prospects available? Number 3, are the salaries lucrative enough? Okay, let's try to break all these 3 questions one by one. First of all, let's talk about question 1 and 2. Right now, if you just go over to the Google search and search for data science jobs available, you'll get to know that on just the LinkedIn job board, there are 7 lakh plus jobs available. If you consider the other job boards, the number of data science jobs available might be even more substantial. Now, that's one thing. Consider this as well. In the last 2 years, 400,000 employees have been laid off by IT companies. And according to the Economic Times report, almost every job was impacted by these layoffs. Some were impacted severely, whereas some faced a less backlash. But consider this, 27% of laid off employees were from an HR background. 22.1% were from software development background, whereas just single digit amount of people were from data science backgrounds. What that means is AI did not harm the data science jobs at all. Also, since both AI and data science go hand in hand, there are predictions that both these job roles together will produce 80 million jobs by the end of decade ahead. What that means is for data science, both the present and future is quite bright. What about salaries, you may ask? Well, let me tell you that data science salaries are one of the highest in the IT industry. Even the junior data scientist earns an average pay between 7 lakh rupees to 19 lakh rupees in India and $92,000 to $200,000 in the USA. You can see that data science as a career clears all the checkboxes that we set out in the beginning. Hence, definitely data science is a great career option you can go for. Now, having said that, let's move forward and discuss how you can become an employable data scientist all by yourself. Basically, to make it happen, you have to be very strategic about what you learn and how you learn it. After doing a thorough consultation with data science trainers and industry experts associated with us at Intellipaat, we have formulated a roadmap that not only will provide you with the necessary skills, but also will prepare you for data science interviews at top companies. So ideally, the very first thing you need to do is go through the concepts of statistics. See, the term data science itself suggests that you'll be dealing with a lot of numbers. If you lack the fundamental math knowledge, doing so will become very difficult. Even if you were to carry out a simple analysis, let's say you want to know if YouTube changes the color of the subscribe button to green, what will happen? In that case, statistics will be important for you to understand the noise in data, to understand what parameters is critical for captured data. Even the basic concept or fundamental ideology behind machine learning like neural network is born out of mathematics. That's why we want you to dedicate a month and a half to revising critical mathematical concepts for data science. See, if you have done engineering and 10+2, you'll already be acquainted with ideas like probability, normal distribution, charts and graphs, etc. All you need to do is revise those concepts and learn few more critical concepts such as mean, variance, bias, Bayes theorem, sampling, hypothesis testing, standard and normal distribution, t-test, etc. To help you do that, we have created a free statistics for data science course. You can just search for the free Intellipaat statistics for data science course over Google and you'll come across this course page. I'll also be dropping it in the description below as well. See, you don't have to become a mathematician here. You just need to understand enough of math to learn and understand the data science concepts. Once you have done that, it's time we get started with the next dependency. That is learning the programming language. For data science, primarily there are 2 languages to choose from. First one is R programming and second one is Python programming. I would prefer learning Python since it is large scale programming language and it doesn't just stop at data science. Again, you don't have to become a Python developer. You just need to learn enough of Python programming to be able to do data science course. Here is the list of concepts you'll have to master. For this task, you can dedicate 2.5 months. Getting acquainted with programming language is not going to be as difficult as it might seem to you right now. Once you get started, you'll realize that you have got it. Next up, you need to go through the libraries such as NumPy, Pandas, Seaborn and Matplotlib. Basically, you'll be doing the exploratory data analysis as the first task in any data science process. Hence, exploring these very basic libraries is a must. Learn to create the data frames and NumPy arrays, how to carry out the mathematical operations on them, and learn about different Pandas and NumPy functions. Also explore the different charts available in Seaborn and Matplotlib. Understand what each chart resembles. Basically, comprehend the language of charts and graphs. You can spend 15 days doing this particular activity. Once you have understood how to use these libraries, it's time you grasp the SQL basics and art of exploratory data analysis. Learning SQL is very important because without it, you'll not be able to interact with data systems and gauge the data that you need. Tasks like wrangling are done with SQL itself, so try to gather the fundamentals of SQL and databases. You can dedicate 1 complete month to learning and practicing with SQL. Also, since we have already dedicated the time to learn statistics and 4 Python libraries, mastering the EDA will not be a difficult task. Basically, you'll discover how to load data, clean it, figure out descriptive statistics and analyze the important attributes, etc. I would recommend you guys to go over the Kaggle, explore many notebooks and figure out how people understand the data. Then try to analyze different sorts of data sets on your own. We can spend 1 month practicing different data sets on Kaggle every day. Doing this activity will give you a boost in confidence as well as help you understand why you did what you did till the point. Next up, you have to take on machine learning algorithms. This is the area where most of the data science aspirants or beginners give up. They try to learn the workings of machine learning algorithms and their logic, but don't comprehend how to apply these algorithms to data and when. They fail to understand a problem in mathematical format and propose a solution using logical reasoning and machine learning algorithms. This is the challenge we need to address at any cost. So what I would recommend is you should learn machine learning algorithms with a hands-on approach. Let's say you understand a certain ML algorithm after watching a video on YouTube, then you need to go onto Kaggle and go through the sample exploratory notebooks based on the very same algorithm. Take pen and paper and jot down what you understood about the exploration. Learn about feature selection techniques, how fine-tuning can be achieved, etc. Keep on doing the Kaggle notebook exploration until you gain a knack for picking patterns in dataset. To do this, we would recommend you spend 3 to 4 months. Once you have a deep understanding of machine learning, walk the extra mile and learn about deep learning, natural language processing, computer vision, etc. For this, you can dedicate an extra 3 months. By fulfilling step 6, you'll acquire all the beginner level data science skills that can get you a job. Although it would take 9.5 months to do so, the efforts will definitely pay off. Next, you'll need to work on building your portfolio as a data scientist. You need to have some good projects under your belt. You can get them done by participating in Kaggle competitions and showing off your skills to the world. Not only will this help you build some awesome projects, but it will also provide you with awards and employment opportunities as well. Mention the projects and competitions you have participated in over to your LinkedIn profile. You can spend 2.5 months working on projects and building your LinkedIn presence. If you follow all these 7 steps and dedicate 7 to 8 hours of learning time every week, you'll be able to master data science for sure. I know that keeping track of what we have covered might come as a challenge. So we have prepared a year-long slow-paced study plan for all of you guys. The link is available in the description. Visit it and get started on the data science learning journey. I hope you guys are clear with the data science roadmap. Remember guys, learning skill takes time. There is no shortcut. And if someone comments that it is possible within a shorter duration, please don't follow along. Give time and prepare well. And you'll become the best professional that every company out there is looking for.
So what does a data scientist do? A data scientist is responsible for analyzing large amounts of data using various scientific methods, processes, algorithms, and systems to extract insights and knowledge that could be used to inform business decisions, drive innovation, and solve complex problems. Here are some of the key tasks that a data scientist may perform, starting with data collection and cleaning. Data scientists are responsible for collecting and preparing data for analysis. This includes identifying relevant data sources, cleaning and processing data to remove inconsistencies and errors, and transforming data into a format that can be easily analyzed. Second, data exploration and visualization. Data scientists use statistical methods and data visualization tools to explore and analyze data. This includes identifying patterns, trends, and relationships in data and using visualization techniques to communicate insights to stakeholders. Third, modeling and analysis. Data scientists develop mathematical models and algorithms to analyze data and make predictions. This includes using machine learning and artificial intelligence techniques to develop predictive models that can be used to inform business decisions. Fourth is deployment and monitoring. Data scientists are responsible for deploying models and solutions in production environments and monitoring their performance to ensure that they continue to provide accurate and relevant insights. Finally, communication and collaboration. Data scientists work closely with stakeholders across the organization to identify business needs, communicate findings and recommendations, and collaborate on solutions. This includes presenting findings to non technical stakeholders and working with cross functional teams to develop solutions to complex problems. Now we look at how to master data science. Step 1 is learning the basics. The first step to mastering data science is to learn the basics. This includes learning programming languages such as Python or R, understanding statistics and probability, and learning how to work with databases. So, the first step is programming languages. Python is one of the most popular programming languages for data science. It has a large and active community and a wide range of libraries and frameworks and is easy to learn. Some of the key libraries for data science in Python include NumPy, Pandas, Matplotlib, and Scikit-learn. Next is R. R is another popular programming language for data science, particularly for statistical computing and graphics. It has a rich ecosystem of packages and tools for data analysis and visualization and is widely used in academic and research settings. Next, we have SQL. SQL is a language used for managing and querying data in relational databases. It is an important skill for data scientists as many data sets are stored in relational databases. SQL is relatively easy to learn and is widely used in the industry. Next is statistics and probability. Statistics and probability are foundational concepts in data science. Descriptive statistics involves summarizing and visualizing data using measures such as mean, median, mode, variance, and standard deviation. Inferential statistics involves making inferences and predictions about a population based on a sample of data. Probability theory is also an important concept in data science as it provides a framework for dealing with uncertainty and randomness. Key concepts in probability theory include probability distributions, conditional probability, and Bayes' theorem. Next is databases. Databases are used to store and manage large amounts of structured data. SQL is a language used for managing and querying data in relational databases, which are the most common type of databases. NoSQL databases such as MongoDB and Cassandra are used for storing unstructured or semi-structured data and are often used in big data applications. Big data and distributed databases such as Hadoop and Spark are used for storing and processing large amounts of data across multiple nodes in a cluster. These technologies are becoming increasingly important as the volume of data generated by organizations continues to grow. Step 2 is working on real-world projects. Once you have learned the basics, the next step is to work on real-world projects. This will help you apply what you have learned and gain practical experience. There are many websites that offer datasets for projects such as Kaggle, UCI Machine Learning Repository, and data.gov. You can also work on projects for non-profit organizations or volunteer for data science projects. This will not only give you practical experience, but will also help you build your portfolio. Datasets and sources. There are many sources of data sets that can be used for data science projects. Kaggle is a popular platform that hosts a large collection of data sets and also hosts data science competitions. The UCI Machine Learning Repository is another popular source of data for machine learning projects. Data.gov is a government run portal that provides access to a wide range of public data sets. Open data portals maintained by governments, universities, and other organizations are also good sources of datasets. These portals provide access to datasets on a variety of topics such as healthcare, education, and transportation. Second is types of projects. There are many types of projects that can be done in data science. Classification and prediction projects involve using data to predict an outcome or classify an observation into a category. Clustering and segmentation projects involve grouping similar observations together based on their attributes. Regression analysis projects involve modeling the relationship between a dependent variable and one or more independent variables. Time series analysis projects involve analyzing data that is collected over time, such as stock prices or weather data. Natural language processing projects involve analyzing text data such as sentiment analysis or text classification. Third is project lifecycle. The data science project lifecycle typically involves several stages including problem formulation, data collection and pre-processing, exploratory data analysis, feature engineering, model building and evaluation, and deployment and maintenance. Problem formulation involves identifying the problem to be solved and formulating a clear research question. Data collection and pre-processing involve acquiring and cleaning the data to be used in the project. Exploratory data analysis involves visualizing and summarizing the data to gain insights and identify patterns. Feature engineering involves selecting and creating relevant features that can be used as input to a machine learning model. Model building and evaluation involve selecting an appropriate machine learning algorithm, training the model on the data, and evaluating its performance on a test set. Deployment and maintenance involve integrating the model into a production environment and continuously monitoring its performance. Moving on to step 3, specialize in a domain. Data science is used in many domains such as healthcare, finance, marketing, and sports. Specializing in a domain can help you gain domain specific knowledge and become an expert in that field. For example, if you're interested in healthcare, you can learn about electronic health records, clinical trials, and healthcare analytics. This will help you understand the data better and make more informed decisions. First, industry specific knowledge. Developing domain specific knowledge is essential for data scientists who work in particular industries such as healthcare, finance, or marketing. This involves understanding the business context and relevant regulations, as well as the specific data sources, data types, and data quality issues that are common in the industry. For example, a data scientist working in healthcare might need to be familiar with electronic health records, medical terminology, and HIPAA regulations. A data scientist working in finance might need to be familiar with financial data sources, financial models, and regulatory requirements. Second is subject specific knowledge. Subject specific knowledge refers to expertise in a particular area of study, such as biology, economics, or social science. This can be particularly valuable for data scientists who work on interdisciplinary projects or who collaborate with experts in other fields. For example, a data scientist working on a project involving gene expression data might need to be familiar with molecular biology and genetics. A data scientist working on a project involving social media data might need to be familiar with sociology and psychology. Third is soft skills. Soft skills are essential for data scientists who work in collaborative environments or who interact with stakeholders such as business leaders or clients. Soft skills include communication skills, teamwork skills, problem solving skills, and project management skills. Effective communication skills are important for data scientists who need to explain complex technical concepts to non technical stakeholders. Teamwork skills are important for data scientists who work in interdisciplinary teams or who collaborate with experts in other fields. Problem solving skills and project management skills are important for data scientists who need to manage complex projects and navigate ambiguity. Step 4 is staying up to date with latest trends and technologies. Starting with continuing education, Continuing education is essential for data scientists who want to stay up to date with the latest trends and technologies. This can include attending conferences and workshops, taking online courses or certifications, and reading relevant books and publications. Second is emerging technologies. Emerging technologies are constantly changing the data science landscape. Some of the emerging technologies that are currently being used in data science include deep learning, natural language processing, and blockchain. Deep learning is a subset of machine learning that involves training neural networks with multiple layers. It has been used for applications such as image recognition and natural language processing. Natural language processing involves analyzing and understanding human language and has applications in areas such as chatbots, sentiment analysis, and text classification. Blockchain is a distributed ledger technology that allows for secure and transparent transactions. It has applications in areas such as finance, healthcare, and supply chain management. Third is ethical and social implications. Data science has ethical and social implications that data scientists should be aware of. Ethical issues in data science include privacy bias and transparency. Social implications include the potential impact of data science on society and the workforce. Data scientists should be aware of best practices for handling sensitive data such as de identification and encryption. They should also be aware of potential biases in data and algorithms and take steps to mitigate them. Transparency in data science involves being transparent about the data sources and methods used in data science projects. Data scientists should also be aware of the potential impact of data science on society and the workforce. For example, data science can be used to improve healthcare outcomes, but it can also perpetuate existing health disparities if data is biased or incomplete. Similarly, data science can automate certain tasks, but it can also lead to job displacement if not managed responsibly. The final step is building a portfolio. Starting with personal projects, building a portfolio is an important step for data scientists who want to demonstrate their skills and expertise to potential employers. A portfolio can include personal projects that showcase the data scientist's ability to solve complex problems and work with real world data. Personal projects can involve working with public data sets or collecting and analyzing data on a topic of interest. For example, a data scientist interested in environmental issues might collect and analyze data on air quality or carbon emissions. Second is Kaggle competitions. Kaggle is a popular platform for data scientists to participate in competitions and showcase their skills. Kaggle competitions involve solving real world problems using data and machine learning algorithms. Participating in Kaggle competitions can help data scientists improve their skills and gain recognition in the data science community. Kaggle also provides an opportunity for data scientists to collaborate with others and learn from their peers. Finally, open source contributions. Contributing to an open source project is another way for data scientists to show their skills and expertise. Open source projects involve collaborating with others to develop and maintain software or data resources that are available to the public. Contributing to open source projects can help data scientists improve their coding skills and gain exposure to new technologies. It can also demonstrate their ability to work collaboratively and contribute to the data science community. Now we'll look at what is the demand for data science professionals. The demand for data science professionals is high and continues to grow rapidly. According to the Bureau of Labor Statistics, employment of computer and information research scientists, which includes data scientists, is projected to grow 19% from 2020 to 2030, much faster than the average for all occupations. This growth is driven by the increasing use of data in organizations across all industries from healthcare and finance to retail and manufacturing. This is indicative of the growing importance of data driven decision making in organizations of all sizes. Overall, the demand for data science professionals is high and is projected to continue growing in the coming years. This presents a significant opportunity for individuals with skills and expertise in data science to pursue rewarding and impactful careers. In conclusion, mastering data science involves a combination of technical and non technical skills and domain specific knowledge and staying up to date with the latest trends and technologies. Building a portfolio of personal projects, Participating in Kaggle competitions and contributing to open source projects can help data scientists demonstrate their skills and expertise to potential employers. As data science continues to evolve, it is important for data scientists to remain flexible and adaptable in order to stay at the forefront of this rapidly changing field.
All right, guys. So today we'll be starting with machine learning, right? The introduction to machine learning. I think we had started with a couple of slides. So we'll be properly starting with introduction to ML today, and then we will be moving on to subsequent topics. All right. So let's get started now. Uh, uh, okay. So let's today's session. Now I'm assuming that all of you have a basic understanding of Python, NumPy, Pandas, visualization. All of these topics have been covered for you, right? All right. Now, what is it that we have studied now, and what is it that we are going to study in the next couple of months, right? Now, till now, you can assume that you have had, so let's say if you wanted to do something on a computer, right? If you, let's say, wanted to use Microsoft Office, MS Word, and things like that, the first thing that we need to do was what? That we had to familiarize ourselves with a computer, right? So till now, what you guys have done is that you guys have actually uh, familiarized yourself with Python, right? What is Python? Python is a tool which will help us in creating these machine learning models that we are going to study about, right? So we have familiarized ourselves with the tool. Now that we are familiar with the tool, we will move on to the machine learning part of the course, wherein we will be picking different kinds of machine learning models that we have, and we will be implementing them through Python. Right. So, what we have covered till now was important because without knowledge of Python, it would have become tough for us to go ahead and implement these models in Python. Right. So, that is what we have done till now. What is going to come now is what exactly machine learning is, right? Today's session is going to be a general session. We are going to clear all the misconceptions about AI, ML, DL, right? Whatever terms are there, what are the different kinds of models that we have within machine learning and all. And then after today, we will be moving on to specific models from tomorrow onwards, right? So let's get started. Machine learning using Python. This is just a basic visualization which we'll be covering. Let's get started with machine learning around us, right? Now, all of you, I am assuming that if you have taken, let's say, a data science course, a business consultant course and all, right, so you would be aware of what you would be doing at the end of the day, right? But still, if you see, there is a lot of machine learning, there is a lot of data science that we are able to perceive around us as well, right? If you go back 10 years from today, maybe not as many companies, maybe not as many websites and applications were using data science, we're using machine learning per se, right? But now you can see that every platform, right? Because there are so many users, there is so many data that they are collecting, right? There is so much amount of data that they are collecting that they cannot do without the implementation of, let's say, data science in their application, website, whatever system they have, right? Now we are going to go through some of the common examples that we have of machine learning around us, right? Before proceeding, do you guys have any examples from your personal life that you feel that might be machine learning? Any idea? Some examples from personal life. Alexa, yes. Recommendations on Netflix, very good. Reel suggestions, Instagram, Facebook, YouTube, exactly. Spotify, yes. Google Ads, Siri. The way we use our phone changes the way battery charges, very good, Rishabh. That's a very specific example. That means that you are noticing these things. That's good. YouTube songs, autoplay. Yes, autoplay. It will, let's say you go ahead and you select one song. And then on the basis of that, let's say that song was a Kishore Kumar song, right? It will go ahead and it will start selecting old songs, right? Amazon, Swiggy food suggestion. Yes. Facial detection. Exactly. Self driving cars, prediction of weather, mobile unlocking through face, very good. Google Maps, face recognition, Spotify, Hi Siri, Gmail, spam emails. Yes. So if you see, Akshay has put in an example that all of us would have seen, right? You see that automatically your spam folder gets on getting like keeps on getting updated, right? Even though you are not marking emails as spam or not spam, but automatically your inbox will know that okay, these mails might be spam. The probability of them being spam might be high, and hence your email, right? Your service provider will automatically take them to the spam folder, right? Chatbots, exactly. Autonomous vehicle, that is your self-driving cars, right? Your ADAS, right? ADAS level 1, ADAS level 2, 3, 4. This is nothing but the complexity of the machine learning deep learning models going up, right? Ad suggestions, smartphone cameras, YouTube ads, chatbot, very good. Traffic signals, to a certain extent, Mohammed Ansari. So there are certain traffic signals that actually work on the incoming traffic. Right now, your timing of the signals will be adaptive. Right, depending upon, let's say, the timing of the day, or depending upon a feed from camera, which actually gives you the real time number of vehicles, right, that might be present in the different lanes that you have. Your traffic signals can be adjusted. So not all traffic signals, but I'm pretty sure that the major cities that we have, there will be certain traffic signals. I know that in Delhi we have certain traffic signals. I am from Lucknow. I know that in Lucknow there are certain traffic signals where you can see that the timing actually adapts itself automatically, right? Same goes for Bangalore, Mumbai, and all. So that's a good example. Speech recognition, fingerprint sensor, stock market prediction. Yes, that's very good. Chat GPT and Bard. Yes, that's the penultimate level of machine learning, deep learning that we are talking about. Right? Exactly. So let's go through these, right? Very quickly, right? I think you guys have talked about this. Recommendations of products, right? The recommendations of products that we see on Amazon, right? That is generally a recommendation model, which is nothing but data science, right? Alexa, your Siri, your voice based assistants coming from any other, let's say, uh, product, right, is nothing but your pure play data science, right? It is pure play voice to text translation, and then on the basis of that, you go ahead and you do whatever the person is saying to do, right? Is asking you to do. All right. Movie recommendations on Netflix, right? On Netflix, Instagram, Facebook, YouTube, everything. Now, how does this work? The recommendation works on your historical data, on your historical behavior. Now, you would have seen that nowadays the recommendations have become so dynamic that even if you go ahead and if you, let's say 5 minutes back, you were watching, let's say, a couple of reels on cricketers, on Virat Kohli, on, let's say, World Cup, right? You will start getting recommendations on that. And the moment that you start not watching those, right? So, see, when you are watching the reels, you are being exposed to every content that is out there. But there will be some reels wherein you are just going to swipe up, right? Within maybe a second, because the content might not be interesting to you. There might be some which you watch more than one times, there might be some which you like, there might be some which you share, right? So all of this behavior is being tracked, all of your historical behavior is being tracked, and on the basis of that, your recommendations are getting more dynamic in nature, right? Even within a short span of, let's say, 20-25 minutes of you using social media, right, your recommendations can keep on getting changing if you keep on changing your behavior, right? So that is the level of recommendation systems that we have today. Traffic prediction in Google, right? So if you want to go from point A to point B, so Google comes up with an estimated time, right? So that estimated time is not a random time. It is not, because see, the estimated time from point A to point B will change depending upon what time of the day is, what day of the week it is, right? Is it a holiday? Is it not a holiday? And lots of factors, right? It will also depend on certain factors such as, like, whether there is a political rally that is going on, whether there is, let's say, an international match that is going on, whether there is a concert that is going on, right? Now, all of these things actually, so what they do is that they take historical data, they take real time data, and they merge both of these data sources and come up with an ETA, right? Generally, you will see that the ETA that they give is generally precise, right? It depends upon the way you drive. You can drive as fast you can as you can. You can drive as slow as you can. At the end of the day, there will be a difference of maybe plus minus 5-10 minutes only, right? Because it takes into account all the conditions. It takes into account the traffic conditions. It takes into account the weather conditions. Everything is taken into account, and then an ETA is given from, let's say, point A to point B, right? So these were just some general slides on what are some of the examples of machine learning data science around us. So Abhishek, Google Map will show the fastest and the easiest route. It's not always the easiest route, it will be the fastest route, right? So that is why you would have seen there was a news recently of two doctors in Kerala who actually died because Google Maps actually showed a road where there was no road, but it was a river, right? So it shows the fastest, not the easiest, right? So for the fastest, what it does is that there are lots of things, right? Now your Google Map is not just an estimation of time, right? Optimization of the route is also at play over here. So if you want to go from point A to point B, so there can be 10 different routes that can be there, right? From point A to point B. So what it does is that it sees that on the basis of the traffic conditions, what is the fastest route from point A to point B, right? Now, I believe I'm not sure if we have this feature, but ideally we should also have this feature which we can activate in Google Maps, which can probably show not the fastest, but the most, let's say, a route which will take you through the major highways and the major roads, right? I don't know if we have that right now, because you would have realized that in most cases, if you know, let's say, a particular city, and you know, if you have to go from point A to point B, what the route might be, Google Maps will try to come up with some new route, right? So let's say there is a highway. It What it will do is that it will take a diversion from the highway. It will take you through the roads of societies, and let's say inner roads of the city, and it will try to maybe reduce the time, right? Any alternative for Google Maps? Mithil, you can use navigations from your cars, you have your Apple Maps as well, right? You have inbuilt navigation as well. You have satellite navigation as well. But I don't think that there is any navigation which is more dynamic and precise as compared to Google Maps. ML does not use only Python, right? So just like that in computer, it's not only Windows on which we can work on, right? There is Linux, Unix, Ubuntu, and 10 different things, right? Mac OS and all. So Python, I would say, is the most popular language because 95% to 98% of the data scientists are using Python. Most of the companies are using Python, right? So why we are doing that, we'll be talking about that later. But then Python is the most popular language, but it is not the only one. You can create data science machine learning models using R. You can do that using other tools as well, right? So it's not only Python, but Python is the most popular language. See, that depends upon what you might have entered some location thinking that it is in Delhi. Maybe the map would have taken some location which is somewhere else, right? We have features like skipping toll or not, right? So if you go ahead and if you give, let's say, the destination at some point, let's say 500 kilometers down the line, it will give you options of, let's say, one route which might be the fastest but might have tolls in it. It will give you another way which might be longer but might not have tolls in it, right? So if you're looking for a cheaper way to travel, maybe you can take the no toll road, right? So that option it has, but I don't think that it has the option of going through, like, giving us options of whether we need the fastest or the most convenient option, right? Let's say there is a Google car that travels, right? And they will try to come up with funny posters and all in front of the Google car, and then they will try to locate that in the satellite, right? In the satellite image. In Google Maps, they will go to Street View and they will try to identify that. So how it works is that, yes, it does not get the entire data from satellite, right? It will get the overall data, let's say the weather conditions and all from the satellite, but the exact, if you see, we have a view wherein we can go ahead and we can do a street view, right? So for the street view, there are actual Google cars which travel across with cameras and which are actually capturing the street view. So it is a combination of that along with the satellite feed that you get. The satellite feed will give you general updates, right? So let's say that there was a flyover, or there was no flyover from point A to point B, and 6 months down the line, there was a flyover, right? Now, that is something that the satellite feed will be able to automatically update, right? But for the street view and all, obviously, satellite view will not be able to penetrate through that. So, for that, we have Google cars and all, which actually travel through the entire whatever routes, whatever options you might have in a city, right? And then it tries to generate the data. All right. Now, moving on to introduction to machine learning. Now, what is machine learning, right? Let's try to understand what machine learning is. We know that there is like an enormous amount of machine learning products and let's say solutions that are around us. But what exactly machine learning is? Let's try to understand that, right? Ina, just hold on for now. I'm just keeping a list. I right now you just have to follow, right? And once when take a break, I will share everything with you. I know that there will be others as well who will be coming out with emails, so let's just wait. All right, so what is machine learning now? Machine learning is a subset of artificial intelligence, gives machine the ability to learn without being explicitly programmed, right? I'm going to explain all of these textbook definitions to you. But before that, let's try to understand what machine learning exactly is, right? Just think of a skill that you would have developed, right? Maybe in your childhood, maybe playing the piano, maybe playing a particular sport, maybe driving a car, anything, right? Was it something that you were able to perfect right in one attempt, or you had to, let's say, practice, and then you were able to, let's say, perfect that? Obviously, let's say I take playing the piano, for example, right? If you play the piano, or let's say, let's take something more common, let's say driving a car, right? Now, driving a car, most of you would have maybe driven a car, maybe driven a bike, Activa, whatever, right? Now, see, you might know the basics from day one. You might know that, okay, accelerator, brake, clutch, steering, gear, and things like that, right? But once when you actually go on the road and once when you start accumulating data, right? Once when you know, so maybe the first time when you go on the road, you hit the brakes too hard, right? What is it that you learn? You learn that, okay, my brakes might be sensitive, so if I want to, let's say, stop the car in the next 5 meter, this is the amount of pressure that I need to apply. If I want to stop the car, let's say, immediately, right, this is the kind of pressure that I need to apply, right? Maybe the second time when you take the car out, you realize that, okay, for the steering wheel, when you have to take a U-turn, right, maybe you make some space towards your right hand side, only then will you be able to make a U-turn in only one attempt. Otherwise, you might have to reverse the car and then you have to adjust and then you would have to do that, right? So there is a lot of learning that you do, right? And on the basis of that, finally, maybe let's say an year down the line, maybe a couple of years down the line, you can say that, okay, I am a skilled driver, because there are so many aspects. And historically, taking whatever experiences you have had, right, taking whatever data you have collected, you have actually gone ahead and you have perfected the process of driving, right? So, just like this, machine learning is what? Machine learning is that creating let's say, I'll talk about models, right? What models are and all. Right now, just let's just think that a model is a machine learning framework, right? Creating a model which takes in historical data, right? And tries to do a specific task. So let's say I want to create a model which can effectively predict which customers of mine are going to leave my store, and or let's say, take a simple example, a model which will predict which customers of mine will buy a protein shake, which customers of buy will not buy a protein shake, right? A simple question. I want a model that will predict that will give me the probability of customers buying, let's say, a protein shake, right? Now, what I will do is that I will give some data to this model, right? Now, this model is not, it is not magic, right? It is not Harry Potter in real life, right? That it will go ahead and it will know everything. I need to give some historical data to this. So if I go ahead and I give, let's say, for the last 1 year, I give the historical buying behavior of all my customers. Maybe I have, let's say, a million customers walking into my store in the last 1 year. And out of these million, let's say I had 50,000 customers who were buying, who actually went ahead and bought a protein shake, right? Now, I have this data. This is my target variable. That is for all the customers who have gone ahead and bought in the protein shake, my target variable will become 1. For the customers who have not bought this particular product, the target variable will become 0. What do I mean by the target variable? The variable that I want to predict, or the thing that I am wanting to predict. I want the model to predict, right? Now, along with this, can you guys think of any other factors which will help me in finding out whether my customer will buy a protein shake or not, right? I want you to think of factors such as age, factors such as what other products they are buying. What features can you think of which will help me in telling whether my customer is interested in buying a protein drink or not? Gender, income, exercise, are they exercising or not, are they going to a gym or not? Now I want you to think from a retail store perspective. If you're a big bazaar, will you know things such as whether my customer goes to the gym or not? Will you know the profession? No, right? Then how can I identify whether these are people who might be interested in a protein shake? No, see, physique, appearance, all of these things are what? This is manual data. You cannot input. Say, when I'm talking about a million customers, will you wait for a million customers to step into your store and take a look at them and tell them that, okay, this one looks fit, this one might buy a protein shake or not, right? This is not effective. I want you to think of data that we can collect easily. Other food item choices, right? Maybe those buying milk, very good. What related products, exactly, right? History, previous purchases, number of times, location, similar products, right? Other products, exactly, buying preferences, exactly, right? So the gist of this is what? The buying preferences. See, how can I differentiate between someone who is interested in a protein drink and someone who is not, right? Let's say I as a customer go to the store and buy Maggie. I as a customer go to the store and I buy cake. I buy, let's say, chocolates. Do I look like the kind of a customer who will go for a protein shake? No, right? Maybe if I'm a customer who is buying, let's say, granola bars, who's buying oats, who's buying, let's say, healthy stuff, right? Maybe the probability might be higher there, right? Now, if let's say I'm able to collect this data, let's say for every customer, I'm able to collect data about the kind of products that they have bought in the last 1 year, right? Do you think that for people who have gone ahead and bought in, let's say, a protein drink, the products that they have bought along with this, will they be different for those from those who have not bought a protein drink? What do you guys think? The patterns will be different, right? People who are buying the protein drink, they might also buy oats, they might also buy, let's say, fruits and vegetables and paneer and chicken and whatnot, right? People who have not bought in a protein shake, maybe they are buying chips and wafers and Maggie and whatnot, right? Right? So if I pass the correct data to the model, right? If I pass the target variable along with that, if I pass the correct data, if I have a model, a mathematical model which is able to extract these patterns out from the features and relate them to the target variable, just like you, just like we, when we were learning how to drive, our human brain, right? Our brain was the model over here which was able to extract these patterns, right? Your brain was able to figure out that when you apply the brake with this pressure, the car will come to a dead stop, and maybe passengers who are traveling might bang their head on the dashboard, right? Then you went ahead and you adjusted the force. Just like that, if I have a model in place which is able to extract these patterns from this data, the data about the products that these customers are buying, and correlate that with the target variable, which is whether they will buy a protein shake or not, right? Now, this process is known as machine learning, right? This overall process of collecting the data, tying it to the target variable through a model, a mathematical model, is something which is known as machine learning. All right. So, Jyotsna, the target variable is the question of interest, right? When we talk about data science, when we talk about machine learning, we talk about making predictions, right? my predictions can be on any aspects, right? So prediction can be, I want to predict whether it is going to rain tomorrow or not. So my target variable will become whether it rained or not, right? Now, in this case, can you guys think of features that will be helpful for us? My target variable has now changed to whether it will rain or not tomorrow. Now, using the historical data, can you think of features which will help me in predicting whether it is going to rain or not? Weather conditions, whether it was humid or not, whether it was cloudy or not. Exactly. Very good, right? So if you see, as soon as my target variable changed, my target variable became rain or not, right? So let's say you go back 365 days. For each and every day, let's say you collect the target variable, that is whether it rained on that day or not. And along with that, you also collect other factors such as the humidity, the precipitation amount, whether it was cloudy or not, whether it was summer, winter, autumn, spring, whatever, right? You collect all of these factors. Will you or will you not be able to make predictions? You will be able to, right? If you collect the correct set of features, obviously you should be able to make predictions, right? Is everyone able to understand the what we mean by a target variable now? All right. Now, see, if I tell you that in order to predict whether it is going to rain tomorrow or not, right? I take a feature which is the number of red color cars that are present in a city, right? Do you think that this feature will be important in making predictions? No, right? So when I asked you that my target variable is rain or not, you guys came up with relevant features, right? You thought of features which will help you in predicting whether it is going to rain or not, right? So just like that, see, if you see your machine learning, your data science, it is not magic, right? It is common sense. You have a certain variable that you want to predict, the target variable, right? Now, the target variable obviously will be affected by some factors, right? When I want to say whether a customer will buy a protein shake or not, that also depends upon his or her other choices, right? So, you want to find that. Now, if in this example, let's say whether a customer is buying a protein shake or not, right? Let's say if I would have taken into account some random feature, right? Let's say the height of a person. Do you think that the height of a person will have anything to do with their probability of buying protein shake or not? No, right? So first thing that you need to first skill that you need to have as a data scientist is understand this concept, right? That see, there will be random data that will be given to you, right? But first thing that you need to do is that you need to ask the question, what is it that you want to predict? Then you need to sit and decide what features will be important, because if I would have taken random features and if I want to go ahead and predict whether it is going to rain or tomorrow, no model in the world will be able to do that, because the features that you have collected are totally random. They are not related with the target variable that you have, correct? So this is one thing that we need to understand. This entire process of your collecting the data, having a target variable, creating a mathematical model on top of that, this entire process is known as machine learning, right? Now if you look at this over here in this definition, one key term that we have is it gives the machine the ability to learn without being explicitly programmed, right? Now this is important because if you see, if I pass the correct data, if I pass the target variable, I don't have to manually sit and I don't have to tell the model that this is this and this is that, right? It will automatically extract the patterns, it will automatically extract the relationships. So machine learning is, I just need to provide the correct data to the model and it will automatically uncover the patterns that are out there, right? Explicitly being means that manually you go ahead. See, there are two things. When you, let's say, when you had to learn to drive a car, either you can have your dad sit next to you and he tells you that, okay, do this, do that, right? That is not machine learning, because your dad is giving instructions. Your dad is telling you that apply the brakes. Your dad is telling you that, okay, hit the accelerator. That is not you learning on your own. That is not machine learning, right? If instead of this, let's say you knew the basics, your dad trusted you and he said that, okay, take my car, go and drive, learn on your own, right? Your dad has given you the resources. He has given you the car. He has filled it with petrol, right? And God has given you a set of eyes, right? You just have to go ahead and you have to learn automatically, right? So explicitly programmed mean that someone is sitting next to you and telling you do this, do that, which we are not doing in this case. In the case of machine learning, we just collect the data, we give it to the model does the rest of the job, right? So that is what we mean by explicitly, right? Okay, shall we move on? Arundhati, I'll be explaining everything. We have AI, ML, and all later in the slides. So just hold on. All right. So machine learning is not this. Do not imagine a set of robots studying in a class. This is just Intellipaat being humorous, right? Now, how does a machine learn? So, how does a machine learn? If you look at this over here, right? This is an example. If you look at this, right, how can you just focus on these images, right? Just focus on these ones of a chihuahua and a cookie, right? Muffin, right? How are you able to identify which images are of a dog and which images are of muffins? What are the things that you are focusing on? Placement, maybe the texture, right? Muffins can be rough. Dogs are mostly smooth, right? The shape of the head for a dog, it is kind of triangular. For a muffin, it is kind of round, right? The dog will only have three black spots, two eyes, and one nose, whereas the muffin, in some cases, can have more than three, or in some cases, can have less than three as well, right? Now, if I'm able to understand these differences, right, I should be able to make out the difference between, let's say, a dog and a muffin, right? Correct. So this is exactly how your machine also learns. If I pass all of this data to my models, right, those models which are able to deal with image data, right, they will try to extract these features. They will see that, okay, all the dogs, they have three black spots, right? They might not know that these are the eyes and the nose, but they see that, okay, these are three black spots. All the images wherein I'm saying that it is a dog, it is kind of a triangular structure, right? But if I move to the image of muffins, in most cases, it is kind of round, right? In the case of muffins, I can see that the black dots can be more than three or can be less than three as well, right? So it will try to extract all of these rules and then it will tie them up together, right? So this is exactly how your machine learning model learns, right? So just like that, if you see the right side example as well, we have a dog, and then we have the Kentucky, we have a fried chicken, right? But so this is how it learns. Once when we move on to complicated models which deal with images and all, right, then we'll be talking about this more. But I hope for now you are aware of how machine learning models work through the examples that I have talked about at least. Okay, all right then. So let's move forward. Uh, Now, see, the example that I took, right, when we were collecting historical data, do you think that that example will work if I don't have any target variable? Let's say I go ahead and I collect all the data about the products that my customers have bought and everything. And I want to predict which customers have, let's say, bought in like which customers will buy a protein shake or not, right? I want to predict that, but let's say that is the data that I don't have. Historically, I don't have the target variable. Do you think that my model will be able to go ahead and make predictions, or will my model be able to learn which customers will buy, which customers will not buy? No, right? So without the target variable, there is nothing that we can do. Without the target variable, can the model learn? No, right? All right. So now let me give you an example. Now you remember CAPTCHA? We used to do this a lot. Nowadays as well, we are doing this a lot. Uh, Now see, there are millions and billions of images that are being uploaded on Google. Correct? And if you go ahead and if you want to search with, let's say, image of a dog, image of, let's say, something, anything, Google will automatically come up with thousands and thousands of options for you, right? The search result will give you thousands and options. Do you think that someone is manually going ahead and labeling those images? Do you think that that is possible for them to do? Ethan, I'll be talking about ChatGPT and all. Every machine learning model will have a target variable, but let's not jump into complicated aspects right now. So, Prachi, there will be gazillions of images that are there on Google, right? Even if you take all the Google employees, right, per employee, they might have, let's say, maybe a million images. That's not possible, right? Tagging these images manually is not possible, right? But what Google did was, and what almost all of these platforms do is that if you remember for from the last 10 years, we have been manually creating target variables for all these tech giants, right? How? Because if you go ahead and if you see, there are cases for these capture like things, right? Google will ask you, what are the images of a fire hydrant, right? What are the images where you can see, let's say, a traffic light, right? So you are manually creating the target label for them. Now, if there are millions and millions of users on Google, every user is, let's say, tagging 9 images. If you take this, these are 9 images, right? So when you say that this image contains a fire hydrant, this image does not contain a fire hydrant, right? You are manually creating target labels, correct? So it's a two-way street. For them, they are authenticating whether you are a robot or not, right? Initially, when we used to do this, right, uh, maybe for the first year, we were only creating labels for them, right? They were not bothered. They just, because let's say if you go back to 2010, 2011, our technology was not so advanced that a chatbot can go ahead and can tick which ones are, let's say, fire hydrant, which ones are not, right? So we are going ahead and we were actually manually creating these target variables for Google, right? Now when Google had, let's say, millions of images, and in front of that they had the target variable which you were actually creating for them, they went ahead and they trained the models. And you fast forward to 2017, 2018, your Google Photos app, it automatically goes ahead. You search with photos with car, you search with photos with dog, it will automatically give all the photos in your Google Drive, in your Google Photos, which have a car or a dog. So you can see how they have used your input to create a model to give you an application which is helping you to do things easily. Did my voice break in between, Prachi? I think so. Creation of the target variable becomes very, very important. Data, obviously, your features, historical data is important, but along with that, the target variable creation is also very important. One more example, go back 8 years from today, Facebook, right? You remember we used to manually tag photos. Okay, this is me, this is my mother, this is my friend, right? Manually, we used to tag profiles. Remember? These days, we do not do that. Why? Facebook was asking you to create the target variables for them because it doesn't know that the image contains you, your mother, your father, your sister, brother, friends, and all, right? So we were actually creating target labels for them. Now, let's say after an year, Facebook had, let's say, 50 samples of your photo, maybe 50 samples of your friend's photo, because maybe 10 samples are coming from your profile, 30 samples are coming from his profile, another 10 samples are coming from some other profile, right? So when you had enough number of samples, you go ahead and you train a model, and now automatically for any user that who has been on Facebook, Instagram for a long amount of time, it will automatically be able to label them, tag them, right? Okay, it will also ask you, is this you, right? For images which are blurred, for images wherein maybe your face is not visible completely, maybe a side face is there. So if you see, it is constantly improving the model, it is constantly trying to better the model that is there, right? All right, so let's move forward then. Now we are going to bust some machine learning myths, right? So we are going to talk about some notations. What do you mean by AI? What do you mean by machine learning, deep learning, and all, right? So let's go through that. Now, first thing that we need to understand is that this is the overall hierarchy of things, right? Artificial intelligence is the bigger block. Then we have machine learning, and then we have deep learning, right? Now let's try to understand one by one what do all of these things mean. Artificial intelligence. I want every one of you to pay attention, right? Any product, anything that humans create, right, which tries to replicate the job of a human is artificial intelligence, right? And a robotic vacuum cleaner, right, which automatically goes ahead and cleans your house depending upon the placement of items and furniture in your house, which will automatically create a trajectory, is artificial intelligence. A self driving car, right, which goes ahead and which takes input from the roads and it tells the car what it needs to do or what it not needs to do, right, is artificial intelligence. But all artificial intelligence is not machine learning, right? If I give you the example of the robo vacuum cleaner is not working on historical data. It is only working on a bunch of sensors and radars through which it is laying out the map of your house, right? It is laying out the structure of your house and it is coming up with a movement plan, right? That okay, this is how I am going to move, maybe in a zigzag way. Let's say that there is a table in front, it is going to change the route. So it is totally an optimization model, right? It is not machine learning. It does not need any historical data, right? On the basis of whatever the present situation is at your house, the sensors will leave out signals through which the radars and the sensors are going to create a trajectory for your house, and on that your robo vacuum cleaner will work, right? This example is not machine learning, but this is artificial intelligence. Why? Because the robo vacuum cleaner is actually helping you do something which otherwise a human would have done, right? So artificial intelligence is something that is artificially created which assists a human. All right. On the other hand, a self driving car is also artificial intelligence, but a self driving car cannot work without historical data, right? Now, a self driving car will come under deep learning or machine learning because so artificial intelligence, there can be two kinds of outcomes. One, you can have products which are artificial intelligence products, but they are not using any historical data, just like a robo vacuum cleaner. But you can also have those products which are using historical data, just like a self driving car, just like a recommendation system, just like Alexa, just like Siri. Correct? Is everyone able to understand the difference between these two? Functional robot, yes, Presley. So your functional robot as well, right? Let's say you go ahead and you create a robot which will help you in cleaning your dishes, right? So that is artificial intelligence. It might not take any historical data, right? So anything that you are creating, right? So you have seen robot restaurants, right? You would have seen in most of the cities nowadays we have a robot restaurant wherein a robot will serve food to you, right? Now, that is not machine learning because the robot cannot improvise on what it needs to do. There is a predefined set of steps that it will have to do. But so that is artificial intelligence, but that will not be considered as machine learning or deep learning. Face recognition is AI. Yes, Jyotsna. So a self-driving car cannot be just AI. Without historical data, you cannot create a self-driving car. I will be talking about these dynamics later on as and when we move to more complicated things, right? But your self-driving car cannot work without historical data. Yatharth, I have not yet come to ML. I am just explaining the two kinds of products that we can have within AI, right? Your artificial intelligence can have data backed products and it can have non data backed products. Non data backed products, example being a robo vacuum cleaner or a robot that helps you clean your dishes, right? These products, they do not need any historical data, right? Then there can also be certain products which need historical data, right? I want you to just, if you are able to understand the difference between these two, that is it for now. Deep learning, machine learning, I have not yet covered that. So please don't ask questions on what deep learning is. Let me cover that first and then you can ask those. So facial recognition works on data. So obviously anything that works on data is also artificial intelligence, right? I'm not saying that only the things that are not working on data is artificial intelligence. I am saying that artificial intelligence will encompass both the cases. fingerprint, face recognition, everything that is ML and DL, and anything which is ML and DL is by default AI, right? Kaushik, not all AI is designed with the help of machine learning. Only those products which are backed by data are held by machine learning, right? Is a deep learning based AI model. So all ML, not maybe, all deep learning and machine learning models are artificial intelligence, but all AI is not ML. Historical data, just like the examples that I've given, right? If you want to predict whether it is going to rain tomorrow or not, you need historical data about when rain has happened in the past, when rain has not happened in the past. Prabhu, this entire course is about examples of AI with historical data. So right now, just try to understand the basic differences. Just try to clear your confusion about what AI, ML, and DL is. Then obviously, as in when we proceed through this course, we will be talking about many more examples. Yes. So facial recognition is artificial intelligence, right? But obviously, within artificial intelligence, it will belong to the machine learning category. ML will require data. AI might or might not. Yes. Now, is everyone able to understand what artificial intelligence is? Right? Now, within artificial intelligence, we have, if you see the smaller bubble, is what machine learning. Machine learning is that all of the products within artificial intelligence which can work only with the presence of data, right? The ones that, so if you see over here, if I talk about if I talk about the robo vacuum cleaner, right? The robo vacuum cleaner will be here, right? Okay. But if I talk about, let's say, a recommendation system, right? A recommendation system which is working on historical data will be here, correct? Right? Because the recommendation system cannot work without your historical data. So it will be within machine learning. All right. Any questions between AI and machine learning? Between the differences of AI and machine learning? AI is the superset, ML is the subset, DL is not the intersection of both, DL is a subset of ML, right? So now I will come to deep learning. Within machine learning, right, there are certain advanced models, right? There are certain machine learning models which try to imitate the functionality of a human brain, right? If you see, the human brain is the most complicated model, right, which can learn things on its own, correct? We know that we have been learning so many skills right from the day when we were born. We learned how to walk, we learned how to sit, we learned how to speak, and gradually we keep on learning complicated things, right? Now, when you are 20, 25, 30 years old, right, with the combination of movements of your hand and foot and whatnot, you can do so many complicated things, right? You can multitask the potential of the human brain doing stupendous things is unlimited, right? Correct. So there are some models which are highly advanced, right, which try to imitate the functionality of the human brain. How does it try to do that? All of that we will be covering when we get started with the deep learning part of this course, right? But those models within machine learning which are way too advanced, right? So it is just like in the world of cars, if let's say all cars were machine learning, right? So your electric cars can be deep learning, right? Because they are actually slightly more advanced, right? They are actually working without the need of, let's say, fuel, right? They are working on a battery. But both of the cars are doing the same thing. They are transporting you from point A to point B. So all the machine learning that you have, their end goal is to go ahead and make predictions using data. But within that, there will be a subset of models which are highly advanced, which try to imitate the functionality of the human brain. And that is what those models are known as deep learning models. All right. Chat GPT is a deep learning model. So deep learning, right? Within machine learning, there is a separate bunch of models, right? Inside machine learning, which are known as deep learning models, right? Now, the deep learning models are specific models which are highly advanced, which try to imitate the functionality of the human brain. How it does that and all that is something that we'll save for later. Right now, all you need to understand is that you would have heard of models such as neural networks, right? Artificial neural networks, deep neural networks, recurrent neural networks. And have you heard the word neurons in a human brain? Presence of perceptrons, neurons in a human brain, right? So just like the neurons work in the case of a human brain, right? When you do something, there is a certain part of your brain, there is a subset of neurons within your brains that actually fire, that gives signals to the different body parts that you have to do this, you have to do that, right? Just like that, there are certain deep learning models which try to imitate the functionality of the human brains. They try to create artificial neurons. These neurons only fire when the need is, right? Right now, it's not the time to go ahead into the technicalities. All you need to understand is that these are complicated models which try to imitate the behavior of a human brain, all right? And that is deep learning. So now if you see, if I talk about chat gpt, now chat gpt is something that will come over here, right? So chat GPT is a, if you see chat GPT exactly behaves like how a human will, right? You ask something and it comes up with an immediate response, right? A dynamic response. And that is what you have over here in chat GPT. All right. Shall we move on then? All right. So all of this we have explained. Artificial intelligence area of computer science emphasizes the creation of intelligent machines that work and react like humans, that is AI. ML, a subset of AI which gives the machine the ability to learn without being explicitly programmed. We have talked about this as well, that when we give data to a machine, it will automatically learn what it needs to do, what it not needs to do. That is ML. DL, it is a subfield of ML which is concerned with algorithms which are inspired by the structure and function of the brain, called artificial neural networks, right? So I hope all of this is clear to everyone. AI, ML, and DL. Now we will move on to myth number two: robots will take up our job, right? What do you guys think? Is this a myth or is this a reality? So, partially true, right? Exactly. It's not totally true. See, it is not going to take up your job, it is going to make your job simple, right? Say, 50 years before, when the computers were invented, people were scared that computers will take up their jobs. Did it take up jobs? It might have, right? Maybe 10% of the jobs. But did it create extra jobs? So many, right? India, Bangalore, Gurgaon, cities like these, right? They are existing, they are into, they are dominating the Indian ecospace. Why? Because of computers, correct? So with the advent of computers, yes, there were jobs that were taken, right? But then there were, maybe if 10 jobs were taken, 100,000 jobs were created as well, right? So yes, there will be certain recurring jobs that might be taken away. But then that is why you guys are here, right? That is why I have a batch of 190 people who want to learn about ML and DL and what data science is, right? Because you guys want to upskill yourself. With upskilling, obviously, you might be able to do much more complicated things in a more easier way, right? So it will not take up your jobs, right? And that is something, because see, I've been using chat gpt for 8 9 months now, right? uh, i I know that chat gpt, right, the output that it gives depends upon the sophistication of the question that you ask to it, right? You will ask a dumb question, it will not have that much intelligence that it will tell you that no, you have framed the question incorrectly. It will give you a response, right? So it takes a human to extract relevant information out of tools like these. So it will not take your job, it will make your job easy. How it has made my job easy? So last year I did something for my client which took 5 days for my team to do. This year the same thing we had to do for the same client, and we did it in a day, right? Because of chat gpt, we were able to come up with a code which was able to, so we did not spend too much time writing the code. All we had to do was we had to give instructions. But these instructions, if I ask someone who is from, let's say, a non data science background, they will not be able to give that because they don't have the experience. So if you don't have the experience, now you can be a very good driver of cars, but if I give you a truck to drive, if I give you a bus to drive, will you be able to drive that? No, right? It will require experience, right? So obviously, these tools are there to help. Your artificial intelligence, all of these things are there to help, right? It will enable you to do more things. It will enable you to do things fast, right? It will enable you to do more complicated things in an easier way. But say, for people who don't like to stay updated, right? You would remember the case study of Nikon, right? Nikon was the, I think, camera, Kodak or Nikon, right? I'm not sure if I remember the name, but they actually, when digital pictures came in, right? Kodak was a company. They actually were resilient. They said that okay, this is not going to stay. They did not upgrade themselves, and eventually they went out of business because right now we are living in a world wherein physical cameras are not even, no one is using that, right? Nokia also, right? So you need to be, obviously you need to be updated with time. Things are getting more tech savvy, so you need to be updated. That is why I have you guys here, and there are thousands and millions of people who are not doing this, who are still living in a bubble that okay, AI is not going to take the world, right? It is doing that, but if you work along with it, you will also grow, right? All right. So this is obviously a myth. So Kodak, Nokia, Panasonic, Xerox, yes. Marketing myopia, exactly, Karan. Hindustan Motors, yes. All right. So let's move on then. Now we will move on to the types of machine learning models, right? Now we have talked about machine learning, but there are different kinds of machine learning models that we have, right? So let's try to understand what these are, because all of the models that we will be studying in the duration of this course will either belong to one of the three categories that you see over here, right? So there are three categories that we have within machine learning, the kind of models, right? The first is supervised learning. Now, what is supervised learning? The examples that I have taken, right? If you see in those examples, we had some data and we had a target variable, right? So there are a bunch of models within machine learning which are known as supervised learning models. These are the models that work with the presence of a target variable. So these are the models which are very similar to the example, that is, let's say I tell you that this is what your target is, right? Let's say your father, he comes and sits next to you and he keeps on telling you that okay, this is the target, you have to do this. Let's say you, the next thing that you have to do is this, next thing you have to, let's say, drive on a highway, you have to change the gear from third to fourth and all, right? You know the target, you know what you are given with, right? And you go ahead and you try to come up with a solution for that, right? So supervised learning is that branch of machine learning wherein you pass a set of features to the model, your data to the model. Along with that, you also pass the target variable. The target variable will tell you that historically, this is how your customers have behaved, right? Go ahead, take the target variable, take the data, and try to come up with patterns that are there, right? So that is known as supervised learning. Exactly. In supervised learning, we will have the input as well as output variable, right? So your target variable will also be there and your features will also be there. Now we also have another sets of models which are known as unsupervised learning, right? Now what is unsupervised learning? As the name suggests, there is no target variable over there, right? There is only features, right? Now there can be cases when you don't have a target variable, but you have lots and lots of data, right? So these are models which do not require a target variable to work with. Now, let's say if I go ahead and I give my customer data, my historical, all my historical customer data, that how many customers I have, what are the products that each and every customer has bought in the last 1, 2 years, whatever, right? And if I apply such models without any target variable, what these models do is that they try to come up with general trends and patterns. So, a very common unsupervised learning model is clustering, right? What clustering does is that it tries to identify customers who are buying similar products. Now, see, for clustering, I don't need any target variable. If I see that, let's say, these are 1,000 customers, all of whom are only buying, let's say, liquor and snacks from my store, I will go ahead and I will say that, okay, these are similar customers. Let's say I have another bunch of customers who are buying bread, butter, eggs, chicken, and let's say such fresh items, right? Maybe all the fresh items, they are not buying pulses, they are not buying rice, they are not buying, let's say, bathroom essentials and all, right? So, on the basis of the products that these customers have bought, these unsupervised learning models will group them together, right? So, unsupervised learning, that branch of machine learning which does not require a target variable, it still requires historical data, right? That is why it is machine learning, but it does not require a target variable, right? Are you guys clear between the differences of supervised and unsupervised learning? I hope everyone is clear with that. Supervised needs a target variable, unsupervised, no target variable, right? Example of unsupervised is clustering. Supervised learning, the examples that we have taken, predicting whether it is going to rain or not, predicting whether my customers will buy protein shake or not. For more examples, just hang on. The next couple of months, we will be talking about so many supervised case studies, spam classifier, right? So I think do not even wait for the next 2 months, right? Just wait for the next 15, 20 minutes as well. We will be going through the examples, right? See, that is the objective of the model, but you are not explicitly passing any data, right? You are not saying that these are the customers who are buying beer, these are the customers who are buying milk and eggs, right? Model is automatically finding that. Obviously, there is an objective of the model that will be the target, but you are not explicitly giving the target as data, right? And that is unsupervised learning. Supervised learning is based, yes, mainly based on yes and no, right? Depending upon, so customer buying a product or not, customer attriting or not, whether it is going to rain tomorrow or not, should I give a loan to this customer or not, right? So questions such as yes or no. So not only yes or no questions, Pooja, just wait on. We'll be talking about supervised learning can be of two types. We can give responses to yes or no questions, or we can also give continuous responses such as the amount of spend that a customer is doing, right? 20 rupees, 100 rupees, right? So let's move on to reinforcement learning. Now, see, reinforcement learning, Charan, just wait. Now, reinforcement learning is the third kind of machine learning. Now, these are those models which automatically, right, adjust their predictions, they adjust the quality of predictions on the basis of your data distributions, right? Now, what do I mean by this? Your reinforcement learnings are those models. So this, you can say that these are the deep learning models which have the ability to adapt, right? When I say the ability to adapt, so let's say I created a model, let's say I created a supervised learning model back in 2020 which was predicting what are the, let's say, items that my customers are going to buy from a medical store, right? Now, back in 2020, this supervised learning model would not have known that COVID is about to come. So maybe this model does not know that mask or sanitizers will become an important part of the future, right? So this model, even today, if you go ahead and use this model even in 2023, because it was created using 2019, 2020 data, it does not know that masks and sanitizers have become a crucial part of every human's life today, right? But the reinforcement learning model, if I talk about reinforcement learning models, right, these are models which keep on updating their predictions as per the customer behavior keeps on changing. So, what the reinforcement learning models do is that they have a feedback loop. That is, from the prediction, the feedback loop will go to the data. Now, let's say back in 2020, my customers were buying something. Now, in 2021, as soon as my customers started buying masks and sanitizers, your reinforcement learning model will retrain itself, right? It will retrain itself and it will adjust the predictions accordingly, right? So as and when your time progresses, if your customer behavior keeps on changing, your reinforcement learning models, which are slightly more complicated models, try to adjust the quality of predictions that they have, right? So that is your reinforcement learning. We are going to talk about all of these in detail as and when we proceed to the course, right? Right now, all you need to understand is that what are the differences between these three, correct? So this model will take feedback from the data, take feedback from how the customers are behaving, and it will update the predictions accordingly, right? So if you see supervised learning, reinforcement learning is more accurate. I would not say more accurate, but it is more robust to time related changes. Ethan, your supervised learning can be as accurate as reinforcement learning, but only till the point that your customer behavior remains the same. The moment that your customer behavior changes, your supervised learning models will lag and reinforcement learning models will adapt, right? Features will obviously be required. No model can work without features, without data, right? Everything will obviously be required. So if you see, supervised learning is nothing but you have a teacher which is actually helping you in understanding what is an apple, what is not an apple, and all, right? Okay, so if you see, that is supervised learning. What are the use cases of supervised learning? Use cases are spam classifiers. We have spam classifiers automated in the emails, which will automatically detect whether an email is spam or not spam. How does it do that? It sees that historically all the emails that are spam, let's say they contain, you have won $10,000, $1 lakh, or let's say apply for a credit card and things like that, right? So any future email that comes, whichever emails have these critical keywords, right, it will automatically assign them as spam. Fingerprint analysis, right? All of this is what this is supervised learning. Your historical data is there. As soon as you go ahead and let's say you enter your fingerprints on the sensor, whatever, right? It knows automatically that this is you. It will have all your details, right? Maybe Aadhaar card or things like that. Unsupervised, if you see, there is no target variable. If I give this data to my model, it will automatically find out on the basis of similarity. Now it sees that these three bananas look very similar, so maybe I should group them together. It sees that orange is right, these three look very similar, the color is same, the texture is same, so maybe I should group them together. It sees these apples and it says that okay, these look similar, so it will automatically group them together, right? So if you see, for unsupervised learning, I do not give any target variable. I do not give any, I explicitly do not tell the model that these are apples, bananas, and all. It will automatically cluster them into your different segments, right? Robots, right? In robotics, reinforcement learning is used a lot because your robots, maybe the first time the robot goes ahead, let's say you create a robot which is supposed to play football, right? The first time when it goes ahead and it kicks the ball, it is not able to kick the football, but it knows that okay, my target is to kick the football. So there will be positive points and there will be negative points. Whenever the robot does a behavior which is not appreciated, points will be deducted, right? The objective of the robot will be to go ahead and achieve as many points as it can, right? So that is reinforcement learning in real life. Clustering is for unsupervised learning. Unsupervised ML clustering, done clustering, right? After that, we can go ahead and we can just scan through the clusters and see whether this group belongs to customers who are buying beer, whether this group belongs to customers who are buying milk, and things like that, right? We need to do that. All of this we are going to study during for the entire duration of this course, right? Course. Unsupervised clustering, there are other, Ishan, there are other models as well, dimensionality reduction and all, right? So don't worry about the topics. Obviously, as and when we proceed, we will be covering all of these topics, right? Unsupervised learning, the two major topics are clustering and dimensionality reduction. So, not you, the model will automatically try to do that, right? In this case, the model will realize that, okay, apples are round and apples are red. Oranges are properly round and they are orange. Bananas are long and they are yellow, right? And it will try to differentiate on the basis of these features. Right now, use case of unsupervised is voice based personal assistant. If you see voice based personal assistant, right, they don't have any target variable. Their objective is to just take an audio data and convert that into text, right? So that is unsupervised learning. How all of this works, we are going to understand later. Netflix recommendations, if you see, if I'm able to group the movies which are similar together, right? Let's say I group all the fictional movies, I group all the action movies, animated movies, right? And let's say you as an end user, you went ahead and you watched animated movies. Now I can start recommending any animated movies from that cluster to you, right? So your recommendation systems are nothing but unsupervised learning. Supervised learning, because it knows which emails are spam. See, historically, you would have done, not you, but all the users, let's say in Gmail, if you remember historically, all these emails were not tagged as spam or not spam. We manually had to do that, right? But once when they had enough data, they were able to create a model for that. So all of that is supervised learning. If model does it on its own, that's unsupervised. Yes. Else, if we pass a target variable, then it is supervised, right? And now moving on to reinforcement learning. Reinforcement learning, if you see here, the model constantly keeps on updating what it's doing, right? We do something and then we reward or penalize the model. Let's say my model and goes ahead and says that my customer will buy a protein shake, but the customer does not go ahead and buy the protein shake. I will come back and I will say, for this customer, your prediction was incorrect. So you need to go ahead and you need to update the rules that you have extracted, right? So that is reinforcement learning. So what will happen is that either you will reward the model or you will penalize the model. On the basis of that, the model will update the policy and it will iterate the process. Now, the classic example for this is your self-driving cars, right? It will take the history, but you don't have to give any target variable, right? In unsupervised learning, if I go ahead and I give all my data about all the movies and the genres that they belong to, right? Unsupervised learning will be able to group the movies together, right? Movies which are similar will belong to one cluster, right? Movies which are, let's say, on the basis of that belong to action genre will be mapped to one cluster. Movies, let's say, which are directed by a specific director, let's say Christopher Nolan, will belong to one segment, one cluster, right? All of this will happen automatically. All right. So supervised learning, unsupervised learning, clear to everyone. I hope no questions there. Now we'll move on to reinforcement learning, right? Now, reinforcement learning, as I've discussed in this case, right? We observed select action using policy. This is nothing but we collect data and we select a model, right? And the model will go ahead and give us the predictions. The predictions are nothing but action, right? So when it goes ahead and gives the predictions, then we collect. So let's say if I have 100 customers, right? Now for 100 customers, let's say for 60, the model gave the correct prediction, and for 40, the predictions were incorrect. So accordingly, we will either reward or penalize the model. Now, in an ideal situation, the model should be able to score 100 points. Let's say one customer, correct prediction one for one customer attributes to a single point. Ideally, the model should collect 100 points, right? But let's say if it gives 60 correct predictions and 40 incorrect. Let's say there is a plus 1 point for a correct prediction and minus one for an incorrect. The model will end up gathering only 20 points, right? Because 60 plus 60 minus 40 will be 20. Now the model tries to optimize, or the model tries to maximize the points that it can achieve, right? So if you see after that, in step 5, it will update the policy. It will try to update the rules, that is because something that it is doing is incorrect, right? Because of which these 40 predictions are coming out to be wrong. So it will try to improvise on that, right? And then this process will go on and on and on until it is able to come up with the maximum number of points, right? So that is what reinforcement learning is. It will update on its own, Prabhu, as long as your data is being fed to the model, right? As long as that there is a continuous pipeline of the data, right? Your model will automatically update the rules, right? And if you see, this is something that we can uh, showcase through this example, right? Now, let's say before conditioning, there is a dog, and this dog, let's say, goes ahead and whenever this dog sees food, it starts to drool, right? Now, reinforcement learning is forcing something to do something which you would want this person or this object to do, right? Now, let's say the next time whenever you give food to this dog, you ring a bell, right? Every time you keep on doing this, whenever you give food to the dog, you ring a bell. And finally, let's say that you have done this process for many number of iterations. Now, one day, if you just go ahead and ring a bell, you don't even give any food, the dog will automatically start drooling, right? Now, this is kind of reinforcement training that usually people do, right? In order to train dogs, in order to train, let's say, animals and all. This is not very close to the example that we have taken, but this is just an example of how Pavlov was maybe a scientist or something, how he actually trained his dog using reinforcement learning, right? So this is just a general example of how exactly reinforcement learning works, right? Now, the typical use case for reinforcement learning is self-driving cars. How? So now all of these cars that you are seeing, right? XUV 700, the self-driving cars, right? With ADAS level 1, ADAS level 2, and all your Teslas and all, right? Do you think that these cars are straight away made and then just rolled out for public? No, right? There is years and years worth of testing and training that has already happened. When let's say if I take an example of an XUV 700, when it was rolled to the public, right? The model that it is using, that would have been trained on using years and years of data. Maybe XUV 700, the inception of the car would have also not been thought of at that point of time, but the model training would have actually commenced, right? Because you can train the model on any car, right? Now, what is this training? This is, see, when, let's say, when I want the car to apply a brakes, right? Let's say in the first iteration, it does not go ahead and it does not apply the brake, and maybe it rams into an object, right? Now, what will happen? I will go ahead and I will give a penalty to this particular action, right? Now, the next time, the model that is running the car will try to update the policy, and on this basis, it continuously, we expose the car to different scenarios, we expose the car to different uh, let's say locations and different situations, right? And we expect the car to train automatically. Why do we want to do this? Because I don't want to create a model which is limited by its learning capability, right? As in when, because see, when, let's say, I buy an XUV 700 and I am, let's say, an aggressive driver, right? Some other customer buys an XUV 700 and this person is a safe driver, right? Now, the ADAS that you have, right, it needs to adapt as per the driver, right? Now, if the driver is aggressive, then maybe the reaction time needs to be slightly fast, right? Now, right now, we are not at a stage wherein we are actually able to see such level of autonomous driving, but eventually, once when these models keep on training, right, just like in the case of Facebook, now that it is automatically able to tag photos, just like that, eventually when we would have collected enough amounts of data, right, we will reach a situation wherein this automated driving can actually be made seamless in, if not all, then probably most of the driving situations, at least in India, right? But this is the, at the back end, the model that is working is nothing but a reinforcement learning model, right? So this was supervised, unsupervised, and reinforcement learning. So self-driving cars, it is not a simple thing, right? It is a combination of different kinds of models. It is reinforcement learning, it is deep learning to a certain extent, it is unsupervised learning. So there is not one single model that is at play over here, right? But the heart of these models will be the reinforcement learning model. Reinforcement learning can be deep learning models only, right? Reinforcement are advanced models that we have. Right. So now moving on to what we can do with machine learning. So if you see what kind of questions we can solve, right? Now we can answer any kind of questions using machine learning, right? Questions such as, is the email spam or not spam, right? Questions such as, what is the price of a house, right? Questions such as, will my customer buy a product? Questions such as, how much spend my customer is going to do in total, right? So there are any kind of questions that you have, we are able to answer those through machine learning. But depending upon the type of questions, we again go ahead and we divide these models into the different categories. Let's try to see what these mean actually, right? Are reinforcement learning models deployed only after achieving 100% score? Actually, not 100%, but maybe you have a predefined cutoff, right? Maybe you say that, okay, 90%, 95%. It depends upon that. But generally, there will be a list of to dos, right? So let's say if you expect your model to do 100 things, then once when the model is able to do those 100, maybe there are additional 50 that the model is still not able to do, and that is what your ADAS level 1, level 2, level 3 and 4 are, right? So till the point that your model is able to do, let's say, 100 things, maybe you will go ahead and you will roll out ADAS level 1, right? Now, adaptive cruise control, if you see level 1 and level 2, you will have features such as adaptive cruise control. Adaptive cruise control is what your car will automatically update the speed depending upon the object in front of it, right? So all of this now gradually, if you look at a totally self-driving car, that is a combination of adaptive cruise control, steering control, object detection, lots of things, right? So depends upon how many checklists or how many items your model is able to do perfectly, and then you roll out different phases, right? Lane monitoring, exactly. I don't think that, see, Teslas, they are slightly ahead, or I think very ahead, when you talk about self-driving cars, right? Because they have been in the market for quite some time now. But still, there are occasions, there are instances, there are news wherein maybe a Tesla is also not able to do something as it was expected to do, right? Now, if I remember some time back, there was an accident that happened for a Tesla car, which was driving on a freeway, right? And in front of the Tesla car, actually, there was a truck that was crossing, right? It was the truck was actually mm, it either it was crossing or it was in front of the car. I'm not sure, but the background of the truck was actually in line with the color of the sky, right? That was exactly blue. I'm not sure it was still moving and all, but the color of the truck was actually very similar to the color of the sky at that point of time, and the car was not able to make out between the truck and the sky. It thought that it was the sky, and it just went on speeding and it rammed into the truck, right? So there might still be 1%, 2% of the situations that the car might not have been exposed to. So, to the situations in which the car might not have been exposed to, now you take a Tesla, you bring it to India. Do you think that it will be able to drive seamlessly? No, no, right? There are dogs, there are cows, there are people who are just coming in front of the car, so many bikes and all. It will obviously fail. So, it depends upon the situation, right? It depends upon the level of training. Now, if you look at an XUV 700, the amount of information and the amount of data that an XUV 700 would have collected over the last 2 years would be more as compared to what Tesla would have done, because US driving norms are pretty standard, right? There are no, there are less people who are actually doing something which is not expected. But in India, when you are driving a car, 30-40% of the cases you are not expecting, people are coming in front of you, people are coming right, left, and center. Animals are there on the road and all, right? So again, it depends upon the level of training. But I don't think that Tesla is perfect. I don't think that anything is perfect as of now. But with time, as and when you accumulate more amounts of data, things will gradually start becoming perfect, right? Because by now, I hope every one of you would have realized that data science is nothing without data, right? The more data that you accumulate, the more instances that you accumulate, the better models you will be able to create. All right. Now, if you remember the supervised learning models, right? Practice makes a machine perfect, along with a daily diet of data, right? Yeah. So if you remember when we talked about supervised learning models, right? Now, supervised learning models were what? They'll have a target variable, right? The difference between supervised and unsupervised was that there should be a target variable. Now, see, what if my target variable is a yes or no thing, right? Let's say whether the customer will buy a product or not. Should I give should I give a loan to this customer or not, right? Will this customer default on his or her payment or not, right? So if you look at this target, in all of the examples, my target variable is a category, right? Is a yes or no thing. So I can represent this as a binary variable, right? Maybe one means pass, zero means fails. Maybe one means rain, zero means not rain. Maybe one means pass the loan, maybe zero means do not pass the loan, correct? So such kinds of the supervised learning models wherein the target variable is categorical in nature. Categorical meaning that the target variable is a category, right? Those models are known as classification models. Can you guys give me other examples of classification models? What can be some real life examples that we can have? Just like predicting spam or not spam, predicting loan default or not, or what can be some other examples? Think from your industry as well. Most of you would be working, most of you would be in college, right? Pass or fail. Drug will be effective or not. Yes, rain prediction. If the person is from specific city or not, that's classification, but not something worth creating a model on, right? But the money will recover or not. All right, male or female, why do you need to predict? But theoretically it's correct, but obviously transaction is fraud or not. Exactly, right? So all such problems wherein your target variable is a category will be known as your classification models. So within supervised learning, we have something known as classification models. Classification models are those models which have a categorical target variable, right? All right. Okay, now moving on, what are the examples of classification? If you see, one example is whether the transaction is fraud or not, someone trying to hack our network or not, right? So this will be one example. Clustering algorithm, which type of house lies in this segment, what type of customers buy this product, right? Here as well, if you see, this is not exactly clustering, but you can use classification to, let's say, group customers who are buying protein shake, customers who are not buying protein shake, customers who are buying healthy, customers who are buying not healthy, customers who will buy the product on an offer, customers who will not buy the product on an offer, right? If you see, in all such cases, my target variable can be categorical in nature, right? Now, moving on, the second kind of supervised learning model is a regression model. Now, if classification is categorical, what do you think regression will be? Right? Obviously, the second option that we have is what? Either my target variable can be category or it can be a continuous numeric value, right? So when your target variable is a continuous variable, right? Then those kinds of supervised learning models are known as regression models, right? Can you think of any real life, real world problems which might be regression problems? Right? So height prediction, price prediction for houses, weight, estimated delivery date. That's not continuous system. That is, uh, uh, this will be a time series problem, right? Will there be another pandemic? No, this is not. This is this you are actually. This is a vague question, right? How can you predict this? COVID numbers, yes. Stock prices, correct. Stock value high or low is not regression. Predicting the exact stock value is regression. Weather forecasting, so your temperature forecasting, yes. Age group, not age group, but predicting the age can be regression. If you group the age, then you are actually creating categories, right? How many runs will Virat Kohli score? Yes, that is a regression problem. Air quality prediction, if you are looking at AQI index, right? Exact AQI index, that is regression. Share market, number of employees leaving my company, yes, that can be regression. Road accidents, yes. Efficacy of a drug to a certain extent. Blood pressure, taxi demand and supply, yes. Sales price, yes. Profit loss, credit score, sales. Life expectancy, yes. Student grade predictions, no. Presley, grade is a category, right? Grade is not a continuous column, continuous variable. Grade can be A, B, C, D. Population is yes, right? clustering is unsupervised, regression is supervised. Regression will have a target variable, salary, birth rate, all types of prediction smartwatch, right? All right. So if you see regression, wherever my target variable is continuous in nature, my supervised learning models will be known as regression models, correct? So what I'll do is that we will stop here for today. All right. Thank you, everyone. Bye.
So question 1. What is the first step in data science process? Your options are option 1, collecting data and preparing it for analysis, option 2, experimenting with and tuning different analytical models, or option 3, defining an analytical hypothesis that could provide business value. What do you guys think is the right answer? Comment it down below. Just a quick info, guys. Intellipaat offers an executive postgraduate certification in data science and AI, where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps, and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
All right. So let's go ahead and let's get started today. So today we'll be starting from with a particular model. Audrey, not right now. First, we'll be going through the theory. We will be understanding what the model is, how does the model work, and then once when the theory is done, then we will be starting with the notebook. In form of time, then which type of problem is here? That is time series. That is time series modeling. That is also there in your curriculum. So once when we reach that part of the course, then I will be talking about time series related data, time series models and all, right? Don't worry, we have that in the course. Now, supervised learning, if you remember, we can divide it into two types, right? One when my target variable is categorical in nature, one when my target variable is continuous in nature, right? Now, the kind of model that we are studying today is a linear regression model. So when I say linear regression, what can you tell? Can you tell me something about the kind of target variable that we will have over here? Continuous, right? Yes. So now, since the model name is linear regression, so by the name itself, you should be able to understand that this is a regression model. And if this is a regression model, this is a supervised learning model which takes into account continuous target variables. Correct? Okay. So let's get started with this model. Now, linear regression, what is linear regression? Now, if you look at the name, right, linear regression. Now, what do you understand by the word linear? All of you would have heard the word linear, right? So, what do you understand by the word linear? What do you mean by this? So, linear may be a line, or maybe, so if you talk about, let's say, processes, let's say if I increase the speed of my car from 30 kilometers per hour to 60 kilometers per hour, how much distance will I be traveling in an hour? The first case, I would have been traveling 30 kilometers. In the second case, I would have been traveling 60 kilometers, right? So if you see, there is a direct relationship between, let's say, the speed of the car and the distance that it travels, right? So there are many processes in and around the world which have a linear relationship. So by linear, see, let's assume that you study for 10 hours and you score 50 marks, right? Let's assume that if you would have studied for 20 hours, you would have scored 100 marks, right? But if you study for 40 hours, will you score more than 100 marks? No, right? The maximum cap will be 100. So maybe the number of hours you study and the marks that you get, it might or it might not be a linear relationship. But if you look at the speed that a car travels with and the distance that it will travel, right, in a fixed amount of time, this will be a linear relationship, right? If my speed is low, the distance traveled will be low. If I increase the speed, let's say 5 times, my distance traveled will also increase by a margin of 5 times. Is that correct? Okay, so if now let's try to understand what we mean by linear regression, right? Now, linear regression, it is a technique of finding the relationship between two or more variables, right? Now, change in dependent variable is associated with change in one or more independent variables. Now, before jumping into this definition, let's first try to understand what we mean by dependent variables and independent variables, right? Can you guys take a shot at this? What do we mean by a dependent variable? What might be a dependent variable in a supervised learning problem, in a regression problem? So, dependent variable is the target variable, right? The variable that is dependent upon other factors, right? Exactly. Very good. So, your dependent variable. So, see, whenever I'm saying target variable, whenever I'm saying dependent variable, whenever I'm saying, let's say, your label, right? All of these words refer to the same thing, that is your target, right? The variable that you want to predict, correct? Whenever I'm saying independent variable, I say features, I say, let's say, dimensions of the data, right? Whenever I'm talking about these things, it means that I'm talking about the features, right? So let's say if I wanted to predict the time that it takes for me to travel from point A to point B, right? And let's say I take the speed of my car as a factor, as a feature, so my feature will become the speed of the car, and my target variable or my dependent variable will become the speed of the car, right? Right. So now if we go through the definition, so linear regression is nothing but it's a technique of finding the relationship between two or more variables. So my one variable will be the target variable that I want to predict. The other variable will be the independent variable, or it can be a host of independent variables. Either you can have a single independent variable, or you can have two, three, four, whatever, depending upon however independent variables you have or you need. Right? So, linear regression is a model which basically establishes a relationship between the target variable and the independent variables or the features that you have. Okay. Now, change in the dependent variable, whatever change we have in the dependent on the target variable, is actually dependent on all the features that you have. So that is why we are including these features in the model, right? Yesterday, if you remember, when we were trying to predict whether it is going to rain or not, we were taking independent features such as what will be the humidity, is it cloudy or not, right? What is the temperature, and things like that, right? So we know that target variable is actually related to the features that we have, and the linear regression model is a model which helps us in finding out this relationship, right? This connection between the two, right? That is what the linear regression model does. Now, if you look at the definition, it only tries to capture the linear dependencies, right? So if you have two features which are varying with each other in a linear fashion, that is, as one increases, the other also increases by the same amount. As one decreases, the other also decreases by the same amount. If you have such relationships in your data, then linear regression model will be able to go ahead and will be able to map the relationship and create a model for you which you can go ahead and use for future predictions. Target variable can never be more than one. Target variable, you can have the most complicated model in the entire world, but the target variable will always remain one single target variable. You cannot have more than one target variables in any machine learning model. That was a classification problem, but your features and target variable, the concept for that will remain the same, right? Co-regression is a metric, right? And correlation is something else. It is dependent. Correlation basically gives the relationship, and regression is a machine learning model, right? So we'll talk about correlation as well in some time, but these are different things. That will still be a linear relationship. So when we increase, what Ishan is asking is that if we increase independent variable by half and the dependent variable increases by, let's say, one, is that still a linear relationship, right? That will also be a linear relationship because you can still estimate this by the equation of a line, right? So regression will take all relationships, right? So if you see, if I increase the speed, my time taken will go down, right? If I decrease the speed, my time taken will go up. So it's not that it will only take positive relationships. It can take inverse relationships as well. It can take direct relationships as well. any kind of relationship which is linear in nature will actually be taken into account by the linear regression model. So it's a variable that stands alone and isn't changed by other variables you are trying to measure is independent variable. Ideally, yes, Yatharth. Weight of the product versus cost of the product. Ideally, it should be linear regression only, Prabhu, because let's say if 1 kg of rice costs 100 rupees, then 2 kg will cost 200, right? 5 kg will cost 500, and so on and so forth. So this will be regression only, linear regression only, right? Or such kinds of problems can be estimated through a linear regression model. Inverse relationship is also linear relationship. I will be covering all of these aspects, right? All these are good questions, but just hold on. I will be covering all of these aspects. For people who are not able to understand these, don't worry. We have just started, right? We have not even gone through the first slide, but all of these concepts will be covered in the coming slides, right? Now, but this definition should be clear to each and everyone, these two definitions. All right. So let's move forward. Now, if you see, regression is a technique that displays the relationship between variable y based on the values of variable x, right? Now, if you see, there is one more notation. Now, let me just write this down so that now, whenever I say target, whenever I say dependent variable, whenever I say predictor, right? Whenever I say y, right? All of this means your target variable, right? Whenever I say features, independent variable, right? Or your, let's say, dimensions or your x, right? All of these are your features. So don't get confused by these. Target, dependent, predictor, y, all of this will generally be y. I am saying y because once when we'll be working on Python, generally the target variable we denote by the variable y, right? Generally the features we denote by the variable x, right? This is a notation. This is a general kind of a thumb rule, you can say, that we use. So that's why just don't get confused by all of these, right? Now, if you see, regression is a technique that displays the relationship between variable y based on the values of variable x, right? So if you see over here, let's say this, which is your temperature, right? Your temperature is the independent variable. The number of clothing that you have to wear is your independent sorry, when your temperature is your independent variable, that is your feature, and the number of clothes that a person needs to wear is your target variable or the dependent variable. So you can see over here that as the temperature will go down, the number of clothes that a person is, let's say, supposed to wear or wants to wear will obviously keep on going up, right? So as and when it becomes colder, maybe you start wearing more layers of clothing, right? As and when it becomes hotter, you decrease the layers of clothing, right? So if you see, both of these variables will have a linear relationship. Inverse relationship, or does it have a direct relationship, these two variables? Inverse, right? If you see, when one is decreasing, that is when temperature is decreasing, your number of clothes that you are wearing is actually going up, right? So it will be inverse relationship. Independent variables behave as the input to the model, whereas the dependent variable is the output that you expect from the model. All right. When temperature increases, so let's say you have the temperature and you have the number of clothes, right? Now, let's say my temperature is 40 degrees. Maybe you wear just a t-shirt, right? Maybe once when your temperature becomes 30 degrees, maybe you wear a t-shirt, along with that you wear a vest. When the temperature becomes 20 degrees, maybe you wear a vest, along with that you wear a t-shirt, along with that you wear a thin jacket, maybe, right? It becomes 10 degrees, your clothing will go up. Maybe you wear a vest, an inner, a t-shirt, a jacket, right? Just like that. So now if you see, when your temperature is decreasing, when it is going from 40 to 10, the number of clothing items that you are wearing is kind of increasing, right? So it is not directly proportional, it is inversely proportional. Okay, so let's move on. Now, some examples, let's say temperatures versus number of cones sold at ice cream store. Now, what do you guys think? Will this have a direct relationship or an indirect relationship? These two variables, temperature and the number of ice cream cones sold. Direct, right? Why direct? Because let's say just try to take some examples, right? Assume that the temperature is 40 degrees. Obviously you will sell more ice creams. When the temperature is, let's say, 10 degrees, obviously ice creams will not sell as much, right? Okay. What about the second one? Do you think that there is any kind of a relationship? No relationship, right? There is no direct relationship that we can see. Maybe, let's say, there might be a certain percentage of people who might be planning to buy cars, let's say. So it's not, buying a car is not dependent upon whether it is going to rain or not, right? Maybe you are buying a car, maybe you are planning to buy a car and you decide to buy a car during the rainy season. But if you are someone who knows about cars, you will definitely not want to purchase a car during the rainy season, because then it might catch rust and things like that, right? So ideally, there is no direct relationship. There can be some hidden relationship over here, but there is no evident relationship with the inches of rain and the number of cars that are sold, right? So it's not about using the cars. You see new cars sold, right? That is the ask. Now, if this would have been changed to inches of rain and number of cars on the road, right? Can you tell me then what would have happened? Let's say over here, I changed this from new cars sold. It is not new cars sold, right? It is number of cars on road, right? What will the relationship be then? Then it will be a direct relationship, right? Obviously, when it is going to rain, people who have bikes and cars both, they will prefer to take their cars, right? They will not take out their bikes in such cases. Correct? All right. Now the last one, daily snowfall versus number of skier visits. Direct or indirect? Direct, right? It will be direct. As snowfall increases, the number of skiers who are visiting will obviously increase, because more the snowfall, more people would be interested in skiing, right? Now there are different kinds of regression model. Today we are studying about linear regression, right? Now if you see, in case of linear regression model, the output that we have from the model is the equation of a straight line, right? In case of linear regression, the output will be the equation of a straight line. We also have a different kind of a model which is known as logistic regression, right? Today we are not studying about logistic regression, so don't worry about that, right? But this is something that is the next topic for us. Once when we'll be done with linear regression, the next topic will be logistic regression for us, right? So today's objective is to study about linear regression. But let's just look at the differences between these two. Now, linear regression and logistic regression, right? These are two models which might have a similar name, because if you see, both are end with regression, right? But there is a very basic difference between the two. The linear regression model is a regression model, whereas the logistic regression model, right, the name is a misnomer. It is not a regression model, it is actually a classification model, right? Why this is called a regression model, this is something that I'll talk about once when we start with logistic regression. But this is ideally, right, this is a regression model, right, in a regression. But this, on the other hand, is a classification model, right? This is the essential difference. Now if you see over here, this works on a target variable which is continuous in nature. Logistic regression works on a target variable which is categorical in nature. Solves the problem of regression, solves the problem of classification. Output is a straight line, the output is a S-shaped curve over here, right? Don't get worried about what logistic regression is right now. The only thing that you need to understand is that logistic regression actually comes from the linear regression model only, right? It is a slight variation of the linear regression model. That is why the name remains the same. But at the end of the day, logistic regression is a classification model. The name is a misnomer, right? Do not confuse it by, if someone asks you whether logistic regression is regression or classification, this is the only model whose name is confusing, whereas it says that it's a regression model, but ideally it's a classification model. All right. Employees at writing, working atmosphere, all of this, see, it depends, right? For a given company, there might be a relationship. For some other company, there might not be. So there are no general answers to these things. As a data scientist, just if you want to become a data scientist, make a note of one thing, that you should never generalize things, right? Every decision that you are making, every statement that you're making should be backed by data. If you're saying that employees at writing is proportional to the working atmosphere, right, then this should be backed by data. You should have some data which actually tells you the same story, right? Only then you can go ahead and you can make such statements. So, Rishabh, what would be the kind of regression where initially the relation is direct, but as the independent variable increases value, there is a peak independent? So, Rishabh, this will not be a linear relationship, right? See, what you are saying is, let's say I have such a case, right? Let's say I have, for some amount of time, I have a straight relationship. And after that, beyond that, your relationship changes to, let's say, something like this, right? So this will not be a linear relationship, right? This will be a non-linear relationship only. So for these we have other kinds of models. Today obviously we are studying about linear regression, so we will only limit ourselves to such problems where the relationship is linear between the target variable and the independent variable. As I said, right, the name is a misnomer. If asked, all you need to say that this is a classification model. Because this is derived from a linear regression model, hence it is called as logistic regression, right? But right now, as I said, don't ask questions of topics which we have not yet started. Don't worry about logistic regression. Once when we start, I will be covering all of these aspects. Just stick to the model that we are trying to learn, right? Okay, now moving forward, simple linear regression is useful for finding relationship between two continuous variables, right? Now, obviously, the model is trying to find out relationships between the target variable and and the features that you have. So this model will help you in establishing the relationship between, let's say, two variables or howsoever many variables you have in your data, right? One is predictor or independent variable, and the other is response or dependent variable. If you see, there are so many terms: predictor or independent variable, or you have response or dependent variable or target variable, right? Now, simple linear regression is the most simplest form of linear regression model where we have only one independent variable and we have only, obviously, the target variable will remain one, right? In case of simple linear regression, I am limited by only a single feature. Only a single feature is used to predict the target variable, right? So let's try to first understand how simple linear regression works. Once when we are able to understand that, then we will move on to the complicated model, which is multiple linear regression, wherein we will be using more than one independent variables, right? Is everyone clear on what simple linear regression is? All right. So let's look at an example, right? So let me give an example from, let's say, a separate example, right? Okay. So let's assume that I have an x-axis, something like this only, right? Uh, let's say I have the x-axis here, right? Let's say I have the x-axis and I have the y-axis. On the x-axis, I have my independent variable, which is the, let's say, the quantity of products bought, right? The, let's say, the quantity of milk purchased, right? How many units of milk someone is purchasing, right? On the y-axis, which is my dependent variable, I have the target variable, which is the overall spend, right? So this will be your, right? This is your overall spend. This is my target variable, spend. I have on my x-axis, I have the independent variable, which is quantity. Now let's assume if I start marking this, right? If I mark this, so this is 0, let's say 1, 1, 8, 4, 1, 6, right? And let's say on the y-axis, you have your spend. So I will take, let's say I start with, this is 100. Let's say I have 90, 70, and then 40, 30, 20, 10, and 0, right? Now, let's say I have one customer who comes in and buys one packet of milk, right? One packet of milk, and let's say a packet of milk costs 20 rupees, right? half liter milk cost, let's say it costs 20 rupees. So if I want to mark this customer on this graph over here, where will I mark him or her? Quantity bought is 1. The price or the spend, overall spend that this customer has done is what? Is 20. So this cross, do you think that this cross represents the customer correctly? Right? Let's say I have another customer. This customer bought 3 units of milk, right? For 3 units of milk, this customer spent, let's say, 60 rupees. Correct? I have another customer who bought 2 units. This customer spent 40 rupees. Another customer who bought 4 spent 80 rupees. Another customer who bought who bought 5 and spent 100 rupees. Correct? Now let's assume I also have customers who actually had some existing points and they went ahead and they took some discount, right? Now let's say I have one customer who bought one packet of milk, but this customer did not spend 20. This customer spent slightly less than 20, maybe 18 rupees, right? I have one more customer, let's say, who bought, let's say, 4 quantities of milk, right? So 3 will be somewhere over here, 4 will be somewhere over here, and 5 will be somewhere over here, right? Now, let's say I have one more customer who bought 3 units of milk, but this customer paid, let's say, slightly less. And I had one more customer who bought 5 units of milk, but this customer, let's say this customer also bought membership, some kind of a membership along with the milk, and this customer paid slightly extra, right? Maybe this customer paid slightly extra, right? Now, if you look at this, can I draw a straight line that can pass through all of these points? No, right? So, what is the best alternative that I have in that case? If I'm not able to draw a line that can pass through all the points, what is the best alternative for me? I have 7 points over here, right? You cannot remove the points. That is your data. So the best option is what? The best option is that I will take a line which is passing through the maximum number of points, right? So if I look at these 5 points, so the 5 customers who did not avail any kind of a discount, if I look at that, that is actually something that is giving me the general trend in my data, correct? If you look at this is actually giving me the general trend in my data. And what if I go ahead and I plot this regression line, right? Now, see, what the model will try to do is that the model will try to fit the maximum points that it can in a line. Obviously, there will be some customers who are paying extra, there will be some customers who are paying less. But if you see, for majority of the customers, this is a linear relationship. And this is what the model tries to do. All of this we'll be trying to understand later as well, right? All right. But this is exactly what linear regression model actually tries to do, that it tries to come up with a linear relationship, right, between the target variable and the independent variable. The target variable over here is the spend. The independent variable over here is the quantity of milk. Correct? All clear? All right. Now, if you see, let's go through some examples of the relationships that we can have, right? Now, if you see over here, so this is, if you see, independent variable x, dependent variable y, and if you are able to draw a straight line, that is nothing but regression, right? Now, if you see, if my line looks like this, that is, my line has a positive slope, right? The slope is positive. What does it mean? All of you would have studied y equals to mx plus c in school, right? School, college, wherever. So a line which has a positive slope, that is such an angle, it means that there is a direct relationship, right? As in, when my independent variable is increasing, the dependent variable is also increasing. Correct? Right? Can you give me any examples from real life of such a relationship, just like the one that I had given to you, distance traveled and the speed of a car? That will have a positive relationship, right? Can you think of other examples as well, which might have a positive relationship? Ice cream and temperature, yes. Student score and our study, yes. Bill, I assume you have the usage. So let's say internet bill along with the usage that you have, the consumption. Experience and salary, very good. Salary and lifestyle, okay. Flights, what is there along with flights, Jyotsna? There should be 2 variables, right? Petrol price and tax, yes, that will have a linear relationship. employee salary and years of experience, T and weather. No, you cannot say, right, whether it will be positive or negative. Depends upon whether you're taking temperature or what. Engagement versus productivity. Yes. Temperature and pressure. Temperature increases, pressure decreases, right? Or is it vice versa? So I am asking for positive relationship. Stock market, no yatharth. I want specific examples, right? Stock market is vague. Disease and patients, that is vague. Oil price and flight ticket, yes, that can have a positive relation because as the oil price increase, right, the ticket price will also increase. Consumption of fuel with distance, okay, speed and distance, festival and sweets, service level and number of customers attending on time, age and height, utility, distance versus time, more features in car versus price of the car, yes. Pressure and force, yes. Symptoms and severity of disease, okay. Recession and unemployment, yes. Child's age and height, yes. More issues versus TRPs, not sure what this means. Growing technology and pollution, yes, that's correct. Population, population and food, discount, purchasing in malls, demand and price. Demand and price are not correct, right? Or that's correct. The more the demand, the more the price, right? So that's also correct. Okay, I got too many examples. That's wonderful, guys. I hope you're able to understand this, right? So there will be some variables which will have a positive relationship, right? So this is the one that we are seeing. For the variables which have a positive relationship, the line that you have will have a positive slope, right? Or if you don't understand slope right now, don't worry. The line will be just like this, right? It will be an increasing line. As one variable is increasing, if you see, as my independent variable is increasing, the dependent variable is also increasing, correct? So now what can you say about this? This is a negative relationship, right? If you see, as my independent variable is increasing, my dependent variable's value is going down, right? How will you identify that? If you see over here, let's say I take any random point over here, right? Let's say I take a random point over here. For this value of x, the value of y will be this. If I increase the value of x, the value of y will actually go down, right? So this shows a inverse relationship between the independent variable and the target variable. What are some examples? Less trees, more temperature, very good. Speed versus time, yes. Oil price, inflation, oil price will increase, inflation will increase, right? So that's probably not sure. Time and distance, time higher than distance, okay. Winter and ice cream consumption, yes. Amount of fruits in market versus price, okay. Pressure versus area, price and demand, demand supply, distance covered versus fuel, yes. Marks versus spent time for studies, altitude and oxygen level, yes. Cost and demand, yes. Demand will increase, so the cost will decrease. Demand will decrease, cost will increase. Okay, I hope all of you are able to understand this. There can be certain variables which might have a negative relationship with each other, right? All right, so let's move on. This is the same, nothing different in this slide, almost the same. Now, this line, right, whatever this line you're seeing, this line is known as the line of linear regression, right? So, we have talked about this earlier as well. Now let's take a look at some examples how we actually plot this line, right? So let's go through that. Now these are observations. I've explained this already, that depending upon your independent variable value and your dependent variable value, you will get some observations which we need to plot, right? Now let's assume that this is the data that we have, right? Let's assume that I have some target variable, right? Let's say if I pick some examples from your the ones that you had given, right? Let me go back, right? So let's take the example of child's age and child's height, right? So let's say on my x-axis you have the age, on your x-axis you have the age, and on the y-axis you have the height, correct? All right. Now let's assume that these are the actual distributions, these are the actual data points that have been distributed, right? Now there will be different children. So let's say I have a child whose age is whatever this represents, and according to that, this is the height, right? So you will have all the whatever data points. Now, can you tell me how many data points we have in this graph? How can I identify the total number of data points? Is there a way to identify that? 11, right? If you just count these dots, if you just count these circles, these are the observations. Each and every circle, right, is an actual observation, is a student. Let's assume that it is a student, right? Now, if you look at age and height, generally with age, height will increase, right? But there can be some children for whom the height increase is exponentially higher, right? And there can be some for whom the height increases, let's say, slightly lower as compared to the normal, right? Not exponentially high, but let's say if with a couple of years, if let's say the age if let's say the height increases by 6 inches, maybe there can be some children for whom it increased by 7 inches or 8 inches. Maybe there can be some for whom it increased by 4 to 5 inches only, right? Okay. But if you see the general trend, as and when my age is increasing, my general trend is saying that your height will also increase. There are outliers that are present in this data, and outliers will be present in every data, right? If you see this is an outlier, if you see this one is an outlier, if you see this one is an outlier, to a certain extent, the points that are far apart from this particular line are outliers, right? But then we have gone ahead and we have created this particular regression line, right? Why have we done that? What do you guys think? Now, see, obviously, in your in your real world data, right, your relationships will not be purely linear. You can estimate them as a linear relationship, but it will not be purely linear, because obviously there will be certain outliers. There will be slight variations that might be happening in the data, but that is fine, right? When I'm creating a model, I'm predicting the general range, right? I might not be able to predict for outliers, but at least for, let's say, 90% of my population, I will be able to go ahead and come up with a decent prediction value, right? Okay, let me just have a look at the questions. Every point represents features of data sets, right? Every point is a point, right? They are not features. Features are on the x axis, that is the age. Target variable is on the y axis, that is height. If you remove the outliers, you will have better results. That's yes, that's true. Line must be close to more dense data. Yes, Ethan, that's correct. All right. Now, see, now we will try to understand how do we arrive at this line of best fit, right? I hope you guys are able to understand what this graph is talking about. What are these data points? What is this regression line? Now, the next topic that we'll be talking about is how do we identify this regression line? Because, see, if I talk about this data, I can have n number of regression lines that can pass through this data, right? I can have, let's say, this is one line. I could have had also one line which might have gone through this, right? I could have had one line which would have gone like this. Why did I go ahead and why did I create this as my final regression line? Why did I not create the other brown lines that you are able to see on the screen? Right? Because the model will have the option to go ahead with n number of lines. But from those n number of lines, it will choose the best fitting line. How does it identify the best fitting line? Right? How does it arrive at the equation of the best fitting line? That is something that we will try to find out now. Okay. Any questions? Okay, so let's move on. Now, if you see, when we are trying to find out the line of best fit, right? Let's try to understand certain things about this, right? Let's go back to this particular graph and let's try to understand some things or how we actually work with this data, right? Now, all of these blue points, right? All of these blue points are your actual data points. Talked about training, and then I have talked about once when you will train the model, after that, you will go ahead, you will use the model to make predictions. Does everyone remember that? So, having that thought in mind, just remember that these points that you are seeing, right? These blue points that you are seeing, these are the training data samples. Imagine that these are 11 children in your class for whom you have gone ahead and you have just taken their age and you have taken their respective heights, right? That is it. Okay. I'll just write this down once again. This is age over here and this is height over here, right? So imagine that these are your current students in your class, these 11, for them, you have gone ahead and you have plotted the age and height, right? From these data points, let's assume that you arrive at this particular best fitting line. How did we arrive at that? Don't worry about that right now. Just imagine that you arrive at this particular point, right? Now, this regression line will become your final model, right? Let's try to understand how we use this model to make predictions, right? Now, let's assume that a new student, your teacher informs that a new student is coming to your class, and the age of the student is 13 years, right? Is 12 years, let's say, right? Now, 12 years on the x-axis, let's imagine that 12 years sits somewhere over here. 12 years is something, or let's say 12 years sits somewhere over here, right? On the x-axis. Now, as per the model, my model will go ahead and my model will make a prediction that the height of this particular student should be this, right? Let's assume that this is a point that intersects at 5 foot 4 inches, right? Let's say this on y axis intersects at 5 foot 4 inches. All right. Does that make sense, everyone? So, what you can say is that for this student, when the age was, let's say, 12 years, my model's prediction actually came out to be 5 foot 4, right? Okay. Now, let's say that once when this student walks in my class, right? Once when I see this student, I realize that the height of the student, the actual height of the student is actually, let's say, over here only, right? Let's say the actual height is somewhere over here, right? So your model actually went ahead and predicted 5 foot 4, but your real height for the student, when the student walked into your class, when you saw the student, was actually, let's assume, 5 foot 6, right? So now, can you calculate the error that you have? You have the actual height of the student, you have the predicted height of the student. By how many inches are we off in predicting the height of the student? 2 inches, right? How did we arrive at? If you see, if instead of doing all of this, if I would have just gone ahead and if I would have just taken this difference of the point from the line, would I have not gotten the same 2 inches value? If you see the distance of this point from this line, the vertical distance of this point from this line will give you exactly 2 inches, right? So can we say that the vertical distance of this point from this line is actually the error of the model? Not the model, but for this particular point. Now, if I ask you to go ahead and calculate the error of the entire model, or if I ask you to calculate the error of all the data points, how can you calculate that? If you go ahead and if you calculate all of these vertical distances, would that not give you the error? I will go ahead and I will calculate all of these vertical distances, right? Summation of all the distances. If I do that, will I not get the error of the model? I will, right? I hope everyone is able to understand this, right? So let's say that the vertical distances or this error for this line, right? Let's say the error for black line comes out to be, let's say, some value, right? Let's say the error comes out to be 25. Just a random value I'm taking, right? Let's say this error is 25. Now, I'm drawing one more regression line, right? Let's say I draw one more regression line, and this line is, let's say, and change the color. The new regression line is, let's assume, this. Not the new, but let's say one more option that we had for the regression line. Let's say it was this, right? And start from here. And let's say the next option was this, right? Now, if I ask you to go ahead and calculate the error of this line, right? This particular orange line from all of these points, right? This error of orange line will always be greater than this 25, right? Why? Because the black line, let's assume that this comes out to be 40. Now, the black line is the best fitting line. When I say the line is a best fit line, it means that the vertical distances of all of these points from this line is the least, right? So any other line, you can Try drawing any other lines through all of these points, and you will always realize that the error of all the rest of the lines will actually be greater than the line of best fit. And that is the reason why it is known as the line of best fit, because this is the line that is giving you the minimum error. This is giving you the minimum vertical distance of all the data points from this line, right? And that is why this is called as the line of best fit. Yagesti, can you not calculate the errors of all the points and just sum them up? You can take a summation, right, of all the values, error values. That's what we are doing over here. That's why we are getting just one value. We take the line which has the least mean of errors, right? Least error value. So the maximum number of points should be closer to the lines, right? So see, it should not be the case that if you have 10 data points, 5 data points are on the line, but the remaining 5 are way too far away from the line. That will also be incorrect, right? Because if you, even in this case, if you calculate the sum of vertical distances, that can be a very high number. So it tries to come up with a line which is closer to all the points. It will not come up with a line which is, let's say, going through 5 data points and not even closer to the remaining 5. That is not the objective over here. The objective over here is to find a line which is closest to all the possible points that are out there. Okay. We don't need to write any equations and all. All of these things will be done in Python, right? We are just trying to understand how the linear regression model works, right? All of these things, you don't have to go ahead and you don't have to create the equation of the line. You don't have to plot the data points like we are doing. All of these things we are doing only to understand how internally the linear regression model works. The answer to your question is same. You don't need to decide anything. If you call the linear regression model, it will automatically try to find out the line of best fit. How it will try to find the line of best fit is by minimizing this error that we are talking about. Once again, to your query as well, it does not pass through all the plotted lines, or it does not pass through the maximum points. It tries to pass through as close to all the points possible, right? Obviously, it will change as and when the data will change, right? How will the line remain same? As and when your data distribution changes, obviously this will keep on changing, right? Pooja, this line is the linear regression model. This line will help me make predictions for future. Less variance equals to a better fit through with the equation of a line, right? Now let's say that this black line, right, this is the model, this is the line of best fit, right? Now imagine that a new student comes in, right? For this new student, you know the age of the student. Let's say the age of the student is 16 years. If the age is 16 years, you will draw a vertical line. Let's say this is 16, right? On the x-axis, let's say this is 16. So at 16, you are going to draw a vertical line which will intersect this line of best fit, right? From here, all you need to do is that you need to see where this line is cutting on the y-axis, and that will become your predicted height of the student. Okay. So now if the age is 16, if this intersects this over here, let's say this intersects at 5'8", then you can go ahead and you can say that the predicted height for a student whose age is 16 years can be around 5'8", right? Now in reality, you know that maybe a student might be 5'9", 5'10", 5'6", 7 and all, right? But this is a prediction. So this you are giving as a general value which most of your data points are going to follow. All right. After error, please explain, Yagyasni. After error, see, the black line is the line which gives you the least error. I'm just trying to explain this to you. How do we arrive at the best fitting line, right? There is nothing to explain after error. If you understand that the best fitting line is the line which is witnessing the least error, that means that this line is the line which is closest to all the points possible, then this is the best possible option for you to go ahead with, right? And hence this will become the best fitting line. Any real-time applications? And there are lots of real-time applications for the linear regression model, right? There are so many in the retail industry, in the finance industry, in the telecom industry. If you want to go ahead with a simple model, right? If you don't want to go ahead with an overly complicated model, a model which just gives you an estimation of where your general predictions can be, then linear regression model can be a very good option for you, because it generally does not take that much amount of time to run, and it gives you a good estimation of where your actual data might lie. This is not an average height, this is a predicted height. You will not know the error, right? I mean, how will you know the error? See, you're predicting this for, let's say, someone whose age is 16. So all you did was you went ahead and you made the prediction. Now your actual data point can be 5 feet, 9 feet, 6 feet, right? Whatever. You want to go ahead, you can calculate the error, but the model will only try to give you the generalized prediction, right? You can calculate the error if you want. You can go ahead and you can calculate that. Once when you get the actual value, you can take the actual value, subtract it with the predicted value, and you can calculate the error as well. What do you mean by how it is predicting? What is the logic? How did we arrive at this black line? Why did we finalize this black line? Why did we not go ahead with some other line? So the process of arriving at this black line, right? This is what your linear regression model is. Because as and when your data distribution will keep on changing, obviously your equation of the line will also keep on changing. Yagyashi, I have explained this so many times. Best fitting line is not the line that goes through the maximum points. What I am trying to make you understand is that best fitting line is the line which will give you the least error. The line that passes through the maximum points will not always be the line which is giving you the least error, right? On occasions, it might happen that you have outliers in your data because of which your best fitting line will change, right? Main goal is to reduce the error, yes. Main goal of every machine learning model, right, is to reduce the error, right? So over here, we are trying to reduce the error by calculating the vertical distances. For some other model, we might be trying to reduce the error by some other way, right? So every machine learning model that we'll be studying throughout the duration of this course, the overall objective will be to reduce the error only. Okay? So that's correct, right? So there are many processes, there are many interactions that you will find in the different domains that you might work with, which have a linear relationship, right? And whenever you have a linear relationship, there is nothing better than a linear regression model to capture that, right? I will be explaining this concept mathematically as well, but right now I'm able to understand, then that's a good start. Anyone who's not able to understand? All right. So if you see, this is what they're explaining over here. The error is what? The error is this vertical distance, right? Your estimated value was the red point, whereas let's say your actual value was this blue point. So this will be the error, right? This will be the error over here. If you go ahead and if you calculate the error of all the data points, your objective is to minimize this error. When your objective is to minimize this error, you will need to find a line of best fit, which is actually giving you the least value of this error, right? So that is what we are trying to do over here. These are some examples. Speed and distance, they have a positive relationship. Distance and speed, right? If you see, y becomes your target variable, which is distance. X becomes your independent variable, which is your speed of the vehicle. M, which is the slope, right? M is the slope, that is the angle that this line will have, right? That is your M. And C is the constant value, that is when X equals the value 0, then what will be the value of the target variable, right? So y equals to mx plus c. You can see that y is the target variable, x is the independent variable, m is the slope of the line, and c is the constant. Correct? Is everyone able to understand these four terms? Y equals to mx plus c. All right. So now if let's say there is a negative relationship, let's say I take time and speed for example. So when I will take time and speed, in that case, your y remains the same. Let's say y becomes time. My x becomes the independent variable, and my slope, sorry, let's come to this, right? So over here, if you see in this example, your slope will become negative, right? As soon as the relationship of the target variable with the independent variable becomes inverse, the slope of the basically the coefficient that is involved with the independent variable will actually become negative, right? X is independent, y is dependent, yes. Okay, shall I move on? Any questions till now? Slope is kind of rate of change only, right? So slope is the rate of change of variable y with respect to variable x. So Muhammad Ansari, if you see, time is less only, right? When speed is high, If you see, when the speed is high, then time is less. When the speed is less, then time is more. So inverse relationship, are you able to understand? If you look at this over here, right? When my speed is, let's say, 10 kilometers per hour, the time travel will be more, right? Sorry, the time taken will be more. When my speed is, let's say, 60 kilometers per hour, then the time taken will be less, right? Abhishek, if m is 0, then it means that there is no relationship between your variable and the target variable and independent variable. So obviously that you will not be creating a linear regression model, right? M equals to 0 means that there is no relationship at all. You will not even have a C value then. There is no graph in that case. Okay. So now let's assume that I have two variables x and y. The value of x is such 1, 2, 3, 4, 5, and the value of y corresponding to the value of x is 4, 3, 4, 2, 5. Right? Let's go ahead and let's plot these data points on this line, right? One by one. First point is what? X is 1, y is 4. Correct? So when x is 1 and y is 4, it will be plotted somewhere over here, right? Similarly, I plot all of these points. You can go ahead and you can check. First one is 1, 4. The second one is 2 and 3. The third one is 3 and 4. Fourth one is 4 and 2. And the fifth one is 5 and 5. Now let's move on. Let's see what happens. If I calculate the average of x and if I calculate the average of y, right? The average of x will come out to be 3 and the average of y will come out to be somewhere around 3.6 something, right? 3.6, 3.8, whatever. So if I just plot these vertical and horizontal lines, just for now, just hold on. So we are just plotting the averages of y and x for now, right? Because that is something that will give me the slope in a way, right? That will give me the slope of the line. So we need to find out the average. See, first of all, guys, you don't need to do all of these things manually. These are just examples. We are just trying to explain how internally linear regression works. Once when we'll move to the hands-on, you will see that all of these things, right? This is something that Python will automatically do for you. All you need to do is that you need to pass a set of independent variables and the target variable, call the model, take the model, run it on the data, take the output and use it as your predictions, right? This is just to understand how what internally happens, right? Now, if the average of x was 3 and the average of y was 3.6, then your line of best fit, right? This will pass through this 3 comma 3.6. Now this is mathematics. This is something that, because your slope is nothing but y minus y average and x minus x average, right? No need to get into the definitions and all. No need to get into the mathematics. But generally what happens is that your line of best fit will pass through the average of x and y both, right? That is what you can see over here, right? Now, if this point is 3 comma 3.6, my best fitting line is the line which is passing through this particular point, right? Okay, let's try to map. Let's try to see how we arrive at these values. Now, the definition of slope is this, right? You don't need to, you can go ahead and if you want, you can calculate the slope using this formula. But once again, as I've said, no need to do that because Python will automatically do this for you. Slope is nothing but summation of x minus x bar, right? So all the values of x, you are going to subtract it from the average of x multiplied by y minus y bar. All the values of y, you are going to subtract them from y bar and you are going to divide it by the summation of x minus x bar whole squared, right? We are going to do this manually. Let's try to find out how, right? So in order to calculate the slope, right, which is m, I need to find out x minus x bar, y minus y bar, and x minus x bar whole square. I have the values of x and y. I have the value of x bar and y bar. Can I calculate x minus x bar and y minus y bar? We can, right? So we'll do that. So for the first point, my data point was 1. The average of x was 3. I do a 1 minus 3, right? Similarly, so I get the value minus 2. Similarly, then I move ahead to the second point. For the second point, the data point was 2, the average was 3. So I do a 2 minus 3, this becomes minus 1, right? Like this, I will do this for all the x data points, right? If you see, 3 minus 3 becomes 0. 4 minus 3 becomes 1, and 5 minus 3 becomes 2. Is this step clear to everyone? Nothing fancy, nothing complicated. Now, can I go ahead and can I calculate y minus y bar as well in a similar way? So you can go ahead and you can do that. We will be calculating y minus y bar, right? And it comes out to be 0.4 for the first, then it comes out to be minus 0.6, and I get all of these values, correct? Now I have both of these. I also need to calculate x minus x bar whole squared. I will just take a square of this particular column and I will get the x minus x bar square as well. I get those. I substitute these values, right? So I calculate the sigma. First of all, if you see it's sigma, so I need to multiply x minus x bar with y minus y bar. I do that. Minus 2 into 0.4 minus 1 into all of this, right? So I do this and I get these values. And then we calculate the summation of all of these values, right? Sigma of x minus x bar whole square and sigma, that is summation of x minus x bar into y minus y bar, right? And I do that, I get this value. This gives me a slope of 1 by 10, right? So I was able to find out the slope of my line, right? Now this is exactly how internally the linear regression model comes up with the slope of the best fitting line. There is no need to plot n different lines and all. Mathematically, this is what we need to do, right? So now that we know the slope, right? I know that the slope is 0.1. I have my data points as well, right? I can go ahead and I can substitute these values to find out the value of C as well. So my X becomes 3, which is the X average. My Y bar becomes 3.6, right? So my Y average was 3.6, my X was 3. So if I go ahead and if I multiply this, right, 3.6 equals to 1 by 10 into 3 plus C, I will be able to find out the value of C, which comes out to be 3.3, right? So now C becomes 3.6 minus 0.3. So eventually your C becomes 3.3. So you are able to find out both your M and C for the linear regression equation. And the final equation that you have actually becomes y equals to 0.1x plus 3.3. The 0.1 was the slope that we have found out. After finding out the slope, we have imputed the slope and the values of y average and x average in the equation to find out the value of C, right? Once when I find out the value of C, I get the final equation, which is the equation of my linear regression line, right? And this becomes my final line. Now, if you see, this line is not passing through all of the data points, but this is the line which is giving you the minimum distance, or this is the line which is giving you the least error from all of these points, right? If you take a vertical distance from all of these points and calculate the error, try creating any other line that passes through these points or that passes far away from these points, you will realize that the minimum error you are getting is from this particular line only. And that is why this is what the linear regression model tries to do. C we have found out by substituting the values of y average, x average, and m. Y average was 3.6, x was 3, m was 1 by 10. If you substitute all these values, you will get the value of C as 3.3. All right. So just one second. Yeah. So now you can also calculate the mean square error, right? Now you have the regression line and you have the actual data points. When you have the regression line and you have the actual data points, all we need to do is that we need to get the predictions. So now for x equals to 1, from the line, I am getting the value 3.2, right? From this particular red line, I'm getting the value 3.1 and so on and so forth. So I will get the predicted values. I have the actual values, right? Using the actual and the predicted, I can go ahead and I can calculate the mean square error or whatever error you want to calculate, correct? That was not any important line, Abhishek. That was just saying that my line of best fit is going to pass through that point, that is 3, 3.6. But in order to find out the slope and the constant, we went ahead and we found out the slope and then we adjusted the line. If you see, our earlier line was actually a random line that we were saying that my best fitting line will be passing through these points, right? So where did it go? If you see this, we were just saying that my best fitting line will be passing through these points. But once when we were able to find out the values of M and C, we adjusted the slope as per the values that we had found out for M and C, right? Now this became the best fitting line for us, right? All right. Are there any questions? So we'll stop here. And then once we are back, we will be moving on to the remaining slides. In this slide, all we are doing is that we are using the equation, right? If you see now, the final equation is 0, y equals to 0.1 x plus 3.3. So you can substitute the different values of x and you can get a predicted value. Now if I substitute x by 1, I will get the prediction of 3.4, right? So you can see that that is what we have, right? You will get the actual values and you will get the predicted values. Through that you can go ahead and you can find out what is your error. You can calculate square error, your MAPE, whatever you want to do, right? Okay. So now finding the best fit line, we have gone through that. This is just kind of an output that we get from the Python model. So I will be showcasing this to you once when we start with the hands-on. So let's hold on for now. Now the next thing that we need to understand is the evaluation metric. Now for our linear regression model, there is an evaluation metric that goes by the name of R square, right? Now, what is R square? R square is basically a metric that tells us how good your line of best fit is or how good your linear regression model is, right? So let's try to understand what do we mean by R square, how do we calculate it, right? And what does different values of R square tell us about, right? So first of all, R square is a metric that is also called as goodness of fit, right? Goodness of fit or R square. And this is a value, nor this is a metric that you get after running your linear regression model, right? In Python, you will be getting outputs, and in the output, you will be getting the R square value as well. Now, R square value ranges from between 0 to 1, right? So first thing that you need to understand about R square is that it ranges between 0 to 1. The second thing that you need to understand about this is that let's say I have a model A, right? So let's say model A has R square of 0.5, right? Let's say I have model B. This model has an R square of, let's say, 0.8, right? So a model, or let's say that linear regression model which has a higher R square is a better model, right? So we aim, when we are creating the linear regression model, our aim or our objective is to get an R square value close to 1, right? So generally any model which has an R square of, let's say, greater than 70%, right, is considered to be a good model, right? Anything less than that, it means that you might probably need to add more features to the model, right? You might need to, let's say, do some feature engineering. Maybe you need to look at whether the variables that you have included are actually correlated to the target variable or not, right? So an R square value of anything less than 0.7, 0.6, that is not a very good R square value. Anything which is greater than 0.7, 70% means that you have created a decent, or you have created a good model, right? 0 means, Charan, that you have used all garbage variables. So if you remember yesterday, if I want to predict the spend of a customer and I take the color of the car that the customer has, if you're using such variables, then you will get an R square equals to 0, right? What if it is 1? If it is 1, then it means that you are the chosen one. You're supposed to be the data scientist of the century. Then you can just drop everything, go grab a can of beer and enjoy, right? If you're able to create a model which gives you an R square of 1, it means that you have done a very good job. Okay. So R square equals to 1 means that your model is the best, right? You cannot do anything better than that. So that's what I'm saying, Abhishek. That's the maximum value, right? You can see over here 0 to 1. By 0 to 1, I mean that R square cannot be beyond 0, beyond 1, cannot go beyond 1, and it cannot be less than 0. It will always be in the range of 0 to 1. Achieving 1 is, I don't think so that it is practically possible. I have never gone ahead and I've never seen a model which can give us an R square of 1. It's kind of next to impossible, because generally there are certain fluctuations that you cannot account for, right? There will always be fluctuations that are unaccounted for. If you have a process that is totally dependent upon certain factors which you are able to include, then maybe you can get an R square of 1. But speaking from my experience, I have never seen any model which gives an R square of 1, right? Now let's try to understand what R square is, right? Now, let's say, let me take an example, right? So let's say I have the target variable of customer spend, right? And I take one feature, which is, uh, let's say, the age of customer, right? I take only one feature, the age of customer, and using this, I get an R square value of, let's say, 0.5, right? Now let's talk about a second model. In this model, my target variable remains the same, but now I am using the age of the customers. I am using, let's say, whether the customer is a member of my store or not, right? I am using what is the income of the customer, right? Let's say now I'm using three features. In order to predict the same variable, that is customer spend, now I'm using three features: age of customer, whether the customer is a member or not, and the income of this customer. Now let's assume that my R square increases to 0.8%, right? 0.8. Now what does this mean? Now, how do we interpret this value, right? How we can interpret this value is R square of 0.5% means, or 0.5 means that given whatever features you have used in the model, you are able to capture 50% variation of the target variable, right? The 50% variation that is happening in the target variable, you are only able to capture that, right? As soon as you added more variables which are important, right? If you see, if I add the whether the customer is a member or not, what is the income of the customer, my R square increased to 0.8, meaning that now I am able, if you see, to explain 80% variance of the target variable, right? Using these three features, right? So you can understand that you need to include relevant features in your model, right? Your independent variables should be relevant. If you are including garbage variables, let's say where you go ahead, you include 20 different variables, but all of these 20 variables are random variables, they are in no way related to your target variable, your R square will not increase, right? Only when you add significant, if you see, variables to your model, your R square value will increase, right? That is the only way to increase the R square value. All right. So R square signifies how good the prediction of the model will be. Yes, Ishan, I can never chill with a can of beer. Um, yes, Charan, if you go by my words, but other than that, you can any day go and grab a can of beer, right? More relevant features increases R square. Yes, right. So the more relevant or the more significant features we will have in our model, the better the model's R square value will be, right? Any questions on this? Now the formula for R square is the one that you can see over here at the bottom, right? That is the predicted value, right? Whatever your predicted value is, subtracted by the mean and divided by the actual, whatever your actual data point is subtracted by the mean, right? So this is just a formula. Don't worry about this. You don't, if you remember the formula, that's okay. No one is going to ask you the formula and all, but you should just understand what we mean by R square and how the R square varies when we are adding significant or insignificant variables to our model. In a way, Sushant, it tells you about how much variance of y is being explained by your features, right? Not exactly how much x explains y, but it explains what variance you are able to explain of the target variable using whatever features you have. How we find yp, Yatharth, I assume you yp you mean the predicted value. Yp is the predicted value, right? That you will get from the model. Just what we have done over here, this substitute the values of x on in your equation and you will get a predicted value. Can we plot multiple independent variables? Akshay, not more than three. We cannot understand more than three dimensions, right? So you will not be able to plot more than three at once, right? So this is just just an example of how we can calculate R square. But once again, there is no need for you to do this. We'll go through this, but at the end of the day, Python will do all this calculation. Now, if you see, if my y predicted was 3.2, right? And my average of y, if you remember, that was 3.6, right? So you will calculate all of these values, right? Then you have your actual y, it is 4, and you will subtract it by your mean of y. You will get all of these values. You will square these values up, and after doing this, if you look at the r square of the model, if you substitute all these values, right, you will find out that the r square of the model, if you see, they're just calculating all the values, yp minus y mean whole square, y minus y mean whole square, all of this is calculated, and we get an r square. I get sigma 1.9 and 5.2. I substitute these values and I get an r square of 36%, right? So 36%, you can see that this model is actually not a good model because the data points are actually way far off, right? Hence the r square is coming out to be a smaller value as well, right? Now, see, the linear regression model cannot do anything. If you are giving in data points which are having a non-linear relationship, over here, if these data points do not have a linear relationship at all, right? These are distributed in a random way. Obviously, linear regression model will not be the best fitting model, and hence that is why you are getting an R square value of 36% only. What do you mean by individual R squared, Arjun? Is it written somewhere? Are you referring to this value 0.36? Guys, any questions? So this was just the calculation of R square, how we calculate R square. You don't need to do this calculation when we are working on large scale data. Obviously, Python will do this for us. That is not the R square, right? These are just the calculations of y minus y mean whole square. The R square is the overall substitution, right? The sigma of yp minus y mean whole square divided by sigma of y minus y mean whole square, right? So the final R square value is 0.36. Right? No worries. So what is good R square value? I told you that just now, Arundhati, right? Anything above 70% is generally good. Anything below 70%, it means that you can add more significant variables, right? So see, R square gives you an intuition of how many relevant features you have included. Let's say for the first model run, you go ahead and you use, let's say, 10 features. And using 10 features, you end up getting an R square of, let's say, 60%, right? Now you know that there are some additional factors that you have not considered. Maybe if you go ahead and if you consider those factors, you should be able to increase the R square value, right? So then you will have to go back, you will have to do some digging, you will have to find some other variables, some other factors, right, which might influence the spend of your customers, right? Now here, if you see, if I want to predict the spend of the customers, do you think that age, income, whether the customer is a member, do you think that that is enough? Apart from that as well, there can be other factors, right? So let's say the lifestyle choices, right? Whether they are married or not, whether they have kids or not, right? There can be n number of factors that can actually drive how much a customer is going to spend in your store, right? So if you get a lower R square value, means that you should do more, you should invest more time in identifying important and significant features. If you're able to identify those, then you should be able to create a model which will be able to give you a better R square value, right? Any questions till now? Yes. All of that we can include, right? Time of the month and all. Now, if you see, as and when my data points start coming closer, now if you see here, my data points were far apart, so my R square came out to be 0.36. Now, if you go ahead and if you calculate the R square for this, here you can see that the data points are much more closer. My R square becomes 0.6. If my data points are almost on the line, my R square increases to 0.9. If my data points are exactly on the line, right, my R square becomes 1. And hence your R square cannot go beyond 1, right? 1 is the maximum value that your R square can attain. All right. So, okay, so that's it on the theory. So are every models this easy? See, no, Charan, linear regression is the most simple model that we are studying, right? So we are starting with the most simple model, but obviously depends upon how it is being explained. There are more complicated models that we'll have, which we'll be studying later. When error will be less, R square will be high. Yes, Kaushik, that's correct. What do you mean by plotting questions on linear regression? All right, then. So thank you, everyone. Okay, bye.
So, question 2. Which of these tools is not an important part of the data science toolkit? Option 1 SQL, option 2 machine learning, option 3 Docker, or option 4 Python? What do you guys think is the right answer? Comment it down below. Just a quick info, guys. Intellipaat offers an executive postgraduate certification in data science and AI, where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps, and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
Okay, so let's try to understand what do we mean by VIF. Now, see, do you guys know the full form of VIF? So VIF stands for variance inflation factor, right? Why do we use VIF? What is the need of using VIF? For multicollinearity, right? What do we mean by this particular term used for multicollinearity, right? Now, what do you understand by this particular term? That is multicollinearity. Any idea? So multicollinearity, right? Multicollinearity means correlation amongst the features, right? Now see, when we are talking about linear regression model, correlation between features, right? Now see, linear regression model, it says that your independent variables, right? Independent variables should be correlated to the target, correct? What it says is that let's say you have features which is spend, quantity, visits, discount that a customer has gotten, right? And then you have the target variable, that is whether the customer buy the product or not, buy or not buy, right? Okay. So these over here, if you see, these are my features, right? Spend, quantity, visits, and discount. And this is my target variable, correct? Now, what is the objective when I'm building the linear regression model? The first objective is that each of these variables, right? Now, spend should be correlated to my target variable, correct? So, my first requirement is that this spend should have a correlation with the target variable. Quantity should be correlated with the target variable. Visits should be correlated, and discount should be correlated, right? That is the first assumption, or that is the first rule of the linear regression model that we have. Now, the second rule says that your independent variables should not be correlated, right? This is what the second rule says over here. Independent variables should not be correlated. What does this mean? This says that I want the independent variables, or I want my features to be correlated with the target variable, but I do not want these variables to be correlated amongst themselves. Spend should not be correlated with quantity. Spend should not be correlated with visits. It should not be correlated with discounts. Similarly, quantity should not be correlated with the visits or discounts, or visits should not be correlated with discounts, and vice versa. Right? Now, first of all, let's try to understand why do we have this particular assumption, right? Now, let's assume that I give you two variables, right? I give you a variable which is spent in dollars, right? And I give you a variable which is spent in rupees, right? And I have the target variable, which is whether the customer will buy a product or not buy, right? Now, these two variables, do you guys think that these two variables will be correlated to each other? The spend in dollars and spend in rupees. Now, say, spend, let's say you spent 100 rupees. You can have two variables, that is, the spend in rupees was, and the spend in dollars was, let's say, $1.1, whatever. You can have that, right? So, these variables will be what? These variables will be correlated between themselves, right? Now, what will happen if I go ahead and if I use these two variables in my model, the same effect, right? Let's say that this spend in dollars has a correlation with buy not buy of a 20%. This spend in rupees has a correlation with this buy not buy of, let's say, 20%. Now, if I'm using both the variables together, I am using the same effect twice, or I am calculating the same effect that spend in dollars and spend in rupees is giving. I am calculating that effect twice. So if, let's say, I was to predict whether the customer was buying or not buying, right? This, using these two features, I might be able to capture the same effect. Whatever information these two variables contain is exactly same. So I'm feeding similar data to my model, but it's just I'm saying that the name of the columns is different, right? So what will happen is that if I'm passing variables which are correlated, then my prediction of the target variable will get wrong, right? Because you might be calculating the same effect more than once. If you're calculating the same effect more than once, obviously your predicted value will become way more off, right? So that is why the second assumption that we have is that your independent variables, your features should not be correlated between themselves, right? And in order to find that, the method that we use is known as VIF, that is variance inflation factor, right? Okay. So now let's try to understand what do we mean, like how do we apply VIF, right? First of all, do you guys know the formula for VIF? So the formula for VIF is 1 minus 1 divided by R square, right? I hope everyone remembers R square. What was R square? R square was the explained variance divided by the total variance. Goodness of it, right? So the formula for VIF is 1 minus 1 upon R square, right? So let me take one example. Let's say I go ahead and I have these features. I have the spend in dollars, I have the spend percentage, I have quantity, and I have quantity ratio, right? Now, or let's take only two of spend in percentage and spend rupees, right? Now, here you should be able to see that your spend percentage and spend dollars will be related to each other, and your quantity and quantity ratio will be correlated to each other, correct? Now, see, one simple way of dealing with highly correlated variables is what? That you go ahead and you either select one of each, right? Let's say you go ahead and not use spend dollars, or you go ahead and not use quantity ratio. You just go ahead, use spend percentage and quantity, and that's it, right? That is one way to do so. But generally, see, it might happen that spend percentage and spend, maybe 80% of the information that these two variables contain is same, but maybe there is some amount of information that spend percentage has which is extra as compared to the spend variable, right? Similarly, quantity and quantity ratio, it might be that these two variables are correlated with each other only by 80%. So meaning that only 80% information that they contain is very similar. The remaining 20% might be dissimilar. So if you're going ahead and if you are directly dropping spend dollars and quantity ratio, you might be missing out on some critical information that you might have wanted to feed to your model, right? So generally, we don't do that. We do not try to get rid of correlated variables manually. If you see that there are two, three variables which are such highly correlated that you're getting correlation values of 90, 95, right? 80, even greater than 80, then you can go ahead and you can exclude those. But in the real world, this will not happen. In the real world, you can have variables which are correlated by, let's say, 30, 40%. So if you get rid of one variable, the 30-40% correlation aspect that was about to get doubled, you have dropped, but the remaining 50-60% information that was new in this variable, that also you have dropped. So you might have dropped some important information from the model, right? So that is where the application of VIF actually comes into play, right? So now let's try to understand what do we mean by VIF, right? Now, if you see VIF, when we apply VIF, right, you would have realized that they would have applied the VIF function only on your feature space. They would have not applied your VIF function on your target variable. Is that true? Okay. So now let's say what I do is that now I am assuming that one of the variables or there are some variables in these which are highly correlated, right? So what if I do one thing, right? I take one of these variables as a target variable, right? Let's say I take spend percentage as the target, right? I take this as a target and I build a model, right? I'm just explaining to you how VIF works, right? I build a model using spend dollars, quantity, and quantity ratio. Now, just answer me one thing. If assuming that this spend percentage has variables which are correlated with itself, right? A spend dollar quantity ratio, do you think that the R square of this model will be high or low? R square is the same metric, right? That we have talked about. If we have variables which are correlated with spend percentage, the R square of this model will be high, right? Okay. So if my R square will be high, can you tell me what my VIF value will be? VIF value will be small or large in that case? VIF will also be large, right? Because if you see 1 upon R square will be small, but if you do 1 minus 1 upon R square, it will also be large, right? Right? So just try to understand this thing that if I go ahead and if I try out different combinations over here, right? Let's say the next combination that I try is spend dollars. I regress it with the remaining features, which is spend percentage, quantity ratio, right? Similarly, I take quantity, I regress it with spend percentage, spend dollar, and quantity ratio, right? And I take quantity ratio and I regress it with, let's say, spend dollars, spend percentage, and quantity, right? Now, let's assume that what happens is that the R square for this model, right? R square for this model is high. Let's assume the R square for this is medium, for this is low, and for this is also low, right? If my R square is high, correspondingly, what will happen? My VIF value will also be high because you can see that the formula for VIF is 1 upon 1 minus R square, meaning that your VIF value will also be high, right? Here, VIF will be medium. Here, VIF will be low. And here, VIF will also be low, right? Is everyone able to understand till here? Now, out of all of these variables, which variable would you want to remove from the model? Is it the variable which has a high R square or is it the variable which has a low R square? The variable which has a high R square, it means that it has variables which are correlated with itself, right? Because if the variables are correlated, only then your R square will be high, right? So what I'll do is that I will go ahead and I will exclude this first variable from my model, right? Okay. Now I will repeat this process again and again and again. I will only get rid of one variable per iteration, right? Now in the second iteration, I will be left with only these three features, right? Now with these three features, I will run the VIF code once again. If let's say I get a VIF value of high for any variable, I will exclude that. Let's say I get VIF value as low for all three, right? I will go ahead and I will use my model or I will build my model using only these features. Okay, now for VIF, right, the general principle is that, see, your VIF value will never be negative, right? If you look at this over here, 1 minus 1 upon R square, the formula, right? your VIF value will always be in the range of 0 to infinity, right? It can go from 0 to infinity. Let's assume that your R square value is very small, right? Right. So this is the formula for VIF. Right now, if you see, if your R square will be high, that is close to 1, then 1 minus a value which is close to 1 will be a small value. If you divide that by 1, so this overall VIF will be a very large value, right? If your R square is close to 0, then your 1 minus 0 will be 1, and 1 divided by 1 will be equal to 1, right? So for those variables which are not correlated to the rest of the features, your R square will be low and hence your VIF will be close to 0, right? Not 0, close to 1. So your VIF can range between 0 to infinity. The general rule of thumb that we have is that anything in the range of 0 to 5 VIFs is considered, you can go ahead and you can accept those features. Any variables which have a VIF of in the range of 0 to 5, you can accept that. Anything which is greater than 5, right, or greater than equal to 6, right? Any variable that has a VIF value of greater than equals to 6, you have to remove that from the model, right? That is the general rule of thumb that we have. Okay. You can calculate the correlation after converting categorical variables to numerical, but as I said, right, let's assume you have a couple of variables which are correlated and the correlation between them is only 50%. Now, how will you decide which feature you want to take away? Because both of the features contain 50% information which is mutual, but both of the features contain an extra 50% information that is new as well. So, which feature do you decide to take away from the model? So, manually, if you're trying to identify correlated features, then generally it becomes a very cumbersome process. You might get rid of an important variable in the process. When you run this, uh, when you try to exclude variables using VIF, you are actually using a statistical approach wherein you are eliminating those features, the information for which is actually contained in the rest of features, right? So let's say if you eliminate a feature which has an high R square value with the rest of the features, meaning that when you eliminate this, no information that this feature contained is actually not is actually absent in your data. Everything is still there. Even when you go ahead and you drop this variable, whatever information that variable contained is being accounted for in some variable or the other that you have in your data, right? So that is why VIF is a more robust solution. It is a more statistically accurate solution and method, right? Overfitting can happen because of presence of too many correlated features. It can also happen because of a model which has trained too much, right? So but for linear regression, yes, you can go ahead with the concept that overfitting in case of linear regression will only happen if you have too many correlated variables, right? When it comes to underfitting, what do you need to do when it comes to underfitting? We need to add more features. It means that you don't have significant features in your model. So you need to add maybe more features, maybe you need to add more data, maybe you have less number of data snapshots. So then you will have to do all of that. All right. All right. So we'll start with linear regression only. So the case study that I have for you is a Boston house price prediction case study. We have Boston house price data. Boston is a city in the US, and for this city, we have the data of some houses that are there in this city, and we have certain factors about these houses, right? Factors such as where the house is located, how far is it from, let's say, a highway, how far is it, let's say, from a corporate center and things like that, right? And using all of this data, we will try to go ahead and we will try to predict the price of the different houses that we have, right? So that's the objective. I'll explain the data to you first. So as of now, just focus on the understanding of the data and the problem that we are trying to solve. Once when everyone is able to understand that, then we will move on to the complexities of the model, right? we are working on collab. I am working on collab. You can work on anything. So see, the only thing that is different, this is Google Colab, right? Now most of you might be using Anaconda, Jupyter notebooks and all, which is nothing but your locally hosted uh, Python versions, right? Now, this is a platform that is by Google. You can also use this if you have a Google Drive. If you are able to save your data on your Google Drive, you should be able to use Google Colab as well. The only thing that is different in Google Colab, now the interface is Python, ID, everything is Python. Now, the one thing that is different here is that while reading the data, if you remember in your usual Jupyter, Anaconda notebooks, right? All you have to do is that you have to do a pd.read_csv and you just have to give the path of the file, right? Wherever that file would be in your local system, you have to give that, right? Over here, because we are working through Google Drive, our data needs to be in our Google Drive. So here, if you see, this is my Google Drive. And if I go to my drive, if I go inside Collab Notebooks, Intellipaat, Weekend Batch, Linear Regression, this is where you will find my data, right? Now, if I want to read this data, I will have to set up my Google Drive. This is a predefined syntax, nothing, you don't need to change anything. You need to give permission to Collab to access the drive, right? So from google.collab, I'm importing drive and I'm mounting the drive. When I mount the drive, you will get a request to authenticate this. And once when you authenticate that, just like I would have done a minute back, you should be able to go ahead and you should be able to establish the connection. Now, if you see when I do this, this is the path of my file on my Google Drive, right? As soon as I do this, I am able to read this data, right? And that is the only difference. Other than that, every syntax that you are able to run on Python, on your Anaconda Jupyter notebooks, the same things you will be able to run here, right? It is essentially Python and nothing is different, right? I would suggest all of you to migrate to Google Colab only because uh, most, I would say 70 to 80% of the corporates that you have, right, they are using either Google Colab or a similar platform. So if you will be comfortable with Colab in your resumes, in your CVs, right, you can add this as a skill as well. Generally people are familiar with your Anaconda Python notebooks and all your locally hosted machines. But when you're working for large corporates, you are not working on locally hosted systems, right? You're you might be connected to GCP, you might be connected to cloud distributed computing and all. And in those cases, Collab or simpler platforms are much more easy to use, right? Till content drive and my drive, everything will remain the same. Even collab notebooks will remain the same. After that, you will have to create your folders. Wherever your data is present, you will have to add that. Okay. All right. So we have been able to read the data, and this is how my data looks like, right? So let's first try to understand what does this data contain, what is our problem, what is the objective. Let's try to understand all of these things, right? Now, if you see over here, I have the description of all the variables, right? This is the description that we have for all the variables. Let's try to understand this. Now, see, each and every row over here in this data is the data about a particular house, right? So if you look at this, this is the data for a particular house. This is the data for maybe, let's say, some other house located in Boston. This is the data for some other house, right? Let's focus on one row. Let's focus on the first row. If I focus on the first row, the first variable that I have is what? Is the variable which is crim. Crim is nothing but crime. So this variable gives you the per capita crime rate by town. So wherever your house is located, right? For that particular location, for that particular pin code, what is the crime rate? That is what the crim variable talks about. Okay. All right. Second variable is Zn. Zn is what? Proportion of residential land zoned for lots over 25,000 square feet. Right. Now, imagine that you are living in a sector where there are lands over 25,000 square feet, which are, let's say, uh, given to industries or let's say given to societies, right? So Zn is a variable that actually talks about that. That is the proportion of the land in that particular area, right? That is given to, or that is zoned for lots over 25,000 square feet. Now, for over 25,000 square feet, it can mean that there is a factory that is coming up, there is a mall that is coming up, there is a society that is coming up, anything. But this is talking about the proportion of land, right? Now, an area which is, let's say, located in an industrial area, it will have a higher proportion of land which has greater than 25,000 square feet of an entire land given to one single unit, right? So if you see over here, it says 18% of the land for wherever this particular house is located is given to lots which are greater than 25,000 square feet. All right, moving on to the third variable, Indus. Indus is proportion of non-retail business acres per town, right? So Indus will basically tell you what is the non-retail business acres in that particular area. So when I say non-retail business, once again, you can have retail specific businesses which can be there around your house, right? You can have malls, you can have a big bazaar, a Spencer, and things like that. But let's say when you start having industries, right? Let's say when you start having the shop for a footwear, right? Or let's say you start having the shop for, let's say, some other thing, maybe for a car showroom or things like that, right? So it is talking about that. It is talking about the percentage of non-retail business acres. Now you can imagine that an area which is a proper housing society, all of these percentages will be low, right? Zn and Indus and all. For a house which is located in an industrial area, or let's say for a house which is located in a corporate area, right? For those houses, all of these proportions will be high, right? Moving on to the fourth variable, it is CHAS. It is the short form for Charles River dummy variable. It is a binary variable. It just says that whether or not your house is situated along the Charles River. Now, Boston as a city, it has a river that flows through it, which is the Charles River. So, this is a binary variable which tells you that whether your house is situated on the banks of the river or not. Now, do you guys think that this is an important variable in predicting the price of a house, or all the variables till now? Do you guys think that these are important? These are important, right? Because a house which is situated on a river bank, obviously it should have a high cost. A house which has a low crime rate, it should have it should have a high cost, and so on and so forth, right? NOx is your pollution related variable, so it talks about nitric oxides concentration. So if NOx percentage will be high, then it means that this house is situated in an area where pollution is high. Maybe this house is situated next to industries, next to malls, right? And hence the pollution content might be high. So this once again talks about the quality of living that you might be having if you choose this house, right? RM is the average number of rooms per dwelling. So RM is, let's say if I talk about a particular area, let's say if I talk about South Delhi, in South Delhi, let's say if I take Saket, if on an average, each and every house, if I take the average of all the houses, the average of the rooms, let's say it comes out to be 2.5. So I'm saying that on an average, a house that is located in Saket will have 2.5 rooms. So just like that over here, your RM says, when it says 6.5, it means that the houses over here are pretty big. And on an average, they contain 6.5 rooms in this particular area. The age is proportion of owner occupied units built prior to 1940, right? Now, age is a variable which tells you about those percentage of houses in this area which were built before 1940. So, in this case, it is saying that 65% of the houses in this area are historical and they were built before 1940, right? So, this talks about whether the houses that are there in this area are new or old. If the houses might be old, maybe the price might be more high, or maybe it might be lesser, right? So age variable talks about that. Moving on to the dis variable, this is the weighted distances to 5 Boston employment centers, right? DIS variable. So this gives you the, so let's say if you want to purchase a house, right? Now, if you're aware with Gurgaon, a house which might be situated closer to Cyber Hub, which is a corporate hub which has all the companies, will probably be the best option for someone who works in a company, right? So the distance, if I go ahead and if I calculate the distance of this of a given house from the five important corporate centers of the city, right? So this distance will give you that uh, information, that is whether this house is situated centrally, whether this house is situated close to the corporate centers, or this house is something which is maybe situated on the outskirts of the city, right? All right. Now, RAD, the next variable is your index of accessibility to radial highways. So, just like distance was talking about the distance to corporate centers, RAD is talking about the index of accessibility. How far are the highways from this particular house, right? Is it situated inside the city, which might be far away from the highways, or is it something that is situated close to the highways that you have, right? Now, tax is the tax that you are paying for that particular house, right? So that is the tax amount per $10,000, right? So per $10,000, you are saying you are paying $296 for this house. PT ratio is pupil to teacher ratio, right? What do we mean by this? So PT ratio tells me that in this area, if there are 15 students, then there is one teacher, right? Now this tells you about the number of schools that you have in and around this particular area. Do you think that a PT ratio of a high PT ratio will be a good thing, or a low PT ratio will be a good thing? Low is good, right? Low means that there are more number of schools in and around your locality. So low PT ratio will actually give you the tell you that this area contains more number of schools. If there are more number of schools, then obviously you have more options to put your children in, right? Then black is the percentage of black population. If you see, black will be the proportion of blacks in this town, right? So this once again, not the proportion of blacks, but count of black people per 10,000 people in total, right? So if you see 396 and all, so this is now generally in the US, if let's say a locality contains more number of black people, maybe there is a high chance of uh, let's say robberies and all, right? So maybe the price of the house might not be very high there, right? So this is talking about that. L stat is the percentage of the lower status population that is living in that particular area, right? So L stat is, if you see 4.98, so 5% population belongs to the lower status, 10% belongs to lower status, and so on and so forth, right? And then medv is the target variable that you have, that is the median value of all the houses that are there in this particular area, right? So if you look at this, medv becomes your target variable. So our objective is to go ahead and predict the medv variable. Ideally your crime rate should be correlated to, let's say, the proportion of, or the black variable, or maybe the lower status variable as well. So this is something that we can check once when we are checking the correlation matrix. See, when you go to buy a house, right? The important factors are what? That your house should be close to highways, your house should be close to malls, your house should be close to schools, hospitals, and all, right? So if it is high, it means that schools, there are not many schools which are around there. So probably the price of the house can be low, right? All right. So this is the data that we have, and the target variable that we have over here is medv. All right. So let's move forward then. So this is, I have done a data dot head over here. So these are the top 5 rows. I also have a function which is known as data dot tail, right? Tail, what it will do is that it will show you the last 5, 10 rows. If you don't give any value, it will automatically show you the last 5 rows. If you want to, let's say, see the last 10 rows, you go ahead and you give a 10 and it will show you the last 10 rows. Correct? So now from here we can see that there are 505 rows over here in this data in total. Okay. Let's look at the shape of the data. We'll do some basic data exploration now. So my shape of the data is I have 516, I have 506 rows and I have 14 columns, right? I will describe my data. Let's go ahead and describe this data. What does this dot T do? Any idea? Transpose, right? So I've just done this for ease of readability. if you do it like this, when you have more number of variables, right, this can you'll have to scroll towards the right, right? So if I just transpose this, it becomes easy to view. So that's why I've transposed. Okay. Now, why do we use the describe function? What do you think is the use of this? Is it just a protocol that we need to follow to know the basic stats? All right. Okay. So all good insights. Let me go through the common answers now. So first of all, I had insights on crime rate and ZN. Right. If you see crime rate, there are areas wherein the crime rate is close to 89%, right? Meaning that these are very unsafe areas. So within Boston City, you have areas wherein the crime rate is as low as 0%, and you also have areas where the crime rate is as high as 89%, right? Similarly, if you look at ZN, there are certain areas in this city where the entire 100% of the land is actually zoned out to lots greater than 25,000 square feet, right? Then Zn, if you see, the max value of Zn is what? 100%, right? 100% means that this variable was giving you the percentage of houses, or sorry, the percentages of the total land which was zoned out to greater than 25,000 lots, right? So there are areas wherein there are locations in the city wherein there are all the land that is zoned out is greater than 25,000 square feet. No land is less than 25,000 square feet. So maybe this is an area which contains of industries. Maybe this is an area which contains of farmhouses only, right? So that's what your ZN is talking about. Now, see, apart from these insights, the describe function also comes in to be very useful as a sanity check of your data, right? Now, let's assume over here I had an age variable. Now, our age variable means something else, but let's assume I had the age of customers, right? Now, let's say you go ahead and look at the minimum and maximum value, and you're seeing that the minimum value is coming out to be 0 and the maximum is coming out to be 200. Then obviously you have to go back and you have to question your data team that how can age be 200, how can age be greater than 80, 90, how can age be less than, let's say, 10, 11, 18 years, right? Whatever your minimum age might be. So your describe function, it helps you in understanding your data, but it also helps you in identifying uh, anomalies, identifying outliers that might be present in the data, right? All right. So let's go ahead and do some basic visualization. Now, I will not be spending too much time on the EDA and all because that is something that you guys have already done, but I will talk about the important concepts, what we need to do and all, right? First thing that we need to do is that we need to start with the visualization of the target variable. What is a target variable over here? A target variable is medv, which is a numerical variable, which is a continuous variable. So I go ahead and I import cbond as SNS and I call the dist plot function, right? This will be the distribution plot. Uh, this is the histogram and this is what I can see, right? What do you guys think? Is this a normally distributed uh, data, or it has some amount of skewness? Or looking at this data, anything that you can make out, any insights that you can think of? Right, skewed, but if you see towards the end, there is a very high percentage over here, right? So there are houses which are very expensive, and there are lots of people who are buying these houses. So if you look at this, right, this is actually true because let's say if you focus on cities like Delhi, Mumbai, and all, maybe mediocre people like us, we might be able to afford a house in the range of 50 lakhs, 1 crore, maybe 1.5 at the max. But then there will be, let's say, people who are rich, people who are businessmen, people who have been living in the city. Their generations would have been in this in the city for years, and these are people who have huge amounts of money, and this will also contribute a significant percentage, right? And these are people who are living in, let's say, villas and farmhouses and all. And hence you can see that for your extremely expensive houses as well, there is a good percentage of distribution that I can see over here in this data, right? So this looks like that this actually looks like real world data because most of your data is populated towards the left hand side, meaning this focuses on your, let's say, people who are below average, or let's say mediocre families, maybe average families, right? Most of the people in a city will be like this. Then if you move from here, right, if you move to 30 till 48 onwards, this percentage will be less, because as and when the price keeps on increasing, the amount of people who are buying those houses obviously goes on decreasing, right? But then there will come a point wherein you are going to reach to the audience which is super rich. The super rich audience, they don't care, right? Even if a house is priced at 50 crore, they have the potential to go ahead and buy it. And that's what we are able to see over here, right? So looks good. I think this is something that tells us about how real world interaction also happens, right? Now, if you want, you can use any other target variable as well, right? But because I know that all of these variables will be correlated to the price of a house, I have taken medv as the target. You see, you do not identify medv as a target variable. uh, you take a business problem and you convert that to a mathematical problem. If your business comes to you and they say that I want you to predict the spend of the customer, and they give you 20 features, will you identify the target variable, or do you already know the target variable? Your target variable, you know that it is the spend of customers, right? Now you will try to collect data which is correlated with spend. This case study is a case study which aims on predicting the price of a house, right? So that's why your medv is the target variable. Aishwarya, go back to the basics of your distributions, visualization, and all. This is right skewed because this has a tail towards the right hand side. All of this is basic stuff. This is a normal distribution, right, with no skew. This will be a normal distribution which is skewed towards the right hand side, or positive skew. This will be a normal distribution with a negative or a left hand skewness, right? Left side skew. All right. Now, like this, you can go ahead and you can plot all the rest of the columns as well, one by one. I will not be doing that. But you can see that this is the distance variable. Now, for the distance variable, this was the distance from highways. So you can see that most of the houses that you have are actually situated very close to the highways in the city. But then there is certain percentage of houses that you have which are actually situated very far apart from the highways, right? So just like this, you can go ahead and you can visualize it for all the variables one by one. But this is an EDA that you can do when when we are done with this session, right? All right. Now let's try to clean this data slightly. Let's see. Say uh, either you can check if the data has dropped, if the data has duplicates or not, or you can just directly go ahead and drop the duplicates, right? So what I'm doing is that directly I'm not checking if there would have been any duplicates in the data, they will be automatically dropped, right? So you do not need to worry about whether there are duplicates or not. Just go ahead and add this condition, drop duplicates, and it will automatically drop your duplicates from the data, right? Now I'll go ahead and I'll check the information on this data. What this will talk about is if there are any missing values in the data or not, and the data type, right? So there are no missing values. All the variables have exactly 506 values populated, and the data type is either float or int, right? So there are no categorical values over here. All the variables are either integer or float. All right. Now let's go ahead and let's check for correlation of all these variables with respect to our target variable, which is medv. Right. So what I do is that I go ahead and I call the correlation function, and I limit the output to only the medv variable. So if you see, this output tells you about the correlation of each and every variable with your target variable, right? I want you to go through each and every variable. What is the difference between dist plot, hist plot? So there is not a very big difference. See, dist plot and hist plot. Hist plot is the histogram directly. Dist plot, in case of dist plot, right, you can also have a distribution along with this. There are certain parameters that we have There was one parameter which is different in his plot. I'm just trying to find that out. Otherwise, there is no difference between his plot and this plot as well. Okay, so this is his plot, right? This was this plot. So let's look at this. Yeah, so here I think you can also play around with the kind, right? So kind, if I give as, let's say there are options which I can give. I'm not sure what options are there. But in the kind, actually, you can change this histogram to a kernel density estimation as well, I think. Let's try KDE. Yeah, so if you see KDE, yes, kind equals to KDE. For disk plot, we have options. If you go ahead and if you can convert this to a distribution plot as well, right? If you want to plot a histogram, you go ahead with the standard option, or you can mention this here. And okay, now let's come to this correlation. Now I want you to go through these correlation values and see if they are making sense, right? I'll give you one example. So if you look at this over here, my crime rate has a negative correlation with Medve, telling me that if crime is higher, then the price of the house will be low and vice versa. And this is something that makes sense, right? This is something that is expected. Now, just go through each and every variable one by one and see if all of the variables are, or the sign of the correlation matrix for all of the variable is making sense or not. Okay. So for the black one, the correlation looks out to be counterintuitive, right? That is where there are more number of blacks, the price of the house is high, right? Now, see, this is something that you can see. Ideally, you will have assumptions about the data. Now, Boston as a city might not be that much affected by, let's say, blacks in a negative way, right? So this is what our data is telling me. So although the correlation value looks out to be counterintuitive, ideally from a normal point of view, maybe if there are more number of blacks, then the crime rate should be high and all. But as you see in our data, for 10,000 people living in an area, there are only blacks in the range of 350 to 400, which is what? Which is only 40 4% or 0.4% of the population, right? Just 0.4%. So that's a very low value. So hence, over here you can see that the correlation is coming out to be positive, right? So that's okay. Medve has a negative correlation with tax. So that means that if tax will be higher, the price of the house will be lower. So maybe the tax structure in Boston would be such that the more that you are paying, right? So see, generally in certain US cities, the tax structure is flat. Even if you buy, let's say, a house of let's say $1 lakh, you are paying, let's say, 10,000 as a tax. Even if you buy a house of $5 lakh, you are paying the same 10,000 as a tax, right? So maybe they have a flat structure for tax. That is why we are seeing a negative correlation. So LSTAT is negative, right? So LSTAT says that lower status population. So the lesser lower status population, the higher the price, and vice versa. RAD is negative, meaning that houses which are situated close to the radial highways, their prices are less. Houses which are situated far apart from the radial houses, their prices are more. Maybe this indicates on the fact that people do not want to live near busy highways where it can be noisy, where maybe the pollution can be high. So people in Boston, they prefer living in areas which are slightly far apart from the highways so that they have more peaceful and quiet living, right? Okay. All right. So, as I said, we are done with the EDA, right? So, this was a concise EDA, but ideally, you should go ahead and you should look at all the different variables, visualize the variables univariate, bivariate. That is something that you can do on your own time, right? Because EDA part remains the same, whatever you have covered in the NumPy, Pandas, visualization aspect, all of those things remain the same, right? Now we will move on to the model building part. Now, while building the model, we need to divide our data. First step that we need to do is that we need to divide our data into our features, that is independent variables, and the dependent variable, that is the target variable, right? So what we will do over here is that at first, what I'm doing is that I will only take the highly correlated variable, right? So first, what I'll do is that I'm using, let's take the most highly correlated variable, which is LStat, right? So I'll take LStat over here as my independent variable. I'm not starting with a multi-linear regression model as of now. As first, as a first step, I'm just starting with your single model, simple linear regression, wherein we will have one single variable and one target variable, right? And for that, I am picking the most highly correlated variable. If you look at this over here, your L stat is a variable which has the highest correlation, right? Followed by RM, and then there are other variables as well. So I'm just taking L stat as a variable and then medv as the target variable. Okay. I will not be using VIF as of now. I think you have the code for that, but as and when we proceed through this course, right, I will be talking about other methods as well for variable action, right? So there are other methods as well, that is using decision trees, random forest, and all. Once when we do that, after that, so those approaches are actually faster as compared to VIF. Now, VIF, you guys understand the logic and all, that's fine, but I will also tell you a downside of AIF. The downside of AIF is that because you are creating, assume you have 100 features, right? In order to calculate VIF, you need to create 100 models of all these 100 features one by one, and you need to come up with 100 R squares. That will be one iteration of VIF, right? Now, if you think about, let's say, if you have to eliminate 50 variables, you will be running 50, you will be running this loop 50 times. So that is, if you have 100 variables in the first iteration, 99 in the second, 98 in the third, so you can do the maths that how many models you are going to build. So this in the real world is not a very time effective way of doing things. So that is why you guys know what VIF is. That is good. You should be knowing about VIF, but as and when we will be moving on to more complicated topics, I will talk about other variable selection techniques which are way faster than VIF and which is something that is used in the industry nowadays, right? All right. So as a first step, first what we are doing is that we are building a model using only one single independent variable, which is LStat, followed by the target variable, which is medv, right? I hope this is clear to everyone. If you look at this, this becomes my data. X is my feature and Y is my target variable. Okay. All right. So what is it that we need to do next? We will look at the size of both X and Y. My X contains 506 elements, Y contains 506 elements. Next thing that we need to do is that we need to divide our data into training and testing. Why do we need to divide our data into training and testing? Any idea? Then what is test for? And to test, right? So train data will be used for training the model. Test data will be used for testing the model's performance, and this will tell us whether the model is overfitting, underfitting, whatever, right? So I can create a model which is giving me a 90% accuracy on training data, but that will not be useful unless if I have a similar accuracy on the testing data, right? So for that, we are using train test split. Train test split is a function, right, which needs input. You pass any data as an input to this model. Over here, I'm passing my X and Y. I pass a test size parameter, which I mark at 0.2. 0.2 meaning that 20% of your rows are going to go in your testing data, right? So for 506, 20% close to 100 rows will be going into your testing data, right? Now, random state equals to 23. What this hyperparameter does is that, so let me explain this to you through an example. Now, let's say I run this. Let's take away the random state variable. I will run this and I will show you what X train contains, right? Just look at the index of X-train values. I will run this once again, right? And I will plot X-train once again. Now compare this X-train with this X-train. Do you see the indexes to be same or different? Different, right? So if you do not specify any random state, then what will happen is that each and every time random values will be going into training and testing, right? Now, random state you can specify as any value, right? Now, let's say if I go ahead and specify this as 20, I go ahead and I run xtrain, right? 7, 268, 80. I will run this once again and I will show you what xtrain looks like once again. And you can see that the exactly same indexes are going into your trained data each and every time. Why do we need to do this? We need to do this because let's say you run your model once without using random state and you get an accuracy of, let's say, 70%. Now, let's say you run the same model in front of your senior and this time you get an accuracy of 68%. Now they will come to you and they will say that why you were saying that it was 70, why is it 68? Right? So if you want to replicate the same outputs each and every time, then you should be using a random state value. It can be anything, it can be any random number. As long as you are taking the same random number each and every time, it does not matter. It will select the same number of rows. Test size is for the test data. 20% is the testing data size. If you look at this test size, if you look at the shape as well of our data, our X train contains 400 rows, X test contains 100 rows. So 80% is for training and 20% is for testing, right? And then we go ahead and we build our model. In order to build our model, I have my training data, I have my testing data. I will import the model from sklearn library, sklearn dot linear model. I import linear regression. I instantiate the model object linear regression in a variable named as regressor. I do a regressor.fit. When I do a dot fit, it will train the model because here I'm passing the training data, that is X train and Y train. Right? If I run this, now your model training is complete. Right? If you look at this, the model training is done. Fit means that as soon as you fit it, it will go ahead and give you the coefficients for the best fitting line, right? So now once when the model has been trained, you can see that I can go ahead and I can find out things such as the intercept value. Intercept was what? It was the constant, and I can find out the coefficient of the model. Now, because I have one single feature, this will become my coefficient. So if you look at this, my equation has actually become medv is equal to 34.927 minus 0.966 multiplied by LStat. LStat was the variable, right? Yeah. So now from here, you can see that the equation of my linear regression model, the equation from the best fitting line is coming out to be this, right? Because my intercept was the constant, that is 34.927, and my coefficient corresponding to the single variable, which is LStat, is coming out to be 0.966, right? So this becomes my equation. Although you don't need to use it manually, you will still be able to arrive at this equation, right? All right. Now that the model training has been done, what do we need to do? We need to make predictions on our testing data, right? So I will go ahead and I will use the same model object, that is regressor. And this time I use the predict function. For training my model, I had used my fit function. For predicting using the same model, that is the same line of best fit which we have gotten, I use a predict function. I do a regressor.predict and I pass my testing data. And whatever values I get, I save it in a variable known as ypred, right? Now ypred, I just convert this to a data frame. If you look at this over here, if I show you ypred, this will be an array, right? Now these are your 104 values of your testing data, 104 predicted values of your testing data, right? So we go ahead and we convert this to a data frame. This is the predicted output. You have created a model to get predictions, right? So this is the predicted output that you are getting. Now, what do we need to do in order to check the performance of the model? We need to compare these predicted values with the real values, right? Actual values. So what I'll do is that I'm converting this to a data frame first of all, right? This array has been converted to a data frame using pd.dataframe function. I pass the array and I pass the column name as predicted, right? To this array, I will append my actual values as well. If you look at this, y test was my actual values, right? These were my actual 102 values. So what I'll do now is that I will add both the actual and the predicted to a data frame known as df underscore pred, right? And I'm just doing some resetting, right? My actual becomes my test data and my predicted becomes my ypred. Because both of these were data frames, I'm just resetting the index, because if you see over here, these have different values. I want the index to have these values 0, 1, 2, 3 till 101, right? And this becomes my actual versus predicted. Now, can you go ahead and can you calculate the error, different kinds of errors? First of all, before going ahead and calculating the different errors, just having a look at this, do you think that the predictions are somewhat close to the actual values, or they are far apart, or they are, let's say, decently apart? Right, so for some cases it is close, for some it is off. If you look at this over here, actual was 21, model is predicting 14. Here 13 and 12 very close. Here 18.9, 18, 13, 16, right? So how can we check the overall performance of the model? We can calculate our error metrics. Now either you can calculate the error over here in the data frame. So what will be the error? If I go ahead and if I calculate the just the error, right, it will be actual minus predicted. So you can calculate it either like this, right? Or you can go ahead and you can see, this is a messy way of doing things. We have inbuilt functions in Python, right? From sklearn I import metrics, and this metrics will contain all the different kinds of errors that there are. So if you look at this, it has mean absolute error, it has mean squared error, it has your root mean square error. Anything that you need, it will go ahead and it will give you that. So if you see, what I'm doing is that I'm calling all of these functions one by one and I'm passing my actual and the predicted values here. If I run this, this will give me the overall error of the model, right? If you see, your mean absolute error is 4.5. What does this tell you? That on an average, your predictions are off by 4, by a value of 4. So 4 over here is nothing but $4,000, right? So your predictions are off by close to $4,000. Right, so we are using the actual function. sklearn is a library which contains all of these models. Okay, now mean squared error is 35. Because this is a squared error, the unit will not be same. If you take the root of mean squared error, that will be RMSE, that is 5.8 5.9, right? I can also calculate something known as mean absolute percentage error. So let's see. So if you see mean absolute percentage error, if I pass the same y test and y pred, I will get on an average, my predictions are off by what percentage, right? So if you look at this, so it says that on an average, my predictions are off by 21%, right? So the model is doing a decent job. It is not doing a very good job. But why is that happening? Because I'm using only one single feature, right? If you see over here, I'm using only one feature, which is LSTAT, and using only one feature, I am still able to create a model which is giving me a percentage error of around 21% only. So obviously, if I increase the number of features, my model accuracy or my model error should decrease, right? Okay, let's try to get the R square score, R square. For R square as well, sklearn.metrics, it has a function which is R square score. All we need to do is that we need to pass y test, y pred and all, and it will give me the R square score. What is the R square score coming out to be? 44%, right? Meaning that these three variables, sorry, this one variable is only able to capture 44% of the variation of your target variable. Okay, so let's assume that these are your actual and predicted values. So what will be your absolute error? Absolute error is what? It will be the, doesn't matter what the sign of the error is, you're just taking a difference of actual minus predicted, right? This will be the actual error that we have. If I take the average of this, that will be what? That will be mean absolute error, right? So this will be MAE. Okay. If I take the average of my actual values, all the actuals, and then I just calculate a percentage, right? That is error divided by the actual average of actual. This will give me mean absolute percentage error. Because here, if you see, I'm converting this error to a percentage with respect to my actual average. Okay. Now, there is also something known as MSE. MSE is what? This 4.86, what percentage is that of your total average of actual value? If you calculate the percentage, this is 4.86 divided by 36 is what? Is around 14%. Now we have something known as mean squared error. Over here, what we do is that we take the square of the error first, right? So if this was my error, I'll do this into the same value, right? Okay. And then if I take an average of this will become your mean square error, right? This will become your MSE. This is the squared error. And if you take a root of this, if you take a under root of this, that will become your RMSE, root mean square error. Why root mean square error? The logic of root mean square error is that the values which are more away, the predicted values which are more far apart than the actual, you want to penalize them more. If you look at this over here, this absolute error squared becomes 1. Square of 0 becomes 0, but the square of 9 becomes 81. So it means that you are giving more weightage, or you are penalizing those data points more, which are far apart from the actual value. All right. So these are your standard errors and how they are calculated. Actual value is the actual value, right? You will have the actual value for the data, whatever your target variable will be. Right now, my R square is coming out to be 44.4%. So now what can we do next? Next, let's do one thing, right? I will add the second highest correlated variable, and ideally, through the assumption, my R square should increase, my errors should decrease, correct? Does that make sense? So what I'll do is that over here only, right? I will repeat the same process, and I will add one more variable, which is RM, to this. I hope that makes sense. So here what I'll do is that I will add the RM feature as well, because RM, you can see, is the next variable which has close to 70% correlation, right? So let's add RM and LStat. Now my features become two, LStat and RM. Target variable remains the same. I divide my data once again into training and testing. You can see that now the shape of your training data becomes 404, 2. Why? Because now you have two variables. I fit the same model. This time in the model, I will get one intercept value as usual, but I will get two coefficients, right? If you look at this, I am getting two coefficients. My equation will be what? My final equation will be med v equals to, so it will be minus 0.24, that's my coefficient, minus 0.66 into L stat, because that was my first variable, plus 4.98 into your RM variable, right? Now here, if you see, the signs are actually telling you whether the variable has a positive influence or a negative influence on your target variable. You see, my lower status variable, because it was negatively correlated with the target variable, it has a negative coefficient over here, meaning that when the value of lower status will decrease by 0.66, your mid-V, that is the price of your house, is going to increase by $1,000. If you look at this, when you are going to add one room to a house, the price of your house is going to increase by $5,000, right? All right. So now let's go ahead and let's check the performance of this new model, right? So let's get the predictions. So these are the new predictions. I will once again do the same things. I will convert this to a data frame. I will take my Y test. I will calculate the overall data frame, right? Now here you can see that this prediction, which was way more off earlier we were getting a value of somewhere around 20, right? Now I'm getting a much more closer value, right? Let's look at these errors, although this is just the overall error. I'll calculate now in a new line, I will calculate the new errors, right? Now I want you to compare the errors from above to below, right? This one was the errors when I used only one single variable. These are the errors when I use two variables. Do you see for each and every error metric, do you see the error value going down? And if I go ahead and if I print the R square score now, can you see that the R square score has also increased from 44 to 58, right? So we can see that as in when we are adding more variables, my overall model performance is actually increasing, right? So now what I'll do is that I'll straight away go ahead and I will use all the variables, right? Directly, right? I'll be using all the variables and we will go ahead and we'll see how our model is performing, right? I'll read the data once again because we have transformed some of the data. We have dropped some variables. So I'm reading the data once again. This is the same data. Ideally, you should be using all the variables that are given to you, but maybe you apply VIF check to eliminate the features which are not required. Maybe you eliminate features by using correlation and all, right? But as in when we proceed forward, right, I will be talking about other feature selection methods. But right now, you can go ahead and you can use all the variables that are given because this is a case study. We are only using those features which are important. How do we need to tackle with variables in the real world? That we'll be learning about in our future sessions. Right. So what I'm doing is that I'm selecting all the features, but the last one as my X, that is the independent variables. I am selecting only the last feature as my target variable. So if you see Y is my target variable, which is midway, and I proceed with the same steps. I split my data into 20% testing and 80% training. So the exact same values that we had seen last time, and there is nothing from a coding point of view, you can see that nothing changes, right? All you have to do is that you have to change the data and your model will automatically adapt. Now if I'm passing all the features, I'm still passing the same model, calling the same model, nothing has changed, right? So if you see over here, I fit my model linear regression, but this time I will be getting many coefficients, right? If you look at this time I'm getting many coefficients. Why do I get so many coefficients this time? My intercept will remain the same, right? Intercept will be the single value only, but I am getting these, right? Exactly, because we have so many features. So for each and every feature, I am getting a coefficient value. So let's go ahead and let's see what are the coefficients for the different features that we have. So what I do is that I create a data frame of my coefficient values. I create a data frame of my column names, right? And what I'll do is that I'll combine both of these data frames together to get these into one column, right? So I do a pd.concat. I concatenate these two and I get this data frame, which basically tells me that the attribute is crim and the coefficient is this. The attribute is Zn and the coefficient is this. Now you can do a very quick sense check that whether the signs of these variables is actually in line with the correlation. You see NOx, this was negatively correlated with my target variable. That is higher the pollution, lower the price. That is why the sign of this variable is coming out to be minus, right? You look at, let's say, anything else, maybe let's say Chas. So if a house is situated next to the Charles River, then the price will be high. Hence, it is positively correlated. Hence, the sign is positive. Okay. We go ahead and now we take the same model and make predictions. I do a regressor.predict using my testing data and I get my predicted values. And then I'll follow the same process. I have my actual values and I have my predicted values. I calculate the error of my model. And now, if you remember previously, let me show you the error from the last values from the last model. It was 4.09, 26, and 5.17, right? And now it is coming at 3.2, 20, and 4.5, right? So you can see that the errors have actually reduced even more. If I look at the R square score now, you can see that the R square score has also increased to 73%, right? And this is how your linear regression model is coded in Python. Now, there are some aspects. See, linear regression model, it's a very basic model. So, whatever is required from a coding point of view, I have included that in this case study, right? There can be n number of additional things that you can do. That is the EDA and all, VIF and all. For VIF, I want you guys to go ahead, and this is an assignment that I'm giving you. I want you to go ahead and I want you to implement VIF in this code and see if you can increase the R square from 73 to some other greater value, right? 73% is decent. You are able to capture 73% variation, right? But you can increase this R square value, right? Slightly if you apply VIF. That is, there will be correlated variables that are present over here in the model which might be impacting, right? But this is overall from an industry standards point of view, you don't need anything else from a linear regression model's point of view, right? This is all that you will need. So if you are able to understand this notebooks, I think you are good with the linear regression model. And just make sure that you understand everything in this notebook and then you should be well placed. If you're applying for a managerial role in a company, if you don't have to do hands on, then you should, it's okay if you don't remember these. But I'm assuming since you're doing a technical course, so you will be obviously applying for a technical job, right? You might be applying for a data scientist job. So obviously in that case, you should be knowing about these concepts and you should be able to replicate these in real world case studies as well, right? So whatever I have done, if you think that now your understanding of linear regression model is complete, so that is wrong, right? You have only covered 20-25% of it. The remaining 70-75% will come once when you do the hands on your own, right? Take the data, start building the models. There are so many data sets that are present online. Go ahead and take those and start applying the linear regression model, because then you will be facing actual issues. And say, it's not that this notebook will work in your actual company, right? Let's say you are given you are asked to solve a problem using linear regression. You cannot go ahead and take the exact same notebook. Yes, the syntax will remain same. Yes, the flow will remain the same, but the data will change, right? So obviously you cannot be blind and you cannot just blindly follow what we are doing over here. So in order to develop that skill, you will have to get your hands dirty. Actual values are values that you have collected historically, right? Actual values, this is the data that was given to us. Now, from that data, we have gone ahead and we have divided it into training and testing. Machine learning is all about using historical data to make predictions, right? So, but while we are building the model, I will use a part of the historical data to just check how well my model is performing.
Question 3. What is machine learning? Option 1. A type of computer. Option 2. A technique for teaching computers to learn from data. Option 3. A programming language. Or option 4. A hardware device. Tell us your answer in the comments below. Just a quick info, guys. Intellipaat offers an executive postgraduate certification in data science and AI, where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps, and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
So we will be talking about a new model, right? Logistic regression. Now, if you remember when we started, when we were going through the introduction, if I talk about, let's say, machine learning, right? Machine learning as a whole, I can go ahead and I can divide machine learning into what two buckets? So supervised and unsupervised, right? So I hope everyone remembers this. Then if we double click on supervised learning, this is something that we can break down into regression and classification, correct? Within supervised, you will have regression kind of models and you will have classification kind of models, right? Last week we had studied linear regression model, which was what? Which was a regression model. That is, our target variable in that case was a continuous target variable. This week we will be studying about the logistic regression model, which is a classification model. Now, the name might suggest that it is a regression model, but logistic regression, the name is a misnomer, right? It does not mean that it is a regression model. By the end of the theory part, you will be able to understand why do we call it as regression. In the short answer is that because logistic regression has evolved from linear regression, that is why we just go ahead and we call it as logistic regression. But at the end of the day, the kind of problems that we will be able to solve using logistic regressions are the problems wherein your target variable can be categorical in nature, right? Can you guys list down any problems that come to your mind when I say categorical or classification problems? What kind of problems will we be able to solve using logistic regression? So, any target variable which is categorical in nature, it can be a category, which can be a yes or a no, right? Or a, let's say, buy, not buy, right? Give a loan to a customer or do not give a loan to a customer. Is the email spam or not spam, right? Any such problems you will be able to solve using the logistic regression model, right? All right. So linear regression, what it did was that it helped us in predicting a continuous target variable. That's what the example over here is, right? The example is a, right, help me find a property with bigger garden area for X bucks, right? So if let's say a customer comes to you and they say that have a I have a spending potential of this much, right? With this much spending potential, what is the area of the house that I can probably get, right? So now this is a kind of problem which linear regression modeling can solve, right? Because you are predicting the area of the house by, let's say, looking at the budget that the customer might have, right? So this is a regression problem, right? So if someone comes to you with such a question, all you can do is that you can go ahead and you can apply the linear regression model, and the model will just go ahead and give you the predictions of the kind of house or the area of the house that the customer can get, and that's what you can go ahead and go back and tell the customer, right? But so now this is just an example, right? These slides are very basic. So this over here, if my target variable becomes the budget of the client, right, on the x-axis, sorry, not the target variable, my independent variable, or that is my feature, becomes the budget or the money that the customer is willing to spend. Then on my y-axis, I have the dependent variable, which is the size of property, right? So I hope you guys are able to understand this, that there will be a positive correlation, right? Obviously, the more you spend, the bigger the house you will be able to buy, right? Okay. Now, if I, let's say, if my independent variable is garden area, right? Then if my garden area will be bigger, then the house area will be smaller, right? If let's say you go ahead and you take all the houses of 2000 square feet, right? Now all the houses of 2000 square feet, let's say one house has a garden of 1000 square feet, right? Other house has a garden of 500 square feet. Now accordingly, if the garden area is high, then obviously the livable area will be low, right? So this is just an example of the negative correlation, right? But this is what we did in case of linear uh, uh, linear regression model, right? And how did we do that? We took our historical data and we went ahead and we plotted that on this particular x and y act, right? Let's say 10 of my existing customers, earlier customers, they would have had 10 different budgets. And on the basis of the budgets that they would have earlier gone ahead and purchased houses of different area sizes, right? So what we'll do is that we will go ahead and we will plot these points, right? So let's say I go ahead and I say that I have a customer who purchased a house which belonged somewhere over here, right? So let's say less budget, less area, right? Then let's say there was a customer who purchased a house somewhere over here, right? Then maybe here, something like this, right? And then using these data points, we will be able to get the equation of a straight line, right? This was what we had studied in case of the linear regression model, right? But can we go ahead and can we use a linear regression model for problems such as, will the property have a good neighborhood? Will it rain tomorrow or not? Is the email spam or not? No, right? We cannot use the linear regression model for these cases, right? I cannot use the regression model over here. I cannot use it over here. I cannot use it over here, right? And in that case, what do we need to do? We need to move on to some other model, right? So if we have a classification problem, that is my target variable is categorical in nature, we need to go ahead and we need to apply logistic regression model, right? So the objective of all of these 12 slides was only to lay the foundation of logistic regression and what kind of questions logistic regression will be able to solve, right? All right. Now, this is again the same thing. Machine learning can be divided into supervised and unsupervised. Right? Just go through this. I hope everyone is able to understand this. SVM is just a model. It is another classification model. So don't get confused by that. All right. So let's move on. Right? Now, before getting started with logistic regression, let's try to understand some basics. Right? I'll just go to a blank page. So let me take an example. I want to collect some data, right? Name, age, and target, that is working or student, right? I want 10 samples over here, right? We have around 12 data points, right? Okay. Now let's try to plot this data. What will we have on my, what will I have on my x-axis? What will I have on my y-axis? If I start plotting this data. So let's say on the x-axis, I have age, right? And on the y-axis, I have the target, that is, let's say, status, right? I'll just write it as status. I'll start my age from 18. I think we have uh, the minimum age as 18, right? So 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 41, 52, or something, right? I think 33 is the maximum that I have in my data as well, right? Yes. Okay. And then how will I plot my target variable over here? So my x-axis is fine. I am able to plot that. How can I plot my target variable over here? What do you guys think? My target is what? My target is categorical in nature, right? So how can I plot that? So see, in Python, obviously, we will convert that into labels. Maybe 0 means that a person is a student, 1 means that a person is working, right? Over here, I'm just writing down the label over here, right? Just for our convenience. I'm just saying that if it is this particular, I'll just give the line. This is a student and this is, let's say, working, right? So I'll draw two horizontal lines which will just tell me whether the person is working or whether the person is a student. Does this make sense? There's just two lines. Wherever a person will be working, so I'll just give you one example. Let's start from the smallest, that is Nandini, right? The youngest in our batch or in this example. So we have Nandini. Where will we plot her name? What do you guys think? She is 18 and she is a student. So I need to mark Nandini over here, right? Does this make sense? X axis is on 18 and the Y axis is on student, right? Now let's move to the next person. After 18, we have Praneeth, who is 21, right? Do we have anyone else in the range? No, right? So Praneeth is 21 and Praneeth is also a student. Then we have 23, we have three people, right? Or four people. So 23 is interesting, correct? So if you look at 23, at 23, we have, we'll start from the top. We have Charan, who is a student, right? Then we have Satyam, who is also a student. So I will just give two crosses over here, right? Slightly above. Okay. Then we have Jaya and we have Vidya, both of whom are working, correct? So for Jaya and Vidya, we will have 2 marks over here, right? So this I will just mark slightly above so that you're able to see. Does this make sense to everyone? Any questions till now? I hope everyone is able to understand how I'm plotting this data. Okay, then who's next? After 23, we have 25, right? We have Mohan, who is 25 and who is working. So this is Mohan. Then we have, uh, after 25, what do we have? We have Gaurav as well, who is working. Yes. So we have Gaurav at 25 who is working. Then who's next? 28, right? We have two people who are 28, Rishabh and Nitin. And Rishabh and Nitin both are working. So we'll have two crosses here, correct? Then we have 31, Harshit, right? Who is working. And then we have Audrey, who's 33 and who's a student, correct? So Audrey will be over here. I think we are done, right? We have 5 over here. Okay. So this is how our data looks like, right? Correct? I hope everyone is able to understand this. All right. Now, all of you know how linear regression model works, right? If let's say, can you try, first of all, can you try fitting a line of best fit which will cross through all of these data points, or which will be closer to all of these data points? Or let's try to apply the linear regression model using the mathematics that we have understood. What will the model try to do over here? See, you can still apply the linear regression model over here, but the how will you try to get the best fitting line is the question, right? Now, see, if I try to, let's say, fit a line which passes through all of these data points, or which is, let's say, closest, what I will get as an output will be something like this, right? Because if you have a line which is something like this, then what will happen is that if you calculate the vertical distances, right, the vertical distances will be somewhat the minimum in for this particular line, correct? Right? Let's assume that we went ahead. Let's say that we actually went ahead with a linear regression model. Now, can you tell me what will my line predict between student and working? So this student, let's say this student is signified by 0, right? By the label 0, and this working is signified by the label 1. right? Let's say this is what we get, right? Now, my linear regression model will say that for someone, so let's say I take this example 31, right? For someone whose age is 31, my linear regression model will say that the output is this, right? This might be the value, let's say 0.8. But what is 0.8? Is 0.8 a label that we have given? No, right? It is nothing. So it is near to working, but see, 0 and 1 over here are labels. I am saying that 0 is a student and 1 is working. But my linear regression model is giving me a value which is somewhere in the center. So how do I know what 0.8 is? It is close to working, that is fine. But then that is not the correct value, right? So do you guys think that linear regression model, first of all, this is the linear regression model is not appropriate over here because one single line cannot fit through all of these data points, right? Second point is that even if I go ahead and even if I apply the linear regression model over here, I'm not, if you go ahead and if you run the model in Python, it will work. But the predictions that you will get from the model, do you think that the predictions will be correct? See, in this case, you cannot say that as a probability, right? Probability is something else, right? This is just a linear value. You can still, so the best interpretation will be that this value is close to 1, so it means that this the probability of, let's say, this person working will be slightly higher. You can say that, but this 0.8 is not a probability that you're getting, correct? Ordinary linear and logistic both can work with more than one variables, right? I'm just giving an example with one single variable because that is easy to understand and explain. But both of these models can work with multiple independent variables, right? Independent features is not a problem. All right. Is everyone able to understand why linear regression model will not be the best model over here? All right. Now, let's say I went ahead and I changed this output to a curve which looked like this, to an S-shaped curve, right? Something, just imagine that this is a smooth curve, but something like this. What if I went ahead and I told you that this is a, I'm not fitting the line of best fit, but I'm fitting a curve of best fit, right? An S-shaped curve. If you look at this looks like an S-shaped curve, not exactly an S over here. But what if I get this as an output? What do you guys think? Will this fit our data points? Most of our data points, there is one data point which we are not able to fit, obviously, but the general data points that we have, the data points which are basically which are depicting the general trend in your data, if I go ahead and if I use this curve, do you think that it will fit the data points much better? Actually, this curve should look something like this. So now I'll just do one thing. What I'll do is that in order to make this data slightly more clear, I will add one more data point. This is a random person, right? XYZ. And this person's age is also 23, right? And they are also working, let's assume, right? So I have added one more data point with 23, and this person is also working, right? Just to support this example slightly more. So let's assume I have one more data point over here, right? Now you have 3 points which are saying that at 23 you are working, and you have 2 points which are saying that at 23 you are a student, right? Now if I go ahead and if I try fitting a curve of best fit, right? Maybe I get an output which looks like this, right? Right? And this, if you see, this is an S-shaped curve, right? Okay. Now at 23, we had 5 instances. We have 5 now. 3 people at 23 are working. 2 people at 23 are students, right? So what my model has done, so what this S-shaped curve has done is that using all the other rest of the data points. Now at 23, it has realized that the probability at 23 to be working is slightly higher as compared to be a student, and hence it has gone ahead and it has adjusted this line, right? But given whatever data we have, do you guys think that this is the best fitting output that we can get? Now, what are these values, right? Now, see, this equation or this curve that you're seeing, this is a curve which will always give you values in the range of 0 to 1, first of all, right? And now let's assume I pick up a point. Let's say I pick up, let's say I go ahead and I get some new data, right? I get a new student whose age, let's say, new student is uh, ABC, and the age of the student is let's say 27, right? What will happen as soon as I get a student whose age is 27? My model will go ahead and draw a vertical line from here to here. As soon as it draws a vertical line from here to here, it will go ahead and it will map this over here, right? Now, this S-shaped curve that you are seeing, right? This is a sigmoid function. We will be talking about this. And the output of this function is always a probability. So, if you look at this over here, when I let me just change the color. When I drew a vertical line from here to here at 27 and a horizontal line from here to here, I might get the probability as 0.99, right? Or maybe equal to 1 as well, right? So, what this curve does is that it gives me output. It will tell me that what is the probability of someone working or what is the probability of someone being a student, right? And this overall, this example that I've talked about, this is what we will be understanding in the next 30-40 slides. And this is what logistic regression is. What logistic regression does is that it basically it evolves the output of the linear regression model. In case of a linear regression model, we are getting a continuous output. In case of the logistic regression model, we are just changing the equation of a straight line to the equation of a S-shaped curve. This S-shaped curve is a curve which gives us probability of a class either being, let's say, true or false, either being, let's say, a student or a working professional, right? So from this S-shaped curve, I will get probabilities. So my logistic regression model will give me probabilities. If it says that the probability of you being a student is 99%, it means that you are lying somewhere over here on the top. If it says that the probability, if the probability of you being working is 99 or 1, then you are on the top. If the probability of you being, let's say, you working is coming out to be 0, right, then it means that you are a student. Now, guys, what will happen at 22? Now, at 22, this curve, if you draw a vertical line, this is cutting somewhere over here. This will cut somewhere over here, and this might give you a probability of around 0.4%, maybe, right? So, on the basis of the data, right, what what we are saying is that maybe 21 to 23 is a critical age wherein you will find a combination of people. At 22, you can have people who are pursuing their masters, and at 21, 22, you can have people who have pursued their bachelor's and who have started working as well, right? So, using only age as a variable, probably you cannot go ahead and you cannot just for the age of 21 to 23, the probabilities might be confusing. But what if I added another variable over here? What if I added the number of degrees that you have, or what is the current degree that you are pursuing? Now, let's say if someone is 22 and they are pursuing their masters, then the probability is more that they are student. Now, let's say someone is 22 and the maximum degree that they have is, let's say, a bachelor's degree, then maybe the probability of them being working will be higher, right? Do we have any threshold value? Prajwal will be talking about all of this. Generally, we have a threshold of 0.5, that is, anything above 0.5 becomes 1, anything below 0.5 becomes 0. But then we have things such as uh, um, um, we have ways to identify the best cutoff, right? I'll be talking about that later once when we move to the hands on. But we have methods which will help us in identifying the best cutoff value. Whether it can be binary, like yes or no, or whether it can be more than two values. So you can have as many values, right? You can have anything which is categorical. So you can have a target variable which has values yes or no, true or false. You can also have a categorical variable, let's say, which is predicting whether the player is a batsman, a bowler, a wicket keeper, all rounder, right? So you can have more than three, four classes as well. See, at 23, the model will predict that the probability of you being working is somewhere around 95%, right? Let's say if I look at 23, the model is giving you somewhere over here. This S-shaped curve vertically is cutting this somewhere over here. So this might say that the probability of you working is around 50%, right? Now, because 23 is a critical area, now this prediction can be incorrect as well, right? In our data, for Charan and Satyam, this prediction was incorrect, right? Because they are actually students, right? They are 23, but they are students. So, see, this is a critical point over here because this age range of 21 to 23 is critical because over here, obviously, some of the students might be moving on from their bachelor's and taking up jobs, right? Some people might decide to, let's say, study more, maybe pursue masters, move out of the country, right? Go and do MS from US, right? Canada, whatever, right? So this is a critical age. Now, if you want to actually make the model's prediction better in this range as well, you can start adding more features, right? Can you guys think of features which will help in clarifying the fact that whether if you are 21 to 23, what is the probability of you being a student or working? What do you guys think? What features can you think of? Additional features over here. The number of degrees I've talked about, right? What is the total number of degrees that the student has? Any other factors that will help you? So let's say you have your friends who are in this age range, right? 21 to 23, right? What factors about them will help you in identifying whether they are working or student? Let's say not friends, let's say friends of friends whom you have met for the first time. How will you try to identify whether they are working or not working? Highest education, that's the same thing, degree, right? That's a good feature, right? What field they are from, right? Let's say if they say medical, you know for sure that they should be students only, right? Because medical is 5 years of your MBBS, then your MS, then your MD, DM, so many things, right? Let's say they say that they are from a technical background, engineering background, right? Or let's say they say that they are from arts background or commerce background. Maybe this can help you in understanding, right? What is their field of education? Let's say they go ahead and they say law, right? As soon as they say law, you realize that maybe law generally will be 5 years, right? 5 to 6 years, maybe LLB will be 5 years, LLB plus LLM might be 6 years, 7 years, right? So maybe then you might realize that all the people who are either lawyers or in the medical field, they will, being at 23, 24, they might still be students, right? Maybe someone who is a student might be spending more time on phone. So for 33 guys, what will happen? My curve is extending till here, right? So what will it give you? It will give working, but this is an outlier, right? Now, see over here as well. Let's say if we had additional features, let's say if we had features that the background, right? Maybe Audrey is from a different background, or maybe let's say uh, if I captured marital status, maybe, right? Now, marital status, maybe there are people who got married at a very young age, and then they, let's say they went ahead and they spent 5 to 6 years in their marriage, and then they decided to come back at their career, right? And when they decided that maybe I'll go ahead and I'll pursue a higher degree, right? Anything. So if you are able to capture other factors which are helping you in quantifying, then the model will be able to predict. But over here, the model will still predict that at 33 you should be working, right? Now there can be cases, or see, the model will just try to find out the general pattern. The general pattern is that generally 18 to till 22, right? You will be a student. Generally after 22, you will be a working professional, right? Now the model, obviously, the predictions that you are getting will be the generalized trend in the population that you're seeing, right? Okay. See, we have given the model that 33 is a student, right? But all the rest of the data points are saying that anyone who is greater than 23 is a working professional. So the model will not make an exception, right? The objective of the model is to generalize the patterns, right? Not to see if my model would have gone ahead and would have, let's say over here, I would have gone ahead and I would have changed this curve from here to here. Do you think that that would have been correct? Let's say I would have gone from here to here. Do you think that this would have been correct? What will this lead to? I'm sure there will be many people who will be greater than 30. So, for those people, your model will start giving incorrect predictions, right? Now, what do you think? Let's say, I have 10 people who are greater than 30 in this batch. Maybe for 8 out of 10 they are working, maybe 7 out of 10 people they are working, right? So there is a 70% probability that anyone who is 33 years old should be working, right? So this will actually lead to overfitting, right? And you don't want to overfit. Overfitting is what? uh, Overfitting is capturing specific roles with respect to the training data. That is not what you want to do. You want to capture general patterns. You want to capture the general trend. Okay. It will not be a sigmoid. Yes, Vidya, that's one. That it will not be a sigmoid. But this was just to explain why 33 was not considered as a student, right? See, after 33, let's say if you have a age range of 33 to 35 wherein you are seeing many students, then the sigmoid curve will shift, right? But generally that will not happen, right? What will happen at 20, Indradev? At 20, the probability of you working will be close to zero. So if the probability of you working is zero, then the probability of being a student will be 1 minus 0, that is close to 1, right? Maybe 99%, 1, whatever. Okay, so now let's move on to the logistic regression part, right? Let's try to understand what happens in case of logistic regression, right? All of this we have covered. Now, logistic regression is a classification model, a statistical classification model, deals with categorical dependent variables. Your target variable can be binary or dichotomous, right? What do we mean by dichotomous? Dichotomous is again a similar word for binary. It means that your categorical variable can have uh, categories. It can be true, false. It can be yes, no. It can be rain, not rain, whatever, right? So that is what you mean by dichotomous or binary, right? Could be multinomial as well, right? So your target variable can be multinomial as well. That is, it's not that only logistic regression will work only for binary variables, right? It can also work for variables which have more than two classes, right? More than two classes, let's say you create a model which will predict the designation of an employee, right? Maybe the designation is a data scientist, maybe senior data scientist, maybe junior, maybe lead, maybe principal, right? So in this case, your target variable can assume, let's say, 4 or 5 different values. So your target variable can also be multinomial, right? Your input data can be both continuous or categorical, correct? So that's what, right? Now, see, if I would have gone and I would have collected more data, if I would have asked each and every 150 people of you, your age and your profession, your whether you are a student or a working professional, do you think that there would have been many instances of people who are greater than 30 and who are student? What will the general direction be? The general direction be is that people who are greater than 30, there will be a very high probability that they are working professionals, right? That is what the model will try to come up with. Okay. Now, what is logistic regression? It's a tool for applied statistics and discrete data analysis. All of these are just definitions. It gives outcomes in terms of probability. You have seen this. in turn helps in classifying the given data, right? When you start getting probabilities, right, you can go ahead and you can arrive at a cutoff, right? You can say that anything above zero point 0.5, let's say any probability above zero point 0.5 that I'm getting in the model, I will consider that person to be a working professional. Any probability which is, let's say, less than zero point 0.5, I will consider that person as a student, right? You also know that. Okay, so let me give you an example. I have two cases. One, for one, the probability of being a working professional is 99%. For the other, the probability of being a working professional is 55%. Right? Do you think that the model is the model is confident in both the cases? No, right? The model is confident is only in only one of the case, that is the where the probability is 99. Where the probability is 55, as soon as you see 55, you should also know that this is a critical age range, right? Because this might be somewhere in the 21 to 23 age group, right? So there, if you are getting a probability as 55, you can go ahead and you can say that this is still this prediction might not be correct, right? But anything, let's say above 90-95%, you can be very sure on those predictions, right? All right, so let's take a look at this example. So I have email. My email can be spam or it can be not spam, right? Let's try to understand how logistic. Now, this will be a very similar example that I've explained. So you should be able to understand this with ease. We will understand the variable, plot the data, draw the curve, and then we will find out the best fitting line, right? Let's get started. The independent variable that we are taking over here is the count of spam words, right? Now, in order to predict whether an email is spam or not spam, what do you guys think is the most important thing? The most important thing is that your email can be containing, let's say, thousands of words. But if in those thousands of words, let's say there are words such as lottery, right? Or let's say $1 million, right? Or let's say free gift, things like that. Do you guys think that these words are trigger words for something being spam or not spam? Correct? All right. So let's assume that I have 100 emails, and for all the 100 emails, through some tool, I'm able to count the total number of spam words that are there, right? Now, obviously, mails which are coming from your known contacts, they might not contain these words a lot, right? And the mails which might be coming from unknown contacts, they might be getting some words such as, let's say, gift, or let's say business trip, or let's say thousands of dollars, $1 million. You have one thing like that, right? Now, if we go ahead and if we just take a count of these words and make that as my independent variable, right? So if you see most common spam words, buy, get paid, guarantee, winner, unlimited, things like that, right? So what I can do is that I can plot the data. Now, this, if you see, is the data that we have, right? Now, the emails that you are seeing over here, which do not contain this disclaimer mark, right? These are the emails which are not spam. The emails which are marked over here, right? These are the emails which are spam. On this axis, you have the count of words, right? The count of spam words. So you can see that when the count of spam words is less than 4, then the email is not spam. When the count of spam words is greater than 4, I can see that the email is coming out to be spam, right? And if I go ahead, now see, this is our data, right? This is data that we have collected, right? Now, see, it might have happened that, let's say, a friend of yours has gone ahead and has sent you, let's say, some kind of an email which is a joke, right? Or some kind of a something, maybe anything, right? So, although the email contains 8 spam words, but it is not a spam, right? See, this is actual data, guys, right? See, your model. So, just like in our case, we had people who were 25, 28, and who were working. And we had one case wherein the age was 33 and they were not working. So you will not go ahead and you are not going to change that, right? That is your actual data. So in your actual data as well, you okay. So see, this is just a bunch of rules. If you are going ahead and you are identifying whether an email is a spam or not spam, it might happen that you have gone ahead and you have classified an email as spam because it contained, let's say, some words which were related to a spam email. But let's assume this was an email which came from your friend. Let's say this was an email which actually came from a bank, or let's say which came from a company wherein actually you would have won something. So in that case, obviously, in reality, it is not a spam, right? Let's assume that you applied for a contest and you actually won. Let's say you went ahead and you paid your bills through cred, and let's say you won a ticket for a match. You will get an email, right, that you have won this thing, and you were asked to, let's say, collect your things from here, or let's say you are asked to call on this number. Okay, so this is actual data that we are talking about. But in most of the cases, let's say 90% of the cases, these emails will be spam. 10% of the cases. Now, this is something that you guys would have also seen, right? Some of the emails that you are actually expecting to be in your inbox, sometimes they go to your spam folder. Why does that happen? Because the model is predicting it to be a spam. That might be a genuine email, right? But the model is predicting it on the basis of whatever content that email has. It is predicting that it is a it is a spam email. The probability of the words, because of the words, the probability of this email being spam is high. Okay, right? So this is actual data. Now, through this actual data, we will try to come up with a generalized curve, right? That's what the objective of machine learning is. There will obviously be outliers. There will always be outliers when you are working with actual data, right? Let's say when you are predicting whether a customer will buy a product or not, do you think that there will be a very linear uh, distribution of data, that let's say anyone who is greater than age of 30, they will buy a diaper, anyone who is less than 30 will buy it? No, right? Even you can be 18 years old, maybe you go to the store and you go ahead and buy a diaper for your sister, for your brother, right? Not for your sister brother, but maybe the child of your sister or brother. But you can also do that, right? So there will be outliers, but the majority data will suggest that if you are greater than 30 or greater than 25, 28, then you are buying a diaper, right? But it does not restrict you from going ahead and buying a diaper. Okay, so can we go ahead and can we plot this data just like we did in the last case? We can do that, right? I have a 0, I have a 1, which is my target variable. On my x-axis, I will have the count of words. If I go ahead and if I plot this, do you guys think that this output makes sense? This is what we have talked about or what we have discussed previously. If you see this, there are two cases which are outliers, right? This case is an outlier and this case is an outlier, but that doesn't matter. The general trend, what does that say? My general trend suggests that this is how your data is distributed. There can be some outliers, but that's totally fine. Right? Now, your real world behavior, right? Your actual real world behavior, when you're collecting real world data, things are not too much rule driven, right? Exactly. Because see, in the real world, you can have a 20-year-old person driving a BMW and you can have a 40-year-old person driving a Maruti 800, right? But the general trend will say that, let's say, someone who is greater than 40 might be driving a BMW, someone who is in the age of 18 to 20 might be driving a bike or let's say, a two-wheeler, or let's say a small car, right? But obviously, there will be outliers because nothing is perfect. Exactly. Okay, so let's proceed in this example. Now, once when we have gone ahead and once when we have plotted our data points, next was what? We actually went ahead and we identified an S-shaped curve, right? Now, just like in the case of linear regression, we were finding the line of best fit. In this case, see, in this case, we can have multiple lines, right? I could have had a line which was, let's say, which looked like this, right? I could have had an S-shaped curve which would have looked like this, right? I could have had an S-shaped curve which would have looked like this. I could have had an S-shaped curve which would have looked like this, right? Why did we go ahead with this particular curve? What is the objective of that? What do you guys think? best fit, less error, minimal error. But in this case, right, the error can we see if a class is, let's say, if the actual value is whether it is where the person is working or a student, and the predicted value is a probability, right? Then error per se, calculation of error. So in this case, right, we do not we find something which is known as the maximum likelihood estimate, right? So I'll talk about that once when we arrive at that point. But over here, the method will be different, but the objective is the same. The objective is to identify the best fitting S-shaped curve, right? Earlier, in case of linear regression, the objective was to find the best fitting line, right? Best fitting linear line. And over here, our objective is to find the best fitting curve, right? So we need to find a regression curve which would be best fit. That would be our logistic regression curve, right? But how do we find the best fit curve, right? Now, this is the mathematically how we try to find this out, right? That is what we are trying to do over here. So let me explain to you how we actually arrive at this best fitting curve, right? That is what next we'll be trying to understand. That is how do we arrive at this particular equation. Okay. Now, first thing that we need to understand over here is that something known as odds, right? Are you guys aware of what we mean by odds? We have something known as probability and we have something known as odds, right? Anyone knows the difference between these two? Okay, so let's say India versus New Zealand, right? Let's take the hot topic. Let's say India won games and New Zealand has won 4 games. These are made up numbers, right? But let's say India has won 6 against New Zealand and New Zealand has won 4. Can you guys calculate the probability of India winning a match? What will be the probability of India winning the match? Yeah, 10, right? 6 divided by 6 plus 4, right? I hope everyone is able to understand this. This will be equals to 6, right? So odds are something that says that what are the odds of something happening, right? When I say odds, so my odds of winning will be 6 favor, 4 will be against, right? So when I say odds, the odds of India winning will be 150%, right? So in case of odds, right, we are not dividing this by the total number of combinations, right? So if you see in probability, we are dividing the favorable events by the total number of events. But in case of odds, we are saying that 3 occasions, right, whenever India plays New Zealand, 6 times India has won, or 6 times India will win, and 4 times New Zealand will win. So the odds of India winning against New Zealand is 3 is to 2 or is 6 is to 4. Does that make sense? Right? This is just the basic definition of how odds are calculated, right? Now, this is the mathematical process of how we actually go ahead and how we find out the best fitting curve, right? So I'll just take you through the process. Uh, Obviously, once when we are building the model, all of these things you don't have to calculate, right? Just like in the case of the linear regression model, we had gone through the mathematics, we have gone ahead and we had understood all the concepts of how we get the best fitting line and all. But you would have seen that when we are building the model in Python, we are not actually going ahead and we are not doing all of these things manually, right? So just like that over here as well, in case of logistic regression as well, we are not going to go ahead and we are not going to do all these calculations. This is just for your information. If someone comes to you and asks you, you can then talk about these things, right? These things generally in interviews as well, interviews maybe someone can ask you these things, but generally in interviews as well, people usually ask you about questions about what you have done, right? Let's say how you have used a logistic regression model to, let's say, solve any client problem, right? I don't think that people nowadays are too much interested, but still it's good to know. So we will go ahead and we will understand this, right? Odds of something happening. What are the odds of something happening? What are the odds of India winning against New Zealand? So the odds are 3:2, right? The probability of India winning is 60%, but the odds of India winning is 3:2. That is three times India has won and two times, or three times India wins, two times New Zealand wins. So that is what the odds are telling us, right? So the odds of India winning against New Zealand is 3:2. That is, there is a higher chance of India winning by three as compared to New Zealand winning by two. Okay. All right. So, see, in case of logistic regression, the first thing that we do is that we calculate the odds and we calculate the log of odds, right? Now, don't ask me why we are doing this. See, at the end of the day, what we are doing is that in order to calculate the probability, all of these things we are doing because we want to go ahead and we want to calculate the probability using the sigmoid function, right? So that is why the first step that we do is that using this particular input, this data that we had collected, if you remember, this was the data, right? So we go ahead and we calculate the log of odds, right? For each and every event, right? So what are the log? What are the log of, first of all, what are the odds of an email being spam or not spam when the count of words is 5? What are the odds of an email being spam or not spam when the count of words is 10, right? If I go ahead and if I calculate this log of odds is a value which can fluctuate between minus infinity to plus infinity, right? Log, any log if you take, right, your log of any particular number, right, it can fluctuate between minus infinity to plus infinity, right? So that is why this log of odds is also something that will fluctuate between minus infinity to plus infinity. And this generally is a straight line, right? That is what we get as an output of this particular thing. But do you think that this is the output that we need? This is first of all a straight line, and this is giving me values in the range of minus infinity to plus infinity. So this obviously is not what we need, right? What we need is an S-shaped curve which gives us values in the range of 0 to 1, correct? So somehow I will go ahead and we will try to convert this line, this straight line, into an S-shaped curve, right? That is what the model tries to do. Now, the objective over here, if you see, is this input. This is something which is varying between minus infinity to plus infinity, right? I want to convert this from which looks something like this to an output which looks like this, right? If you see over here, I am getting my outputs in the range of 0 to 1, correct? And this is something that we do through the use of a sigmoid function, right? Now, a sigmoid is the function that we are basically using in our case in order to go ahead and in order to convert this equation of a straight line, the one that you're able to see over here, into an S-shaped curve. The sigmoid function takes any possible input, right? You can give any possible input to the sigmoid function in the range of minus infinity to plus infinity, right? The output of the sigmoid function will always be a number in the range of 0 to 1. Okay. Now, if I talk about the sigmoid function, for sigmoid function, the definition or the function is 1 plus e to the power minus x, right? This is the formula or this is the definition of the sigmoid function. Now, if I give you an example, right? You can calculate this as well. Right? You can give any value. So let's say I give a value which is a very large value, right? If you go ahead and calculate the output of this, right? If you look at this, the output of this, let's say if I give 100, right? Output is 1. The greater value I give, it comes out to be 1. Let's say I give minus 10. If you see this, the output is still in the range of 0 to 1. If I give, let's say, something like this, it becomes 0. Let's say I give 100, it will become 3.72 into 10 to the power minus something, right? So if you see the value, the output will always fluctuate between 0 to 1 for the sigmoid function. You can try it, right, for any given range of values, and it will always be in the range of 0 to 1. So what we do over here is that after calculating the log of odds, we apply the sigmoid function. Okay. All right. So that's what we will be doing over here. Let's move forward. All right. Now, see, this is your likelihood is nothing but odds, right? We will calculate the individual likelihood as basically the odds of an email being spam or not spam when the count of words is, let's say, 2, 3, 4, 5. Through that, we will calculate the log likelihood. So wherever you are seeing likelihood actually refers to odds, right? Through my data, I will calculate the individual likelihood, that is the individual odd of anything happening. So let's say, if I give you an example, let's say when my count of words were 5, right? When my count of words were 5, I had spam emails as 4, and I had not spam emails as 1, right? So what will be my log of odds? What will be my odds for spam is to non-spam? It will be 4 is to 1, right? 4 is to 1, correct? So we need to calculate this for all the possible values. That will be the individual likelihood. Through this, we will be calculating the log likelihood. So my output will be 4 over here. This will not give 4 is to 1. The output will be equal to 4, right? So we are going to go ahead and we are going to take the log of 4. Now, obviously, as and when if you see the log of odds of or the odds of something happening will increase, the log value will also increase. As and when the odds of something happening will decrease, right? The log of that value will also decrease, right? So that is what we do over here, right? Once when we have calculated the likelihood or the odds, we will go ahead and we will calculate the log likelihood. And then we will go ahead and this value, whatever this value is coming out to be, we are going to take it through the sigmoid function, and this will give me the S-shaped curve, right? That's what the objective is. In case of multi-classification models, right, there will be multiple equations that will come out as an input, right, as an output. So let's say if your target is, let's say, high, medium, low, right? Let's say first value is high, second is high, third is medium, then fourth is low, then this is medium, then this is low, right? So you are actually creating three separate models. First will be, let's say, target 1, right? Or let's say target high. Over here, all the values which are high will be 1, rest all will become 0, right? Second will be, let's say, target medium. Over here, all the values which are medium will become 1, rest all will become 0. Third will be target low, and everything which is not low will become 0, right? Now this, you will go ahead and you will fit 3 different logistic regression models, right? You are not going to do that. The model is going to do that internally. But through this, the model will give you 3 probabilities. So let's say it gives you the probability of high as 70%, the probability of medium as 20%, and the probability of low as 10%, right? So that's how you will do. So if you are able to understand binary, the same binary model will be applied many times whenever you are working with multi-class models. You don't need to do that. The model will automatically do that for you. So see, likelihood is nothing but odds. So if the odds of India winning is 6/4, which is 1.5, if I take a log of that, log of odds or log likelihood, right? Both of these things are same. So log likelihood will be nothing but log of 6/4. Okay. So let's say I have six spam words, right? For my data, which contains six spam words, can it happen that let's say 10 emails are spam and let's say two emails are not spam? So, can you calculate the probability of an email being spam or not spam in this case? What will that be? What is the probability of an email being spam when 10 are spam and 2 are not spam when your word count is 4? What is the probability that you will get? 10 by 12. What will be the odds that you will get? Odds in favor 10 by 2. So that's what we are calculating, right? Now, this we will calculate for each and every word count, right? So, spam words 1, what is the odds? Spam words 2, what are the odds? Spam words 3, what are the odds? And so on and so forth, right? And then you will calculate the log of the same values. This will give you an output which will look like a straight line. The output can be anywhere between minus infinity to plus infinity. This output, if I want to go ahead and if I want to convert this into a value which is in the range of 0 to 1, we will be applying the sigmoid function, right? Now over here they are explaining, we are explaining odds, right? So the same examples that I have taken. So this guy went fishing 5 times, caught a fish 2 times, failed to catch 3 times. What is the probability? So the probability of catching a fish is 2 by 5, right? But the odds are 2 by 3, right? This is the same example that I've explained. Obviously, for actual data, I will know all of these concepts I've talked about previously, right? Yeah. See, if you don't have historical data, how can you build a model on that? So for historical emails, obviously, you should be having all of these things. For your historical emails, you should be knowing what emails were spam, what emails were not spam, right? And then you should also have additional variables such as how many spam words were there, how many spam words were not there, right? Your data collection will obviously happen. And for your historical data, for your historical emails that are already there in your inbox, you can manually label them, right? That whether they are spam or not spam. So using that data only, we are actually going ahead and calculating all of these words, right? Now, if I go ahead and if I take the log of odds, right? So if I calculate the odds and if I take the log of that, right? So if you see log odds of catching on sunny day is this, log odds of catching on rainy day is this. And there is something known as log of odds ratio. That is, what we do is that we calculate the log of both the ratios, right? That is, odds in favor of catching a fish, odds in favor of catching a fish on a rainy day, right? So if I do this, this is something which is known as log of odds, right? Log of odds ratio. And this is what we are calculating in our data, right? In our data, if I go back to my example, if let's say my odds were 4 by 1, or let's take 6 by 4, odds for India winning, right, was 6 by 4, and odds for New Zealand was 4%, right? So my log of odds ratio, I have something known as log of odds ratio, will be log of 6 by 4, right? This whole thing divided by log of 4 by 10, right? That is the log of odds ratio. Odds and odds ratio, if you see the difference, odds is nothing but you calculate the log of odds. Odds ratio is that you calculate the ratio first of all of your odds, right? That is, odds can be two value, right? It can be in favor of, let's say, India winning, in favor of, let's say, New Zealand winning, and then you calculate the ratio of that and you calculate the log of that particular value. All right. And now, if you see, if I go ahead and if I calculate the log of odds, right? Odds over here is odds ratio only. These slides are slightly confusing. I've asked Intellipaat to correct this. But wherever you see odds, you know that this is odds ratio, right? So what we do is that we calculate the log of odds ratio for each and every. Now, See, if for my input data which look like this, if I calculate the log of odds, my output will look like this, which is minus infinity. My output will go in the range of minus infinity to plus infinity, right? Now, once when I get this, the second option is that I go ahead and I apply the sigmoid function. So we are getting the log 0.44. So how will we see the impact of the database? Database, there is no database. Whatever logs you are taking, right, it is actually transforming your data, which was in the range of 0 to 1. I believe that's what you're trying to ask, right? Your original data, which was class 0 or 1, these were categorical, these were hard classes, which were converted into labels, right? Now, these labels we are converting into a numerical value by taking the log of odds. Now, this value can be anywhere in the range of minus infinity to plus infinity. So, your 0.44, if let's say you are getting 0.44, that will be somewhere over here in this curve. So, basically, we are converting our classes, our hard classes, to log of odds, because till now our 0 and 1 were actually just representing whether an email is spam or not spam, right? And these were categorical, this was a categorical variable converted into labels. Now through that I am getting a numerical value which is giving me the log of odds, right? Now, this is just an explanation of why your log of odds can be minus infinity to plus infinity. People who are comfortable with maths, you can go ahead and see this. People who are not, don't worry. These are things that I've never ever know. Like, I have seen people asking these questions, right? If you understand, good. If you don't understand, that is also fine. These are not very important things, right? Now, see, log of anything divided by zero, right, will always be infinity plus infinity, because this will be a non-defined number, right? So whenever, in the cases when the probability of an email being spam is high, right, this will be 1 by 0, right, and your 1 by 0 will be tending to infinity, right? Similarly, probability of spam divided by not spam, over here they are just trying to explain, so this same concept will apply on your C. If you talk about odds ratio, right, odds ratio, let's say I take a case where you have 4 by 0 divided by 0 by 4, right? Let's say I have a case wherein you have all cases being spam, right, no cases being not spam, right? So in that case as well, your log can either be something which is divided by 0, it will be plus infinity, right? Or if it is the other way around, it will be minus infinity. So this is just for the example, this is just to explain. The log of odds ratio will remain the same that we have talked about, right? This is just explaining why our log can be plus infinity, or our log values can be in the range of minus infinity to plus infinity, right? So if you look at this over here as well, this will be 1 by 0, and all of this will be tending to plus infinity, right? Once again, don't put too much focus on these slides. This is all mathematical, purely mathematical, not very important. The other case, when let's say it is the probability of not spam is 0, so this will become log of 0 by 1, which will be log of 0 minus log of 1, which will become minus infinity, right? So this just tells us, this is just a mathematical proof that the log of odds ratio will be a value which will be in the range of minus infinity to plus infinity, right? So if we understand this, now this is the output that we are getting, right? When we go ahead and we take the log of odds ratio, this is the output that we will be getting, that is in the range of minus infinity to plus infinity. So for people who are finding this confusing, some words of encouragement from me, these things will never be asked to you, right? So if just go through this, try to understand, go through the recording once again. If you're able to understand, very good, right? If you're not able to understand, try to go through the recordings, try to understand whatever you can, right? But at the end of the day, generally the questions that are asked is that, what let's say, what is the output of a logistic regression model, right? It is a sigmoid function. It is an S-shaped curve, right? What do you mean by odds? What do you mean by log of odds? Things like that, right? So all of these are things which people will generally ask. If you're applying for a job of a data scientist, people are not interested in you understanding the mathematics behind any model. They are uh, they are interested in understanding whether or not you can apply a logistic regression in a real world scenario, right? They will be asking questions to you such as, can I go ahead and can I apply a logistic regression model to, let's say, a problem statement wherein I have to predict the spend of my customers or I have to predict churn within my customers, right? These are the kind of questions that you should be expecting. If you are applying for the role of a statistician, if you are applying for the role of a research analyst, in those cases, you can expect such questions. But I'm assuming the objective for most of you would be to apply for data science roles, correct? So all right. Now, this is what we get, right? When I take the log of odds, I get values in the range of minus infinity to plus infinity, right? And now, for each and every email, these are the log of odds which we can get, right? With these values only, we have plotted this equation of straight line, right? Now, if I apply the sigmoid function on this straight line, which was the log of odds value, right? If I apply the sigmoid function, I will start getting something which looks like this, right? My output will become an S-shaped curve. This is a standard, this is the property of the sigmoid function that any input, it can be any value minus infinity to plus infinity, it will convert that in the range of 0 to 1, right? And this is how we actually get the probability using the logistic regression model. All right. That's what I'm saying, right? This is just to explain why the log of odds will be in the range of minus infinity to plus infinity. So these slides are slightly confusing. So don't worry about this. This is just to explain that a log can take values in the range of minus infinity to plus infinity. This is not what we are taking in case of logistic regression, right? If we take the odds of mail being non-spam in the numerator, then a probability close to 1 will tell you that the mail is non-spam. A probability close to 0 will tell you that a mail is spam. All right. Now, what does the sigmoid function mean? All of this is same, right? Sigmoid function is the standard function that we use in the case of this model, logistic regression, right? The sigmoid function is this: e to the power x plus upon 1 plus e to the power minus x. If you will simplify this, it will become 1 upon 1 plus e to the power minus x, right? Something like that. Once again, no need to go into the mathematical details, right? If you look at this, it can either be, you can represent it as e to the power x plus upon 1 plus e to the power minus x, or if you divide this whole thing by e to the power x, it will become 1 upon 1 plus e to the power minus x, right? Now, a sigmoid function, the property is that it approaches 0 as and when your x approaches minus infinity, right? And it approaches 1 as and when your x approaches plus infinity, right? This is the property of a sigmoid function, because of which we are using it as a transformation in the logistic regression model. When we calculate the log of odds, after calculating the log of odds, we use the sigmoid function, right? So if you see in our example as well, uh, if we go ahead and if we apply the sigmoid function after calculating the log of odds, we will get an S-shaped curve which looks like this, right? It takes any real valued number and maps into a value between 0 to 1, helpful while solving classification problems, right? All of these things I have explained previously as well, right? Now, what will happen by on this particular output, we will apply the sigmoid function and it will give me this particular output, right? Uh, it will give me the equation of the S-shaped curve, correct? Now, the important part that we need to understand is this, right? So let me explain this part. This is important, and I want every one of you to be able to understand this, right? Now, just like in the case of line of best fit, we were calculating the sum of squared errors, right? Now, let's try to understand what will happen in this case. In our case, how will we try to find out the best fitting S-shaped curve, right? So let's try to understand this concept. Now, if you remember, we had data points. Let's say we had, right, I'll plot some data points over here. And let's say I plot some data points over here, right? And I have, let's say, some outliers over here and here, right? Now, obviously, from these data points, I can pass many S-shaped curves. Is that correct? There can be many different S-shaped curves that can pass through these particular data points, right? So let's say this is one, right? Let's say this is one, right? Let's say this is one, and let's assume this is one, correct? Let's take three examples. Is everyone able to understand this, that there can be multiple different outputs, right? Just let me scroll down and I'll see which example they are taking. Right now, let's try to see. Now, see visually, can you tell me which is the best fitting S-shaped curve out of these three? Is it the red one, the blue one, or the green one? Visually, it is green, right? It is green, right? Because green, if you see, is passing through the majority of the data points correctly. The red one is not passing through these four and these two, six. The blue one is not passing through these so many data points, right? So the green one is the best fitting one. But over here, can we apply any concepts such as calculating the vertical distances from the line? And because this is not a regression problem, right? This is a categorical problem. Now, see, in this case, what if I do a simple thing, right? I want that S-shaped curve which maximizes the probability of each and every data point, right? So let's say when I say the probability of point one, right? I'll explain this. Just hold on. Let's say I take all of these points till the nth point, right? That sigmoid curve. Now, see, look at this look at this green curve that we are talking about, right? All the data points that you're seeing over here on top, what will the probability be for these data points? In what range will the probability be for these data points? The red ones, close to 1, maybe 0.99, right? So let's say there are how many? 1, 2, 3, 4, 5, 6, 7 data points. So for these 7 data points, let's say the probability is 0.99, right? I'll not take one, let's say it is 0.99. And for the bottom data points, that is these are 7 top data points, these are 7 bottom data points. What is the probability for them being spam? So this is spam, right? And this is not spam. That will be close to 0, right? 0.001 maybe. So if the probability of spam is 0.001, what will be the probability of not spam? 0.99, correct? Now, if I multiply all of these data points, right? Now, see, for these two data points, the probability will be incorrect, right? So let's write those as well. Two data points, the ones that you are seeing over here, the probability will be close to 0. Is that correct? For these two, the probability will be close to 0, right? Because my model is saying that these two data points actually should not be spam, correct? And for these two data points, the probability will be close to 0.99 for these two, the bottom two. The probability of spam will be 0.99. So the probability of not spam will once again be 0.01. All right. Now, If I go ahead and if I multiply all of these probabilities together, right? Let's assume I go ahead and I multiply all of these probabilities and I get some value, right? Multiplication of probability. Let's say I get this value as, I will obviously be getting a value in the range of 0.99 something. Let's say I cannot have a value which is greater than 1. Let's say I get a probability of zero point 0.9, or let's say I say probability red, right? I get this as 0.99. If I multiply all of these probabilities with each other, let's say I get a value of in the range of 0.99. Now, if I calculate the same probability for red, what do you guys think? Will this probability be greater than 0.99, less than, or equal to? Calculate the mispredictions, calculate the total number of correct and incorrect. Now, if you see for the red line, there are 5 data points at the bottom which will have probability of 0.99, and it will have 7 on top which will have 0.99. So 12 will be 0.99, but there will be 6 data points for whom the probability will be 0.01. So 0.99 to the power of 12 in this case. In the first case, it was 0.99 to the power of 14. Correct? If I calculate the same probability for the blue one, what will that be? So let's say for this probability of red, I get 0.98, right? If I calculate the same thing for probability of blue, can you guys tell me how many probabilities for blue will be in the range of 0.99? Can you give me a count? So 6, 7, 8, 9, right? Very good. So I will have 0.99 to the power of 9 and then 0.01 to the power of 7, 8, whatever, right? Is everyone able to understand this? So let's say I get probability of blue as 0.96, right? Which line is the best fitting line for me? The green one, right? Because it is actually, see, the green line is the line which is accurately predicting most of the probabilities. So obviously if I multiply all of these probability values, whatever value I'm getting will be the largest possible value, right? And this is what is known as maximum likelihood estimate, right? Maximum likelihood estimate. So just like in the case of linear regression, we used to calculate what? In the case of linear regression, we used to calculate sum of squared of residuals, right? In order to find the line of best fit. In this case, in the case of logistic regression, we are finding the maximum likelihood estimate. The maximum likelihood estimate is that S-shaped curve which is giving you the maximum probability if you multiply all of these points together. Okay. So it can be any value, but what I'm saying is that for green, this value will be high, right? Because it is 0.99 to the power 14 into 0.01 to the power 4 for green. For red, it is 0.99 to the power 12 into 0.01 to the power 6, right? So it can be any value, but what I'm saying is that for the green one, the value will be the highest. So the probability for them being not spam is 0.99. So for the points which are spam, we are calculating the probability of spam. For the points which are not spam, we are calculating the probability of them not being spam. And because we have our actual data, we are able to know which are spam and which are not spam, right? In order to find the best fitting S-shaped curve, right? Because see, there can be n number of S-shaped curves that are passing through here. How do you know that the green one is the best one? Just like in the case of linear regression model, we were finding the line of best fit, right? There can be n number of data points. There can be n number of lines that are passing through a set of data points. So 12 are the number of points which are having the correct, which are assigned the correct probability, right? But if you see for the green ones, all of these 7 data points on top, they are just next to the green line. For the red one, if you look at the bottom, these 2 data points are not there close to the red line. So for them, the probabilities will be incorrect. These points will be classified as spam. Okay. See, outliers in the target variable you will always keep, right? Because that is the target that you want to predict. Generally, you will keep them. But if there are many, let's say if there are only outliers or let's say less than 1%, then it doesn't matter. But it also depends from model to model. There are certain models which are able to deal with outliers appropriately, like logistic regression will not be influenced by outliers by a very high margin, but linear regression will be, right? So now if you look at this, right, the probability that we calculate, right, if we go ahead and if we calculate these probabilities for each and every data point, right, so this, if you see, we are just calculating the sigmoid function. Okay.
Question 4. Which of these products use machine learning? Option 1 Google Maps, option 2 Netflix, option 3 TikTok, or option 4 all of the above. What do you think is the right answer? Comment it down below. Just a quick info, guys. Intellipaat offers an executive postgraduate certification in data science and AI, where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps, and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
All right, then we had started with the logistic regression model. We have gone through the theoretical aspect of what logistic regression is, right? How does the model arrive at the equation of best fitting S-shaped curve, right? We calculate the log of odds. Through the log of odds, we then apply the sigmoid function. The sigmoid function gives us an S-shaped curve. Now, this S-shaped curve is a curve which actually gives us probabilities as the output, right? My input range, the output of my sigmoid function will be anywhere in the range of 0 to 1, right, which will be the predicted probability that we usually get. The input to the sigmoid function can be anywhere between minus infinity to plus infinity, and using the sigmoid function we try to arrive at probabilities, right? And we had covered till this particular part. Now, how do we identify the best fitting S-shaped curve, right? So I was explaining on this particular aspect, just like in case of uh, linear regression, we had the sum of squared errors, right? In order to find the line of best fit, what did we do? We actually calculated the vertical sum of squared distances for each and every point from the line, and we were looking for a line which will minimize this particular distance, right? If you remember, we were trying to minimize the vertical sum of squared distances that we were calculating, right? In case of logistic regression model, we work with something which is known as MLE, right? MLE stands for maximum likelihood estimate, right? What does this mean? So I was giving an example. All right. So let's look at this. Let's assume this is my X and Y axis, right? Now, within my X and Y axis, you will have some, let's say your X axis is the age, the same example that I had taken yesterday, and your Y axis is the interest, that is whether you are working or you are right, right? So now this variable, this could have two values. If I label in code my classes, I can have the working encoded as value 1, right? Or I can have, let's say, student encoded as value 0. I'm keeping it slightly above so that it is easy to see, right? Now, let's say for people who are less than a given age range, I was getting that in most of the cases, these students people who are less than a given age, right, are students. And for other cases, let's say we were seeing that beyond a given age, right, generally you will be working, right, something like this. Then there could be outliers as well. Maybe let's assume that there is a 19-year-old person who is working. Maybe they have their own startup, right? I can have, let's say, a 30-year-old person who is a student. Maybe these are people who have pursued their jobs for 10, 12 years and now they have opted to go for their master's or PhD or whatever, right? But if you look at the general trend of this data, what does the general trend look like? If you look at the general trend, I can see that beyond a given age, right, you will the probability of you working will be higher, and below a given age, the probability of you being a student will be higher, right? Is everyone able to understand till this part? Now, if you remember, we knew that the sigmoid function is a function which gives us an S-shaped curve, right? All right. So the sigmoid function is a function which gives us an S-shaped curve as an output, right? Now let's say I go ahead and I get an S-shaped curve which looks like this, right? Or let's say I get a different S-shaped curve which looks like this, right? Or the one that I'm marking in green is apparently the correct curve. Let's say I get an S-shaped curve which looks like this, right? Now, my logistic regression model, right? Which curve out of these three it should select? How will we find that? Just like in the case of linear regression, we were talking about how do we select the line of best fit. Over here, my question has changed now that how will you identify which line is the best fitting line? What do you guys think? The green one will be the best one. That is obvious from here. Now, why do we think that the green is the best one? So green one covers the maximum points. That is correct. How can we identify that the green one is covering the maximum number of points? If I multiply the probabilities of all of these points, right, the probabilities that I have gotten from the model, if my line is covering maximum number of points, then the probability of the predicted probability that I'm getting from all of these points should be high, right? Now, let's do a very simple exercise. So let's say this is the green model, right? Let's say this is the red model, right? And let's say I have a blue, which is this one, right? Let's say these are three lines. Now, can you go ahead and can you tell me how many classes will be predicted accurately by the green line? You will have to count. For the green one, how many are predicted accurately? At the bottom, we have 9, and on the top, we have once again 9, right? So we have 18 correct predictions for green. And how many predictions for green will be incorrect? Incorrect for green will be 1. Is it 1? No, right? It will be a. For green, you have 1, 2, 3, 4, 5, 6. 6 will be incorrect, right? What about red? The red one looks to be doing better, right? If you see the red one, it is giving us 19 correct predictions and only 5 predictions which are incorrect, right? And what about the blue one? Blue one will be correct and 10 incorrect, right? Now, which line do you think will be the best performing line? Is it the green or the red? Red, right? Why is red? Why will red be the best performing line? If I go ahead and if I multiply all the correct probabilities, right? Now the correct probabilities, the 18 ones that we are seeing, the ones that are there on the top will be close to will be close to 1. So let's say I take 0.99. So I will have 0.99 to the power of 18, correct? This will be multiplied by, let's say, I say the incorrect probabilities are coming out to be 0.01, right? So this will be multiplied by what? Multiplied by 6, right? This is for the green one. Similarly, for the red line, what I will have is that I will have this to the power 19 and this to the power 5. And for the blue line, we will have this to the power 14 and this to the power 10. Which value which value do you think will be the maximum out of these three? The red one, right? Right. So this is what we mean by a maximum likelihood estimate. We are trying to identify a line which is giving me the maximum probability. When I multiply all possible probabilities that are coming out, it gives me the maximum probability, right? That is an example. I'm just assuming that for an incorrect probability, if you look at these points, right? If you look at these points, my model is predicting a probability of somewhere around, or let's take this point. For this point, my predicted probability should have been 0.99, but my predicted probability will be somewhere down below, right? So down below, I'm assuming that it will be close to 0. Okay. Now, the same concept has been explained in the examples on this slide, right? So we had done till here. If we go ahead and if we start getting the predicted probabilities now, right? Now, if you remember, this was the log of odds. This log of odds, if I take this to the sigmoid function, I will get a predicted probability, right? If I get this for all the possible values, right? If I go ahead and I get this value for all the possible emails that I have in my training data, right? I will get the probabilities for each and every point. If you see, for this point, second point, I am getting the probability as 0.99. For the third point, I am getting the probability as 0.01 after passing through the value, whatever value we got through the log of odds. If we pass that through the sigmoid function, these are the probabilities that we are having. If I go ahead and I generate the probability for all the data points using this transformation, using this particular log of odds, right? I will be getting these as the probability values, right? Probability of a mail being spam, the first point, it is around 0.01. Second point, once again, same. Third point, 0.03. Fourth, 0.05. For the fifth point onwards, it is coming out to be 979999, right? Okay. Now, how will I find the maximum likelihood value over here? I will have to multiply these probability values, right? Now, if you compare this with actual data, these are the emails which were spam. Is that correct? In the real data as well, these were the emails which were spam and these were the emails which were non-spam. So the probability of these mails being spam is coming out to be high, which is good. How will I be able to calculate the probabilities of these emails not being spam? How can I get that? If the probability of being spam is 0.01, then what will be the probability of these mails not being spam? Probability of not spam. If my probability of spam is 0.01, then what is the probability of not spam? 0.99, right? So 1 minus 0.01, so that will be 0.99. So now, since these points in reality are not spam, right? I am marking them by green. Since these points in reality are spam, so what I need to do is that I need to multiply these 4 by 0.99, which was the probability of being spam. I need to multiply these 4 with the probability of them not being spam. Not being spam, I will do a 1 minus of 0.01. Is everyone able to understand this concept? The same thing that I've explained in the diagram. So that's what we'll do, right? We'll go ahead and we will multiply all of these. Now, if you see, For the first four probabilities, we are taking 1 minus 0.01. For the last four, they will be as it is. Because the first four emails, in reality, they were not spam. When they were not spam, then the probability of them not being spam will be 1 minus 0.01. For the last four, these emails were spam. Since these emails were spam, the probability remains as it is. Now, this, if I multiply, I will get a value, right? If I multiply this, now generally what we do over here is that we take the log of this as well, right? In order to calculate the log likelihood. So I am taking the log of this, and when I take the log of this entire thing, I get a value which is minus 0.084, right? This is the log likelihood that I'm getting for this particular equation, that for this particular sigmoid curve, right? Instead of just multiplying the probabilities, we have multiplied the probabilities and calculated the log of the same, right? Not a very big difference. All right. So now, see, I drew this line as 1. What if I go ahead and I rotate this line slightly, right? If I will rotate this line slightly, my sigmoid curve will also change. What do you guys think? If I rotate this line like this as well, my sigmoid curve will change, right? So if I rotate this curve multiple times and I calculate this same value, this log likelihood that you are seeing over here, right? This log likelihood, what do you think this value will be the maximum for which curve? The curve which is covering the maximum number of points, right? This value will be maximum for only that curve which is going through the maximum number of points in my data. If the point is going through the maximum number of points, then it means that we are able to cover the majority proportion. Hence, that is the best fitting S-shaped curve that we have, right? So what we do is that we go ahead and we rotate this line further. Now see, all of these things you don't have to do. I'm just explaining the concept of internally how the logistic regression model tries to come up with the best fitting S-shaped curve, right? If I rotate this line further, let's say like this, my probabilities will change because my sigmoid curve will change. Now, maybe you get these values, right? If you go ahead and calculate the log of this, you are seeing that the value has gone down even further, minus 0.207. Line A, my log likelihood was minus 0.084. Line B, my log likelihood was minus 0.207. Which line has the maximum value of the log likelihood out of these two, out of A and B? A is minus 0.084, B is minus 0.07. So obviously it will be A, right? These are negative values. So line A has a better likelihood value than line B. Hence, you will go ahead and you will choose the line A as the best possible. Now, the model, what it tries to do is that it rotates and tries to come up with multiple sigmoid curves and sees the one which is giving you the maximum likelihood value, right? But that is the overall process. You will keep on rotating the line until we get the maximum log likelihood value, right? Whichever line is giving you the maximum log likelihood, that particular line will become the logistic regression model's output. All right. And this is what we do while when we are when we are trying to find out the best fitting S-shaped curve using MLE. MLE is nothing but maximum likelihood estimate, wherein we are calculating the log likelihood. If you want to know whether it is maximum or not, you can manually plot the data points and you can go ahead and rotate the line manually, and you should be able to see which is the best possible S-shaped curve. This is not an easy task to do. So obviously there is no way for you to find it out until and unless you mathematically try to prove this. All right, guys. So this is it with respect to the theory of logistic regression. All right. So this is logistic regression. Summary, we have taken a look back at the linear regression model, looked at the kind of problems that linear regression would not be able to solve. That's where we laid the foundation of logistic regression. And after doing that, we go ahead and we have understand what logistic regression model is. Why do we need to use the logistic regression model? How does the model work? And through that, we have been able to understand how this particular model works, right? So we start by plotting the data, we draw a regression line, pass it through the sigmoid function, which will give us an S-shaped curve. We keep on rotating the line. While rotating the line, we are trying to identify that S-shaped curve, which is giving me the maximum likelihood, right? And we use MLE to find out the best fitted regression, not line, it will be the curve. And this is what the process is, right? We start with the log of odds, then we use the sigmoid function, and then we use MLE in order to estimate the equation of the line of best fit, right? Or S-shaped curve of best fit over here. What kind of target variables will logistic regression model be able to deal with? Anything which is categorical in nature. The use cases are anything that is categorical, right? Any process that you can capture in a categorical variable, right? India versus New Zealand, right? Whether India will win or not. How can you predict that? If you have historical data about the historical matches, about all the players and all, your logistic regression model can help you in predicting what are the probabilities of India winning or not, right? If you follow cricket, if you follow any sport, if you go on to Google and if you check the score, there will always be a live prediction, right? Wherein they will give you a predicted probability of which team has a higher chance of winning. What is that? That is the outcome of a logistic regression model or any other classification model, right? Win predictor. So if you see win predictor, the probabilities that we get, the sum becomes one, right? If the chances of India winning are 63, New Zealand winning will be 37. So these are probabilities. These are predictions that are coming out by looking at the current scores and comparing that with historical data. We get probabilities. Probabilities will always be in the range of 0 to 1. So that will not be linear regression. I'm not talking about score prediction. I'm talking about chances of winning, right? Chances of a team winning. Prediction of score, that will be linear regression. So if you're predicting the score that India will make, New Zealand will make, that will be a linear regression model. So these emails at the bottom, if you see the actual label is what? Actual label is 0. 0 is what? Okay, so let's stop here then for the theoretical part. There are some couple of more concepts that I want to explain to you guys, which are not there in the deck. So I'll move to that now. Right. Now, you guys remember for our linear regression model, what were the evaluation metrics that we had? Evaluation metric for the regression models. We had many, right? Mean squared error, R square, MSE, that is the same, root mean square error, that is RMSE, MAPE, mean absolute percentage error, absolute error. Now, my question to you is, do you think that the same evaluation metrics will be applicable when we are working on a classification problem? So, ideally, no, right? That will not work. Now, why it will not work? Let me explain that to you. Okay, so let's say I had a target variable of rain, right? Or let's say I take some other target variable that is, let's say whether the customer will churn or not, right? So let's say I have my customers, right? My customers are over here. Let's say I have customer IDs. Right? I'll have 10, right? So 10 are fine. Okay, so let's say these are the customer IDs that we had, and the actual data that we had is this customer churned, this customer did not churn, this customer did not churn, this churned, this one did not, this one did not, this one did not, this did, and this one did not, right? This is my actual data. Okay. Now let's assume that I build a logistic regression model, and from this, I get a predicted churn. After building the model, I will be able to get a predicted churn. Correct? Now, how many types of predictions can I get from the model? I can get a I can get correct predictions, right? Correct predictions will be what? Correct will be, let's say, actually my customer churned and my model also predicted the same. Or let's say, actually my customer did not churn and my model also predicted the same thing, right? So these will be the correct predictions. Okay. I can also have incorrect predictions, such as my customer churned, but my model said that no, they are not going to churn. Or my customer did not churn, my sorry, in this case, my customer did not churn, but my model said otherwise. Or I can have the vice versa case as well. That is, the customer churned, but my model said that no, your customer did not churn. What do you guys think? Do you think that these are the four kinds of predictions that we can get from a classification model? Does this make sense? The first two are correct predictions. If you look at this, whatever my model is predicting is actually correct. And the second two are incorrect predictions. All right. So let's do one thing, right? I will go ahead and I will generate this entire data randomly. So let's say this value, this is correct, this is correct, this is incorrect, this is correct, this is correct, and this is also correct, right? Let's say these were the actual and the predicted values, right? Now, can you calculate the accuracy of this model? How can we calculate the accuracy of this model? Any idea? We cannot do actual minus predicted over here, right? That is not correct because these are classes. What I can do is that I can, let's say I create a flag variable, that is whether the predictions are correct or not, right? Okay. So let's say this one, actual and predicted both are correct. This is correct prediction. This is correct prediction. This is not correct, right? This is also not correct, right? This is correct. This is correct. This is not correct. This is correct. This is correct. And this is correct. Does this make sense? I have just listed down the predictions which were correct and the predictions which were not correct. If I go ahead and if I take a sum of this should be this is not a binary variable. So let me do 1, 0. This 1 is for correct predictions, 0 is for incorrect, right? This is 1, this is 1, this is 0, 1, 1, 1, right? Now, if I take a sum of this will give me how many predictions were correct for me, right? And what were my total number of predictions? My total predictions were 10, right? Now, can you give me the performance of this model? How can I calculate the performance? Accuracy will be what? It will be this divided by this, right? Which will be 70%. Okay. Is this clear to everyone? Now, this is the accuracy, right? But if you look at the incorrect predictions, right? If you look at the incorrect predictions, there are two kind of predictions that we have in incorrect as well. Even in the correct predictions, there are two kind of predictions we have. This over here is known as a true positive, right? TP. What is TP? TP is that your actual value was also positive and the predicted value was also positive. This is a true positive prediction from my model, right? If I look at this one, that is 0 and 0, these are true negatives. That is, my actual value was also a 0 and my predicted value was also a 0. Both of them were 0. Both of these are true predictions, but between the correct predictions as well, I also have two types. One are the positive predictions, that is, people who are churning out, right? The model is able to predict them correctly. People who are not churning, the model is also able to predict them correctly. So the true positives and the true negatives, these are the two kind of correct predictions that your model will be able to give. Is that correct? Now let's come to the incorrect predictions, right? If I come to the incorrect predictions, So let's focus on these two. This is true positive, right? Because my actual is also 1 and my predicted is also 1. These ones, 0 and 0, are your true negatives. Why? Because your actual is also 0 and the predicted is also 0. This one over here is what? This one is a false positive. Why? Because this model over here for this row, the model is incorrectly predicting that this customer is going to churn, whereas in reality the customer did not churn. Similarly, this last one is a false negative, right? My model is predicting that this customer is not going to churn, whereas this customer has gone ahead and this customer has churned. Now, can you go ahead and can you tell me the labels for the rest of the classes? What will this be? This will be TP. Next one, TN. This one, FP. This one, this will be TN. This will be TP. And this will also be TN, correct? All right. Now, what if I go ahead and I now do something which is, so if you look at this, right? If I take the model predictions over here and if I take the actual values over here, right? I can have my true positives over here. That is, my model was predicting correct and actuality as well. My outputs were correct. I can have my true negatives over here, right? I can have my false positives over here and I can have my false negatives over here, right? I'll explain what this is. This is something which is known as a confusion matrix, right? Now, what is a confusion matrix? I'm just trying to explain that to you. So if I go ahead and if I populate all of these things like this, right? I have my model results on the row. I have my actual results on the columns. And I just populate. If I go ahead and if I populate these numbers, right? Let me do that over here and see what happens. Now, can you give me a count of true positives that are there in this data? How many true positive predictions are there in these 10 values? 3. So true positives are 3. What are the true negative values? How many TNs? 4. How many false positives? 2. How many false negatives? 1. Right? Now, this is something which is known as the confusion matrix. You have the model predictions here, you have the actual values over here. And let's try. This is how we, first of all, calculate, or this is how we create the confusion matrix. Right? Now, I will tell you what the use of this confusion matrix is. Right? Now, from this confusion matrix, we can calculate many different metrics which will be used for any classification model. Right? First, we'll start with accuracy. Can you give me the accuracy from this confusion matrix? What are the total number of correct predictions that we have? 7. What is 7? If you look at 7, 7 is nothing but TP plus TN, right? Your correct number of predictions are what? Nothing but TP plus TN. If I divide this by the total predictions, right? Total predictions are what? TP plus FP plus TN plus FN, correct? So your accuracy of the model will be this. Make sense? Right? Now, there is something known as precision. Right? Now, precision, the formula is TP divided by TP plus SP. Let's try to understand what this means. First of all, can you give me what the precision of this model will be using the count of values that we have? What will be the precision of this model? What is TP? TP is 3. And what is FP? FP is 2. TP plus FP will be 5. So your precision will come out to be what? Your precision will be 60%. Right? Now, what does this mean? If I only limit my model's predictions to the positive predictions, right? If I only go ahead and I limit the predictions to the positive ones. If I just limit my model's predictions to the positive predictions, that is, the ones which have where my model is predicting a 1, right? Well, this, let's say this, right? This, and this, right? My model in total is giving me 5 positive predictions. Is that correct? Out of these 5, how many predictions are correct? 3, right? Only 3. So what my precision is saying, if you look at precision, my precision is saying that out of the total number of positive predictions that my model is giving, how many are actually correct? Does that make sense? Right now, I am only focusing on the positive predictions. I am calculating the precision for only the positive predictions. If my model is saying that 5 customers are going to churn, out of those 5, how many are really churning out? That is what my precision is telling me about. Correct? Now, I have also one more metric which is known as recall, right? Now, recall is TP divided by TT plus Fn. Can you calculate the recall for this model, first of all, before we move forward? Recall for this model will be what? 3 by 4? 75%. Now, what does recall mean? Now, recall over here is telling me that out of the total positive predictions that were there in the actual data, let's try to mark this, right? What are my TP plus Fn in my data? My TP plus Fn are nothing but, if you look at this data, right, all of the predictions that were positive or that were 1 in the real data. In the actual data, how many predictions were positive? If you look at this, in the actual data, there are only 4 predictions which were positive, right? Out of these 4, how many my model is correctly able to identify? If you look at the first one, the model is able to correctly identify. If you look at the third one, the model is correctly able to identify. If you look at the last one, the model is correctly able to identify. So my recall becomes 75%, right? Now see, a very simple, let me explain this through an example, right? Let's say you have 100 patients, or let's say you have patients 1,000. Out of these 1,000, you have uh, 10 patients who have cancer, right? And you have no cancer. You have 990 patients who don't have cancer, right? Okay. Let's assume my model, I create a model which goes ahead and says that all the patients, all the 1,000 patients do not have cancer. What will be the accuracy of this model? My model is saying that all 1,000 patients, they do not have cancer. What does this mean? Can you give me the accuracy of this model? So if my model is saying that all 1,000 people have cancer, these 990, for these 990 patients, the prediction will be correct, right? Because they don't have cancer. But for these 10 patients, the prediction will be incorrect. But if you calculate the accuracy will be what? It will be 990 divided by 1,000, right? Because 990 predictions are still correct. So the accuracy will come out to be what? 99%, right? But do you think that this is a good model? So you might have killed these 10 people for whom you are not able to predict that they have cancer. Maybe they went ahead, they did some tests, and through the tests, you were able to say that, okay, you don't have cancer. But in reality, these patients actually had cancer. So do you think that this model with an accuracy of 99% is going to help you? No. So the first point that I was making, that I have made over here, is that accuracy will not always be the key performing indicator for you, correct? Because depending upon the uh, seriousness of the predictions, right? It might happen that only 1% people have cancer. It might happen that only 1% people have COVID. Your model can go ahead and say that all 100% don't have COVID. Still, your accuracy will remain 99%. But that does not solve your problem, correct? So this explains the fact why accuracy is not the best performing evaluation metric for classification models. Is everyone able to understand this? Okay. Now let's come to the second aspect, right? Now, if not accuracy, then what, right? So let's try to understand this through another use case. Let's say in this data only, right? Let's assume I give an example from a similar domain. Let's say I have 1,000 customers. Out of these 1,000, let's assume that the customers who have churned are 50. Yeah, right? The model that you create, right? It predicts model churn says that 100 customers are going to churn, right? Your model says that 100 customers are going to churn, but in the 100 customers that your model is saying that are going to churn, only 30 customers who have actually churned are there, right? Only 30 from the actual base are there, right? Does this make sense? See, your model can go ahead and can say that 100 customers have churned. Or 100 customers will churn, right? Or let me take another example, right? Let's say my model is saying that 20 customers are churning, and through this, it is able to capture 15 customers who had actually churned. Does this make sense? Or let me make this simple. Let's say all the 20 customers who are churning, your model is able to identify those 20 correctly, right? I'll make this simple. In reality, there were 50 customers who were churning, but your model is only able to identify 20, right? Now, can you go ahead and can you calculate the precision of this model? What will the precision be of this model? My model is saying that only 20 customers will churn, and those 20 are actual customers who have churned in the data, right? These 20 in reality have churned. So my precision will be what? The true positives, that is 20, divided by true positives, which is 20, plus false positives. Are there any false positives? My model is not making any incorrect prediction. For all the 20 customers to whom it is for whom it is saying that they will churn, they are actually churning. So this will be 0, right? So your precision will come out to be 100%, right? But do you think that this is a good model? Your model has not been able to identify 30 customers yet. If you calculate the recall of this model, the recall of this model will become 20 divided by 20 plus 30, because there will be 30 false negatives that will be there in the model, right? And your recall will come out to be 40%. So even though you can have a precision of 100%, your recall is coming out to be a lesser value, right? Now, if you go back to the definition of precision and recall, your precision looks at out of the total positive predictions that you are getting from the model, how many are correct. It doesn't matter how many are there in the actual data. In actuality, there might be 100 patients who have cancer. But if your model is predicting 20 have cancer and all the 20 in reality do, the precision will become 100%. But the recall will become 20 by 100, which is only 20%. The recall will focus on what? On out of the total people who have cancer, how many your model was able to predict correctly. Does this make sense? So I'll explain precision and recall once more. Accuracy should be clear to everyone, right? Precision and recall, I am explaining once more, right? What is precision? If you look at this precision over here, precision only focuses on the positive predictions that your model is giving, right? Let's assume that 100 patients had cancer, but your model says that only 50 have cancer, right? And your model is able to correctly identify 50 customers or 50 patients from the set of 100 patients who had cancer. Now your precision for this model will become 100%. Why? Because the model was saying that 50 people will have cancer, and these 50 people in reality have cancer, right? They actually went ahead and they had cancer. But do you think a precision of 100% will do justice to your model in this case when you have 50 other people who are not being identified correctly? No, right? So, in order to capture the entire data, we have something known as recall. What recall says is that out of the total number of people who have cancer, how many your model is able to identify correctly, right? So your recall will be 50, which is the number of people your model is able to identify correctly having cancer, divided by the total number of people who have cancer, which is 100. So the recall will become 50%. Even though you have a precision of 100%, as soon as your recall becomes 50%, you will realize that your model is not doing a very good job. All right. Accuracy identifies overall correct predictions. Your precision and recall will focus, your precision will focus on the percentage of predictions that are correct, right? The percentage of positive predictions that you're getting from the model, how many are correct out of those. Your recall will focus on out of the actual number of positive values, how many you are able to identify correctly. These all of these metrics are for classification model only, right? Now see, the name of this, all of this is confusion matrix. It is bound to have confusion, right? You are bound to have confusion. Don't worry, take time, but try to understand this. This is a very important concept. 50 to 60% of the interviews, people would be asking you questions around confusion matrix. Hypothesis testing, no, right? No one will ask you questions around those topics, right? Statistics, not as much. Confusion matrix, this is the like this is the big daddy of questions that you have, right? Confusion matrix. I know data scientists having 8 to 10 years of experience who are still not able to explain confusion matrix, right? So this is a very important concept, right? Generally, recall, in 99% of the cases, we need to look at recall and precision together, right? Because see, let's say you get a model which is giving you 100% recall, but the precision is 20%. What does that mean? That means that you are able to capture all the population, but in order to capture all the population, you are coming up with a lot of incorrect predictions as well, right? A recall of 100% and a precision of 20% means that although, so let's say you are able to capture, let's say you have a model which is correctly predicting that 100 patients have cancer. But along with these 100, it is also predicting another 400 will have cancer who in reality will not have cancer. Now your recall will become 100%, right? Because you are able to identify 100 patients correctly. But because your model is predicting 500 people in total will have cancer, your precision will become 100 by 500, which will be 20%, right? For this churn example, the accuracy is 70%, right? For this churn example as well, right? The same thing. I have not considered all the values. So the accuracy, take the accuracy example from here only, right? Accuracy is nothing but the correct predictions. Whatever correct predictions you have, that will become the accuracy of the model. Confusion matrix is for classification models. For regression models, we have R square, RMSE, MSE, and all. Those are not as complicated metrics, but still they can be asked. But generally, confusion matrix will be the most, I think this is the topmost question that any interviewer will ask you, right? When you're applying for job interviews. So now we'll move on to the hands-on of the logistic regression model, right? And I think we'll get started with the case study. Okay, so we have covered the logistic regression model theory. We have covered the evaluation metrics, right? That these are the important aspects. And now we will move on to the hands-on, right? Now, in today's hands-on, the data that we have is data about patients who have suffered from a heart attack and of certain other people who have not suffered from a heart attack, right? So the target variable that we have over here, this target variable is a categorical target variable which indicates whether a person has suffered from a heart attack or not, right? has had a heart disease in the past, right? So that's the target variable. Now we want to predict this target variable by using a bunch of factors, right? By using a bunch of medical factors that we have collected about these patients, right? So the data that we have today consists of all of these features. So we have the age of a patient, right? So my data will be unique at a patient level, right? For each and every patient, my target will say whether the patient has had a heart attack in the past or not. And then I will, let's say there is a patient who had a heart attack. I will talk about the aspects such as what is the age of this particular patient, right? That will be one. So the age, what is the sex of the patient, right? Male, female. What is this CP? So CP is the short form for chest pain type, right? So there can be different kinds of chest pain that a person can have, right? So if you see, these are 0, 1, 2, 3. These are medical terms. Someone who is familiar with these will be able to explain or understand these. But even if you're not familiar, that's okay. Then we have the rest BPS. This is the resting blood pressure of the patient, right? What is the resting blood pressure of the patient? So you will have that metric, right? Then we have cholesterol, that is the cholesterol level of the patient. We have FBS, which is fasting blood sugar. We have rest ECG. So this stands for resting electrocardiographic results. So your tests that we have, right, with respect to heart, ECG. We have THALAC. This refers to the maximum heart rate achieved by the patient during an exercise test. So there is an exercise test that usually is carried out for people who have heart diseases in order to identify the in order to find out the maximum capacity of the heart, right? So that is THALAC, right? Exang is once again, this is once more a kind of a test, whereas exercise, when a patient does exercise, right, when you are, let's say, running, there will come a point wherein you start feeling some kind of a pain in your chest, right? So that is your Exang variable. Old peak, this represents the depression induced by exercise relative to rest. Slope refers to the slope of the peak of exercise. So now, if you see, all of these are highly specific, highly technical terms. CA stands for the number of major vessels colored by fluoroscopy. So basically, this tells you how many vessels are blocked, right? That will be that we will get to know by CA. Finally, we have the target variable, that is whether or not the patient has had a heart attack in the past, right? So this is the data that we have. Now, what do you guys think? Do you think that the features that we have are important, are significant features which will help us in predicting whether a patient might suffer from a heart disease or not, right? So looks good. So let's go ahead, let's read this data. So the data that I have explained just now, the same data is contained in the CSV. And you can see over here that this is all the variables that we have talked about, they are present over here, right? And we have the target variable, which is whether the person has had an heart attack or not, right? So looking at the target variable, looking at the features, do you guys think that logistic regression is the best suited model for this? Yes, right? All right. So let's get started with the EDA, right? We'll commence with the EDA of this model. So EDA, first we'll try to find out the distribution of the target variable, right? Now the distribution of the target variable, that is how many patients suffered a heart attack, how many patients did not in this data. Let's try to find that out. I have 303 rows in total over here. So there are 303 patient records that we have. Now, if I go ahead and if I call the value counts function, right? So either you can do datasets.target or you can do dataset colon, in double quotes, you can give target, right? So if you look at this here, I can see that 54% of the patients in this data have had an heart attack in the past, right? 45% patients have not have not suffered from a heart attack. What does this do? Normalize equals to true. If I do not give this parameter, this will give me the count, right? This will just give me a count. If you want to see the proportion or the ratio, you will give normalize equals to true, right? So this gives me 0.54, 0.45. If you want to look at the percentage, you will multiply this by 100, right? As simple as that. Shape of the data 303, 13. This we have already seen. So 303 patients in total. So that's good. We have seen the value counts. So no need for this. And we can get this. We can go ahead and we can plot the target variable distribution as well. So I'm using a count plot, passing my target column. Data becomes data set. I give a palette. If you want to change the color, you can give a specific color. If you exclude this, it will take the default color of, I think, blue and orange, whatever that has, right? If you see blue and orange, right? So if you want to change the color, you can give the palette as well. Any color that you want to give, you can give that. All right. Any questions till now? Let's look at the correlation metrics over here, right? Next thing, so I'm not doing a very proper EDA over here. The EDA that you have done in the Python notebooks previously, right? In your sessions that would have been conducted for Python and EDA visualization and all of these, right? If you go through those, right, this a similar level of EDA you are supposed to be doing over here as well, right? So let's look at the correlation heat map. So dataset.core, this will give me the correlation output. I go ahead and I just plot this in a heat map, right? And this is what my output looks like, right? Uh, Now you can either look at this heat map or you can also look at the tabular output as well, right? We can increase the size as well. Atinder, I will give this assignment to you guys. It's easy. All you have to do is that you have to give the figure size. Try figuring that out. Yeah, figure size is there, right? Now, if you want to look at this, you can see this. Now let's focus on the target variable at the bottom. Right, let's look at the target variable at the bottom over here. You can see that the target variable that we have, just go through this and see if you feel that this target variable is correlated with the variables that we have or not. What do you guys think? Do the correlations look good? So if you see, each and every variable has a decent correlation with the target, right? Now I will not see very high values over here. Why? Can someone tell me why I will not see very high values over here for correlation? So see, our target variable is categorical in nature, right? Our target variable is not linear in nature. Now, correlation is a metric that works well with two variables which are linearly distributed, right? Over here, one variable is categorical, the other might be linear. But if you are trying to find out the correlation of a categorical variable with some other linear variable, you will be able to get values, but the correlation can never become one, right? It can not become -1, because what will happen is that your one variable can only assume two values, that is 0 and 1. The other might extend from, let's say, 0 to 100, 0 to 500, 0 to 1000, whatever, right? So but for categorical variables, a correlation of 20-30% is also very good, right? So in such cases, what you're seeing, right, correlation of, let's say, 43%, right, 13, 42%, all of these things are very good, right? This correlation tells us that there is a decent healthy correlation of my target variable with these variables, right? So it means that the variables are correlated to a good effect. Now, if you just wanted to see the correlation of the target variable, we could have also seen it like this, right? Just limit the output to the target variable. All right. Right. In this case, although we have not checked this, but let's also look at the data set.info. This will tell us if there are any null values or not. You can see that there are no null values in this data set, right? All right. So we'll go ahead and we'll describe the features that we have, right? Have a look at this. What do you see over here? Can you come up with some generic insights, anything which is out of the ordinary that you're able to see over here. Just go through just do a basic sanity check of each and every variable and see if it makes sense or not. If I eliminate t, this is the output. If I keep t, this is the output. And this is just for transpose. Okay, transposing it, if you have more number of features, it is easy to look at the output then, right? Otherwise, you'll have to scroll towards the right hand side. All right, so everything looks good, right? Age minimum is 29, maximum is 77, right? Similarly, your this is your heart rate, right? You can see that heart rate is minimum 94, maximum 200, right? You have all your thallic and all of these things, right? So everything looks good. So I think the data that we have is good. There are no funny values, there are no incorrect values that are there in the data. So I think we can get started with model building, right? So what are the steps that we need to follow while building the models? So first thing that we need to do is we need to divide our data into features and target, right? So I will divide my data into X and Y. So for that, I am selecting all but the last features in data frame X. I am selecting only the last feature in my data frame Y. That's correct, Vidya. So if you see, this is my X variable, which contains all the features, and this is my Y variable, which contains only the target, right? Next, we will go ahead and we will split this data into training and testing, right? Now, for training and testing, what do we do? I call the train test split function. I am passing both my features and my target variable. I give the test size as 20%. So 20% will be for testing, 80% will be for training. Random state, I've explained last time. It's the same hyperparameter, the same objective, whatever we were doing in linear regression. Random state has the same objective here as well. The function remains the same, right? And this function will return 4 different values: x train, x test, y train, and y test. And x train, x test will have 80-20% values of your x data frame. Y train, y test will have 80-20% values of your y data frame, right? So now this is how our data looks like. If you see, x train has 242 rows, and x train will have x test will have the remaining, that is 61 something rows, right? 61 rows in x test, right? And this is all that we need to do with our data. And now we are ready with building the model, right? For building the model, just like in our last week's case, right? Linear regression, we had imported the linear regression model. This time we are importing the logistic regression model. From sklearn.linear model, we import logistic regression, right? I call the model object in the log model variable, right? I instantiate logistic regression. To train the model, I use the fit function and I pass the x train and the y train data, right? So this is my training data. X train will contain the features, y train will contain the target variable, right? Now my training is done, right? My training of the model is done. I can use this model to generate predictions, right? So what we'll do is that we will start with the predictions. Okay. Now, once when the model is fit, I can use this model to make predictions, right? I have my actual data. I have my predicted data, right? First, I will get my predictions. So I use my test data, right? I use the log model object and I predict. Now, this time I'm not using the fit function. I'm using the predict function. So log model.predict, I pass the testing data. As soon as I use log model.predict and pass my testing data, I will get predictions over here in bypred, right? So I do this. You can see that this is the length of bypred. I have 67 predictions, and you can see that this is what I'm getting as predictions, right? If you see, I am directly getting the predictions as 0 or 1. How do I get 0 or 1? Any probability which will be greater than 0.5 will become 1. Any probability which will be less than 0.5 will become 0, right? Automatically, the cutoff will be created by the model. If I want to print the accuracy of the model, I have a function which is log model.score. If I pass the training data over here, this will give me the accuracy of the training data. So the accuracy of this model on training data is around 85%. For the same, if I give the testing data, log model.score x test y test, you can see that the accuracy of the same model on testing data is 80%, which is decent, right? I do not see that the accuracy has gone down by a very high margin, right? The accuracy has remained almost stable. 85% on training and 80% on testing. This is a good enough number, right? All right. But now we know that accuracy obviously is not everything that we have to focus on, right? In this case as well, if you remember, we have heart patients. Now, it might happen that my model is incorrectly predicting someone to be not having an heart attack when they have a higher risk of getting an heart attack, right? So, do you think that accuracy will be the metric that will help me, or do we need to go with any other metric? If yes, then which metric do you think we should use? Recall, right? So we will be using recall, precision recall together, but recall will have the higher weightage, right? So for that, let's try to generate the confusion matrix. So for the confusion matrix, what I do is that I call from sklearn.metrics, I import the confusion matrix function, right? This is a pre-built function that we have. You can see over here that this is your confusion matrix function, right? It's there in the sklearn.metrics library only. I call the confusion matrix function. To this function, I need to pass the actual values of y train and the predicted values. So actual is y train, the predicted is log model.predict x train, right? Either you can save it in a variable and pass that, or you can directly get the predictions, right? I run this, and you can see that this is the confusion matrix that we are getting, right? Now for the confusion matrix, you can see that this is for your 0 class, this is for your 1 class, right? Similarly, this is for your 0 class and this is for your 1 class, right? So let's see what my performance is. Now, 120 people out of around 142, my model is correctly able to identify that these people will have heart attack, right? 14 people, it is incorrectly classifying that they will have heart attacks. 22 people, the model is not able to classify that they will have heart attacks, right? Now, if you want to identify the precision recall, I have a metric. Now, confusion matrix will just give me the TP, FP, TN, FN values, right? It will not give me precision recall and all. So if you want to generate the precision recall accuracy, I have another function known as classification report. Now, the classification report, I call this function on the same training data, the actual Y and the predicted Y. I run this, and you can see that these are the precisions and recalls that your model is giving for the class 1. Now, if you see for the class 1, that is people having heart attack, the precision is 85% and recall is 90%. What do you guys think? Is this a good enough value? This is decent, right? My model is covering 90% of heart attack patients. In reality, 90%, if there are 100 people who had a heart attack, my model is able to cover at least 90 of them, which is good, right? My model is doing a decent job over here. I can also generate the same confusion matrix for my testing data. This was for my training data, and this is the same for my testing data. And I can also generate the classification report for my training data. Sorry, for my testing data. So you can see that for my testing data as well, my recall is 84 and my precision is around 79%, which is decent, right? 79%. See, accuracy is not the evaluation metric that we are focusing on over here, right? I think precision, Karan, you're talking about precision, 7984. So this is not very good. Yeah, yes. So considering this is a medical use case, this is not a very good metric. But logistic regression is a very simple model, right? As compared to other classification models. This is what logistic regression is able to do. But as in when we move ahead in our course and we start studying about more complicated models, we will try to increase this value, right? Right now, the model is doing a decent job. It is not doing a very exceptional job. It is doing an okay job, right? Yes, your decision tree based models, your random forest, XGBoost, those models generally perform better than the typical parametric models such as these logistic models and all, right? So we'll see that. So yeah, I think that's it. There is not much to the case study over here. You guys would have seen this logistic regression. Uh, Implementing the model is quite easy. Understanding the model is actually what is slightly more tough, right? Now, this is a simple case study that I have taken. Once when we will proceed through the course, right? Once when we have seen almost all the popular models, then I will be taking you through a bigger case study wherein I will be talking about how in the real world we approach such problems, right? In the real world, if you have a categorical target variable, right, you will not generally go ahead and fit only one single model, right? You will when you go to when you have to buy a car, do you go ahead and do you just take the test drive of one? No, right? You will take, let's say, many test drives, and then whatever car suits you the most, you will buy that. So just like that, while building the model, we do not build just one model, right? So right now the knowledge that we have is limited. So that is why I have taken a simpler case study. But once when we know about all other classification models as well, after that I will be taking one more complicated case study wherein we will see how we can test out different models, how we can identify the best performing model, and how then we can take that model and improve the results even further, right? And that is it on logistic regression that we had to cover for today, right?
Question 5. In which category does linear regression belong to? Option 1 unsupervised learning, option 2 supervised learning, option 3 both supervised and unsupervised learning, or option 4 neither supervised nor unsupervised learning. Tell us your answers in the comment sections below. Just a quick info, guys. Intellipaat offers an executive postgraduate certification in data science and AI, where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps, and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
Hey, hi everyone. Today we'll be starting with a new topic, right? We'll be starting with decision trees and random forests. So basically tree-based models, right? So make sure that your concepts are clear there. Let's say I have two features, gender and designation, right? Let's say gender is male, female, female, male, male, female, male, right? Let's say this is the data for gender. Now this is designation. So let's say I have data scientist, I have senior data scientist, I have data scientist, I have lead data scientist, I have data scientist, I have once again data scientist, and once again senior data scientist, right? Okay, so let's assume that these are two columns, right? In our data. Okay. Now these are obviously non-numeric columns. But the models that we are studying about, they are numeric models, right? So how do we convert these values or these columns into numerical type, right? That is what label encoding or one-hot encoding is all about, right? Now let's first look at label encoding. Now what is label encoding? If I was to go ahead and if I was to convert this data into labels, right? I have to convert this into a numeric form, right? How can I do that? Let's say I go ahead and the same two variables, the most easiest thing for me to do is what? The most easiest thing for me to do is to assign numeric labels to these columns, right? Let's say same data, I have gender, right? I have designation, right? Same data. Now what I say is that male, right? All the values which is male will become 1, right? All the value which is female will become 2, right? So let's say I go ahead and I take this as an example. So male becomes 1, female becomes 2, 2, 1, 1, 2, 1. Right? This will become your data. Right? Now, this is what labeling coding is. Right? Similarly, if I take designation, let's say data scientist becomes 1, senior data scientist becomes 2, data scientist 1, lead data scientist becomes 3, data scientist 1, then 1, then 2. Right? So, this is how I can convert my data to a numerical form. Right? Okay. But if you look at these two variables, right, the these two variables are categorical, but in categorical as well, right, these variables are slightly different. Binary and all is fine, but if you look at the overall how these two variables are created, see, for designation there is an order, right? A data scientist is the junior most position. Then you have a senior data scientist. Then you have a lead data scientist, right? Over here, the values are related to each other, or there is a sequence, there is an order in the values. But do you think that within male and females, do we have any order? It's not that a male is greater than female or a female is greater than male, right? Such kinds of variables, categorical variables, where the values are not related to each other or do not have a specific order, are known as what? Nominal categorical variables, right? I'll say nominal only, nominal variables, right? The second variable, if you look at this designation has an order, right? What is the order? I know that data scientist is junior, senior data scientist is one level up, lead is one level up, right? These kinds of categorical variables are known as ordinal variables, right? Other examples of nominal variables, nominal categorical variables, country, region, grades nominal. Thus, guys, what do you think? Grades will not be nominal, right? Grades will be ordinal because grade A, grade B, grade C, you know that A is the maximum, B is, let's say, second, then C, right? Political party, blood type, right? Very good. Yeah, so that will be ordinal. And can you give me examples of ordinal variables? Brand of car, yes. Ordinal variables, rank, grades, yes. Employee ID is not ordinal, Darsh. Percentage is not a categorical variable, Mayur. Roll number is not a categorical variable. We need to think of categorical variables, right? Not numerical. Department is yes, subjects is no, measurement is numeric, property type, quality of product, yes, maybe good, bad, average, right? Family relation, yeah, so basically first cousin, second cousin, something like that. Range of income, shirt size, yes, good example. Income is numeric, but if you say range of income, what Yatharth has mentioned, that can be correct because you might have, let's say, 50,000 to a lakh to 2 lakh, 2 lakh to 5 lakh, something like that, right? Air quality is numeric, not a categorical variable. All right, so is everyone clear with the between the difference between ordinal and nominal? Car variants, yes, that's a good example. Siddharth, or sorry, one second. Yeah, Siddharth, right? Disease is nominal. Survey 1 to 5 less. Right. I think most of you, all of you should be clear between the differences of ordinal and nominal, right? Now, now that we understand the difference between nominal and ordinal, now see, when I convert this gender to a numerical value of 1, 2, my model will automatically assume that 2 is greater than 1. That signifies that female is greater than male. Is that true? Do we have any implication wherein we know that female is greater than male or male is greater than female? Male is greater than female. Obviously, people have those thoughts, but let's talk about facts, right? These are things that we you cannot have an order, right? We cannot say, let's say if I have data about countries, right? I cannot say that, let's say, country A is greater than country B. Obviously, on the basis of certain economical aspects and all, you can say that, but with respect to whatever problem you're solving, it doesn't matter, right? So, do you think that converting this gender to these labels makes sense? This is incorrect, right? Because if I'm making male as one and female as two, I am automatically inducing bias. I am introducing bias in my model. I'm saying that female is greater than male. If I do vice versa, I will say male is greater than female. So that's incorrect, right? And if you look for the second variable, designation, do you think that this labeling coding makes sense for the second variable for designation? Second makes sense, right? Because three being assigned to lead data scientist, two being assigned to senior, one being assigned to data scientist, that's correct, right? So if you see, label encoding over here in this case was incorrect for the gender variable, but it was correct for the designation variable, right? So then how do we treat variables such as gender, right? How do we treat variables which are nominal in nature, right? Now let's move to another thing which is known as one hot encoding. Now what one hot encoding does is that it takes the same data and it transforms it in a slightly different way, right? I'll take all three, all two. So this is for, let's say, the gender. This is for designation. I'm giving you examples of both, then we'll decide which one is correct, which one is incorrect, right? So now when I will do one hot encoding, right, there are functions in Python that will automatically do all of this. But let's say this variable becomes gender underscore male, right? I'm just writing G because there's no space. This will become gender underscore female. This will become designation underscore DS. This will become designation underscore SDS, which is senior. This will become designation underscore LDS, which is lead, right? I'll explain what this means. Now let's focus on the first variable, which is gender, right? Now what one hot encoding does is, one hot encoding is this one, right? It creates binary variables for every uh, nominal variable that you have or any categorical variable that you pass, right? Now for the first row, it's a male, right? When it's a male, this will become 1 and this will become 0, correct? For the second person is a female, so male column will become 0, female column will become 1, right? Same for this one, right? Then we'll have this, then we'll have second last one will be female, and then we'll have this once again. Does this make sense to everyone? Now, what I have done is that I have taken the gender column and I have created binary variables for all the unique values that this particular column can take, right? Now, if I do the same thing for the designation variable, what will happen? This is 1, 0, 0, right? This is 0, 1, 0, right? This is once again 1, 0, 0. This is 0. This is lead, right? So 0, 0, 1. Then once again this, and then 0, 1, 0, right? Now, first of all, if we focus on the male, if we focus on the gender column, this is completely bias free now. That's correct, Charan, right? So do you guys think that this is a correct uh, conversion of this particular variable gender? This is correct, right? I am not saying that male is greater than female or not. I am just replicating the same information in a numeric way with a bias free approach, right? I am not giving any bias to any of the values that are there. Why did I not give any bias? Because obviously gender is a nominal variable, right? Now, if I move to the second column, which is designation, now see this, we all should agree, right, that this is the correct approach. This one is correct, right? This is correct. Now, what do you guys think about these last three columns? Is it correct or is it incorrect? Yes, that will be, yeah, guess me, that will be zero. That's my bad. How should I make that zero now? So let's say this is zero, right? All right. Now, for the designation column, do you think that this transformation, one hot encoding, do you think that this is correct? So, Rishabh, that's what I'm just trying to clarify. See, in the nominal variables case, this was incorrect. But over here, do you think that this approach is incorrect? This also looks correct, right? What is different in this one? So, if I compare, let's say this from this, what is the difference? Process is not lengthy, Vishal. So this is just a one-step process. Yeah. So you are actually making your data more complicated. That is correct. If you are implying that. So see, for our ordinal variables, right, both approaches can be correct. But if you look at the second approach, in the second approach, you are losing information about this variable. The information that you are losing is the order, right? So I am, although it is correct. It is saying that this first person is a data scientist, second is a senior, third is a lead, and so on and so forth, right? Whatever. It is, that information is intact. But the model now does not know that a senior data scientist is greater than a data scientist. A lead data scientist is greater than senior data scientist. So you are only portraying 50% of the information. So there is lack of information that is happening in the second case, right? So this is how we treat our categorical variables, right? Now, as a data scientist, I am glad that this question was asked. Uh, these concepts, I have interviewed people having 8 to 10 years of experience, and these concepts were not even clear to them, right? But now, if I go ahead and if I give you a case study, right, I go ahead and I give you a case study, I'll tell you that you have two columns. One is the department of the products that they belong to, right? And one is the product name, right? Now, I want you to tell me how will you convert these two categorical variables into a numeric form? What will be your response? One is department, the other one is the name of the product. How will you convert these into a numerical form? This is a question. So assume that the department column, right? I believe the example would be confusing, but assume that the department column has, let's say, milk is mapped to dairy, dairy is mapped to consumables, consumables is mapped to, let's say, something else, right? So if that is the case, if let's say department is something that has an order, right, then in that case, that will be uh, transformed using one hot encoding. Sorry, label encoding, and the product names will be classified or will be converted using one hot encoding, right? Yes. Okay. So, all right, then let's get started. Any other questions? Abhishek, try this on your own. I will not show any example. Try this on your own. Explore around this. Then ask me any questions that you might have, right? Go and search for a confusion matrix with three classes. You will get many examples, right? Try to understand this. Then try to think. Everything is not about me explaining to you, right? If you are, I have explained the basic concept to you. I'll be honest, in this course, we are just explaining that there will be many concepts that you will have to extend, that you will have to learn, right? You cannot learn everything in a course. Try to invest some time. Everything, if I am going to spoon feed each and everything to you, you will never be able to reason, you will never be able to develop the critical thinking. And data science, whatever you are learning till today, it is not that data science will stop here, right? There will be development, there will be so many things that will happen, right? So you need to have the skill to learn things on your own as well. Whatever I have taught in the confusion matrix, I can vouch for this, that that is 100%. Now, all you need to do is that you need to extend that information, that knowledge to additional classes, right? First, make sure that you are pretty clear on what confusion matrix means, what confusion matrix is. You are able to understand everything for the binary confusion matrix. If you are able to, I don't see any reason you will not be able to understand for the 3 class or the 4 class, right? All right then. So let's get started. Decision tree and random forest. If we have a flow chart, and what kind of problems are these models helping us in solving? Two models, right? Linear regression, logistic regression. Linear regression was what? Classification. No, regression. Logistic regression was classification, right? Does data science end here? No, right? When you go to buy a car, is it only Tata, Maruti? That is there only just one brand? No, right? You have options. Just like that, in case of machine learning data science, we have options. It's not that there is only one model for classification, one model for regression. There are different models. We need to go ahead and we need to explore all the models. We need to see which model is working the best, right? Whatever model is working the best for us, for our case, right? We go ahead and we choose that. Just like maybe for you, you might prefer, let's say, a Skoda car or a Volkswagen car. Your father might prefer a Maruti, right? Right. And your, let's say, someone else might prefer a Tata or a Mahindra, right? So just like that, depending upon what your requirements are, your requirement might be stability, your requirement might be features, your requirement might be anything. Just like that, from a model as well, your requirement might be a simple model, your requirement might be a non-linear model, your requirement might be explanation of the factors that are driving the model, right? On the basis of that, we actually select the model. Even on top of that, not every data will fit to all the possible models that are out there. Every data distribution is different, and every model that we are studying, the inherent architecture is also different, right? So when the architecture is different, then when we are exposing different distributions of data to the same model might respond well to one kind of a data and might not respond well to another kind, to which, let's say, some other model might actually do a better job, right? So hence it is not only linear logistic that we use, there are other models as well, right? When I say other models, this week we will be focusing on decision trees and random forests, right? These are very common models in the world of data science, these tree based models. So we'll first try to understand what a decision tree is. Then a decision tree, once when we understand decision trees, then we will move on to random forest, because random forest is nothing but it is a variation of the decision tree model, right? So yes, Harshit, decision tree, your random forest, they can be used for both classification and regression tasks, right? So the linear regression model that we have studied till now, it was only limited to regression, right? Logistic regression was only limited to classification, right? Whereas our decision tree models that we are studying today and tomorrow, most probably, are models which can do both the things, right? It can also help you with a target variable which is categorical. It can also help you with a target variable which is continuous in nature, right? So let's get started with the theory now. Tree-based models are said to be the most used supervised learning models. They can be used for both classification and regression problems. We can create highly accurate and stable predictive models using these tree-based models. Right now, tree-based models are very, very popular. Why? They are easy to use, right? They are explainable, and this is something that we have been doing a lot, right? So they are easy to understand as well. When I'll be talking about the concepts, right, you will find that you are able to relate with these tree based models, because generally that is what we also do in our life, right? That's what our objective also, whenever we have to do something, right, we go ahead and we apply a bunch of rules, right? We apply a bunch of conditions, right? So let's say I take a very simple example. Let's say that you need to hang out with your friends, right? And you need to decide on a place where you have to go and meet and eat, right? Is it a straightforward process? First of all, let's say you have 5 friends, and let's say one friend comes up to you and they say that, okay, we'll go and we'll meet, we'll have dinner in, let's say, a particular restaurant, right? Let's say Burger King, right? Not even a restaurant, a fast food joint. But does that happen this way? No, right? There will be so many factors. So let's say 5 friends, you get together, you go ahead and you decide that you have to finalize a restaurant, right? Now, can you guys think of what factors can be there which might affect which restaurant you might go or you might not go to? Any idea? What factors drive food? What kind of food you want to eat? Distance, yes. Proximity, good. Ambience, is it dinner? Is it lunch? Season, cuisine, price, yes. So many factors, right? So very good, right? So let's do one thing. Let's try to build a decision tree and see how the decision tree will actually help us in making certain decisions about the population, right? Now let's say this is my entire data. This is my entire data. I will take restaurants in NCR, right? Delhi NCR. Taking this as an example, you can extend this to your city. Let's say that the total number of restaurants in Delhi NCR are 1,000, right? Just for example, let's say I go ahead and I take this, right? Okay. Now let's try to identify. Okay, so what according to you guys will be the most important aspect over here? When five friends are meeting, let's assume one is from Noida, one is from Gurgaon, one is from Faridabad, one is from Ghaziabad. Then what is the first thing that you will have in your mind? Distance, right? Let's assume that the first aspect or the first condition for everyone is distance, right? So a very simple rule, let me go ahead and let me apply a very simple rule over here in this data. I will go ahead and I will say that, let's say every friend is saying that I don't want to travel more than 20-30 kilometers. The friend who is situated in Noida, if he has to go to Gurgaon, he or she might have to travel 50-60 kilometers, right? Similarly, Faridabad has to go to Ghaziabad 40-50 kilometers, right? So let's say the first condition that we apply is distance less than 25 kilometers, right? What are all the restaurants, right? That what are all the possible restaurants which have the distance of less than 25 kilometers or greater than 25, right? Now let's assume that distance less than 25 kilometers, out of the 1,000, there are only 200 restaurants, right? Which will have distance of less than 25 kilometers, right? These are 200, and let's say these are 800 restaurants, correct? Now, what do you guys think? What will be the next criterion? What might be the next criterion over here? Cuisine, maybe. I think let's go to cuisine. So, right. So, let's say in cuisine, or let's say first, let's try to decide whether it is veg or non veg, right? So, you can have a condition such as, let's say, is it Navratri? Or let's say simple, right? I'll just write veg, all the veg restaurants and all the non-veg restaurants. Let's say on whatever factors you are able to arrive at a decision, do you want to eat veg or do you want to eat non-veg, right? Now let's say you decide that you have to go ahead and you have to eat non-veg, right? Let's say 80 are veg, 80 restaurants, 120 are non-veg, right? Okay. So let's say this is then 80 and 120. Now you will go ahead and you will split this further, right? Now this process will keep on happening, correct? Now the next filter can be, let's say, what kind of cuisine within non-veg do you want to go for? Mughlai? Do you want to go for Punjabi? Do you want to go for American, Italian, Mexican, whatever, right? So this, you can imagine, this tree will keep on growing. Does that make sense? Right? We can keep on growing this tree to any extent possible, but as long as we are keeping features which are important, right? As long as we are keeping features which are relevant, our decision tree will stay relevant and significant, right? Now let's assume that I take a case of five friends who are in college who want to select the best possible or a place wherein they can eat, right? So for them, what will happen? This decision tree will come from here to here, right? This will then come from here to here because they decided that they have to eat non-veg. And then let's say on the basis of all the rest of the conditions, they finalize that they are going to go to these. They have these five restaurants as the option. Now they will go ahead and they will decide these five amongst themselves, right? Now see, this decision tree can also serve a purpose for other cases as well, right? Now let's say the same in the same area, we have a group of friends who want to eat at a restaurant which is less than 25 kilometers, but they are looking for a veg option. Now, within the wedge option as well, if you keep on growing this tree further, right, you should be able to identify the best options for you, right? Even over here, towards the right hand side, if you would have grown this tree forward, you would have seen that, okay, greater than 25 kilometers, maybe you travel to Gurgaon, maybe you go to Murthal, whatever, right? But if you see, if you capture all possible outcomes, right, of out of all the 1,000 restaurants that are there in Delhi NCR, you can go ahead and you can divide each and every restaurant to each and every condition or a combination of conditions, right? And this is how we generally create a decision tree, right? Similarly, when you have to go and you have to buy a car, how do you decide? You will decide a budget, you will decide features, you will decide whether it is petrol, diesel, electric, you will decide what brands you need to go for, right? There are so many factors, and on the basis of this, yes, 5-seater, 7-seater, SUV, hatchback, sedan, saloon, whatever, right? So, isn't this how we actually arrive at decisions? Isn't this that in most of the cases you make, whenever you are making a life decision in a, let's say, in a uh, disciplined way, isn't this how you will actually approach a question or approach a situation? So, this is generally what we mean by decision trees. Let's go through some theory around decision trees, and gradually we will try to understand what how decision trees actually work, right? Now, tree-based models are the most used supervised learning models, algorithms. They can be used for both classification regression. We have gone through this. There are two kinds of tree-based models that we will be going through: decision trees and random forest. However, it is not limited to these two. There are other models as well. But if you understand these two, you should be able to extend the knowledge from here to the other models as well. Right? Let's get started with the decision tree. How is it different from putting criteria and assigning weights to them for decision? So we are not assigning weights over here, right, Rishabh? We are dividing our population as per our need, right? As per our requirement. There are no weights that are being applied over here. If you're comparing this with logistic regression, linear regression, in case of linear logistic regression, we were getting the output by combining all the factors, assigning different weights, and then coming up with a common factor. Here, we are taking each and every factor and we are seeing what we are applying conditions on that, and we are trying to come up with homogeneous groups, right? So let's say if your entire population was this, right? So let's say you have, so let's say these are the different options or the different, this is how your data is distributed, just an example. So what decision tree is doing is that it is creating boundaries, it is creating rules. It is saying anything which is from here to here will be a cross. Anything from here to here will be a tick. Anything from here to here will be a heart, right? During this process, there can be misclassifications, but over here, we are not assigning weights. We are creating these decision boundaries. The rules that we are applying, they are actually dividing your data into homogeneous groups, right? Kind of like if else. Right? Now, decision tree, a graphical representation of all possible solutions to a decision. A decision tree is mostly used on classification problems. Decisions are mainly based on some conditions. Decisions made can be easily explained, right? So just go through this definition and see if you're able to understand this. Let's say distance has highest precedence, wedge is priority. You might still arrive at the same conclusion. So see, here you have only assigned, you have not even assigned weights, right? You are just saying that, see, when I say that distance has the highest precedence, it is not only distance which is going to give you the prediction, right? We are taking distance as the first cutoff or as the first criterion. After applying distance, you are applying some other criterion as well. I am not saying that the distance has the highest weightage over here. I am saying that I am splitting my data on the basis of distance first because that makes sense first, right? Then if I take some other, if I'm taking any other variable after distance, it does not mean that the importance of that variable has gone down. Overall, all of these rules that you are creating, they work together to go ahead and to come up with the final predictions. So in case of logistic regression, linear regression, we were assigning weights. Here we are not assigning weights anywhere. We are just trying to come up with a combined set of rules which helps us in getting homogeneous groups, right? If I'm looking for people who have churned, if I'm looking for people who have not churned, we are trying to identify those groups. This is what clustering will also do. Clustering will be unsupervised, Harshit. This will be supervised. There will be a target variable over here. Go to the intricacies of the decision tree, and then you should be able to understand it in more detail. All right. Now, I'll talk about the random forest later. But yeah, so let's get first started with the decision tree. Because once when we understand one decision tree, then we will move on to random forest, right? So I'll come back to this slide. Let's first get started with decision trees, right? Now, what do we mean by decision trees? Uh, or let's do one thing. Let me give you a general introduction, right? Now, let's do a small exercise, right? Can Okay, I'll make this easy. Just one second. Let's see how many people are active. I am. There is a file over here which is customer churn in this drive link. Or let me create a new file. I am creating a new document over here. I'm naming it as age prediction, right? I want you to make a guess. I want you to guess my age, and I want you to write your prediction over here, right? I want genuine guesses only, right? I don't want vague values, right? Whatever you feel uh, might be my age, go ahead and make a prediction over here. I will be able to track what you are writing, so don't think of being creative, right? All right, try now. Guys, just have a look at the cells. Don't overwrite others' predictions. If you want, you can write your name as well in front in column B. Column A, you can give the prediction. Column B, you can give the name. Abhishek, you need to predict my age. This Excel is there in the drive. Go to this Excel, and in a row, you need to enter what do you think my age might be, and you need to write your name in column B. Presley, you can, yeah, type refresh, or sorry, refresh. Don't overwrite what others are writing on. Hmm. All right. Once you're done, you can just move out of the file so that I know. All right. I think this is good. So we can stop here. All right. Okay, so let me just format this. Right. All right. I hope the screen is visible to everyone. Right. Now, see, this is your. I'm taking each and every one of you as a decision tree. Why? Because see, when you have gone ahead and when you have made a prediction, for me, right, for my age, you would have actually gone ahead and you would have considered different things about me, right? Maybe someone would have gone ahead and maybe some of you would have made this prediction by the basis of how I speak. Maybe someone would have known that I have around 10 to 12 years of experience, going by the normal standard logic of your, let's say, 16 to 17 years for your 12th, 4 years for a bachelor's, maybe a couple of years for the master's and all. On the basis of that, you would have gone ahead and you would have made these predictions, right? Now, see, each and every one of you, while you went ahead and while you made a prediction, you would have had some, you would have thought of certain factors, right? If someone goes ahead and says that I'm 28 years old, they would have thought about something, right? But at the end of the day, all of you guys are what? All of each and every one of you single-handedly was acting like a decision tree. You went ahead, there were n number of possible outcomes of age that you could have predicted for me, right? But you went ahead and you gave a specific value for my age. Is that correct? Does this make sense? All of you are individual models, right? Individual decision tree models, right? Now, if I go ahead and if I give my actual age, right? If I write my actual age over here, right? So my actual age is actually 33. I'll be 34 in a couple of days. So I think 1st November, right? Yeah. So let's take 33 as of now, right? Or let's take 34 only. Okay. Now my actual age is 34. If I go by my actual age, and if I see how many of you have been able to correctly identify my age, right? Let's see, right? So if you look at this, there are how many? There are only 7 people. Why is this? Yeah. Yes. So there are only 7 people, right, who have been able to predict my age correctly, right? And how many I had in total? 48 people. Is that correct? But out of those 46 people, there are only 7 people who were able to identify my age correctly. Exactly. Right? Let's do one thing. Let's take the average over here. Right? I also don't know what this will be. Let's calculate the average over here. Right? Now, the average age that we get over here is, if I round this up, let's say I get 33 as the average age, right? Over here. Now, if I calculate the error from each and every one of you, right? Let's say if I calculate the error from here, I'll take, let's say, this minus this, and I will take the square of this, right? Once again, I'll take the error squared. If I take this, then my overall squared error, right? If I go ahead and if I divide this by, if I take the average error, my average error will come out to be how much? It will be around 23.6, right? On an average, you guys are actually off by around 23, which is the squared error. If I take the under root, it will be around 4.5 years, right? On an average, you guys are off by 4.5 years. But if I take this model, that is the average, over here, my error will be what? My error will be 33 minus 34 whole squared, which will be equal to 1, right? So using this model, or using the average of all of your predictions, my average error was close to 1. But if I would have used, let's say I would have gone ahead with a decision tree, which, let's say, by Charan, or let's say by Harshit, or let's say by Ved, right? In all of these cases, the probability of me getting a less error will be very less, right? You can see that the error is 81, error is 25, right? In most of your cases, you guys have been able to identify my age correctly. But see, when I'm building a decision tree, I am actually depending on only one expert, right? What if I create hundreds of decision trees and I take the average of the predictions from each and every decision tree, right? This process of calculating, or this process of employing multiple decision trees in order to get a prediction, is known as a random forest, right? So if I go back to this, if you see, random forest builds multiple decision trees and merges them together to get a more correct and stable prediction. Now, if you see over here, in this case, even though there are people who have predicted my age to be 25, or let's say 29 and all, even though there are models which are off with their predictions, still my overall average is very, very close to my actual age, right? So you can build 100 decision trees. Maybe 20 of them are very off. Maybe 20 of them are decently off. Maybe 60 of them are very close. Once when you take the average, right, you are going to combine. When you are combining the outputs from so many models, you are going to even out the predictions. Maybe one model says that my age is 30. The other says that my age is 40. If you take the average, you come to 35, which is only 1 year away from my actual age, right? Right? So this is what we mean by random forest, right? So Prabhu, here if you see, right, if I would have gone, so this is just an example that I'm giving, right? This is not correct. Let's not look at this, right? Only look at this errors, right? Now, when you're building the decision tree, there are high chances that you might get an error of 1 or 0, or let's say 4. But there are also chances that you might get an error which is higher, right? You might also get an error which is 16, which is 25, right? Which is 81, right? So, if you look at this, if you bank on individual decision trees, there are lesser chances for you to be correct. There is a chance wherein you can be off by a very high margin as well, right? But when you go ahead and when you actually take the average of so many models, right, in those cases, generally you will not be off by a very high margin. That's what I'm trying to explain, right? That was incorrect, this part, so I've just taken that away, right? So if you look at this random forest, it builds multiple decision trees and merges them together to get a more accurate and stable prediction. These types of models, right? Random forest is something that is called, these models are actually called ensembles, right? Ensembling is a technique wherein you combine multiple learners together, right? So if you see where a group of weak models combine to form a powerful model, right? Now, this is trained with the bagging method. What is bagging? Bagging is nothing but you create a bag of models. When I asked 46 of you went ahead and made the predictions. I took the average. So basically, I bagged all the models and I took the average from all the models, right? This is what random forest means. We'll understand more about this when we get into the detail. But now we will get started with decision trees, right? So, Yatharth, if you're building a random forest, it will automatically build multiple decision trees. So, in case of a random forest, your hyperparameter will be number of trees, decision trees, right? So, and the predictions will be more stable. We'll have a look at that with real world data. Your dependent variable can be anything. It can be continuous. It can be categorical, whatever, right? All right. Now let's try to understand how exactly random forests predict accurately. Random forests predict accurately than decision tree. See, random forests will give you more stable predictions, right? It might happen that one decision tree gives you an accuracy of 90%, but in the testing data, it might happen that the accuracy becomes 80%, 85%, right? If a random forest gives you an accuracy of, let's say, 85%, more often than not, in any testing data, your accuracy will be in the same range only. So the predictions from a random forest, right, they are more stable. So if a random forest says 85% accuracy and a decision tree says 90% accuracy, you can bank on the accuracy of the random forest more. Because on unseen data, you can give as many instances of unseen data to the random forest, the overall accuracy might remain in the same range only. For a decision tree, your accuracy might fluctuate. It might go to 80%, it might go to 90%, it might go to 70%. And as a data scientist, you are always looking for stable models. Because what if you create a decision tree, it gives you an accuracy of 90%. You go to your leaders, they say that, okay, great job, right? You go ahead and you tell them that the accuracy is 90%. They go ahead and they take your model into production. And in the real world, that model gives you an accuracy of 75%, right? You will lose your job, right? So a decision tree is not a very stable model generally when you compare that with a random forest, right? That's what the implication is here. See, mostly, yeah, if you talk about popularity, your tree based models are more popular with categorical target variables, because for continuous target variables, your regression models and there are other models as well which do a decent job. But yes, I would say 8 out of 10 cases, people will be using these tree based models for your categorical target variable prediction. So, okay, why did each and every one of you give different predictions for my age? What was different? Each and every one of you are different. The way you are thinking is different, right? So if linear regression model every time we run it gives the same result, then why when we are running different decision trees on the same model, why are we getting different outputs, right? So the answer to this is that when we run the random forest model, right, we only pass a limited amount of information to each and every decision tree. If I have my 100% data, there are hyperparameters which will limit the amount of information flow. To every decision tree, I am only passing a certain subset of the data, right? Let's say decision tree number one, I pass only 70% randomly sampled rows. Decision tree number two, 70% randomly sampled rows from the same data. Now, this 70% sample will be different as compared to the one that was shared to decision tree number one, right? So, if you see, essentially, we are passing from the same data, right? The subsets that we are passing are somewhat different. They are not exactly the same, they are not exactly different, but they are slightly different. Now, when I do this, the models are forced to take into consideration. Now, let's say if I take an example of the restaurant selection, maybe one decision tree gets distance as a column, maybe the other decision tree does not get distance as a column, then it will be forced to take some other variable into consideration, which if distance would have been there, which in that case that variable would might not have been taken into consideration form, right? So when we force the decision tree to learn on different samples of data, we ensure that whatever piece of information is there in the model is being extracted by the different decision trees that we have. So we have an option of random state as well. But even if you see, random state was for the training test split. But let's assume that you have 80% of your training data, which are, let's say, 80,000 rows. Now, if you pass these 80,000 rows, all the rows at once to 100 decision trees, each and every decision tree will give you the same output, irrespective of how many times you run it. But if from these 80,000 rows, let's say you pass a sample of 70,000 only to each and every decision tree, randomly selected each and every time, then the output will be different. Columns will also vary, rows will also vary. So both will vary. We are going to pass a subset of the rows and columns both. Right. So all of these things, people who are not able to understand, just wait till we get started with random forest, and then I will be explaining all of these things. But as of now, let's get started with decision tree. Right. Now I'll give you one more example. The earlier example was slightly generic. Let me give you one more example about decision trees. Right. Now let's come back to a data science problem. Right. The most common data science problem that we have been seeing is the problem of churn, right? Let's say we have a look at this, or let's take something relatable, right? Everyone would be following cricket, I'm assuming. Let's say India versus England, right? I'm going to make up these numbers, but I think this should be, you should be able to relate to this. Let's say India versus England. Let's assume that India has played, the total matches that have happened are 100. I'm just taking a random example, right? These are not actual values. And let's assume the matches that are won by India are only 10, right? So the win percentage comes out to be what? The win percentage comes out to be 10%, right? Correct? Okay. Now let's see how can we, let's try to break this data down, right? Let's try to build a decision tree on top of this data, right? Now see, when we are building the decision trees, the objective for us is to increase the purity of of the nodes of the decision tree. What do I mean by purity, right? Let's try to understand what we mean by purity first, and then we will move forward. Now see, this particular, or let me change this to 10% looks bad, right? Let's change this to 50%. India versus England. Matches are 100. One or 50, right? So the win percentage becomes 50%, right? Now, if you look at this root node, this has 50% observations of India winning and 50% observations of India losing, right? Now, can you guys tell me, people who watch cricket, right, or in general as well, what can be some factors which can help us in identifying what are when does India win against England, right? Any idea what are some of the factors that you can think of? What might be the most important factor over here? So most important factor is which where are they playing? Are they playing in India or are they playing in England? Correct? Right? So let's say if I divide my data, let's say if I apply the condition playing in India, right, and playing in England. Let's say when I do playing in India, out of these 100 matches, let's assume that out of these 100, India has played 40 matches in India and India has played 60 matches in England, right? Out of these 40, let's assume that India has won 30 matches, right? And over here, out of these 60, now the remaining are what? Remaining are 20, right? India has won 20. Okay. Can you calculate the percentage of winning now? What is the percentage of India winning when they are playing in India? It is 75%, right? 30 by 40 will be 75%. The percentage of win when they are playing in England is what? Is 20 by 60, which is 33%. Does this make sense? Now, essentially, what I have been able to do is that I have been able to increase this 50 from 50 to 75 over here, and I have been able to decrease this 50 from 50 to 33 over here, right? What if I also see there will be n number of factors? How do I know that this is the most important factor? Let's say I take one more example, or I take one more factor. Let's say the second factor that I take is, uh, let's say, pitch spin friendly, right? And pitch is, let's say, fast bowler friendly, right? Okay. Now, let's say using these conditions, if I divide the same data, let's say that India has played England in 60 matches when the pitch is spin friendly, right? And out of these 60, let's assume that India has won uh, 40 matches, right? 140. And let's say when the pitch was fast bowler, it was a fast wicket. Over here, India has won how many? 10, correct? Right? Now, if you see, the win percentage will be how much? Over here, the win percentage will be what? 40 by 60 will be 66%, right? And over here, it will be how much? It will be 25%, correct? Okay. Now, you have been able to increase this 50 from 50 to 66 and decrease this 50 from 50 to 25. Out of these two, which one will you select? What do you guys think? Why first one? Both will matter, but which one will have a which one will be used as the first variable for split? What do you think? Now see, in the first case, the what I have, see, when I do 75 and see the 50% I was able to increase to 75. So basically 25% increase, and the 50% I was able to reduce to 33. So that is a 17% decrease. So if I add these two up, the amount of information increase or decrease that I'm getting over here is what? Is 42%. Right? Does this calculation make sense to everyone? See, I get 75 in one as compared to 50 in other. So that gives me a 25% increase. And for the second one, I get 50 minus 33, which gives me a 17% decrease, right? Overall, if I sum this up, I get 25 plus 17, which is how much? Which is 42% increase or decrease in the purity, right? This is the first case. If I look at the second case, I'm getting how much? I'm getting 66 minus 50, which is equal to 16%. And in the second case, I'm getting 50 minus 25, which is equal to 25%. If I sum this up, I will get how many? 41%. Which approach is giving me a higher increase or decrease in purity? Is it the first one or the second one? First one, right? Even though it is closed, but it is the first split that is actually helping me in a, or it is, see, at the end of the day, I will be satisfied if all of the matches that India have won was over here on the left hand side. All of the matches that India lost were over here on the right hand side, right? So what I'll do is that I'll go ahead and I'll take this first variable as the split, right? So I'll say playing in India, right? Or I will say playing in England, right? When I divide this data, I will delete this now. I hope there are no questions on this, right? Now, when India is playing in India, then my stats were what? I had played how many? 60 matches, 60 or 40? 40 matches, 131, and percentage was 75%, right? And when India was playing in England, I had played 60 matches, I had 120, and my percentage was 33%, right? Now let's take this further, right? I'll split this particular node even further. Let's say now the second condition that we apply is spin friendly pitches, right? Now this is, let's say, spin friendly pitch, and this is, let's say, fast bowler pitch, right? Let's assume if I had gone ahead and if I had divided this, right? Let's say from here to here. So let's say that out of 40, there were 30 matches which were spin friendly, right? And out of this, India won all 30, right? Just an example, so don't go on actual numbers. Let's say 10 were fast bowler friendly, and out of this, India lost all 0-1. Now you can see that the win percentage becomes 0%, right? Now let's say over here as well, similarly, if I apply the same rule, right, that is whether the pitch was spin friendly or not. Let's say this was spin friendly and this was fast bowler friendly. And let's say spin friendly, there were, let's assume 25 matches in spin friendly pitches. India won 20. Your win percentage was how much? 80%, right? And let's say over here, we have the remaining matches, right? 35 matches were bowler. India won 5. Win percentage was how much? 100 by 7. That will be how much? 14.3. Let's take 14.3%, right? So win percentage will be 14.3%. Will it be 35? I'm not sure. 5 by 35, 1 by 7, 100 by 7, right? 7 will be 1, 4, yeah, 14 point something. Correct? Okay, yeah, this will be 0-1 here. Sorry. Thank you, Charan. So there are no matches that are won here. So these are 35 matches. Sorry. Good catch. 0-1. So 0%. Now see, what was my overall objective? My overall objective over here was to see over here in this case, if I had, let's say, if I had just, this is just to give you an idea, if I had 15 ticks and I had 15 crosses, right? So basically, I have 50% representation of both the classes. Ticks can be wins and crosses can be lost, right? So let's say these are 15 and 15, 30, right? So this is not what I want. What I want is, I want more number of, so let's say if I have 3 of these, and if I have, let's say, 7 of the ticks. So although this is 75%, but let's keep it 70. This is what I wanted, right? In the second case, what I had was, I had more number of crosses, right? Let's say 1, 2, 3. I had 6 crosses and I had only 3 ticks. So if you see overall, I am trying to increase or decrease the purity, right? In the final case, if you look at this particular output, I have all ticks, right? Whatever number are there, all are ticks. In this one, all are crosses, right? So the objective of the decision tree is to increase the purity of the resultant node. Either it should have all the matches which India had won, or it should have all the matches which India has lost, right? Now, if you see after doing all of this, now if someone comes to you, right, they say that India is playing a match against England in England and it is a fast bowler friendly pitch. What will you say? What will your prediction be? Will India win or lose? India will lose, right? If you say India is playing England in India and the pitch is, let's say, spin friendly, right? You will say 100% India will win. Now, these are just two variables. Obviously, you understand that India winning or losing will be a function of so many factors, right? But this is just to explain to you how exactly decision trees will work, right? Okay. All right, then. So let's proceed with the theory of decision tree. So now I want you to go through this example on your own. I have given you a couple of examples and see if you're able to understand this or not. Your target variable over here is label. Using the target variable label, they are trying to create a decision tree, right? Now just go through this and see. I think the example should be clear to everyone. But go through this example in detail. You should be able to understand each and every step. Let me know in the chat window if you're able to. If not, then also let me know. All right. So if you see, this is easy. My target label has three unique values. It can either be mango, lemon, or cherry. We are trying to identify a fruit on the basis of the color and the diameter, right? So the first split that it is taking is checking whether the diameter is greater than 3 or not. If it is less than 3, then all the cases, right? If you see, for when the diameter is less than 3, I'm getting a node which is 100% pure. I'm getting all cherries over here, right? So this is a totally pure node, and this is what my decision tree aspires to get, right? So this is good. Now if I come to the right hand side, I see that there are two mangoes and there are one lemon over here at this split. Then if I apply one more split, that is color equals to yellow. Now if you see, when the color is equal to green, when the color is not equal to yellow, and the diameter is greater than 3, 100% chances of that fruit being a mango, right? So this once again gives me the maximum possible purity. But over here, if the diameter is greater than 3 and the color is yellow, then you cannot be sure. Then there can be a 50% probability that it is a mango. Then there can also be a 50% probability that it might be a lemon. Using these two features, you cannot go ahead and you cannot identify what the fruit might be if the diameter is greater than 3 and if the color is yellow, right? Right, I can see that most of you are able to understand this. Okay, so we'll proceed. Now let's go through the terminology of some of the decision tree things that we have, right? Now see, I'll start with here. Let's say the root node. The root node is what? The root node is your overall population, the entire population. That is when you have not started splitting the tree into subsets, right? That is the root node. Your entire population will be the root node, right? The parent or child node will be any node that is broken down into subnodes, right? So the root node will become the parent node and all the other nodes that are branched. So if let's say if this was a tree, let's say this was a tree that we had created, let's assume. So first of all, my root node over here is what? The root node is the top one. This also becomes my parent node to these two childs, right? So my parent node will become this and the child nodes will become this. If I go ahead and if I split this even further, then this particular node will become the parent node, right? Now for this split, right, if I do this split, now this becomes the parent node and this becomes the child node. If you talk about this split, this becomes the parent and these two become the child nodes, right? If I don't, the part wherein I stop my tree from growing, right? So let's say this was the entire tree. The nodes which are not divided further into child nodes are known as leaf nodes. So these four nodes that you are seeing at the bottom, these will become the leaf nodes because they are the leaves of the decision tree. There is nothing else that is going to come out from these leaves, right? This will become the leaf node. The process of splitting the root node or the parent node into child nodes is known as splitting, right? If you focus on specific area of the decision tree, let's say if you just focus on this area, this will be called as a branch or a subtree. So you can see that all the terminology is very, very synonymous to an actual tree, right? And the process of splitting, or let's say the process of cutting away a branch, right? And why do we do that? I will talk about that later. But let's say if I go ahead and if I take this branch away, this process is known as pruning, right? We'll talk about pruning in detail. Why do we need to pruning? What is the use and all? But these are the overall common terminology that we have for decision trees, right? Now let's have a look at one more example. Now this is a proper example with some data. Go through this and try to understand what we are trying to do over here. This is the target variable, that is play or don't play, and these are my features, right? So what are we doing here? We are using these four features, that is the outlook, the temperature, humidity, and windy conditions, that is the weather conditions. We are using these weather conditions to go ahead and predict whether you should play or not, right? So I'll take this data and I'll see how a decision tree will build itself. All right. So, how to decide whether you need to go outside to play or not on the basis of the weather conditions? If you need to build a decision tree, let's see how the decision tree will be built. Right. Now, the first thing is what we need to identify. Now, can you tell by looking at this data manually? Can you tell which feature will be used for the first split? Is there a way to do that? Why Outlook? Can we look or can we tell this by having a look at the data? No, right? We will have to, just like in the previous case, I was taking examples of, let's say, India playing in England, playing in India. What was the purity like? Yeah, I took the second variable, whether the pitch is spin friendly or fast bowler friendly. And then I went ahead and I actually found out that whichever split is giving me a more purity increase, I will go ahead and I will take that, right? So I cannot manually decide this. I need to decide which variable will be selected as the first variable by looking at the purity of the split, right? So all of you who are saying outlook, temperature, now see manually by having a look at the data, we can never tell. Now see here we have only 10, 12 rows. In the real world, you might have thousands and millions rows, right? Will you have a look at the data and say that this is the column that you need to use? No, right? We need a statistical way of identifying this. Make sense? Let's try to find out how does this exactly happen. Now, a decision tree, right? There are four criterions that we can use, right? Not all four together. One of these four can be used to go ahead and to identify the best split, right? Which feature needs to be accounted for the best split. So we have entropy, we have information gain, we have reduction in variance, we have Gini index. All of these four, the objective is simple. The objective is to identify how pure the resultant nodes are. If you remember from our previous example, when I had started with India and England, the overall distribution was 50% matches India had won, 50% matches England had won, right? Then, when we went ahead with the splits, I was trying to manually identify which split is giving me a higher increase in purity, right? So, instead of manually doing that, these four metrics, one of these four will help you in identifying which feature is giving you the best split, right? So, entropy, information gain, reduction in variance, Gini index, these are the four options that you have. While building the models, you can play around with any of these options, right? Overall objective remains the same. It's just that the approach will be slightly different, right? So let's have a look at entropy, right? I'll give you an example of entropy, how entropy works. I'll give you this example with the actual data, and you will have a look at, you will be able to understand what or how entropy is actually used to calculate the best feature for the split, right? Now the formula for entropy is simple, right? Now if you would have studied entropy in school, entropy was what? I think you would have studied this in physics, thermodynamics, and all, right? Entropy was what? And entropy was how much random your state can be, right? If you have a physical state which contains, let's say, 50% of one kind of values, 50%, or let's say, we used to talk about entropy with respect to electrons and all, right? I don't remember everything now. But a system wherein the electrons are actually, let's say, moving in different directions will have a higher entropy. I am looking for a system which wherein the variance or wherein the electrons are moving in the same direction, right? I'm not sure if it was electrons, protons, neutrons, whatever, right? But it was something to do about mobility, right? Let's try to understand here. Entropy is nothing but the randomness of a state, right? The randomness of a given state. So here, if you look at this in our example, let's go back to our data. Let's calculate the entropy. The formula for entropy is simple. The probability of yes into the log of probability of yes minus probability of no into log of probability of no. Both of these values are coming out to be minus, right? Now, first of all, can you tell me from this data what is the probability of getting a yes and what is the probability of getting a no? How can we find that? Probability of yes is 9 by 14. I have 14 observations in total and I have 9 yeses and I have 5 no's, right? So probability of yes will be 9 by 14, probability of no will be 5 by 14. If I apply this formula, right, over here, then I will get the entropy of the state, right? Now, see, let's try to understand this. Let's assume that the probability of yes in a system is 0.5. A probability of yes in a system of 0.5 means what? That there are 50% yeses and 50% nos, right? For such a system, the entropy will be equal to 1. That is, this system is totally random, right? If you look at this curve, the entropy will be equal to 1 when the probability is equal to 0.5. If the probability is 0 or equal to 1, then the entropy will be equal to 0, right? So in our case, let's have a look at what is the probability of the overall of the initial state of the decision tree, right? Now the probability of yes or the number of yeses were 9, number of no's were 5. We can go ahead and we can impute all of these values. So minus 9 by 14 into log 9 by 14 base 2 minus 5 by 14 into log 5 by 14 base 2. Calculate this and you get an entropy of 0.94. What does 0.94 tell you? Does it tell you that your system is totally random, or does it tell you that your system is totally pure? This value is close to 1, right? Random, right? Pure will be close to 0. Charan, that's the formula. It will always be base 2. All right. So this is the entropy of the root node. Now, what do I need to do next? Now, the information gain, I'll come to this later. Let's first calculate the entropy of the overall system, right? Now, how do I identify which variable I need to take? Is it outlook? Is it temperature, humidity, or windy? So what I'll do is that one by one, I will use each of the variables to divide this data and I will calculate the entropy of the resultant state, right? So let's start with the first variable, which is outlook. If I divide this data by outlook, my outlook has three values, right? Sunny, overcast, and rainy. Correct? So if I divide the data by outlook, my tree will look like this, right? It will have one branch for sunny, one for overcast, and one for rainy. Correct? Can you give me the probability of yes or no for sunny? What is the probability of yes for sunny, the probability of yes for overcast, and the probability of yes for rainy? 2 by 5 for sunny, for overcast, 1, for rainy, 3 by 5, right? Correct? But this is the individual and or these are the individual probabilities. So first let's calculate the we will calculate the entropy, right? So what I do is that I calculate the entropy for outlook equals to sunny, for overcast and rainy. You can see this, these are the same things that you have talked about, right? 2 by 5 into log 2 by 5 minus 3 by 5 log 3 by 5. This is for sunny, this is for overcast. Now you can see that for overcast it was a pure node. Your entropy is coming out to be 0, right? Then similarly, rainy, the entropy is 0.971. Now, if you want to calculate the overall entropy, right, for this split, you will have to take the weighted average of all the entropies that we are getting. So I take 5 by 14 into 0.97 because there were 5 values for sunny. I take 4 by 14 for overcast because there were 4 values, and I take 5 by 14 for rainy because there were 5 values, and the overall entropy comes out to be 0.693, right? Now, information gain is nothing but entropy of the root, entropy of the parent node minus the entropy of the child node, because that tells you how much entropy, how much increase or how much decrease in purity you have been able to achieve. So my root node had an entropy of 0.94, my resultant node has an entropy of 0.693, so the information gain is 0.247, right? So the more, so if outlook is giving me an information gain of 0.247, I will calculate the same value for all the others. The variable which is able to give me the highest value of this difference, right, will be the variable that I will choose. Does that make sense? If I split using Outlook, my entropy is decreasing from 0.94 to 693. That is a close to 0.25 decrease in entropy. So this is the information gain, right? So let's go ahead and let's calculate this for all the rest as well, right? Correct? So let's take windy, the next one. If I take windy, have a look at windy. When it is false, I get how many? I get the probability of yes equals to 6 by 8. When it is true, I get the probability of yes equals to 3 by 6. Correct? We can calculate the same values, right? I go ahead and I calculate the I will calculate the entropy. One for windy, true. One for windy, false. What is my gain? 0.94 minus 0.892, 0.048. Now, out of outlook and windy, which variable will we select? Given that we had only these two, which variable would you have gone ahead and selected? Outlook, right? Because it is giving you more information gain. Windy is decreasing your entropy from 0.94 to only 0.892, whereas outlook was decreasing your entropy from 0.94 to 0.693. Our objective is to make this entropy value close to zero, right? So out of these two, we would have selected outlook, right? Now this is the visual description. Now, if you go ahead and if you do this for all the possible variables one by one, right? I have done for outlook, windy, you do this for temperature, humidity, and all, you will realize that outlook is the one which is giving you the highest entropy value, right? Can you do this for temperature and give me what the entropy value will be? Let's do this for temperature as well. I will write the entropy values, the information gain for all. For outlook, gain was close to 0.25. Windy, the gain was equal to how much? For windy, it is 0.048. Can you calculate the same for temperature? Information gain should be high, Akshay. Entropy should be close to zero. So my information gain is parent node minus the entropy of the child node. So this is the gain, right? Now let's calculate this for temperature. What are you guys getting for temperature? Let's have a look at hot. This is no, this is no, this is yes, and this is yes. So the probability of yes will be what? Will be equals to 1 by 2, right? For hot, correct? Similarly, if you look at mild, this is yes, this is no, this is yes, and this is yes, and this is no, right? So over here, the probability of yes will be 3 by 5, no will be 2 by 5. If you look at cool, this is yes, this is no, this is this. Okay, one more mild was there, and this is yes, right? So I hope you can calculate this, right? This will be straightforward. We'll not do this. You can leave it if you want to, because we'll have to calculate logs and all. But this is straightforward, right? Now see, like this, we need to calculate the entropy of all the columns. Select the one which is giving you the maximum information gain, right? And you can imagine that this is doing this for such a small data, if this is time consuming, then obviously doing this for a large amount of data, it is something that will obviously be very more complicated, right? So hence this is something that obviously we don't have to do in Python. Whenever we are calling the decision tree function, right, it will actually do this for us. Okay, all right. So now we will move on to random forest. I will complete the theory for both today. I'll try to do that. And then tomorrow we will directly do the hands-on of both, right? So let's move to the theory of random forest now. All right. Now, random forest, we have understood the basics. Now, decision trees have been around for a long time and also known to suffer from bias and variance. We will have a large bias with simple trees and a large variance with complex trees, right? Now, we need to understand what bias and variance is, first of all, right? Now, see, a decision tree, right? If I let the decision tree grow, right, to the maximum possible extent, a decision tree does not have any limit, right? It can keep on growing until and unless all your data points have been classified into the correct classes, right? So you can have a decision tree which might keep on growing, right? Let's say this results in 2, this results in 2, right? Let's say this results in another 2, then this results in another 2. Right? Let me take this to this level only. Now you can see that this is how these two got split. then these two got split further, these two got split even further, then this got split from here to here, this is here to here, right? This one is split from here to here, and this is from here to here, right? Now, see, if I keep on letting the tree grow, what will happen is that if I do not limit the growth of my tree, right? Each and every data point might become a node, right? If you have 10,000 samples, right? If you have 10,000 samples, your leaf nodes might become equal to 10,000. So, what the decision tree will do is that it will actually create customized rules for each and every row of your data. Now, is this something that you need, or do you need a generalized model at the end of the day? I need what? I need a generalized model, right? One split will result in only two. Yes, Vishal. If you have only two unique values in the target variable, even if it is a regression problem. So these are binary decision trees, right? They will always result in two, right? So if I keep on if I let the tree grow to the maximum possible extent, the tree will overfit, right? When a tree overfits, it can give you, so the how do we find out whether a tree is overfitting? Overfitting will give you around, let's say, 100% on training, or let's say something lesser on testing. Now, this is overfitting, right? We have also something known as underfitting. Underfitting is what, let's say, you knew that you can get an accuracy of around 80%, but the model is giving 60% on training, right? And let's say because it's a general model gives, let's say, 65% on testing, right? So this is overfitting and this is underfitting. Now if you look at this, bias is this, right? Bias is basically the how much your model is giving the accuracy on the training data, right? So the training data accuracy is known as bias, and the testing data accuracy is known as variance. Now, if you analyze this, what happens is that in case of a decision tree, we get a high bias and a low variance. High bias means that your accuracy, right? Or so see, bias is basically the error, right? So if I get 100% accuracy, that means we get a low bias and we get a high variance. High variance means that the error is high, right? So when my model is overfitting, in case of decision trees, if I let the model grow to the maximum possible extent, it will overfit. When it will overfit, it will give me a low bias, that is, my error on training data will be low, but the variance, that is the error on testing data, will be high. I don't want such a model, right? I want a model which gives me a low bias and a low variance. That is, both the error on training and testing data should be low. In order to tackle this problem, we have something which is known as a random forest. What a random forest does is that it tries to tackle the problem of bias and variance. Right? Ensemble methods combine several decision trees to produce better predictive performance than utilizing a single decision tree. So we have talked about this, right? Okay. Now this is what ensembling is. Now if you see, I have my data, my original data set. I will divide this data into different training sets which are randomly sampled from my original data set. Right? Now training set 1 will be a sample of data set. Training set 2 will be a sample of data set, and so on and so forth. On all of these different data sets, we will be making our different decision tree models, right? So if you see model 1, model 2 till model k, I will go ahead and I will combine the results, and this is something that is known as ensembling of a model, right? Ensembling methods, ensembling models are models which create multiple base learners, take their predictions and then combine their predictions in order to give you the final prediction. Now, a random forest is a bagging model, right? Bagging means that you create a bag of models, right? You go ahead and create a bag of decision tree models and then you combine them, right? Random forest, a technique to to create multiple decision trees, right? Used when our goal is to reduce the variance of a decision tree, right? What was variance? Variance was the error in the testing data, right? I want to decrease the error in the testing data, right? So whenever or not whenever, it is always whenever you are building a machine learning model, your aim is to always reduce the error on the testing data. Your training error will by default, you take any model, you take any tree based model, and the more it trains, the error will eventually become zero, right? But the objective is to simultaneously, as and when the training error is becoming close to zero, the objective is to simultaneously decrease the testing error as well, right? Now, if I give you another example, so let's say that you had to appear for a test in school, college, whatever, and let's say this test was on, let's say, trigonometry, right? There were 50 questions in your mathematics book. You went ahead and you memorized all the 50 questions, right? And you expected that there will be questions that will be coming from this particular these 50 questions only in the test that you are about to give, right? So during training, although you have spent time in memorizing the functions, right, you have not spent time in understanding the general concepts, right? Now, what happens is that, let's say, during the test, your teacher, they go ahead and they restructure the way the questions were asked. These are the new questions in the test are not the questions from the 50 questions in the book, right? Now, if you would have remembered, or if you would have understood the general concepts, right, the general uh, rules, whatever the concepts might be, you will be able to tackle these questions. But if you have only memorized the questions from the 50 set of question bank, right, you will not be able to replicate a similar performance on the test, right? So this is what overfitting actually means. You are overestimating yourself. While training, you are getting an accuracy of 100%, right? But while testing, your accuracy becomes 80%. So this is what you are, while training, you were doing great, right? But when the actual moment came to perform, right, when the model was exposed to new data, when you were given the actual questions from the test, you were not able to perform, right? And whenever you are in such a situation, these bagging models will actually help you in reducing the overfitting. All right. Okay, so if you see, a random forest is a bagging model. Now see, ensembling can be anything. Ensemble can be, I can also do one thing, right? I can, let's say I go ahead and I do, let's say this model is a, I build a logistic regression model, right? Let's say the second model is a decision tree model, right? Okay. Let's say the third model is a, let's say, knife based model, right? So I can also do an ensembling of models by using different models. That will be an ensemble model. But in case of a random forest, I am not creating different models. What is random forest? Random forest is a model wherein I am creating n different models, but all the n different models are actually decision trees. How are they different? They are different because each and every decision tree is getting a different sample or a different snapshot of the data. Okay, right? So this is what the concept of bagging is. Now the basic differences between decision trees and random forest. If we input a training data set with features and labels, it will formulate some sets of rules which will be used to make predictions. Random forest will randomly pick observations and features to build several decision trees. If you have 100 rows, or let's say if you have 1,000 rows and 10 columns, decision tree will take all the data at once. A random forest will take a subset of the rows and a subset of the features, right? If you ask the random forest to build 50 decision trees, 50 decision trees will be built on, let's say, then you ask that, okay, 50% of the rows and 80% of the features. So every decision tree will get 500 rows and 5 columns of data, which will be randomly sampled from the original data set, right? And then you go ahead and you combine. Mostly a random forest prevents overfitting by creating random subsets of features and building smaller trees using these subsets. Deep decision trees might suffer from overfitting, right? Now, when we are, see, uh, another example, I'll give you two team options, right? One is a team option wherein India as a team, right? I have, let's say I talk about batsmen, I have Rohit Sharma, I have Virat Kohli, I have Shubman Gill, I have Shreyas Iyer, I have Ravindra Jadeja, I have KL Rahul, I'm not sure if I mentioned that. I have all of these, right? This is one team wherein I have all performers who are equally likely to perform. Or I give you another team which has Sachin Tendulkar and it has four other players who are not very stable, right? They might perform or they might not perform. Which team will you go ahead with? Now this is, I think, an incorrect example. Let me give you a general example. Two teams of 11 players each. One team contains two star players and nine uh, average players. The other team contains 11 better than average players, right? Which team will you go ahead with? Is it the first one or is it the second one? Second one, right? Why second? Because in case of the second team, you are not heavily dependent on only a couple of players. The first team might overfit. That is, while practicing, it might happen that you are performing well because your two star players are performing well. But the day of the match, let's assume, right? Maybe 8 out of 10 cases your star players are performing well. But let's assume about those two cases when it is the semi final or final when they fail. As soon as they fail, the entire team will fail, right? So, isn't it better to go for a model which is giving you a similar performance on both training and testing, right? So, that's what, when I'm building a decision tree, I am banking on only one set of model. I am only banking on Sachin Tendulkar. If he will play, India will win. If he will not play, India will lose. But if I'm going with a random forest, I'm banking on a team of different experts, right? It might happen that out of the 11, maybe two might fail, but still the rest of the nine are doing their job. And if they are doing their job, then there is a high chance that you are going to get stable output, stable results, right? Now, how does a random forest work? So algorithm creates random subsets with random values. So this, I believe everyone knows by now, that if you want to create 50 decision trees, you will create 50 random subsets of the original data. For each subset, you will create a decision tree. Each tree is built from a sample. It creates multiple decision trees and then merges the results, right? Sampling is done on the training data. Every time a new sample is chosen to build the tree, introduction of random. So this is the same topic, that same part, that every decision tree will be built on a different sample of data. This prevents overfitting of the model, which is a serious concern. This also yields much better performing generalized models. Right? All right. Now, can you tell me what will happen? Let's say I built 50 decision trees. And the problem that I was solving was a classification problem. Let's say out of the 50 decision trees, 40 are saying that India will win and 10 are saying that India will lose. What will the final output be? Right? Why are you saying win? Because if you take a vote, you will say that 40 models or 40 decision trees are saying India will win. So the majority vote goes to India winning, right? So that's why. So, in case of a classification problem, you are going to take a vote of all the individual models, and the category that gets the highest vote will get the will become the output. Right now, what if this was a regression problem that I was solving? Right. Let's say I'm predicting the runs that Virat Kohli will score. Right. Let's say the 50 models, they are giving me a range of runs in the range of, let's say, 40 to 80, right? Now, what will, in this case, what are you going to take as the output? Let's say one model is saying 40, other is saying 45, other is saying 89, then one is saying 110, one is saying 70. Logically speaking, you will take the average, right? That's what you did in my case. When we were predicting the age, we took the average age, right? So in case of a regression problem, the random forest will take the average, right? In case of a classification problem, the random forest will take the mode or the popularity or the most uh, commonly voted class, right? Okay, so all right then. So we'll stop here for today. Thank you, everyone.
Question 6. How many variables are required to represent a linear regression model? Option 1 3, option 2 2, option 3 1, or option 4, 4? What do you guys think is the right answer? Tell us in the comment section. Just a quick info, guys. Intellipaat offers an executive postgraduate certification in data science and AI, where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps, and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
Today's random forest hands-on, I will include the decision tree model as well, right? So that you are able to see how the decision tree works. Feature engineering is, so let's say I give you a data, right? This data contains, I hope my screen is visible to everyone, right? Let's say I have this, I give you this data and the data contains these three variables, right? So one way is that you go ahead and you use only these three variables, right? But what if I go ahead and I create an additional variable, right? Let's say spend per quantity, right? So this, what I'll do is that I will take the spend and I will divide that by the quantity, right? What if I take percentage spend, right? What if I create these variables? So feature engineering is basically creating additional features from whatever data has been given to you, right? Okay. For the previous batches, I am only teaching them. So I have taken almost all the batches. I have not taught XGBoost till now. I don't have a problem in that. You can reach out to the Intellipaat team. I don't think that it will take too much time, but then you can reach out to Intellipaat because I don't have any slides around XGBoost and all that is given to me. Harshit, I have not talked about Smart even once. From where did you hear about Smart? So you can just keep this question for now. Once when we'll be going for a break or towards the end of the session, I can take this question, right? There is nothing to learn in feature engineering comes with knowledge about a particular domain, right? Understanding of the data. So there is it is something that you will have to pick up with experience and understanding, right? If I give you if I give you the total number of wickets that Jasprit Bumrah has taken or the wickets that he has taken in the different matches and the runs that he has given, what will you do? If you understand the variables, you can go ahead and you, let's say, you can calculate how many balls he bowls between when he takes a wicket, right? Maybe 20 balls per wicket, 30 balls per wicket. Feature engineering, so that is not something, there are no defined set of rules, right? Feature engineering can be anything. So if you understand whatever data has been given to you, if you understand what are the different features that, now see, obviously, if I have, let's say, I had this data, right? Now, along with this, let's say, along with spend quantity, now let's say here only, if I go ahead and if I create a variable quantity per spend, do you think that we should do that? Do you think that that should be right? That should be correct? No. Why not? Because this doesn't make sense, right? So, so that's fine, but quantity per spend, does it make sense? Spend per quantity still makes sense, right? But quantity per spend, what will you get? You will get that if you spend a rupee, what is the quantity that you are getting? Maybe point 0.1, point 0.2, right? So all of this is logical. This is something that you should be able to do if you have an understanding of the different columns, if you understand your data. Then feature engineering is something that you should be able to learn automatically as and when you gain experience in data science. Let's say you have salary of an employee and you have experience, right? Now, let's say salary is the target variable and with experience you want to predict this, right? Now let's assume, I'm sure that this will not be true in most countries, but let's assume that we have a country wherein with experience your salary increases exponentially, right? Let's say something like this. Maybe some field, maybe if I talk about data science only, right? As in when you will start having more experience, let's say you start with 0 years of experience, right? So 0, 1, 4, right? Now let's say the general data says that once when you have 6 to 7 years of experience, after that your salary is going to grow exponentially, right? There is no bound, right? Now, obviously, now do you guys think that linear regression will be able to come up with the correct equation over here? What do you guys think? No, right? Now, so generally, if you see that your relationship between two variables is not linear, so Ishan, what you are saying that can also be done, right? Polynomial regression. But in this case, if you even if you go ahead with let's say x square or x cube, you might not be able to generalize, right? Even though you might be able to as well, but before doing that, we try to transform our data, right? Now this looks uh, like this growth. If you look at this growth, right? This looks to be exponential in nature, right? What if I take a log? If I take a log of this data, you will get the transformation will look something like this, right? The transformed value will look something like this. As soon as you take a log, you will see that this will start showing a linear relationship. It might become like this, it might become like this, maybe, right? Something like this. So, transformation in case of linear regression, if you feel that there is not a the relationship between the target variable and the independent variable is not linear in nature, you can go ahead and you can apply some transformations there. All right. Any other questions? Yes. Okay. So let's get started then. All right. We had covered decision tree. Decision tree hands-on is done last week. I will be covering decision tree hands-on today as well. Right. So in the case study that I created for random forest, I will add the code for decision tree as well. Uh, and we had covered theory for random forest, right? Whatever we have covered till now, on the basis of that, can you tell me the essential differences between a decision tree and a random forest model? What are the basic differences that you are able to remember? So, Harshit, for your case, how do we come to the conclusion if there is a tie in both the leaf nodes? So tie is what if let's say you have two leaf nodes, right, coming from a branch, and in both of the leaf nodes, the probability is coming out to be 50-50. Probability will come out to be 50-50. Let's say there are 100 instances, 50 instances are of people who have churned, 50 instances are of those people who have not churned. So that will be a tie, right? In case of classification models, in case of classification trees, you are going to take vote. You are going to take a vote, right? And a tie will be when you have equal instances of both the classes, right? Random forest is a collection of decision trees. Yes, we build multiple decision trees and bagging to be more specific. All right, that's correct. So I'll just cover the last few slides of random forest. I'll go through what we had covered last week, but then I think we'll not be spending too much time on this. Okay. Now, we have talked about the fact that a random forest is nothing but a collection of different decision trees, right? So, if you see, a random forest is also known as a bagging model. Here, what we are doing is that we are creating different multiple decision trees. Now, can you guys tell me how will these decision trees be different? Essentially, if I'm building the decision trees using the same data, the output should be same, right? So when we are building random forest, we are saying that each and every decision tree is different. So how do we ensure that each and every decision tree will be different in nature? Right? Yes. So for each and every decision tree, we are giving a different sample of data, right? So we do not pass the entire data to each and every decision tree, because if we would have been passing the entire data, every decision tree is going to give us the exact same output, right? So what we do is that we do something known as bootstrapping. So that's correct. So bootstrapping is nothing but sampling with replacement, right? So let's say I give a sample. I say that I'm going to provide 70% rows and 70% features. So for every decision tree, I'm going to randomly sample 70% columns and 70% feature rows, and I'm going to pass this data. For the next decision tree, once again, I will have my original data intact. I will once again take a random sample of 70% rows and columns, right? So that is how essentially each and every decision tree will be different. When I'm doing this, I am creating different I am basically creating lots and lots of weak learners, right? All of these decision trees, they are called weak learners. Why? Because they are not exposed to the entire data. They are exposed to only a certain part of the data. But the thought process here being that when we combine the predictions from each and every decision tree, because each and every decision tree is looking at different aspects of data, we should be able to cover all the aspects, and then the probability that we get, that should be a much more stable probability, and the model will be a much more generalized model, right? So all of this we had covered, that in case of random forest, if it is a classification model, we are going to take vote. If it is a regression model, then we are going to take the average, right? So all of these things we had covered. Okay. Now this is what was left, important hyperparameters in a random forest model, right? Now before we move on to that, I want you guys to think around what hyperparameters do you think will be there in case of a random forest model. Now I believe you have done the hands-on of decision trees last week. So you would have looked at some hyperparameters for the decision tree as well, right? So, what hyperparameters do you think random forest will have? Some will be similar to the hyperparameters that a decision tree has, and some will be different as well, right? So, number of trees will be one, right? Now, what is a random forest? A collection of different decision trees. How many trees do you need to build? That will obviously be a hyperparameter, right? Do you need to build 5, 10, 50, 100, 500? That will be a hyperparameter. So that's correct, Sandhya. What kind of splitting criterion you were planning to use? So the same hyperparameter that was there in case of the decision tree, that will also be applicable over here as well, right? That is the entropy, Gini index, information gain, chi-square, whatever, right? Depth of the decision tree. This will also be an important hyperparameter. That is how deep your different decision trees can go, right? So that will be depth. Any others that you can think of? There is there are two that will be very important. Exactly. So max features will be one. That's correct, Charan. What is max features? How many features do you need to consider, right? In each and every decision tree. If you have uh, 20 features in the entire data, do you need to use 80% of those, 70% of those? Because that is something that will uh, tell you what sample or what percentage of the data you are passing to each and every decision tree, right? So we have max features. Max depth, yes, max depth, Aniket, is the depth of each and every decision tree that will be there, right? So almost, yeah, I think these are the important ones. So let's have a look at this. The first one is n estimators. That is the total number of trees that you want to create, that you want to build, right? That will be one. Moving on, we have max features. That is the total number of features that you will pass to each and every decision tree, right? So is the maximum number of features the random forest considers to split a node or to create a decision tree. So max features, this is something that ranges between 0 to 1. If you give a value of 0.5, it will take 50% features of your base data, right? If your base data has 10 features, and if you take 0.5, it will take 5 features, right? A minimum sample leaf is similar to what we had in case of decision trees. That is, how many minimum samples should be present in a node to be considered as a leaf, right? So determine the minimum number of leaves that are required to split an internal node, right? Can you guys tell me what this particular hyperparameter, right? Minimum sample leaf, how will it affect a tree? First of all, do you guys understand this hyperparameter? Are all of you able to understand what we mean by this hyperparameter? Minimum sample leaf. All right. So let's say my tree is coming from above, right? From top. And this is one branch of the tree. Let's assume this is one branch of the tree. This over here contains, let's say, 10 rows, right? Okay. This is just one node I'm talking about. Let's say I take this further, I take this one step further and I divide this into two other nodes. Now, let's say when I divide this, this has 7 rows, right, out of 10, and this has 3 rows. Now, let's say if I divide this further, I'm just giving you specific, I'm not dividing each and every node, but just for this example's sake, I am splitting, keeping on splitting this, right? So let's say now we have 1 row over here, right? And let's say I have 2 rows over here. And then this will go further, and then this will split itself once again into one row each, right? So 1 row will be over here, right? And 1 row will be over here. Do you see a problem with this particular tree, decision tree? Do you see any problem here? Right? So Aniket has given the correct answer. So what it has done is that, right, it has actually built the decision tree to the maximum possible depth. So this decision tree will overfit, definitely. Your objective of building a decision tree is not to come up with rules for each and every row. Your objective is to identify generalized trends, right? Generalized rules. So what if I want to stop the growth of my tree as soon as a leaf node gets 10 rows, right? So this hyperparameter that you see, right? Minimum sample leaves. It tells you the minimum number of leaves that are required to, this is not right. It tells you the minimum number of samples that you need in a leaf in order to go ahead and split it forward. Let's say I say that the minimum sample leaf is 12. I'm saying that you can only split a leaf if it contains 12 rows in itself, right? Now, as soon as my decision tree will come over here, it will see that there are 10 rows. 10 rows are less than 12. So what it will do is that it will stop the growth of the tree over here only. It will not let the tree grow further beyond this point, right? The growth will be stopped over here, which will actually contain overfitting. Does that make sense? Minimum sample leaves, meaning minimum number of samples that should be present in a leaf in order to split it further. We have considered the purity to end the split. So Vijeshwaran, see, decision tree or splitting is a hungry process. It will keep on doing it until and unless it achieves 100% purity. But where to stop? If you don't stop the growth of the tree, right, it will grow to the maximum possible extent, because when it grows to the maximum possible extent, if you see over here, right, each and every row has been assigned to a node, which is not our objective, right? Our objective is to increase the purity, but our objective is not to increase the purity by creating a bunch of rules for each and every row. We are looking for general set of rules. We are looking for that, okay, if, let's say, if temperature is less than 20 degrees, then it is going to rain. We are not looking for if temperature is in the range of 19 to 20, it will range. If it is 90, 18.5 to 19, it will not rain, and so on and so forth, because that is overfitting. You are clearly overthinking, right? So we don't want that. So although the criterion of splitting is purity, that is a hungry process. Splitting of a decision tree on the basis of purity will be hungry, because all it will want to do is that it will want to increase the purity of the nodes that it is coming up with, right? But then you will have to assign some kind of a criterion beyond which your splitting should stop. If you get the answer faster, does it mean that it has increased predictive power? I don't think so, Arjun. Time doesn't matter. Predictive power has to do with accuracy, right? That is mathematical, but uh, I have given you so many examples, right, from general life as well. Uh, Overfitting is what? Say I give you a bunch of questions on decision trees, and I ask you to understand the questions, and I will take a test tomorrow, right? You go ahead and you, instead of understanding the questions, you go ahead and you just uh, mug up all the questions, right? That okay, this is this, the answer to this is this, the answer to this is that, and so on and so forth. Obviously, or while you are testing yourself, while you are training or while you are learning, you will feel that you know everything. But have you learned the concepts? No, right? You have just gone ahead and you have just, because you wanted to get, you're thinking that if you will be able to learn, or if you will be able to mug up all the questions, you are thinking that you will be getting the same questions. So while training, you get 100% accuracy, because for each and every question you have not understood the logic, you have not understood the what how the answer has come and all. You have just mugged up all the answers, right? Now, when you arrive at the actual test, obviously, if you don't know the concepts, you will not be able to perform. Just like that, over here, if you are assigning rules for each and every row, just for the sake of it, just for the sake of getting the maximum purity, you are splitting the decision tree to the maximum possible extent. So your training accuracy will obviously be 100%. But then once when you go ahead and when you test your model's performance, at that point of time, the accuracy will be lesser, right? So that's why we cannot let the tree grow to the maximum possible extent. See, if the tree growing to the maximum possible extent, you get 100% accuracy, and the same accuracy you are getting in testing data, then you can do that. But that will not happen. That is never going to happen. All right. Okay, so these are some of the hyperparameters. Once again, these are not all. There are many hyperparameters, many other hyperparameters as well, but these are the important hyperparameters. Once when you start building these models, that's why I keep on saying is that whatever you get from here, go ahead, take this and try to implement this on some case studies, on some data sets that you can get on the web, right? And try to experiment around with all the different hyperparameters, because then only you will be able to understand the impact of all of these. Now, there are certain hyperparameters in for the tree-based models which help you in increasing the model speed, right? So reducing the time that it takes to train the model, right? So one parameter we have is n jobs. N jobs is a parameter which you can assign different values to. If you make n jobs equals to -1, right, it will initialize parallel processing. So parallel processing can only happen if your processor supports that. Let's say you have a GPU, or you're working on cloud, or you have a distributed computing platform. In that case, if you give n jobs equals to -1, then the different decision trees that you are building, right, they will be built parallelly, simultaneously, which will make the model training process fast, right? If you give n jobs equals to if you give n jobs equals to +1, then it will turn off parallel processing, right? Random state, I hope everyone is able to understand this. It will make the model's output replicable. That is, each and every time the same output will be generated, right? Why do we need this? You might get an accuracy of 99% while training. You might go to your seniors and say accuracy is 99. You run it again and the accuracy drops to 98, 97. They might question you why this is happening, right? So, in order to replicate the same performances each and every time, we give a random state value. It can be any random number. As long as you give the same value, the output will always be the same. Now, the third one that we have is out of bag score, also called out of bag sampling. OOB is short form for out of bag. Now, this is a cross validation method in which about a third of the data is not used to train the model and can be used to evaluate its performance. Now, while we are building decision trees, right? Now, let's say you have given that 70% of your rows are going to go as an input each and every decision tree. So when the decision tree would have been built, after that, to test the out of bag or to test the performance of the decision trees on a data which it has not been exposed to, it will take the remaining 30% rows, right, which were not exposed to the model while training. It will take those 30% rows and it will calculate the model's performance there. Now, let's say if on 70%, the single decision tree is giving you an accuracy of 80%, right? Then for the remaining 30% data as well, the accuracy should be in the same range. right? That's where you will get to understand whether the tree is overfitting or whether the random forest is overfitting or not, right? So this is out of back score. All right. So I think this is the same example, but just that they're saying that each and every there will be different decision trees that will be built. Now let's say if I build these three decision trees, from two I'm getting the output as yes, from one I'm getting the output as no. So the final prediction will be that yes, the game is going to happen because if you take a vote, yes will get two votes and no will get one vote, right? And this is it on the theory. Any questions? Now we are done on the we are done with the theory of decision tree and random forest, everything. Now we will be moving on to the hands-on of random forest and decision trees, right? All right. So let's get started with the hands-on then. Let's get started then. Now the data that we'll be working with today is churn data, this customer churn that we have, right? So if you have a look at this data contains customer IDs, and then it contains lots of customer related features, right? That is gender, whether the customer is a senior citizen or not, right? Whether it's a partner, whether they have a partner or not, that is, whether they are single or married, how many dependents, what is the tenure of the customer with this company, right? So, this is telecom data basically. So, in this data, if you see, each and every row is a customer, right? Now, this first customer is a female customer, right? Senior citizen, no. They have a partner, yes. No dependents. Tenure, one. This person has been with this company for 1 year. Do they have a phone service? No. Do they have multiple lines on phone service? No. Do they have a net connection, internet? Yes. They have a DSL connection, right? Online security, no. Online backup, yes. Device protection, they have not opted for that. Tech support, they have not opted for that. Streaming TV, no. Streaming movies, no. Contract, they have a month to month contract, right? They are paying the bill each and every month. So there can be different kinds of contracts that we have. This is US data, right? So the contract over here is month to month. Paperless billing, yes, that is true. So they are not getting a bill, paper bill. They have opted for paperless billing. Their payment method is electronic check, and their monthly charges are $30, close to 30. Total charges are the same, and then we have the target variable, that is churn or not, right? That is yes or no. So this customer has not churned. Similarly, if you look at, let's say, this particular customer, this customer is a male, senior no, partner no, dependents no, tenure is 2 years. And if you look at this, you will have all the factors for this customer as well, right? So on the basis of this, we have the target variable, which is churn. Now we will be reading this data, and then we will be building our decision trees and random forest models on top of this data, right? Any questions on this data? This is straightforward telecom data that we have. Just go through each and every feature one by one and see if you're able to understand these features. Once when you give me a go ahead, then I will proceed with the case study, right? Just go through this data. To I want you guys to open this Excel sheet. Just have a look at this data. Don't change anything. I don't think that you can, but tenure is not age, Audrey. Tenure is the tenure of the customer with this company. So do you think that you will have a 1 year old customer? No, right? Female, this person has been with this company for 1 year, right? So there are other customers who have been with this company for a very longer period of time. So maybe that's why this would have been confusing. But tenure is the time period for which these customers have been with this particular platform. Now see, you should ideally go ahead and dig deeper over here and try to find out, is there a difference between no and no internet service, right? If there is a difference, then you will have to consider them separately as two different values. If there is no difference, then you will have to label this no these values as same, right? You can change this no internet service to no only, right? But that's a good catch. But if you look at this over here, It actually means that these are the customers. Now, if you see over here, this is a customer who does not have any net service. They have opted for only phone service. So when they have opted for phone service, they don't have an option of going ahead with all of these online security, online backup, and all. Right. So if you pay attention to this, by looking at this data only, you will be able to understand that this no internet service is different from no. In this case, the customer doesn't need this particular service, right? The backup and security, device protection, and all, because they don't have any internet service. In this case, the customer could have availed, but they have not chosen to take this particular service, right? So that's the basic difference. Similarly, for the multiple lines and that one, exactly. Audrey, I've explained churn so many times. Most of my examples have been around churn. How did you not understand churn then? Customers leaving is churn. So, Audrey, churn is nothing but customers who are leaving you, right? I think I have said age, right? But this tenure is in months. So, this makes more sense, right? Because 62 months, 72 months, so 4 or 5 years. So, tenure is in months. That's correct. Good. That's a good insight, Rohan. All right, then. So, let's get started with the notebook then. So we will be going ahead and we will be reading this data. So let's first import the libraries. So I'm importing NumPy and Pandas. I'm importing the random forest classifier. Let me also import decision tree, right? So we will also import decision tree. Then we will go ahead and we will read this data. My data is in my Google Drive. I'm running this code on Colab. Hence, I'm using this piece of code. I am using these libraries, Google Colab. I'm mounting the drive and all. If you are running this code from your locally hosted Jupyter notebooks, you can comment this out. You can uncomment this and you can give the path to your file over here, right? But since I am running this on Colab, I need to give all of this. These two lines are standard. For the third line, I'm just giving a pd.read_csv, and then I'm just giving the path to my drives, right? And this is the customer churn CSV. I will run this. The first time we run this, it will ask for authentication on Google Colab. Since I have already run this, it will not ask for that. So you can see that it has been able to read the data, and now I'll do a data.head, and you can see that the data that we were seeing on the Excel has been read over here in Python, right? Just do a basic sense check over here. All the columns are there. All the values that we were seeing in the Excel are also visible over here. Nothing has changed, right? The quality of the data looks to be same, right? We will go ahead and we will check that, but still looks like everything is in order, right? All right. What do we need to do next? We have read the data. Shall we go to the model building directly, or are there any other steps that we need to do? We need to explore this data, right? So I will do a basic EDA over here, but ideally for you, once when you have this notebook, right? I want you guys to go ahead, take this notebook and do a proper EDA on this data, right? Take each and every column, do the univariate analysis, bivariate analysis, see if you're able to generate any insights and all, right? So try doing that. Yeah, right. So I will be doing a basic ETA just to check if there are any missing values and all. And then we will move on. So let's have a look at the columns, the different columns that I have. This I'm doing just to check that all the columns that I had seen in the Excel, do we have those or not? Right. So you can just do a quick check, and all the columns that we were seeing in the Excel, right? We have those. So here, if you see, we had how many? We had 21 columns over here. If I go ahead and if I take, let's say if I convert this to a list and then I take the length of the list, I also get 21 columns, right? So looks like everything is there. Every column that we had seen in the Excel is over here, right? At times it can happen while you are reading the data, maybe some of the columns might be corrupt, right? So Python will not read them automatically. So this is a good practice to do, right? Then we'll check the data types. What are the D types of what are the data types of all the different columns? So you can have a look at this, right? Now, customer ID, gender, all of these are object, partner dependents, object, phone service, till paperless billing, payment method is object, monthly charges is float, and rest all are objects, right? So most of the data over here in this case are of the object type. Object meaning that it might be categorical in nature, right? All right. Okay. What other functions could I have used over here? What other functions could have been there which would have helped me in identifying the data types apart from this D types function? Info. So let's have a look at info. So info will give you two things, missing values and what is the data type. One thing we know, there are no missing values, but then along with that, we are also getting the data types, right? Now, I want you guys to go through all of this columns one by one and just see if the data types corresponding to these columns make sense or not. Because you have visualized this data in the CSV, you should be able to remember, or if you are not able to remember, go back to the CSV and see whether the data types that you are seeing over here are correct or not. What do you guys think? Are there any uh, anomalies that you are able to see? Anything that looks incorrect? So, right. So if you look at total charges, right, I think all the rest look fine. For senior citizens, Saran, that's fine, right? If you look at the senior citizen column, it is 0 or 1, but Python has automatically write that as a categorical column, so that should be fine. But if you look at total charges column, which is towards the end, right, this column looks to be this column looks to be object in nature, right? If you see total charges, monthly charges are coming out to be float, but the total charges are coming out to be object. Now, this is something that you would have been able to catch only if you would have done two things. That is, first, you would have had a look, you would have had a basic sense of how the data looks like, what are the different columns. Because now that you understood that total charges is a numerical column, what is the definition, you were able to identify that object is incorrect, right? And secondly, then when you went ahead and when you check the data types, you will have to go through each and every column one by one and see if every column has a correct data type or not. So here we are able to identify that this is incorrect, right? Now, why this is incorrect? If you look at this, there are no null values over here in the monthly charges column, but over here in the total charges column, you can see that there are blanks, right? And there might also be some incorrect values that might be populated, right? So there are lots of values. Now, this is a continuous variable, but it is problematic, right? Going through this and trying to identify which values are correct or which values are incorrect, that can be a very time consuming process, right? Here we have only 8,000 rows, right? 8,000, 4,000, whatever, right? But in our actual data, we might be having rows running into millions and billions. So you cannot scan through the entire data. So what we do is that we have a function that is, I will forcefully convert this column into a numeric column. How will that happen? I'm doing a pd.to numeric, right? And I'm passing this column over here. Now, if I would have not passed, now let's look at this, right? So now let's say I do not pass errors equals to course over here. What will happen? It will give you an error. Why? Because at a given position where it is finding a non-numeric value entry, it is not able to convert that to a numeric number, right? So hence we have the option of errors equals to course. So when I do errors equals to course, what will happen is that it will actually drop those rows from your data, right? Any rows which or any rows coming from this column which are not numeric, they will be taken away. And now if I run this, if I do this, you will see that now we are able to convert. So we are forcefully converting this into our numeric data. Now, when I do errors equals to course, what will happen is that all the values which were null, they will actually forcefully be converted into zero. into a numeric value, right? So that's what has happened over here. That is for all these observations, right? These ones, if you see, for these uh, 11 or 10, these 10 observations, it would have forcefully converted them into the number 0, right? And now if I once again go ahead and do a data type check, you can see that both monthly charges and total charges have become numerical in nature. So let's check this as well. Karthik, I'll read this once again. This is the data.head. Let's look at the shape of the data, right? I have 7,043 rows and 21 columns, right? We will go ahead and we will coerce this. We will convert this into numeric. We will once again do this. This is fine. And once again, I do a shape and you see 7043 only, right? So the shape of the data will remain the same. What it does is that any non-numeric value, right, it will automatically convert them to 0. Kaushik, one question. If we have a column monthly charges and a contract column as object, now I want a new column as total charges. What do you mean by this? You're saying that using monthly charges and contract column, you want to have total charges. How can you get that? One is, how can you get total charges column using one categorical and one numerical feature? You can't, right? You cannot do any feature engineering on one categorical, one numeric column. Paperless billing will be object only. So Mithul, paperless billing is what? It is, I think, yes or no? Something like that. No. So it is yes or no, right? So object is fine. So this will be converted to categorical in Python. Conversion of non-numeric or null values to numeric will affect further analysis. See, that's something that you can analyze. Now see, over here, what I would have done is that what this code will do is that this will manually convert these into 0. All these values will become 0, right? But what do you guys think? What could have been a better thing to do over here? Instead of converting them to 0, what do you think would have been a better approach? Okay, have a look at the entire data first, right? Now look at the total charges column. See if you can extrapolate this column from some other details. Can we do that? So this is what I'm talking about, right? You will have to be smart. If I take monthly charges column and if I multiply this by the tenure, what will I get? Okay, have a look at this. This is, I have taken the monthly charges column and I have multiplied this by tenure, right? Now I want you to compare. Now let me take this, right? I will take this divided by this for each and every column. Not the monthly charges, sorry. I will take this divided by the total charges, right? If I do this for all the values, right? Now, what do you see? Anything that you are able to understand from here? What am I doing? Any idea what I'm trying to do over here? 490, it will show an error. That's correct, right? So, Mithul, that's correct. If I focus on only the blanks over here, it will not give any values, right? So, that's correct. But for others, can you think of or are you able to extract any insight from here? Now, approximately these two values are very similar, right? See, when someone is going for monthly billing, maybe they are being charged more. When someone is going for yearly billing, maybe they get a 1%, 2%, 5% discount. But in all the cases, you will see that this value and this value will be very, very close to each other. 1889, 1936, 108, 107, 1840, 1900, right? Now, what if I go ahead and for the columns which are having missing values in total charges, instead of imputing these values with blanks, what if I impute these values by, right, this multiplied by the your tenure column? What if I do this for only these entries? Now you can see over here why I am getting the error, right? We are able to dig the error because the tenure for these customers is coming out to be zero, right? So these are those customers for whom the tenure is coming out to zero. Because the tenure is coming out to be zero, the total charges is coming out to be zero as well, right? Now, what does it tell you? What can we do next? If we don't have any tenure and we are seeing that the monthly charges are these, the best estimation is what? That the tenure will be no, not drop, right? The easy way is what? You can impute the total charges by the monthly charges for 1 month, because these are existing customers. If these customers have not churned, they are new customers, right? If their monthly charge is 52, the bill that will be generated for them will be what? 52, 20, 80. So all you have to do is that you have to do this. Now, this is, I am saying that this is sensible missing value imputation that you are doing. You are looking at the data, you are seeing what values are missing. Is there any relationship of the missing values and all, right? And through that, we are trying to impute these missing values. Now, dropping is the most easy way out. If you want to drop as well, I'm not saying that that is incorrect, but generally, you will not drop until and unless you are able to figure out some way of imputing the missing values, right? Either all the values being zero is also fine, or you could have imputed these missing values by using the monthly charges column. Okay. But I think zero should be fine. So we will go ahead with the value zero only, because till now, these customers have not paid any bill. Hence, we are getting a total charge equal to zero. Right. All right then. So let's move forward. Let's check for missing values now. So obviously, there are no missing values because we have checked info before. There are missing values, right? Why do I see missing values now? Earlier, we were not able to see any missing values, but now we are able to see missing values. Any idea? If you see previously, I was not able to see any missing values, right? When we had done this info, there were no missing values that we were able to find. But now we are getting missing values. Why? Because we changed the data type, and what errors equals to course has done is that it has imputed those values by nan, right? I was incorrect when I said it will impute that by zero. It has imputed the values by nan, right? So hence I am getting 11 missing values over here. So what we'll do is that we will go ahead and we will, if you want, you can drop. If you want, you can do a fill NA as well, right? That's totally up to you. Now there are 7,043 rows. You could have dropped this data as well. Either you can do a fill NA or you can do a drop NA. That's totally up to you, right? So what do you guys want to do? Do you want to drop or do you want to impute the missing values with zero? Because these are all new customers. They have only joined me recently, right? The tenure is equal to 0 months. When the tenure is equal to 0 months, I don't have any concrete data, and creating a model of attrition, creating a model predicting churn using customers which are totally new, right, is not correct, right? So hence we go ahead and we drop this. When we drop this, after dropping, you can see that now the shape has changed. We have 7043 previously. Now we have 7032 rows only, right? All good. Now we will drop other columns as well. Customer ID is a column that is not required, right? So it is a one-to-one mapping. So I'll be dropping customer ID as well. So in place equals to true. I don't have to assign this back to the same data frame. Let's describe this data frame. Now here I have included object, right? So it will describe all the object columns, right? All the categorical columns. And if I just go ahead and if I use the simple describe function, it will automatically take the numerical values and it will discard all the categorical values, right? So you can look at this over here. Senior citizens, there are 16% senior citizens. On an average, the tenure is around 32 months, that is close to 3 years. Monthly charges are around $64, right? And your total charges, average total charges are around $2,200, right? If you look at the categorical columns, your gender, male has a higher weightage. There are more males as compared to females. More number of people are not married. More number of people have no dependents. Phone service, around 6,352 people in this data have opted for phone service, right? Internet service, 3,000 people have opted for internet service. Out of that, the topmost occurring value is fiber optic, right? So you can see this that for all the categorical variables, if you want to use the describe function, you can use a include equals to object, right? And then obviously there are lots of categorical columns. So what we will do is that we need to do label encoding over here, right? We need to manually convert all of these categorical variables into labels. Now, either you could have used label encoded directly, right? But what I am doing is that I am assigning for each and every column I'm going ahead and I'm giving the mapping manually, right? Manually, because if let's say in some case there is a particular order or sequence that you have to follow, you can do that, right? So you can see that for all the categorical variables, for this one I am just mapping a dictionary. For all the values which are yes, they will be converted to 1. All the values which are no will be converted to 0. If I would have done label encoding uh, automatically, right, by using the function, it might have happened that no might have become 1 or yes might have become 0. So just to make sure that the labels are logical and they make sense, we have gone ahead with a manual mapping, right? Although it does not make any difference in the model performance and all, but from an understanding point of view, it might become confusing, right? Because generally, yes, we will assign to value 1. True, we will assign to value 1. False, we will assign to 0. No, we will assign to 0, right? So if you see, we have gone ahead and mapped each and every variable one by one. No phone service means that the customer doesn't even have an option of choosing between security, right? Between, let's say, all the extra services that you need, right? And a no means that the customer has the option, but the customer has not opted for that option. So no and no service, no phone service, no let's say internet service and all, there is a difference between these two values. This will be nominal only. See, it depends upon how you interpret this, right? Maybe no and no internet service, no and one, right? There can be an order or there cannot be an order. But your point is good. If you feel that for some of the variables you would want to create dummy variables, you can go ahead and you can do that, right? We will be moving forward with this only. But generally, yes, you will have to have a look at how these values are related. If they would have been ordered, we could have used label encoding. If they would have been not ordered, we could have gone ahead with one hot encoding, right? So you can play around with that. Can our models work with this data? So if you look at this data, there are all these object variables, yes, no, male, female. These are mathematical models, right? Do you think that they can work with this data? No, right? They can work with only numerical columns, right? But we have only three numerical columns over here. In this data, we have by default, if you look at this, we have only four columns which are numerical in nature. So all the categorical columns, we need to convert them into a numerical form, right? So that's why we need to do. Did I not discuss label encoding, one hot encoding in detail with you guys last time? I think I did, right? Okay, so just go through that, right? I have explained all of these things in detail. Anything which is number, why do you need to encode that? Any data which is numeric in nature, there is no need to encode that, right? The objective of encoding is to convert categorical variables into numeric variables, right? So there is no need of converting numeric data into another numeric form, right? You will be able to understand whether it is nominal column or it is a column which has order of values, right? If there is a specific order, the sad news is that you will have to do it manually. Not manually, you can assign labels, you can create a code and all. If it is nominal, then you can go ahead with one hot encoding. But generally, you don't have such columns, right? If you have that, you will be having categories sitting on top of the 100 labels that you have, right? And generally, your data engineering team will be creating these labels. So, but yes, if you have such cases wherein you have more than 100 categories and all, then if there is no other way, then you will have to do it manually only. Okay, now after doing the label encoding, you can see that this is how our data looks like, right? Now our entire data has been converted into a numerical form, right? And now we can feed this data to any mathematical model, right? Let's move on to the visualization. Let's have a look at, I'll just do a basic visualization of the target variable and a correlation matrix. So you can see here the value counts of the target variable. So if I multiply this by 100, 73% customers have not churned and 26% customers have churned. If you want to plot this in using a bar plot, you can do this as well, right? So you can see that around 73% customers not churned, 27%, close to 27% customers are churned, right? These things are very basic, right? I don't expect these things you can also check on your own, right? And I've explained this last time as well. I distinctly remember I've explained all of these things. But try these things on your own, right? If I don't do a normalize equals to true, what will happen? If I make it as false, any idea what will happen? It will not give the ratio, it will give you the count. Some things you can explore on your own as well, right? These are basic operations. And if you are applying yourself, if you are practicing during the weekdays, right, you should not be asking these questions again and again. Every time there is someone who asks these questions. I think last time also I had covered this, but that's why I say just try to be hands on and then you will start remembering all of these things, right? Normalize will convert this data into a ratio. All right. Now I can also get the heat map. I can also get the correlation matrix, which can be given in the heat map, right? So for that, I just call the core function and pass it through the heat map function, which will generate the correlation matrix. I've given the color map as red, yellow, blue. If you don't give this, it will take the normal red, yellow, whatever heat map color it has, right? So if you give this annotate equals to true, it will write these values. If you make it as false, it will not write. Format, if I make it as 0.2f, you will see that it will print till two decimal places, right? These are basic, still I'm explaining, but let me reduce the size, right? So you can see that this is the heat map. Can you give me some examples of variable which are highly correlated? Right. So lots of variables now, tenure, total charges, right? If you look at all of these variables are related with monthly charges, internet service, online security, and all of these. But the good thing over here is that we are building decision trees random forest, right? So even if variables are correlated, it's fine, right? Unlike linear regression, logistic regression, wherein model performance will be impacted, over here it does not impact the model performance as much because we want to build different decision trees which will take a snapshot of the data, right? So if it's okay if the variables are correlated, it should not be the case that variables are correlated to let's say 99% or 95% greater than that, right? That means that essentially the same information is there. That should not happen. But other than that, even if you have variables which are decently correlated and you're building tree based models, it should not pose too much of a problem, right? I think we can get rid of this. I'll be using a different function. So, all right. Now, if you see over here, till now we had not transformed the target variable, right? The label encoding that we had done, we had not included the target variable over here. So we need to encode the target variable as well. So we will do that over here. So churn was our target variable. So we map the values yes to 1 and the values no to 0, right? So we do this. Then we divide our data into our features and the target variable. So the usual steps that we follow. So X becomes my all set of features. So what I'm doing is that I'm selecting all the columns, but the last column. The last column is the column churn, which is my target variable. And in Y, I am only selecting my last column, right? So I do this. And now if you have a look at X and Y will only be the target variable. I can show you the shape. If I show you the shape of X, it will have 19 columns only. And if I show you Y will be a single column, right? Which is your target variable. Next, we need to divide our data into training and testing. So I call train test function. 20% in testing, 80% in training, and I run this, and this will split my data. I've given the random state as zero. So random state as zero. Each and every time, same rows will be going into training and testing, right? If I show you the shape of X test, it is around 1400 rows because I had 7,000 in my data, and 20% of that will be testing. And if I sum both X test and X train, you will see that you get the overall 7032 rows that we had in our data, right? All good till now? Any questions? So these are the usual steps that we follow. Now we will get started with the model. So first we will go ahead with the decision tree model. So for the decision tree, right, we just call the decision tree classifier with the standard parameters, and we pass our training data X train and Y train. So first step, we need to instantiate the model object, which we are doing over here, tree dot decision tree classifier. This we are assigning to a variable CLF, right, which is the short for classifier. I'll do a CLF dot fit. When I do a fit, I'm passing the training data. That means that the model training has started, right? And then once when the model has been trained, I go ahead and I use the predict function to get my predictions on the training data and the testing data both. And I am saving these values as y train pred and y test pred, right? The predicted values. So I run this. This will run super fast. And then I print the accuracy. Accuracy score is a function which will give the accuracy of the model. And I need to pass the predicted values and the real values of the target variable actual. So the training data accuracy and the testing data accuracy I'm printing together. And you can see that over here. This gives me a 99%, close to 100% accuracy on training and only 73% accuracy on testing. What do you guys think? Is this a good model, or this is an overfitting model or underfitting? Overfitting, right? So let's try the random forest model. So in a similar way, I will import the random forest classifier, instantiate the model object here. We go ahead and we do this, and let me just make the same code, right? So if you see this is the same code, exact same that we have done. So I fit the model random forest classifier on the training data, and I get predictions both on my training and testing data, and then I print the accuracy of both the models, right? Now, what do you guys think? Now, see, these are bare models. So, obviously, with the bare models, I'm just running this to see which model is performing better out of these two. Hyperparameter tuning, we are going to do at a later point of time. But the hyperparameter tuning, we will only do for the model which is doing a better job, right? So, out of these two, decision tree and random forest, which one do you think is doing a good job, doing a better job? Random forest, right? Yes, the random forest model is also overfitting, but still you can see that the testing accuracy here was 73. Here it is almost 6% higher. Okay, so this all we have printed. All of this is not required. We have already printed this. All right. So from here, from these bunch of codes, what we have gotten is that between the decision tree and the random forest model, it is the random forest model which is performing better, right? Does everyone concur with this? All right. So now for the random forest model, we will be moving on to the hyperparameter tuning, right? Now, how do we do the hyperparameter tuning? Well, let's try to have a look at that, right? Okay. Now there are different hyperparameters that we have, right? We have gone through these. We have bootstrap, max depth, max features, sample leaf, sample split estimators, and all. We will be trying to optimize most of these hyperparameters, right? Chiranjeevi, I have explained ensembling so many times last week as well, right? Go through the recordings. I will not be repeating all of these things again and again. Ensembling, I have talked about this, that random forest is an ensembling model. It creates a group of decision trees, right? All of these things you should be able to uh, understand, right? Because I've explained these things not once, more than once. So then please don't ask these questions again and again, right? Either revise, be updated, or if you're not doing that, then just at least, okay, everything has been covered. So if you're lagging on the recordings and all, then that's fine. Just go through the recordings. You should be able to cover everything, right? Now, I'll come to this piece of code later, but let's try to understand. Now, see, in order to optimize the hyperparameters, how can we do that? Now, uh, every hyperparameter, right? If I look at each and every hyperparameter, that is number of trees, max features, the depth of each and every tree, I can iterate each and every hyperparameter through n number of values, right? So what will you do? Will you run the model 200 times? Let's say one model you run with number of trees equals to 5, other you run with 10, other you run with 15, 20. Do you think that you should do this manually, or there should be an automated function which will help you in doing this, right? So what we do is that we create a grid. This grid will have all the different possible values of the hyperparameters that we want to test, that we want to experiment with, right? So if you look at this over here, for each and every hyperparameter that I want to play around with, right? That I want to play around with the values. What I'm doing is that I am creating a list of possible values that they can take, right? Starting with n estimators, right? If you see, I have my n estimators as a list, which is starting from 200 going till 2000 with 10 values between. So 200, 400, 600, 800 till 2000. Max features is a hyperparameter which takes on two values, auto and square root. Auto is automatically the model will find out how many, what is the fraction of features that it needs to consider. Square root is that if I have 19 columns, it will take the square root of that. That is close to 4 columns will be given to each and every decision tree. Similarly, max depth, I am iterating this from 10 to 110 with 11 values in between, that is 10, 20, 30, 40, 50 till 110. Minimum sample split, this is the one that I have explained, 2, 5, 10. Minimum samples leaf, 1 to 4. These are the values that I'm giving, and bootstrapping, either it will be true or it will be false, right? So looking at these, right, can you give me the total number of combinations that the model needs to try over here? Now see, if I give you one by one, if I run this, each and every, so if I show you the length of the first hyperparameter, that is n estimators, it will have 10 values, right? If I give you the length of, if I give you this multiplied by this, so you will get 20 combinations, right? So you can see what I'm doing over here is that I am multiplying by the length of each and every hyperparameter that I have, right? If I go ahead and if I multiply all of these values, you will see that there are around 4,000 combinations, 4,000 possible combinations that we need to try in order to find out the best set of hyperparameter values. Is everyone able to understand this? What do we mean by this 3960? How did I come to this? So, see, for n estimators, if I show you n estimators, right, I will try these different values for n estimators. Okay. For max features, I will be trying these two values, right? Max depth, I will be trying all of these values. Now, for each and every hyperparameter, if these are the list of values that I have, in order to find out the best. Now, let's say if I have max depth as 10, max depth of 10 will be iterated with n estimators equals to 200, max features auto, right? Minimum sample split 2, minimum leaf 1, and so on and so forth. Then the same iteration will happen for max depth equals to 20. Does this make sense? Every permutation and combination will be tried, right? So if you find out the total number of permutations or combinations, they will be how many? They will be 3960. Why? I am multiplying by the length of each and every hyperparameter values, right? So n estimators will have 10 values. 10 multiplied by 2 will become 20. 20 multiplied by 11, right, will become 220. 220 multiplied by 3 will become 660. 660 multiplied by 3 will become 1980. 1980 multiplied by 2 will become 3960. Correct? So these are the total number of combinations that you will have to try in order to find out the best hyperparameter for this model. The performance of all the models will be different, right? Because at least one hyperparameter will be different each and every time. Okay, so that's what I'm just trying to show over here, that if we multiply all of these, we get 3960 combinations, right? And that is what we have defined over here, right? We have created a list of all the values. Through this, I have defined a dictionary. This dictionary is a random grid, right? Here, if you see the key value pairs, I have given n estimators. The key is n estimators, and the values are all the values that your n estimators can take. That is 200, 400, and all. Max features all the values that it can take. If I run this and if I print the random grid, you can see that this is your overall grid that we have, right? These are all the possible combinations that the model will try one by one. Okay, everything will change, Charan, right? Max features auto and square root. One time it will be identified automatically, other time it will be the square root of all the features. So that's what I'm coming to. Now see, you can see that there are 3960 combinations. If you run this on actual data, assuming that one model takes, let's say, 10 minutes to build, 10 minutes to run, it will take 3960 into 10, that is 39,600 minutes, right? If I do 39,600 divided by 60, you will get how many hours? 660 hours, right? And if you do 660 divided by 24, you will get 27 days, right? So close to 1 month you will take for training the model. Do you think that you will have this much amount of time while doing hyper while building a model? No, right? So that's why we have something known as randomized search CV, right? So what randomized search CV does is that, let me show you this. Now, randomized search CV is a technique which what it will do is that it will take this random grid, right? And through this random grid, it will intelligently iterate through all the different possible combinations. You will have to tell how many iterations you need to run, right? Let's say there are 39,600 in total, but you only have the time to run 100. So randomized search CV will intelligently run only 100 combinations, right? How will it do that? So let's say it started with 200 trees, right? 200 trees, let's say it realized that the accuracy was 80%. When it then what it will do is that it will run the next iteration with 2000 trees. That is the next maximum value. And let's say through that it realized that the accuracy was 90%, right? Now it will try to come to the middle, right? So it will try to guess the best possible parameters. Randomized search CV, first of all, it will happen in a random way, but this random selection will be intelligently driven, right? So on the basis of that, what happens is that we don't go ahead and we run all possible combinations because that will be more time consuming. What we do instead is that we call this function randomize search CV, and if you have the bandwidth of running more iterations, let's say you can run 200 iterations, you can do that, right? Then what will happen is that you might get the exact set of values, but with randomized search CV you might get to a very you might get to the ballpark, right? You might not get the best possible hyperparameters, but you might get closer to the ballpark, right? So that's what we do in randomized search CV. If you look at this over here, what I do is that I call the random forest classifier, and then I do not train the model over here. I do not pass any data. Before doing that, I instantiate a model object of randomized search CV. In randomized search CV, I pass the random forest model. Till now, there has been no data that has been passed to the random forest model, right? Then the second parameter that I pass is the random grid. That is the parameters on which this particular RF model will run. Third hyperparameter I pass is the number of iterations. I say that do not run 3960 iterations, right? Which we can see over here. I say that I only have the time to run 100 iterations, right? The scoring I give as negative mean square absolute error. This is just to look at the performance of the model, right? So this is a standard value that you can give. I give cross validation as 3. right? Cross validation, it will divide the data into three folds, use two folds for training, one for testing. Verbose equals to will print out the performance, right? This particular line that you are seeing, this you will get from verbose equals to 2. Random state 42, n jobs equals to -1. If you remember, parallel processing will be true. Return train score for the best possible model. Whatever model is coming out to be the best, it will return the training score, right? Now, if you will run this, I'm not going to run this because this takes around 50-60 minutes to run, right? So I have run this before, but I want you to run this once when we are done with today's session, and you will see how it will take a good enough amount of time. Run this with n iter 100, increase that to 200, 500, and you will see that the time will keep on increasing, right? But once when I would have run this, right, I will get in this RF2 parameter. So I think this notebook would have disconnected. Uh, I will not run this again. I have the best model results over here only. This is the best model. So I will take this. You can run this on your own time. And once when you run this, you run the best params and all, right. You will get the, okay. So you'll have to run this again. I think this would have, the details would have been dropped off. But once when you run this, right, and you run this code, this will give you the best params. Anyways, the best params that we were getting from this model, right, before I had run this cell, the output that you were seeing over here was this, right? I'll just comment this out and then leave it. So the best parameters that we were getting from this randomized search CV was n estimators as 2000, that is 2000 trees. Minimum sample split were 10, minimum sample leaf were 1, max features was square root, max depth was 10, and bootstrap was false, right? Now, if I run this random forest classifier with these models, right now, I know why this is not working because we have run this already, right? RF2. So this will uh, overwrite over here, right? So that's why. So once when you run this again, right, you should be able to get the best parameters. Now I have rerun the model. I have rerun the random forest model with the best set of hyperparameter values, right? And now if we go ahead and if we check the model performance using the same code, let's take this only. Okay. So now if you see, if I run this, all right. So you can see one thing that first of all, the testing accuracy has increased slightly, right? It has increased by close to 1%. Your training accuracy has come down. So your overfitting has actually reduced in the model. The testing accuracy has not gone up by by a very high margin because if you see here, it was 79%. And here after running your hyperparameter tuning, it has become around close to 80%, right? So 80%, 79%, only a 1% change, but that's fine. Still, we have been able to increase the accuracy by close to 1%, and the your training accuracy has come down. That means that the overfitting aspect of this model has actually gone down, right? This is now in the hyperparameters, right? You can play around with different sets of values. It's not that this is a given, right? I have only given you an idea of how do we do this. Now you could have also done, let's say, started with 100, gone till 500, given a gap of 50, right? In between 100, 150, 200 and all, right? Now all of these things you need to do. Hyperparameter tuning is basically a very manual process. You will have to try different combinations again and again, right? Only then you will be able to identify the best possible model. Now over here, the 80% that we are getting, it's not that this is it. You can increase this even more because these hyperparameters that we are getting, right, this once again is coming from randomized search CV, right? So this can, you might go ahead and you might try, let's say, values slightly above or slightly below and try to see if the performance of the model is actually getting better, right? Okay. Okay, then evaluation of the model. One thing that we get from these tree-based models is something known as feature importance, right? So if you do, if you call the model object and call the function feature importance, it will pass you a list of weights, right? Now these list of weights are in the same order as your data, right? So what we do is that we create a data frame by combining the feature names and the importance that we are getting from feature importance. So I do this. So you can see that I am dropping the churn variable from our original data and all. I create a new data frame df. Feature will become my column names and importance will become the importance that we are getting from here. And after running this, if I run this, you can see that these are the important features, right? These are not sorted. I can go ahead and I can sort these values by importance. So if I sort these values by importance, you can see that these variables are coming out to be important in predicting the churn. So you can see that tenure is the most important variable, contract is the second highest, and this is what we were seeing, right? That these variables were correlated as well, right? Total charges, monthly charges, all of these variables in this order are coming out to be important. Variables such as partner, gender, dependents, all of these doesn't look to be important from a modeling point of view, right? If you want to plot this, you can also plot the feature importance. So I'll just go ahead and I'll plot a bar plot. X-axis is my feature, Y is my importance, and you can see that this is how the feature importance are varying, right? Now, if you want to rerun this model by eliminating some of the features which are not important, you can do that as well, right? So in this way, your tree-based models can also function as your variable selection as well, right? You can use them for feature selection as well, right? So this is the feature importance, and also we can generate the classification report. So as from sklearn.metrics, all of these are standard, right? We have used this in logistic regression as well. If I pass the values for, so let's say this is my y test spread. So this is the classification report for our testing data. And similarly, if I take this and if you want this for training data, you can get train and train over here. And this is the classification report for the training data. Here you will see everything, the precision and recall. For training data, the precision for class 0 is 90, the precision for class 1 is 83. For testing, it is 84 and 65. The recall is 91 and 95, 70 and 50, right? So you can have a look at this. Overall accuracy, you can see 80% in the testing data and 88% in the training data, right? And this is generally all the things that we do, right? We just look at the model performance, and on the now, till now, we have covered only three classification models: logistic regression, random forest, and decision trees. Now, if you want, you can also apply logistic regression model over here and see if it is able to perform better than these two models, right? Then, ideally, towards the end, you will go ahead and you will select that model which is giving you the best performance, right? So this is it, right? This is all that we had to cover in the hands-on. Uh, are there any questions? Are you guys able to hear me? There is total silence for the last 10 minutes. It is not overfitting. Accuracy is the best on your testing data. So, but still there is further room for improvement. So what I will ask you guys to do is that take this notebook, try to improve upon this notebook, play around with the hyperparameters, right? Over here, if you see um, this grid that we had defined, right? Don't just stick to these values, right? Try other values as well and see if they are working better or not, right? So you need to do that because if I run this, right? If I run this now, this will take a lot of amount of time, right? So generally, this if you want to run this in lesser time, you can reduce the number of iterations, but that doesn't make sense because it will not be able to get the best possible parameter there, right? So that's it for today, guys.
Question 7. What is logistic regression used for? Option 1 classification, option 2 regression, option 3 clustering, or option 4 all of these. Tell us your answers in the comment section below. Just a quick info, guys. Intellipaat offers an executive postgraduate certification in data science and AI, where you can master skills like data analysis, data wrangling, SQL, machine learning, PySpark, MLOps, and AI by receiving training from the world's top 1% industry experts and IT faculty. With this course, we have already helped thousands of professionals to successfully transition their careers. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given in the description below and take the first step towards career growth in data science and AI.
So, have you ever wondered which book to read next? Well, I often have, and to me, book recommendations are a fascinating issue. And that is exactly what we're going to do today. So, our dataset for the case study comprises of these 4 files: ratings.csv, books.csv, booktags.csv, and tags.csv. So, as the name suggests, ratings.csv contains all users' ratings of the books. So, there are a total of 980,000 ratings for 10,000 books from 53,424 users. So, the books.csv contains more information on the books, such as the author's name, publication year, book ID, and so on. Then we have the booktags.csv file. So, this file comprises of all tag IDs users have assigned to the books and the corresponding tag counts. So, the tag IDs basically denote the categories into which the books fall into, and the counts denote the number of books belonging to each category. And we have the tags.csv file. So this file contains all the tag names corresponding to the tag IDs. That is, it gives out the labels corresponding to different tag IDs. So these are the tasks which you'd have to perform in this project. So in the first phase, we do a bit of data cleaning. So we'll start off by removing the duplicate ratings. That is, there are cases where a user has rated the same book more than one time. So we'll go ahead and remove all these instances. After which we'll go ahead and remove those users who have rated fewer than 3 books. Right guys, so we are into our studio now. So let us go ahead and load all of the packages required for our case study. So these are all of the packages required. Alright, now after which I'll load the 4 files from our dataset. So these are the 4 files. So we have books.csv, ratings.csv, booktags.csv, and tags.csv. And I am storing this in objects books, ratings, book tags, and tags. So we have loaded these 4 files. Now let us have a glance at these 4 files. So I'll be using the view function to have a glance at our 4 files. Right, so these are our datasets, guys. So we have the ratings dataset, which comprises of these 3 columns: book ID, user ID, and the rating. Then we have the books dataset, and these are the columns. So it has ID, book ID, work ID, ISBN, the author's name. Then we have the original publication year, original title, language code, and so on. After which we have the book tags. And here the columns are Goodreads book ID, tag ID, and the count. And then we have the tags dataset. Here we have the tag ID and the corresponding tag name for that tag ID. Alright. So as part of our first phase, we had to do a bit of data cleaning. And the first task of our first phase was to remove all of the duplicate ratings. And to do that, we'd have to find out how many times has one single user rated one particular book. And this would be the command for that. So here what I'm doing is I am grouping this ratings data set by user ID and book ID. After which I am using the mutate function, and I'll add a new column to this, and that new column would be given by the n function from the deployer. So this basically would give us the number of times a single user has rated one particular book. And I'm giving the name of the new column to be capital N, and I'm storing the result back to ratings. So let me have a glance at ratings now. View of ratings. So we see that a new column has been added. So this is the user number. So the user number 314 has rated the book number 1 only once. Similarly, if we take this case over here, the user number 2900 has rated the book number 1 only once. So let me go down and see if there are some changes over here in the count of n. Right, so let's have a glance at these 2 cases over here. So the user number 4206 has rated the book number 8945 two times over here, right? So these are the duplicate ratings which I'm talking about. So these records need to be removed, right? Right, so now let me also use the table function to find out the distribution of these duplicate ratings. So I'll use table function and I will give in ratings $n over here, which would give me the count of the different ratings given by one particular user to one particular book, right? So this value over here tells us that there have been 5 instances where one particular user has rated the same book 5 times. This tells us that there are 28 instances where the same user has rated the same book 4 times. This tells us that there have been 156 instances where the same user has rated the same book 3 times. And this tells us that there are 4,298 instances where the same user has rated the same book 2 times. And this is all of those cases which are not duplicate. That is, the user has rated that particular book only 1 time. Right. So now what I'll do is from this ratings data set, I will filter out all of those duplicate records and I will store them in a new object. So I will put in the name of the dataset, which should be ratings over here, and I will use the filter function to select all of those records where n is greater than 1. That is, which have duplicate ratings, and I will store it in a new object. So we have successfully created this new object. Now let me have a glance at this view of duplicate ratings. Right, so there are 4,487 entries in total which have duplicate ratings. Or in other words, there have been 4,487 instances where the same user has rated the same book more than 1 time. Right, now we'll go ahead and remove all of these duplicate ratings. Now this is a very simple command to do that. So from the ratings object, all you have to do is filter out only those records where the value of n equals to 1. So this basically means that we are filtering out those records where one particular user has rated one particular book only once, and I am storing this result back to the ratings dataset. Right, so we have done the changes. Now let me have a glance at it. View of ratings. Right, so these are all of the records where there are no duplicate ratings. So our second task was to remove all of those users who have rated fewer than 3 books. So for this, we'd have to start off by grouping the users with respect to user ID first and find out the number of ratings given by each user. So I will select this command over here and I'll paste it over here. So I have given ratings over here and I'm grouping this ratings with respect to user ID. After which I am using the mutate function, and over here again I am adding a new column, and that new column would be ratings given, and I will get that ratings given column with the help of this n function from the deployer package. So this n function from the deployer package would basically give me the number of ratings given by each user. Right, so I will store this back into the ratings dataset. Now let me have a glance at it. View of ratings. So this is the user ID. So the user number 314 has given 181 ratings in total. The user ID 439 has given 173 ratings in total. Similarly, the user ID 9246 has given 190 ratings in total. So now we'll go ahead and remove all of those user IDs who have given less than 3 ratings. So this is the command for that. I have again given ratings over here and I am filtering out only those records where the ratings given by each user is greater than 2. That is, each user has at least rated 3 books or more, and I am storing the result back to ratings. So view of ratings. So this is our final data set. So we see that there are 960,595 entries in total. So we are done with the first phase. In the second phase, we'll do some data exploration. So we'll start off by extracting a sample set of 2% records from the entire data set. Then we will make a bar plot for the distribution of ratings. That is, we'd want to analyze the count of different ratings. After which we'll make a plot to understand how many times each book has been rated. Then we'll make a plot for the percentage distribution of different genres. Going ahead, we'll find the top 10 books with highest ratings. And finally, we'll find out the 10 most popular books. Right, so we are back to our studio again, and it's time for phase 2 now. So the first task in our phase 2 was to select a sample from the entire data set. So I'll go ahead and set a seed so that if I ever want to run these commands again, I can get the same results. So I'll set the seed value to be 1. And I'll set a user fraction of 0.02. That is, from the entire user base, I need only 2% of the sample users. So I am assigning this value of 0.02 to a new vector and naming that new vector to be user fraction. Now after which I will find out all of the unique user IDs. So I am using the unique function over here, and I will give in the user ID column from the ratings dataset. So this will give me all of the unique user IDs, and I am storing the result in the users object. Now after this, let me have a glance at the number of the unique user IDs. So length of users. So we see that there are 45,016 unique user IDs in total. So we need 2% of these unique user IDs. So 2% of this would be 0.02 into 45016. So this would give us 900 users. So from 45,016 users in total, we would need 900 users. Right. So we'll do a random sampling of 900 users from the entire user base. So this is the command for that. So I am using the sample function, and this is the list of all of the users. And from all of the users, I only need 900 of the users. So earlier we had multiplied the user fraction into the length of the users, which gave a value of 900 point something. So we are basically rounding that off, and I will store that result in sample users. So now let me have a glance at the length of sample users over here. Length of sample users. So you see that there are 900 sample users in total. Now let me also have a glance at the number of ratings. So initially the number of ratings which we have is 9,60,595. So now what I'll do is, from this ratings data set, I will be filtering out only those user IDs which are present in the sample users object. That is, I would need only the sample users from all of the users. And I will store the result back to ratings. Right, now let me have a glance at the number of ratings. So n row of ratings. So now we see that the number of ratings has reduced to 18,832. So initially we had more than 9 lakh ratings. So now after filtering the data set, we have just 18,832 ratings. Alright. So our second task was to make a distribution of these ratings. So let me go ahead and do that. So guys, this is the command for that. So again, I am using the ratings data set, and on top of this, I am building the ggplot. So here, I am mapping the rating column onto the x-axis. So this column over here, so we have different ratings, 1, 2, 3, 4 and 5. So I am mapping this column onto the x-axis. So the fill color would also be determined by the rating column. And after that, since we'd have to make a bar plot, I am using the geom bar function. And the color which I give to the boundary of the bar plot would be gray 20. And the color which would be coming to all of these bars would be from this palette over here. So the palette is YLGNBU. So this stands for yellow, green and blue. So we'll be giving this inside the scale fill brewer function. Right. And I am also setting the guides to be false. Let me hit enter. So this is what we get. Let me zoom this now. So this is quite an interesting plot, isn't it? So let's have a glance at this bar over here. So this basically tells us that there are more than 6,000 cases where a rating of 4 star was given. Now, similarly, we see that there are more than 5,000 cases where a rating of 5 star was given. And this bar over here, so this tells us that around 4,700 times a rating of 3 star was given. So the count of these two bars is quite low. So there have been very less cases where a rating of 1 star was given. So maybe not even 500 times a rating of 1 star was given. So this is for the rating of 2 stars. So around 1,000 times rating of 2 stars would have been given. So guys, this is the distribution of the ratings. Now after which we had to find the number of ratings per each book. So let's also do that. So here again I start off by giving the ratings data set, and I would have to group this with respect to book ID because I'd want to find the number of ratings per each book. So that is why I am grouping it with respect to book ID. Now after grouping it, I will use the summarize function. So basically inside this summarize function, I will basically get the count of number of ratings for each book. So here I am again using the n function. So this n function would give me the number of ratings per each book, and I'm also naming the result to be number of ratings per book. After which I'll again use the pipe operator and add a layer of the ggplot on top of it, and I am assigning the number of ratings per book onto the x-axis. The fill color is orange, the boundary color is gray 20, and the x-axis values would range from 0 to 40. Right guys, so this is the plot. Let me zoom this now. So from this graph, we can basically infer that there is not even one case where a book was rated more than 10 times. So let's have a glance at this bar over here. So this tells us that there are more than 2,500 instances where a single book was rated only by one user. So this is for those instances where a single book was rated by two users, or in other words, a single book was rated 2 times. This is for those instances which tells us that a single book was rated by 3 users, or in other words, a single book was rated 3 times. And the count for this is around 1,500 times. Right, so this plot was for the number of ratings per each book. Then we had to get the percentage distribution of the different genres. So what we'll do is we'll start off by making a new object and giving it the name genres. So this genres object would basically have a list of different genres in it. So I have basically listed down a bunch of different genres over here, and I am storing all of these into the genres object. So the different genres are art, biography, science, thriller, travel, humor and comedy, and so on. So after building the genres object, what we'll do is from this tags data set, I will be extracting only those tag names which are present in the genres. Or in other words, I am extracting only those genres which are listed down over here. So this is the command for that. So what I'm basically doing over here is I am finding out if the listed genres are present in the tag names or not. And if they are present, I am extracting only those genres and I am storing them in available genres. So let me hit enter and let me actually see what are the available genres. Right, so these are all of the available genres in the tags dataset. So there are 27 genres in total, and these are Christian, business, poetry, philosophy, science, and so on. Now similarly, I will extract all of the corresponding tag IDs with respect to the tag names. So let me find out which are the available tags. So over here, I am basically extracting all of those tag IDs if the tag name is present in one of the available genres, right? So if the tag name is present in one of the available genres, only those tag IDs I'm extracting. And similarly, if the tag name is not present in the available genre, then I won't be extracting those tag IDs. And I am storing the result in available tags. So next we had to make a plot for the percentage of each genre. So let's go ahead and do that. So before we do that, let's actually get a count of the different genres available. So this would be the command for that. Let me print it over here. So what I'm basically doing over here is from the book tags dataset, I am extracting only those tag IDs which are present in available tags. And then again, I am grouping it with respect to the tag ID. After which I'll use the summarize function and get the number of counts of each of these tag IDs. Or in other words, I'll get the count of the different genres. So let me hit enter and let me see what do we get. So this is the tag ID 2938, and for this corresponding genre, the count is 436. That is, there are 436 books belonging to this genre. Similarly, this is the tag ID 4605 and the count is 1109. So this means that there are 1109 books present for this particular genre over here. And let's take this over here. So the tag ID is 7778 and the count is 469. So this means that there are 469 books present with respect to this genre. Now let me go ahead and also find the percentage. So let me select all of this code over here. Right. So now we had run the command till here. Now, so we basically got the count of each genre. Now, after getting the count of each genre, I am ungrouping it again. After that, I will use the mutate function and find the total count. That is the total count of all of the genres combined. And I am also creating a new column percentage. So this percentage over here, I am dividing n upon sum of n. That is, this would give me the percentage of each of the genre. And after getting the percentage of each of the genre, I will arrange the data set in descending order. And after arranging the data set in descending order, I will also left join the tags data set to the book tags data set. And the joining would be done by the tag ID column over here. So let me store this in a new object. So let's say book info. Now let me have a glance at it. View of book info. Right. So guys, this is the tag ID. This is the count of the tag ID. That is the number of times this genre is present. And this column gives us the total count of all of the genres. This gives us the percentage of the genre. And this is the tag name, which is fantasy. So we've got our data set ready. Now we'll go ahead and make a plot on top of this. So now let me go ahead and make a plot. So the object name was actually book info. So let me change this to book info over here. And on top of this book info object, I am adding a ggplot layer. So here I'll be mapping the percentage column onto the y-axis and the tag name column onto the x-axis. And the fill would be determined by the percentage column. And since we'd want to make a bar plot, we'll be using the geom_bar function, and the stat which I've used is identity. And I'll also use the quad flip function over here because I'd want these bars to be stacked horizontally and not vertically. And the color to these bars would be determined by this palette over here. So this is YLORD. So this would be for yellow, orange and red. And the label which I've given for the y-axis is percentage, and the label which I've given for the x-axis is genre. Let me hit enter. Right guys, so this is the plot. So here I have mapped genre onto the y-axis, percentage onto the x-axis. So we see that fantasy is the most prevalent data set, or in other words, most of the books belong to the fantasy genre, and the least percentage is of the cookbooks. So this was the distribution of the percentage of different genres. So up next we'll go ahead and find the top 10 books with highest rating. So this would be the command for that. So if you have to find out the top 10 books with highest rating, all we have to do is arrange this average rating column in descending order, and that is what we are doing over here. So here I have given the name of the object, which is books, and I am arranging this data set in inverse order of average rating. After which I am selecting just the top 10 records, and the columns which I'd be selecting are title, ratings count and average rating. So let me store it in top 10. Let me have a glance at top 10 now. Right guys, so these are the top 10 highest rated books. So the Complete Calvin and Hobbes is the book with the highest rating. So it has the highest average rating of 4.82. And then we have Words of Radiance, so it has a rating of 4.77. Third in place is the Harry Potter box set, which has 4.77 rating. Fourth is ESV Study Bible, which has a rating of 4.76. Fifth in the list is Mark of the Lion Trilogy, which has an average rating of 4.76. Right guys, so we have successfully found out the top 10 books with highest ratings. Next we'll go ahead and also find the top 10 most popular books. So this would be the command for that. So to find out the top 10 most popular books, we'd have to arrange this ratings count column in descending order. That is, whichever book has the most number of ratings, it would automatically mean that it is the most popular book. Right, so this is the command for that. Let me run it over here. So here what we are doing is, on the books dataset, I am arranging it in inverse order of the ratings count column, and then I will be extracting the top 10 records, and I'll be selecting the title column, the ratings count column, and the average count column. So let me store this in top popular. Let me have a glance at top popular. Right, so these are the top 10 most popular books. So the most popular book in the list is The Hunger Games, which has the highest ratings count. Then the second most popular book is Harry Potter. Third most popular book is Twilight. And the fourth most popular book is To Kill a Mockingbird. In the third phase, we'll finally do some recommending. So we'll start off by building the user-based collaborative filtering model. And then we'll recommend 6 new books for 2 different readers. Right guys, so it's finally time to recommend some books. So before we go ahead and do that, we'd actually have to restructure our data a bit. So our data actually needs to be in the form of a matrix where all the rows should correspond to the users and all the columns should correspond to the books. So the dimension names would then nothing be but the user IDs and the book IDs. So the user IDs would represent all of the rows and the book IDs would represent all of the columns. So let me go ahead and extract all of the dimension names first. So here with this command, what I'm doing is I am extracting all of the unique user IDs and I'm also extracting all of the unique book IDs and I'm storing them in this object dimension names. So this is our first task. So we have basically got all of our dimension names. Now we'll go ahead and convert the format of our data frame from long format to wide format. So with this command, what we are doing is we are actually selecting the book ID, the user ID and the rating columns from this data frame over here. And I'll be splitting this book ID column. That is, this value of book ID 1 would become one column. This value of book ID 2 would become the second column. This value of book ID 3 would become the third column and so on. And these rating values over here, they would become the values for the corresponding book IDs. So this is how we can use the spread function to spread out our data frame from long format to wide format. And we'll also remove the user ID column because it doesn't serve a purpose, and I will store it in a new object and name that object to be rating mat. So let me hit enter. Right, so we have created our rating matrix. So we have created the rating mat object. Now let me have a glance at the class of this. So class of rating mat. So we see that this is still in the form of a data frame. But we can build our user-based collaborative filtering model only on top of the real rating matrix. So first we'd have to go ahead and convert this data frame into a matrix. So let me do that. So here with the help of as.matrix function, I am converting the class of rating mat from a data frame to a matrix and I am storing the result back to rating mat. Right. So now let me have a glance at the class. So class of rating mat, and we see that now it is a matrix. So let me have a glance at the first 5 rows and the first 5 columns of it. So these are the first 5 rows and these are the first 5 columns. So we see that this user ID column has not been removed. So let us go ahead and manually remove these. So what I'm doing is I am manually removing this first column and I am storing it back into rating mat. Now let me have a glance at first 5 rows and first 5 columns. Right. So these are the first 5 rows and these are the first 5 columns. So these rows basically correspond to all of the user IDs and these columns basically correspond to all of the book IDs. So these NA values which you see over here, so this basically means that the first user has not rated the first book, the first user has not rated the second book, similarly the fourth user has not rated the third book, and so on. Right, so we have our rating metrics ready. Now let me also assign the dimension names to the dimension names of this rating mat object. So here I am assigning all of the dimension names which I've extracted to the dim names of the rating mat. Right. So now let me have a glance at the dim names of rating mat. So dim names of rating mat. So these are all of the dimension names for the rows. So this is the name for row number 1, this is the name for row number 2, and this is the name for row number 3. So this basically signifies that all of the rows are represented by the user IDs. Similarly, if I go down, then we have all of the book IDs. So all of the columns are represented by the book IDs over here. Now let me use the dim function to find out the number of rows and columns in the matrix. So we see that there are 900 rows and 8,431 columns. Or in other words, there are 900 users and 8,431 books. So we have got our metrics ready, but we can't just build a user-based collaborative filtering model on top of the metrics. So we have something known as a real rating matrix. And the recommender lab basically works only on this type of object. So I will store this rating mat into a new object and name that object's name to be rating mat 0. Let me again have a glance at the number of dimensions of this. Dim of rating mat 0. So we have the same number of rows and columns. So again here, the number of rows are 900 and the number of columns are 8431. Now after this, what we'll do is, wherever we have NA values, we will replace those NA values with 0. So in rating mat 0, wherever we find NA values, I am replacing those NA values with 0. So now let me again have a glance at the first 5 rows and the first 5 columns of this. So it'd be rating mat 0, 1 to 5 and 1 to 5. So we see that all of the NA values have been replaced with zeros. So now we can go ahead and convert this matrix into a sparse matrix. So I'll be using the as function and I am converting this rating mat 0 object into a sparse matrix, and I will store this in a new object and name that object to be sparse ratings. Now let me again have a glance at the first 5 rows and first 5 columns of this. So sparse ratings 1 to 5 and 1 to 5. So this is how a sparse matrix looks like. So basically with the help of a sparse matrix, we end up saving a lot of space. Now it's the last part of the transforming. So we will go ahead and convert this sparse matrix into a real rating matrix. So for this we would need the new function, and with the help of new function I am converting this sparse ratings object into a real rating matrix. So this over here takes in 2 parameters. So the first parameter is basically what we are trying to convert this into, and then we give in the data which we are trying to convert, and I'll store this result in real ratings object. Let me print real ratings now and let's see what do we get. Real rating. So this is what we get. So it is a rating matrix where there are 900 rows and 8431 columns, and it is of class real rating matrix with 18,832 ratings. Right. So we finally have our real rating matrix ready. So now we can go ahead and build a model on it. So what we'll do is we'll go ahead and split the data set into train and test sets. So it'll be a 80-20 split. So I'll be using the sample function to create this 80-20 split over here. So I am using the sample function, and I will generate true or false values over here, and this sampling would be with replacement, and the probability is 80-20. That is, I would want to divide the data set into 2 parts, where the first part would comprise of 80% of all of the observations, and the second part would comprise of 20% of the rest of the observations. and I will store the split criteria in a new object and name that object to be split book. So now in real ratings, wherever the value of split book is equal to true, I will select all of those records and store those records in regtrain. Similarly, from the real ratings matrix, wherever the value of split book is assigned to be false, I am extracting all of those observations and storing those observations in reg test. So we have our training and testing sets ready. Now we can finally go ahead and build our first model. So we'll be using the recommender function, and this over here takes in two parameters. First is the training set on which we'd want to build the model, and next is the method or the type of the recommender model which we'd want to build. And since we'd want to build a user-based collaborative filtering model, we'll given the type to be UBCF. So if we wanted an item-based collaborating filtering model, then the method would be IBCF. But in our case, since we want user-based collaborative filtering model, so the method would be UBCF, and I will store the result in an object which would be rec model UBCF. Right, so I have successfully built the model. Now I'll give a value for the number of books to be recommended. So I am assigning the value 6 to a vector, and the name of that vector is nRecommended UBCF. So this basically lets us know that we'd have to recommend 6 books in total. Right, so the model building process is done. So let me go ahead and predict the values. So I'd have to use the predict function for this. So over here, this takes in 3 parameters. First is the model which you built. Next is the dataset on which we'd want to predict the values. And third is the number of values to be recommended. Right. So first we'll given the model which you built, which is rec model UBCF, and then we'd want to predict on top of the test set. So the test set is rec test, and the number of books to be recommended is 6, which is stored in nRecommended UBCF, and I will store this result in rec predicted UBCF. Right, so the prediction is also done. Now let me go ahead and find out the item numbers which have been predicted. So now that we have predicted the values, let's go ahead and recommend some books to user number 1. So here we will use this object rec predicted UBCF. So this is the object which we've just built using the predict function. And I'd want to find out the item numbers which have been recommended to user number 1. So this command over here, rec predicted UBCF @items1. So this will give me the column numbers which have been recommended to user number 1. So let me have a glance at user 1 book numbers. So this basically means that user 1 has been recommended to read these books which are present at columns 2177, column number 6343, column number 423, column number 1908, column number 2274, and column number 2514. Now we just have the column numbers. So let's actually find out the labels for these column numbers. Right, so from rec predicted UBCF, we have the item labels, and inside the item labels, I will give in the book numbers which have been recommended. Right, so these are the item labels. So the book ID, which is under column number 2177, is 2636. The book ID which is under column number 6343 is 7482. Similarly, the book ID which is under column number 2274 is 2750. So we have successfully got the book IDs. So now that we have the book IDs ready, let's actually use these book IDs to extract the name of the book and the name of the author. Right, so what I'll do is I will extract the title of the book and the author's name, where the book ID is 549. So the name of the book is Cordry and the author's name is Don Freeman. Similarly, let me extract the title and the author's name, where the book ID is 2750. So here we see that the book recommended is Mrs. Pigglewiggle, and the authors are Betty McDonald and Alexandra Boyger. Similarly, let me extract the titles for the book ID 3029. Let's see what do we get. 3029. So the book recommended is Rage of Angels and the author is Sidney Sheldon. Right, so these are the 6 books which have been recommended, and this is how we can extract the name of the book and the author of the book. Now, similarly, let's also go ahead and recommend 6 books for the user number 5. So this is what I'd have to do. I will be using the rec predicted UBCF object, and I'll be using the @tag and extracting the items for user number 5, and I'll store this result in user 5 book numbers. So now that we have the item numbers, let's actually extract the column numbers for each of these items. So for this, the command would be rec predicted UBCF @item labels, and inside this I will give in the book numbers. Right, so these are the book IDs which have been predicted. Right, so similarly, let's extract the title and authors for some of these book IDs. So we are extracting the title and the author's name, where the book ID is 4624. So the recommended book, so the name of the recommended book is The Girl Who Circumnavigated Fairyland in a Ship of Her Own Making, and the author is Catherine M. Valentine and Anna Wan. Similarly, let's extract the name of the book and the author's name, where the book ID is 6867. So here the book is Malgudi Days, and it's been written by R.K. Narayan and Jumpalari. Now let me extract the title and the author's name for the book ID, which is 7326. So the book's name is Doctors, and it has been written by Eric Segal. Right guys, so we have successfully implemented the user-based collaborative filtering model, and we have recommended 6 books to 2 different users.
Alright, so now let's have a look at the quiz. So which of these libraries is used to implement collaborative filtering models in R? And these are your options. Is it Recommender, or Recommender Lab, or UBCF Lab, or Collab Lab? So what do you think is the answer? So what do you think is correct? Put down in the chat box and we'll reply. Right, so we'll start off with the questions. So this is our first question over here. So we have this diamonds data set, and we are supposed to extract only those rows where the price value is greater than 1000 and the cut is equal to ideal. So this is our data set over here. So we'd want to extract only those records where the value of the cut is equal to ideal, and this price which you see, and this price needs to be greater than 1000. And we are supposed to implement this with R. So let's do that. Now this diamonds dataset is a part of the ggplot2 package. So first we'll go ahead and load this ggplot2 package. So I'll use the command library of ggplot2, and then let me have a glance at this dataset. So I will use view of diamonds, and this is our diamonds dataset over here. So this is our dataset, which comprises of these columns: caret, cut, color, clarity, depth, table, and so on. So our task was to extract only those records where the price value was greater than 1000 and the cut was equal to ideal. And to do that, we'll be using the deployer package. So I'll be loading the deployer package. So deployer is basically a package which is based on grammar of data manipulation. And this is the command to extract those particular records. So first, what I'm doing is, from this diamonds data set, I'll be using the filter function which is part of the deployer package. And with the help of this filter function, I'm giving 2 conditions inside this. So the first condition is the price needs to be greater than 1000. After that, I'll use the AND operator and then given the second condition. So the second condition is the cut needs to be equal to ideal. And I'll store the result in diamonds 1000 ideal. I'll hit enter. Now let me have a glance at the result. View of diamonds 1000 ideal. So you see that there are 14,700 entries in total where the cut is equal to ideal and the price of the diamond is greater than 1000. So out of the 53,940 records, we have filtered out 14,700 records where the cut is equal to ideal and the price is greater than 1000. Now we have our second question over here. So on the same diamonds dataset, we are supposed to make a scatter plot between the price and the caret. And we are supposed to do that using the ggplot2 package. So over here, the price needs to be on the y-axis and the caret needs to be on the x-axis. So this column, it needs to be on the x-axis, and then we have price. This needs to be on the y-axis.
and the color of the points need to be determined by the cut value. So again, let's head back to R and let's implement this. So again, to implement the scatter plot using ggplot, we are supposed to load the ggplot2 package. Alright, and this would be a command to make that particular scatter plot. So ggplot2 is something which is based on grammar of data visualization. So ggplot helps us to stack multiple layers on top of each other. So first off, we'll start with the data layer. On top of the data layer, we'll stack the aesthetics layer. And on top of the aesthetics layer, we'll stack the geometry layer. So first, we have the data layer where we'll give the name of the data frame to this data attribute. And we are working with the diamonds data frame. So the first layer is diamonds. After that, we will map these columns onto the aesthetics. So using this aesthetics attribute inside this ggplot function, I will map this caret column to the x aesthetic, and similarly I will map this price column onto the y aesthetic. And as the question stated, the color of these points need to be determined by the cut column. So again, I'm reiterating it. Caret is mapped onto the x aesthetic, price is mapped onto the y aesthetic, and cut is mapped onto the color aesthetic. And once these two layers are done, we are supposed to build the final layer, which is basically the geometry. And since we are supposed to make a scatter plot, we'll be using the geom point geometry. And this gives us the required scatter plot. Let me zoom this. So as we see over here, price is mapped onto the y-axis, caret is mapped onto the x-axis. And these colors which you see, these basically denote the different cut values. So yellow, it denotes the ideal cut, and this purple which you see, that denotes the fair cut. So you see that if the cut is fair, then mostly the price of the diamond is higher and also the caret value is higher. And when it comes to the ideal cut, we see that the caret range of the ideal cut, it starts from 0 and it's mostly till 3 or 4. So this is the sort of interpretation which we can make from the scatter plot. And then we have our next question. So this time we are supposed to introduce 25% missing values in the iris data set and impute the sepal length column with the mean, and similarly impute the petal length column with the median. So this is the iris dataset. So again, let's head back to RStudio and perform these tasks. Let me have a glance at the iris dataset first. View of iris. So this is our iris dataset, which comprises of these 5 columns. So we have sepal length, sepal width, petal width, and species. And our first task is to introduce 25% missing values in this entire dataset, and that'll be totally random. And to introduce missing values, we'll be using the Miss Forest package. So let me load the Miss Forest package using the library function. Now, this Miss Forest package comprises of this prod_any function. And using this prod_any function, I'll be introducing 25% missing values. So this basically takes in 2 parameters. First is the data frame or the object into which we are supposed to introduce missing values. The second parameter is the percentage of missing values that we'd want to introduce. So in this iris data frame, we are supposed to introduce 25% missing values. So I'll give the value of 0.25 and I'll store this in a new object and name that object to be iris.mis. Now let me have a glance at this modified dataset. View of iris.mis. So this is a new data frame which comprises of 25% missing values. Now I'm supposed to impute this sepal length column with the mean and similarly this petal length column with the median. And to impute those 2 columns separately, I would require the HMISC package. So I'll load this package now. Library of HMISC. And this package comprises of the impute function with the help of which I'll be imputing different columns. So first I'll use the width function, and this takes in 2 parameters. First is the data frame which consists of missing values. So in this data frame we are supposed to impute the missing values. So this is the iris.mis data frame and this is the first parameter. Next we'll use the impute function, and inside the impute function again it takes in 2 parameters. First is the column which we want to impute. Next is the function by which we want to impute this column. So I want to impute the missing values in the column with the mean of this column. So wherever you see any values in this column, all of those values would be replaced with the mean of this column. And I'll store the result back to this column, which is iris.mis $sepal length. I'll hit enter. Now let me have a glance at this imputed dataset. So view of iris.mis. So you see that wherever we had the any values, all of those values have been imputed with the mean. So this 5.85562 which you see, this is nothing but the mean. So initially there was an any value over here and that has been imputed with the mean. Similarly, there was an any value over here and that has been imputed with the mean of this column. Next, similarly, we are supposed to impute this column with the median of this column. So let us do that. So again, I'll use the with function and then pass in this data frame with the missing values. After that, I'll use the impute function and I am supposed to impute this petal length column, and the imputation would be done with the help of the median function. So wherever there are any values, all of those any values would be replaced with the median of this column, and the final result, I'll store it back to the same column. I'll hit enter. Now again, let me have a glance at the modified data frame. So view of iris.mis. So this is a modified data frame. So this 4.2 which you see, this is nothing but the median of this column, right? So wherever there were any values, those any values have been replaced with the median of the petal length. Now let's head on to the next question. So what do you understand by linear regression? Well, linear regression is a supervised learning algorithm which helps us in finding the linear relationship between two variables. So one is the predictor or the independent variable and the other is the response or the dependent variable. So we try to understand how does the dependent variable change with the independent variable. So linear regression is a supervised learning algorithm which helps us in finding the linear relationship between two variables. So one is the predictor or the independent variable and the other is the response or the dependent variable. And we try to understand how does the dependent variable change with the independent variable. So let's say there's this telecom company called as Neo, and now the data scientist at this company wants to understand if there's a linear relationship between the monthly charges incurred by the customer and the tenure of the customer. So he collects all of the data and builds a linear model between the monthly charges and the tenure. So here, monthly charges would be the dependent variable and tenure would be the independent variable. And in linear regression, there could be more than one independent variable. So if there's just one independent variable, it is known as simple linear regression. And if there's more than one independent variable, it is known as multiple linear regression. So guys, this is the underlying concept of linear regression, where we have one dependent variable and multiple or a single independent variable, and we try to understand the linear relationship between the dependent variable and the independent variables. So next, we're supposed to implement this simple linear regression in R on this empty cars dataset, where the dependent variable is this MPG column and the independent variable is this displacement column. So again, let's head back to RStudio and implement the simple linear regression. So this is our empty cars data frame, which comprises of all these columns. So we have MPG, the number of cylinders, displacement, horsepower, DRAT, weight, cusick, VS, AM, gear, and carb. So as the question stated, MPG is our dependent variable and displacement is our independent variable. And we want to try to understand how does MPG vary with respect to the displacement of this column. So now, before we go ahead and implement the model on top of this data frame, we are supposed to divide this data frame into training and testing set so that the model does not overfit the data. So what happens when we don't divide the data set into training and testing sets is it overfits this data set. And when we give it new data, it'll fail miserably on that new data. So that is why it is always necessary to divide a data set into train and test sets. So let's go ahead and do that. And to divide a data set, we would require this caret package. So let me load up this caret package, library of caret. And this caret package comprises of the create data partition function. Now, this create data partition function would give me true or false labels. And this create data partition function comprises of these parameters over here.
First is the column which determines the split. So that is obviously the MPG column. And then we are supposed to give in the split ratio. So I am giving the split ratio would be 0.65. That is 65% of the labels of this column would have the true label, and the rest 35% of the records would have the false label. And I am storing this into the split tag object. So again, I'm reiterating it. So I am taking this empty $MPG column data set, and 65% of the records would have the true tag associated with it, and the rest 35% of the records would have the false tag associated with it. And I'm storing this result in split tag object. Now, once I have the split tag object ready, what I'll do is, from this entire empty cars data frame, I'll select all of those records where the split tag value is true, and I will store those records in the training set. Similarly, from the empty cars data frame, wherever the split tag value is equal to false. So if I just give in split tag, it'll have all of the true values in it. And when I put in the minus symbol in front of the split tag object, it'll contain all of the false labels. And I will select all of these records and store them in the test set. So now we have our training and testing sets ready. Now let's have a look at the number of rows in training and testing set. So I'll type in n row of train. So see that there are 23 rows in the training set. Similarly, I'll type in n row of test. And now we see that there are 9 rows in the testing set. Now we'll go ahead and build a model on top of the training set. And to build the simple linear model, we would require the lm function. This lm function again takes in 2 parameters. First is the formula. So over here, the formula is mpg tilde symbol displacement. So whatever column we give on the left side of the tilde symbol, that is taken as the dependent variable, and whatever columns we give on the right side of the tilde symbol, all of them are taken as the independent variables. So this time mpg is our dependent variable and displacement is our independent variable, and we are building this model on top of the train set. And we'll store this result in mod underscore empty cars. So now that we've built the model on top of the train set, it's time to predict the values on top of the test set. So for that purpose, we'll be using this predict function, which again takes in 2 parameters. First parameter is the model which we've built, and the second parameter is the data frame on which you want to predict values. So we want to predict values for the test set, and I will store this in predict empty cars. Now let me have a glance at the predicted values. So head of pred empty cars. So these are the predicted values of MPG for all of these cars. So Mazda RX-4 WAG, the mileage predicted for this car is 22.55. The mileage predicted for Valiant is 20.04. The mileage predicted for Mercedes is 18.08, and so on. So this is how we can build a simple linear model on top of this empty cars dataset. So now we'd have to calculate the RMSE value for the model built. Now when we actually build a regression model, it predicts certain Y values associated with a given X value. But there always is an error associated with this prediction. So to get an estimate of average error during prediction, RMSE or root mean square error is used. So again, let's go ahead and calculate the RMSE value for the model which we've just built. So now that we have the actual values and the predicted values, let's bind both of them into a single data frame. So for that purpose, I will use the cbind function, and our actual values are basically present in this MPG column from the test set. And our predicted values are stored in this pred empty cars object, which we had created in the previous question. So I will create this new column and name that column to be actual. And again, similarly, I'll create another column and I'll name it as predicted, which would have the predicted values. And I will store this in a new object and name that to be final data. Let me have a glance at it. View of final data. So these are the actual values of all of the mileage, and these are the predicted values of the mileage for these cars. Now we see that there is an error present in the prediction. Now what we have is actually a matrix. So we are supposed to convert this matrix into a data frame. So I will use the as.dataframe function and convert this object into a data frame. So as.dataframe, I'll pass in this object which is final data, and I'll store the result in final data again. Now I'll have a glance at the same thing. View of final data. So these are the actual values, these are the predicted values, and we see that there is an error present in the prediction. Now the error is basically difference between the actual values and the predicted values. So let's go ahead and calculate the error in prediction for each of these records. So to calculate the error, all I have to do is subtract the predicted values from the actual value. So it will be final data $actual minus final data $predicted. And I will store this result in a new object and name that object to be error. So now that we've done this, I will also go ahead and bind this error calculated to the same final data frame. So cbind, I'll bind the error object to this final data and I'll store the result in final data again. So it'll be view of final data. So this time we have the actual values, we have the predicted values, and we also have the error in prediction for each of these records. Now to get the average error which is present throughout all of the predictions, we would have to calculate the root mean square error. So the root mean square error, as the name states, first we'd have to calculate the error, then we'd have to take the square of it, then we'd have to take the mean of it, and then finally we'll take the square root. So this is how we can calculate the root mean square error. So final data $error, and we'll square this error first. After that, we'll take the mean of this squared error, and then finally we'll take the square root of the mean squared error. So this is what we have. So the RMSE value for this model which we built is 4.33. Now you guys need to keep in mind that the lower the value of RMSE is, the better the model. So let's say if we had some other model and the RMSE value for that model was 5, then this model would be better than that model. Similarly, let's say if another model's RMSE value was 2, then the second model would be better than the model which you built. Now, similarly, we are supposed to implement simple linear regression in Python on this Boston dataset, where the dependent variable is this MEDV column and the independent variable is the LSTAT column. So now in the data science interview questions, it's not necessary that you'll be asked questions only with respect to one programming language. So you might be asked questions with respect to R and Python, both of them. So that's why it's necessary to be good with both of these languages. Right, so I'll head on to Jupyter Notebook and implement simple linear regression on top of this Boston dataset. So I'll start off by loading the pandas package. So I'll type in import pandas as PD, and then I'll load this Boston dataset. And to load the dataset, I'll be using the read_csv function. So pd.read_csv and the name of the file, which is boston.csv, and I'll store this in the data object. So now that we've loaded the data, let me have a glance at the head of this data. So these are all the columns and the first 5 records present in the data frame. So we have Crim, Zn, Indus, Cas, Knox, age, and so on. And for the task of simple linear regression, MEDV is our dependent variable and LSTAT is our independent variable. So this MEDV is basically the median value of price of the houses. And we are trying to understand what is the median value of the price of the houses with respect to this LSTAT column over here. Now, before we go ahead and implement the model, let's understand the dataset a bit more. So I'll use this data.shape, which would give me the number of rows and columns present in this data frame. So we see that there are 506 rows in total and 14 columns in total. Now I'll go ahead and separate the independent and dependent variable from this entire data frame. So for that purpose, I'll use this data.loc, and since I want all of the records, I'll take all of the records, and the only columns which I want from this entire data frame are LSTAT and MEDV. And I'll store this result in data1, and I'll also have a glance at the first 5 records of this data frame. So these are the first 5 records of this new data frame where I have only LSTAT and MEDV columns. Now I'll also go ahead and do a bit of visualization with respect to these 2 columns. And for that purpose, I would require the matplotlib package. So I'll go ahead and import this matplotlib package as well. So here what I'm doing is, I am mapping the LSTAT column onto the x-axis and the MEDV column onto the y-axis. And I will give the label of the x-axis as LSTAT and the label of the y-axis as MEDV. And finally, I'll show this graph which I've built. So what I've built is basically a scatter plot where MEDV is on the y-axis and LSTAT is on the x-axis. So you see that as LSTAT increases, MEDV decreases. So there is an inverse relationship between MEDV and LSTAT. So again, I'm reiterating it. As LSTAT increases, MEDV decreases. So this tells us that there is an inverse relationship between MEDV and LSTAT columns. Now, to build the model, we are supposed to separate the independent variable and dependent variable into two separate objects. So I'll take this LSTAT column from data1 and store it into X object. Similarly, I'll take this MEDV column from data1 object and store it in Y object over here. So X consists of my independent variable and Y consists of my dependent variable. Now it's time to divide the data set into training and test sets. So we have this train test split function from sklearn.model selection. I'll go ahead and load that function. And this function over here takes these three parameters. So X and Y are basically the dependent variable and the independent variable. And then we have test size is equal to 0.2. So this states that 80% of the records would be in the training set and 20% of the records would be in the testing set. So it's a 80-20 split. And this random state which you see, so this is basically a seed value, so that if I want to get the same values again, I can set the same random state to get the same values. And I am storing these values in xtrain, xtest, ytrain and ytest. So xtrain contains all of the train values for that independent variable. Xtest contains all of the test values for the independent variable. Similarly, ytrain contains all of the train values for the dependent variable and ytest contains all of the test values for the dependent variable. So now that we have xtrain, xtest, ytrain and ytest, it's finally time to build the model. So I'll go ahead and load the linear regression model from sklearn.linear model and then I'll fit the model. So first I'll create an instance of this. So linear regression, and I'll create an instance and I'll name that instance to be regressor. And with the help of this instance, I'll fit the model on top of the training set. So regressor dot fit, and I will pass in xtrain and ytrain. So to sum it up, what I'm basically doing is building the linear regression model on top of the training set, which basically comprises of the independent variable and the dependent variable. I'll click on run. Now let me have a glance at the intercept and the m value of it. So linear regression is nothing but y equals mx plus c. And that c is nothing but the intercept. So you see that the intercept is 34.12. And m, which you see, this is the coefficient. This coefficient is nothing but the slope. And you see that the coefficient is minus 0.91. So there is a negative value associated with the coefficient because there is an inverse relationship between the dependent variable and the independent variable as we saw over here. So as LSTAT increases, MEDV decreases. And that is the reason this coefficient is associated with a negative value. So now that we've built the model, it's time to predict the values on top of the test set. So again, I'll use this instance and I will use the predict function with the help of this instance. So regressor.predict, and I will pass in this xtest object inside this function and I'll store this in the ypred object. So we've built the model and we've also predicted the values. Now let me have a glance at the number of rows and columns of the actual values and the predicted values. So we see that both the predicted values and the actual values comprises of 102 records in total. So now that we predicted the values, we'll go ahead and calculate some metrics. So we'll find out the mean absolute error, the mean squared error and the root mean squared error. I'll click on run. So see that the mean absolute error for this model is 4.69, the mean squared error is 43 and the root mean squared error is 6.62. So again, the lower the values of these three, it means the better the model is. So let's say if we are comparing these values with some other model, and if these values are less than that second model, then the first model would be better than the second model. So that was implementing simple linear regression in Python. Now we have our next question over here. So the question is, what do you understand by logistic regression? Well, logistic regression is actually a classification algorithm which can be used when the dependent variable is binary. So let's take this example. So here we are trying to determine whether it will rain or not on the basis of temperature and humidity. That is, temperature and humidity are the independent variables and rain would be our dependent variable. That is, we're trying to understand whether it will rain or not on the basis of the temperature and the humidity. And again, logistic regression algorithm, it actually produces an S-curve. So let's say x-axis over here, it represents the number of runs scored by Virat Kohli, and the y-axis represents the probability of Team India winning the match. So let's say this point over here, it denotes 50 runs. So what we can see from this graph is, so if Virat Kohli scores more than 50 runs, then there is a greater probability for Team India to win the match. And similarly, if Virat Kohli scores less than 50 runs, then the probability of Team India winning the match is less than 50%. So let's take this value over here. So let's say the number of runs scored by Virat Kohli is around 60. So if the number of runs scored by Virat Kohli is around 60, then the probability of Team India winning the match would be, let's say, around 65% or so. Again, let's take this value over here. So let's say this is around 97 runs or 95 runs. And if Virat Kohli scores 95 or 97 runs, then the probability of Team India winning the match is 1, which is 100%, isn't it? So similarly, this value over here. So let's say this is around 5 runs or 10 runs. So if Virat Kohli scores 5 or 10 runs, then the probability of Team India winning the match is 0. So basically in logistic regression, the y value lies within 0 and 1 range. And this is how logistic regression works. So now we are supposed to implement logistic regression on this hard data set where the dependent variable is this target column and the independent variable is the age column. So let's go ahead and implement logistic regression. So let me start off by loading this data set first. I'll use the read.csv function. Now let me have a glance at this dataset, view of heart. So this is our entire data frame, and this target which you see, this is our dependent variable, and we have the age column over here, and this is the independent variable. So we are actually supposed to rename this. So we see that the column name is incorrect over here. So our first task would be to rename this column. Let me go ahead and do that. So I'll use the column names function and I'll pass in this data frame which is heart, and I am supposed to rename the first column. So I'll give in 1 inside the parenthesis and I will rename this to be age. So now again, let me have a glance at this modified data frame. So it'll be view of heart. So see that we have successfully renamed this column from IH to age. Now let me have a structure of this data frame. So structure of heart. So you see that most of these are integers. But then again, since we are building a logistic regression model on top of this data set, this final target column is supposed to be categorical. It cannot be an integer. So we'll go ahead and convert this into a factor. So I'll use the as.factor function and convert this integer value into a categorical value. So as.factor, and I'll pass in this column over here, which is hard $target. And I'll store the result back to hard $target. Now again, let me have a glance at the structure. So that will be structure of hard $target. So initially it was integer. Now we have converted that integer column into a categorical value, which has 2 levels, which are 0 and 1. So now I'll actually build a simple logistic regression model, and I'll not divide this data set into training and testing sets. So we'll do this and we'll see what are the different probability values for the person to have heart disease on the basis of the different age values. And to build the logistic regression model, we'll be using the GLM function. So again, this takes in 3 parameters over here. First parameter is the formula. So here target $age is the formula, which basically indicates that target is our dependent variable and age is our independent variable. And we are building this model on top of the entire data frame, and family is equal to binomial. So when we state family is equal to binomial, we are basically telling R that this is a logistic regression model. And I'll store the result in log mod 1. So now let me have a glance at the summary of the model which we've just built. So summary of log mod 1. So we have this p-value over here, and we see that there are 3 stars associated with this p-value. So this basically means that we can reject the null hypothesis. That is, the null hypothesis states that there is no relationship between the age and the target columns. But since we have 3 stars over here, this states that the null hypothesis can be rejected and there is a strong relationship between the age column and the target column. Now again, we have other parameters over here. So we have something known as null deviance and residual deviance. So simply put, the lower the deviance value, the better the model. So this null deviance basically tells us the deviance of the model when we don't have any independent variables. That is, when we are trying to predict the value of the target column with only the intercept. So if that's the case, then null deviance is 417.64. And residual deviance is that deviance when we include the independent variables and try to predict the target column. So when we include the independent variable, which is age, we see that the residual deviance drops. So initially when there were no independent variables, the null deviance was 417. After we included the age column, we see that the null deviance has reduced to 401. So this basically means that there is a strong relationship between the age column and the target column, and that is why the deviance has reduced. So now that we've built the model, we will go ahead and predict some values. So now I want to know the probability of the person not having heart disease when his age is equal to 30. So now let me actually head back to this data frame over here. So the values in this target column, it is 0 and 1. So when we predict the values, we get the prediction for 0. That is the person not having heart disease. So when the person's age is 30, we see that the probability of the person not having heart disease is 81.2%. Now similarly, I'll predict the probability of the person not having heart disease when the age is 50. So when the age is 50, we see that the person not having heart disease, the probability, it comes down to 60%. Now what I'll do is, I'll predict the values for a set of age values. So this time the age value, it starts at 29 and it goes on till 77. So I'll get a set of predictions starting from 29 to 77. So you see that when the age is 29, the probability of the person not having heart disease is 82%. Similarly, when the age of the person is 30, the probability of the person not having heart disease is 81%. So as the age increases from 29 to 77, the probability of the person not having heart disease decreases. So this is the final case over here when the age of the person is 77. So when the age of the person is 77, the probability that the person does not have a heart disease is 26%. So this is quite an interesting relationship, isn't it? So we see that as the age of the person increases, there is more likelihood that the person would have heart disease. So this model we built on top of the entire data set. Now what we'll do is, we'll divide this data set into train and test sets and build the model on top of the train set and predict the values on top of the test set. So again, for that purpose, I would require this caret package. So library of caret. Again, this caret package comprises of the create data partition function. So this takes in these parameters over here. So this is the split criteria, which is hard dollar target. That is, I want to split this data frame with respect to this target column. And the split ratio, which I'm stating over here, is 0.7. That is, 70% of the records would have the true label associated with them, and the rest 30% records would have the false label associated with them. And the final result, I am storing it in split tag. Now, what I'll do is, from the entire hard data frame, whichever records have the true label associated with them in the split tag, I'll take all of those records and I'll store them in the training set. Similarly, from the entire hard data frame, wherever the split tag value is equal to false, I'll take all of them and I will store them in the test set. So I have my training and my testing sets ready. Now let me have a glance at the number of rows of the training and testing set. So n row of train, there are 213 rows.
and n row of test, there are 90 rows. So now that we have the training and testing sets ready, let me go ahead and build the model on top of the training set. So again, we'll use this GLM function and build the model. So this time the formula is the same, which is basically target tilde symbol age. So target is the dependent variable, age is the independent variable, and we're trying to determine the probability of the patient having heart disease with respect to his age. And we are building this model on top of the train set. And since this is a logistic regression model, the family would be equal to binomial, and I'll store this result in log mod 2. Now that we've built the model, it's time to predict the values. So I'll use the predict function, and this again takes in these three parameters. First is the model which we've just built, and then second parameter is the object on which we want to predict the values. So we want to predict the values on top of the test set. And finally, we'll set the type to be equal to response, which will basically give us probabilities for these predictions, and I'll store the result in pred heart. So let me have a look at the range of the predicted values. So we see that the range of the predicted values of the heart disease, it varies from 0.21 to 0.86. That is, the probability of the patient having heart disease, it varies from 21% to 86%. And this is how we can build a simple logistic regression model on top of this heart disease dataset. Now let's head on to the next question. So what is a confusion matrix? So confusion matrix is actually a table which is used to estimate the performance of a model. It tabulates actual values and the predicted values in a 2x2 matrix. So these are the actual values and these are the predicted values. So this what you see, true positives. So this denotes all of those records where the actual values were true and the predicted values were also true. So these denote all of the true positives. After that, we have the false negatives. So false negatives denotes all of those records where the actual values were true, but the predicted value was false. So where the actual value is true, but the predicted value is false, that is known as a false negative. Then we have false positives. So in false positive, the actual value is false, but the predicted value is true. And such values are known as false positives. And finally, we have the true negatives where the actual values are false and the predicted values are also false. So if we want to get the correct values, then correct values should basically represent all of the true positives and the true negatives. And this is how confusion matrix actually works. So now we are supposed to build a confusion matrix for the model which we built, where the threshold value for the probability of predicted values is 0.6, and then we have to find the accuracy of the model. So as I've already stated, accuracy is basically true positives plus true negatives upon all of the values. So this left diagonal represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been incorrectly classified. So when we divide the left diagonal with all of the values, that is when we'll get the accuracy of the model. So let's go to RStudio and find out the accuracy of the model which we built. So to build a confusion matrix in R, we'll be using the table function, and inside the table function, first we'll give in the actual values and then we'll give the predicted values. So the actual values are stored in this target column of the test set, and the predicted values are stored in the pred heart object which we had created. And then we saw that the range of the probabilities, it was from 0.2 to 0.8. So from that range of 0.2 to 0.8, I am setting a probability threshold of 0.6. That is, wherever the probability is greater than 0.6, it will be classified as 0. Or in other words, it will be classified that the person does not have heart disease. And similarly, wherever the probability is less than 0.6, it will be classified as 1. Or in other words, that the patient has heart disease. So I'm reiterating it again. So wherever the probability of pred heart is greater than 0.6, it will be classified as 0. And wherever the probability of pred heart is less than 0.6, it will be classified as 1. So let's go ahead and build a confusion matrix.
So see that this is our confusion matrix, and this left diagonal represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been incorrectly classified. And if you want to find the accuracy, all we have to do is divide this left diagonal with all of the values. So that'll be 31 plus 17 divided by 31 plus 17 plus 10 plus 32. So you see that we get an overall accuracy of 53% for this model which we built. Now let's head on to the next question. So what do you understand by true positive rate and false positive rate? So let's start with true positive rate. So in machine learning, true positive rate, which is also referred to as sensitivity or recall, is used to measure the percentage of actual positives which are correctly identified. So the formula for true positive rate is true positives divided by all the positives. So I am stating it again. True positive rate is basically the measure of the percentage of actual positives which have been correctly identified. Now let's look at false positive rate. So false positive rate is basically the probability of falsely rejecting the null hypothesis for a particular test. So the false positive rate is calculated as the ratio between the number of negative events wrongly categorized as positive, that is all of the false positives, upon the total number of actual events. So this is how we can calculate true positive rate and false positive rate. Now we have the next question, and we're supposed to explain what is ROC curve. So ROC curve, which actually stands for receiver operating characteristic, is basically a plot between the true positive rate and the false positive rate. And it helps us to find out the right trade-off between the true positive rate and the false positive rate for different probability thresholds of the predicted values. So the closer the curve is to the upper left corner, the better the model is. Or in other words, whichever curve has greater area under it, that would be the better model. So let's say we have this curve over here, and let's say there is another curve which goes like this, which is nearer to this upper left corner. Then in that case, since the second curve covers greater area under it, that would be a better model than the first model. So this ROC curve helps us to find out the area under the curve as well as the right trade-off between the true positive rate and the false positive rate. Now we are supposed to build the ROC curve on top of the logistic regression model which we've built. So let's head back to our studio and do that. So to build the ROC curve, we would have to load the ROCR package. So I'll use the library function and load up the ROCR package. Now this ROCR package comprises of the prediction function, which would give me a prediction object. So this takes in two parameters. First parameter is all of the predicted values. So this spread hat comprises of all of the predicted probabilities for the target column. And the second parameter is the labels of the dependent variable. So test$target has all of the labels of the dependent variable, and I will store this result of the prediction object in ROC pred hat. So now that we've created the prediction object, we can go ahead and build the ROC curve. And to build the ROC curve, we'll use the performance function, which is again a part of the ROCR package. So this over here takes in three parameters. First is the prediction object which you built. So the name of the object was ROC pred hat. After that, we will just give in TPR and FPR. So TPR and FPR stands for true positive rate and false positive rate. So for this prediction object which we built, we are basically trying to find out the right trade-off between the true positive rate and the false positive rate. And I'm storing the result in ROC curve. Now, let me go ahead and plot this ROC curve which I've just built. So this is our ROC curve over here. Let me zoom this. So we have this curve for different probability values over here. So this what you see are the different probability values. And our ideal curve should be something like this, where we have more of true positives and less of false positives. And this green color which you see, so this green color actually represents the ideal threshold value. So the ideal threshold value over here would be somewhere between 0.48 and 0.62. So this is where we would have the ideal threshold value of the probability. And this is somewhere where we can get the right trade-off between the true positive rate and the false positive rate. So maybe it could be this over here. So this point which we see, so the probability would be somewhere around 0.5 or somewhere around 0.55. So this is where we could get the right trade-off between the true positive rate and the false positive rate. So now that we've built a logistic regression model in R, again we need to know how to build a logistic regression model in Python. So this time we are supposed to build this logistic regression model on top of this customer churn data frame, where the dependent variable is this churn column and the independent variable is this monthly charges column. And after that, we are supposed to find out the log loss of the model. So we are basically trying to determine whether the customer would churn or not on the basis of this monthly charges column. So again, I'll start off by loading the pandas data frame and also load the customer churn.csv file. And for that purpose, I'll be using the pd.readcsv function. Right, so we have successfully loaded the file. Now it's time to have a glance at the head of this data set. So these are the different columns which we have. So we have this customer ID, then we have the gender of the customer, we have the senior citizen column, which tells us whether the customer is a senior citizen or not. This column tells us whether the customer has a partner or not. This column tells us if the customer has any dependents or not, the tenure of the customer, whether the customer has phone service or not, and so on. Sort of all of these columns, the columns which are of our concern would be the monthly charges column and churn column. So this monthly charges column basically tells us the monthly charges incurred by the customer in dollars, and this churn column tells us whether the customer would churn or not. So now since we have our data the data set with us, let me go ahead and separate the dependent variable and the independent variable into two separate objects. So I'll store this monthly charges column from this customer churn data frame in the X object. Similarly, I'll store this churn column from the customer churn data frame in the Y object. So we have our dependent variable and independent variable to be separate. Now I'll go ahead and divide this model into training and testing set. And for that purpose, I would require this train test split function, which is part of the sklearn.model selection package. Now, I'll use this train test split function, and this takes in these parameters. First are basically the independent variable and the dependent variable. So the independent variable is stored in X and the dependent variable is stored in Y. After that, I'll set the test size to be equal to 0.3. So this basically states that 70% of the records would be in the training set and the rest 30% of the records would be in the test set. And again, I'll set a random state value so that I can use these same values again if I want to. And I am storing all of these values into xtrain, xtest, ytrain and ytest. So xtrain comprises of the training set of the independent variable. Similarly, xtest comprises of the test set for the independent variables. After that, we have ytrain, which comprises of training set for the dependent variable. And then we have ytest, which is the test set for the dependent variable. So now we have xtrain, xtest, ytrain and ytest. It's time to build the model, predict the values and get the log loss value. So first I will import this logistic regression function from this sklearn.linear model package, and I'll create an instance of logistic regression. I'll store it in L, and then I'll fit the model on top of the training set. So L.fit, and I'm fitting the model on top of xtrain and ytrain. After that, I'll predict the probabilities on top of the test set. So L.predict underscore proba, and I'll pass in x underscore test, and I'll store the predicted probabilities in y underscore pred. So now that we've fit the model and also predicted the probabilities, it's time to look at the metrics. So the question stated that we were supposed to find out the log loss. So I'll just import the log loss from sklearn.metrics, and inside this log loss function, I will pass in the actual values and the predicted values. So actual values are stored in ytest and predicted values are stored in ypred. So we get a log loss value of 0.55. Now again, similar to RMSE, the lower the value of log loss, the better the model is. So again, let's say if there is another model and the log loss value of that second model is less than this, then that second model would be better than this model. Now we'll head on to the next question. So what do you understand by decision tree? So decision tree is a supervised learning algorithm which is used for both classification and regression. Right. So decision tree can be used for both classification purpose as well as regression purpose. So in this case, the dependent variable can be both a numerical value as well as a categorical value. So there is a flowchart-like structure where the topmost node is known as the root node, the internal nodes with children are known as the branch nodes, and the final nodes